G'day viewers. In this segment we'll learn about the User Datagram Protocol, or UDP. UDP provides the datagram service at the socket layer. And as I've said before, it's really a glorified layer on top of IP, which really allows packets or datagrams to be delivered. So in this segment we'll learn the ins and outs of what's behind UDP, and the answer is really not a lot more than IP itself. Okay, so UDP as a datagram protocol, an unreliable one at that, it's used by applications that either don't want reliability or that don't want some other kind of abstraction than messages, such as a byte stream. So there are several examples here. One example is a voice over IP application. Typically for real-time conferencing, we don't want reliability there, so UDP is a good fit. Other kinds of protocols that might use messages would be the DNS and RPC, which stands for Remote Procedure Call. We haven't actually seen the DNS yet, we'll see it later, but it's the machinery that maps between host names like www.uw.edu and addresses, IP addresses. And maybe a third class would even be bootstrapping protocols such as DHCP. Since these are used to get the network going, it's easier in some sense if they don't rely on all of the complex machinery of TCP. By the way, you can see from this list and reasoning that if an application wants both reliability and messages, then it has work to do. UDP gives you unreliable messages, TCP gives you a reliable byte stream. Reliable messages fall somewhat in between. So for instance, protocols that want that, like the DNS, must provide the reliability themselves as part of the application level protocol. So in that sense, the internet protocols, TCP and UDP, aren't a good fit to all applications. Okay, so we can see how datagrams are used at the socket layer. Let's see. Here is a simple time sequence diagram. We have a client and a server. The client is sending a request to the server who's returning a reply. The socket calls we would make to cause this to happen would be, first of all, we would need a socket on both sides. Now, on the server side, we'd need to bind that socket to an address, a well-known port, so that the client could contact. So we now simply want to send a datagram. What do we need to do? Well, usually the server will call receive, in this case receive from, to receive a message. That's a blocking call, so that really says I want to receive a message, and the process then blocks while the kernel waits for a message to come along. At some later time, the client will call send to send a request from the client to the server. At this stage, the receive from call will unblock and will have the information there, and the server can then process the request. On the client side, right after sending to, since we'll be expecting a reply, we'll call receive from. This instructs the client now to wait for a message. And after the server has finished processing the request, it will send. It will send that reply using send to. And then the receive from call will be unblocked. The reply will be received by the client and the client will process it. And then at some later time, when everyone's done, they'll call close to tidy up. So those are the sequence of socket calls which is used with datagram sockets for a very simple client-server exchange. I've cleaned it up here on this figure, and you might note that I've just starred the calls which block, which sort of explains how the flow of programs. Okay, so that's how you'd use a datagram socket. We did see examples of using sockets previously a long time ago in the course, but they were for stream sockets, so the datagram sockets are slightly different. No connections and slightly different forms of receive and send. We can also look at what's going on at the host while we make all of these calls. This picture here shows the buffering that happens inside the transport layer. We have the application layer at top, so this is all of the app processes which are running. They use the sockets and ports to interface to the transport layer. And at the bottom of this picture we have packets, and they're going out the physical network, so I'll just draw a wire. Now there's buffering inside the transport layer. When an app calls, when segments come in from a transport peer on the other side, they're placed in these buffers inside the kernel. You can see that for some sockets there are many different segments sitting here in the buffer. They're going to wait there until the app calls receive, at which time they'll be pulled from the kernel and handed up to the application. Similarly, an application might have data to send. And when it does, if it calls send to, that data goes down to the kernel where it sits in a buffer temporarily. An application might send more quickly than that information could be put on the local network Y, in which case there'd be a little bit of temporary buffering inside the kernel. But as you can see here, the setup is fairly simple. We just have that buffer as a staging point between the send and receive operations. Down the bottom here, this block saying port mux demux is simply the multiplexer and demultiplexer, which is using the port information when you get a segment in to assign it to the right queue, and vice versa, taking segments from all of those queues and sending them out into the network. Well, there's not too much more we can look at for UDP. I can show you the header. You'll see the header is actually very simple. It's pictured here. It has the ports, those 16-bit ports, which identify the sending and receiving application processes. It has a length field. You can send datagrams of up to 64 kilobytes in length. There's also a checksum, a 16-bit internet checksum, just for a little bit of added reliability. But this is pretty much IP. There's only one other thing I can think of to tell you, and that's a little bit about the checksum. The checksum here, well, first of all, it's optional, but second, it covers not only the UDP segment, but it also covers the IP addresses that are passed down with the UDP segment to the data layer. And these are checksum by placing them in the form of what's called an IP pseudo header. You can see it pictured below here, the source addresses and a little bit of information. The checksum covers this block prepended to the UDP segment. It's a little unusual that we would have these source addresses here inside the transport layer. It almost sounds like a layer violation. It's not quite, because these are parameters that the UDP layer knows and is passing down. The UDP as a transport layer protocol is passing down to the network layer to tell it where to send things. But it does show you some of the linkage between layers that we often conveniently ignore. And a final trick is that a value of 0 in the checksum means there is no checksum. That's how it's optional. With a quirk of our ones complement checksum, there are two different values for 0. So if the checksum comes out to really be 0, we can send it in the form of all ones. That's an equivalent value for 0, rather than all bit 0, which will indicate there's no checksum. That's it. That's UDP. G'day viewers. In this segment I'll talk about how connections are set up. So TCP implements a connection-oriented stream service. To implement that, we need to know how it sets up connections, and that's what we'll cover. Connection establishment is really the process of the sender and receiver coordinating or synchronizing themselves to prepare for the start of data transfer. To do this, or as part of this, they need to either tell one another or agree on a set of parameters, including, for instance, the size of messages, the maximum size of segments, which they'll send amongst one another. All of this operation is really done with segments, which transfer control information rather than data. This is called signaling, and it's really to set up connection state in the sender and the receiver. You could think of it as analogous to dial-in in the telephone network before you have a conversation and actually transfer the data. In TCP, a connection is established with what is known as the three-way handshake. This is a fairly common term that you'll hear about, the three-way handshake. It sets up a connection between an active party that's initiating it, typically the client, and a passive party, we'll call that the server, and it opens the connection for data transfer in both directions. The way it works is that each side probes the other by picking a fresh initial sequence number, and the other side needs to be able to echo this sequence number to connect. So here are the segments that would be exchanged. First, the client will send a SYN, that's short for synchronize, a SYN segment, and it will pick its initial sequence number. We'll call it X. Next, the server will reply with an ACK. We'll actually ACK X plus 1. because the SYN is considered to take up 1 byte of sequence number space, and in TCP you ACK the next expected byte, so you're now expecting x plus 1. The server will also send its own SYN, and it will pick its own fresh initial sequence number, that's Y. These two operations can be combined in one segment, just as a little bit of an optimization. And then once this arrives at the client will send back an ACK. This time for Y plus 1 for the other direction. Then both sides will have received the answers to their probe, so they'll both be happy that the connection's open. We'll go into this in a little more detail and look at the properties of this scheme. But I'll tell you now that it was chosen to involve these 3 packets rather than a simpler 2-packet exchange to be highly robust against various error cases, even against packets which have been delayed and duplicated in the network. Okay, so here is a cleaned up version of that diagram, and I've spelled out the steps for you here if you want to go through them. You can see that first of all the client is sending the SYN with X as its initial sequence value. I've also shown in here every packet in TCP carries a sequence number, so I've shown the sequence numbers here in both directions. So you can see on the last packet it's carrying a sequence number, even though before I only showed the ACK. I'll also mention that these SYNs are retransmitted if they're lost. The exchange here shows what happens if everything goes well and neither of these SYNs is lost. But of course, SYNs could be lost just like any segment. So if you really want to set up a connection, you might need to resend your SYNs and add a little bit of reliability. As a side effect of this handshake, the client and the server then agree on sequence numbers that they can use to start numbering their data from then on. So the data that's transferred over TCP doesn't start at sequence number 1 and so forth. It starts following whatever random initial sequence number was chosen by the client and the server, with different numbers in each direction. Now let's look at some of the robustness of this scheme. This picture is going to help us walk through a bit of a bizarre error scenario. Let's say that the packets from a client that the client sent to set up that connection were somehow duplicated, delayed in the network for, I don't know, maybe 30 seconds or so, and then later, when any previous connection has died and gone away, they arrive at a server. This is very improbable, but like all network protocols, we'd like them to work well in the common case, but work correctly in all cases. So even in this case, we would like the protocol to be correct, and in this case not establish a connection if the segments are just these delayed duplicates. So let's see what will happen with the protocol. Okay, so this SYN will magically arrive at the server. The server will say, okay, wonderful, someone's setting up a connection. It will reply, it will send back an ACK with X plus 1, and it will send its own SYN with its initial sequence number of Y. Now when this arrives at the client will reject this packet. It will not know what's going on and say, well, this is not for me, because I haven't sent a SYN recently that corresponds to this. So I'm simply going to throw this away. Nonetheless, because we're imagining that both of these packets have been delayed and duplicated, the second segment will arrive at the server as though in answer to the server's packet. What will happen? Well, the server will look at this packet and the ACK number here will be wrong. If this was a previous connection and we're choosing different initial sequence numbers each time, then the ACK here will be for some previous number Z plus 1. It will not be Y plus 1. So these things are not equal. This will allow, even plus or minus 1, this will allow the server to reject this packet and know that it's part of a failed connection attempt. Okay, so even in this improbable case, the connection has behaved properly by not establishing a connection. And here's a cleaned up version of that. So as I say here, it's cleanly rejected on both sides. Well, in what follows, what we'll do is go through the connection state machine. I've described to you the three-way handshake that's used to set up TCP connections. But various possible other states can occur while connections are being set up. So connections are usually specified with a state machine, a finite state machine, that captures all of the different states and transitions that either side can be in at any given time. It's a way of capturing all of the different parts of the specification together in a way that can be reasoned about, not simply the common case normal path through the sequence. So in these kind of diagrams, the states are rectangles. They're a state that a sender or receiver can be in. The lines are transitions. They have arrows on the end to show you which way they go. And they have a little bit of notation on them. The first part, if I just look at this example here, connect, is the trigger event which caused something to happen. That will either be a packet arriving or a socket API being called. And here, someone has called the connect socket call. Then there's a slash, and it's followed by an action. And this action is something which will be done in response to the trigger. In this case, a SYN packet is sent out. Okay, so the purpose of this, so this connection state machine will be run both at the client and at the server. Each of these hosts will be running its own instance of this machine and independently walking through states. And we would like a connection establishment to go from the closed state, when no one is connected, to the established state on both sides, so that after the three-way handshake, both sides think that they've moved from closed to established. Let's just try and follow this diagram and see the path through this sequence, through this finite state machine if you're a client. Okay, so the client is going to start here. Now, what will the client do? It was the active party that's initiating the connection, so it's going to call connect. That will take us on this transition line here down to the SYN sent state. And as part of that, the trigger was connect, but the action is send, so the client will send a SYN to the server. We're now in the SYN sent state, twiddling our thumbs, just waiting for something good to happen. What could possibly happen? Well, this bottom transition is what is going to happen if all is successful. And you can see this bottom transition is triggered by the receipt of a SYN ACK from the other side. That's the server applying with its own SYN and acknowledging our ACK, the client's ACK. Okay, so we'll make this transition here, and you can also see that in response to receiving that packet, the client will send out its own ACK, answering the SYN from the other side. And the client will then proceed to the established state. So the client is there, the client's being connected. What about the server? What's the path of the server? Well, on the server we started in this closed state initially too. Now, the way we got out of that was that on the server, as part of setting up the server, we called listen. That triggered this transition to the listen state. There was no action, no external change, nothing was sent out. The server was really in this listen state just waiting. So it's going to sit here and wait and eventually hoping that something will happen. And it does when the client sends in a SYN. That's this SYN arriving here. We will then take this transition down here to the SYN receive state. We get the SYN in and we will reply by sending our own SYN ACK back. So now we're in the SYN receive state. We've sent our SYN ACK. We're just waiting around. If all goes well again, then the client should reply with an ACK, and that will cause this transition to happen. The ACK causes the transition, we do nothing, and we arrive in the established state. At this stage, both the client and the server should have proceeded from closed to established, and this is how a connection gets set up. Here is just the time sequence diagram that we looked at before. This time it's shown with the states on either side. So you can see the client started and closed. The connect must have been called here. And that caused the SYN to be sent, transitioning us to SYN sent. And when we got the ACK back, we went to the established state and we were good. So actually at this point here, the client considers the connection to be open for business as soon as it's replied and sent its ACK in response to the server's SYN. On the other side, we started and closed, and the server must have called the listen socket call in here. That's what moved us to the listen state. And then all of the other transitions are based on packets coming in and so forth. Okay, so that's the connection state machine. These finite state machines are a useful tool for specifying all of the different states that the client and the server or the different parties in the state machine can reach and handle all cases. We looked at just one common case, but actually, and here's something interesting, the TCP connection state machine handles the case where the client and the server happen to decide to open a connection to one another simultaneously. In this case, it's probably better described as peer-to-peer rather than client-server. But TCP should support any model, even the case where two sides decide to open that connection simultaneously. If you investigate that case in the connection in the connection state machine, you should find that it will work and both sides will go from closed to established in the connection. You can try that for yourself at home and check that it works. G'day viewers. In this segment we'll talk about how to release connections. Well, we've talked about how to set up connections with TCP, so now it's time to talk about how to tear them down. In connection release, the main task is to close down both sides of the connection in an orderly way so that all of the pending data is delivered before both sides hang up, as well as cleaning up any state that's left over in the sender and receiver. So the key problem here is to provide this reliability to deliver the pending data in a nice clean way while doing the release. In TCP, we use what's called a symmetric close to handle this problem, where either direction of data transfer closes itself independently. So it's possible to have connections which are half open temporarily on the way to being closed. So here's how connection release works with TCP. To ensure that the data is delivered properly, we don't want one side or the other to simply just hang up anytime it wants to. When one party decides to end the connection, that's called the active party, they proceed with this sequence. They send what's called a FIN to the other side. It stands for finalize. X, the sequence number here, will be whatever sequence number we happen to be at in the connection. So it's not a random number like it was for opening the connection. And the other side will then ACK this, and again it will ACK X plus 1 because the FIN is considered to occupy 1 byte of sequence number space. And we're going to ACK the next expected byte. So at this stage, the connection has been closed in the direction from the active party to the passive party, but it's only half closed. We also have to perform the second step and do the same procedure in the reverse direction. So the second party now, when it decides that it's had enough with this connection, because after all, when one side hangs up, there's really not much more you usually want to do, the second side will send its own FIN. That will have a different sequence number Y, and the active party will wait until it can be ACKed, and at this stage the connection is closed. You could imagine that this FIN and ACK in the middle could be combined if you like. Often they're separate packets just because of the logic, but they could also be combined into one packet as they were with the SYN and the ACK. Here's a cleaned up version of that diagram just to show you. I note here that the FINs can be retransmitted if either of them were lost. Just like all data segments, they can be lost. So if you want to do something with them, you might need to provide a little bit of reliability. And just like the connection establishment, there's also a part of the connection state machine that's used for releasing the connection. As before, both the parties, the client and the server or whoever is interacting, run their own instance of this state machine. And to hang up, we want them to both move separately from the established state to the closed state. This is the release that we want. We just have to get there somewhere. Let me also remind you that in the state machine, rectangles, such as the ones I've outlined like established, are the states in which the connection finds itself, and the arrows between them are the transitions. The first portion on an arrow is the trigger action, such as receiving a FIN segment. And the second portion on those transition arrows after the slash is the response or the action that the party takes, such as sending an ACK. Okay, so let's use this state machine, just as we did for connection establishment. And now look at how the active party can close the connection in the direction from itself to the other side. We're going to start in the established state because that's where we were when the connection was running. The active party decides to do a close, calls the close socket call. That's here, and that's going to take us on this path. As part of this transition, we send a fin packet to the other side. Now we're in the fin wait 1 state. We wait in this state for a little while, and what are we waiting for? We're waiting to receive an ACK from the other side. When we receive an ACK from the other side, we need to take no actions, and we move to the fin wait 2 state. Here, what are we waiting for? Well, actually, by this state, we've closed the connection in the direction from ourselves to the other side, and we're just waiting around for the other side of the connection to close the other direction so we can clean up all of the state and go home. That will happen when the other side sends a fin here. When we receive that, we'll take this transition path, we'll send back an ACK, and we'll go into a time wait state. And then later, after some amount of time has passed and a timeout occurs, we'll go to the close state and we're done. I'll get to that timeout in just a moment. You can see here, by the way, that there's a different path through here. If I just look at this arrow here, you can see this is what happens if you combine the fin and the ACK together. We still get through the state machine in the right way. The right thing happens. Let's look at the passive party. It started in the established state. And then at some stage it received a fin from the other side. That's this input here, which caused a transition to this state, a passive closed state, and we replied by sending an ACK. The other side doesn't want to talk to us anymore. We've acknowledged that. At this point, the transport layer is in the closed wait state, and it's just waiting around. And what it's waiting for is the application to realize that no more data is coming in on this direction of the connection. If the app calls receive, it will find there's no data there, that the connection's ended. The app then at some stage will issue a close socket call. That will move us down to this state. We'll send our own fin, we'll go into the last ACK state. We will wait. What we're waiting for is to receive an ACK from the other side, the ACK for our fin. That will take us through here to the closed state. And we don't have to do anything, we simply move to this state and the connection has been closed. Yes, so both sides, the client and the server, have now both gotten from established to closed. By the way, either of them could have chosen to close the connection first. Which case occurs just depends on the application protocol itself. And here is another version of the time sequence diagram we looked at before with all of the different states on it. So you can see how we moved from established here to here. The close must have been called. That caused us to send the fin, move through states, and then progress through the states as new packets were added. On the other side, after we had received the fin and sent back the ACK, we went into the closed wait stage. At this stage, our app should work out that something is up and that there's no more useful information on the connection and call close. And when it does, we'll send our fin, get our ACK back, and we're done. Now you might notice there is a timeout state here. So a period of time elapses between the last action there and entering the closed state on the active side. What is all of this about? Well, this timeout is potentially a long wait. We actually wait up to twice the maximum segment lifetime. The maximum segment lifetime is the largest amount of time it can take a segment to be delivered through the network. So we're really waiting just in case there are any last packets going on. What could have happened is that an ACK might have been lost, the ACK we sent. In that case, sometime later we will get a fin from the other side. So we're waiting around just in case that happens. If that did happen, then we would like to catch that fin and respond to it so that we'll have a nice orderly close and tear the connection down properly. If we didn't, we might interfere somewhat with a subsequent connection. And that's why TCP uses a time wait connection, just as a bit of a trade-off to go the extra mile to try and make sure that the connection has been closed properly. And now we've torn down the connections. G'day viewers. In this segment we'll talk about the sliding window algorithm for reliable data transfer. So the sliding window is one of the most well-known algorithms in computer networking. It combines pipelining for performance with reliability. And it does this by building on what we've seen before, the stop and wait algorithm, which used ARQ, automatic repeat request, with a window size of 1. Okay, so let me go back there and start at the beginning. I said that ARQ, automatic repeat request, well, that's a mechanism that provides reliability by retransmitting packets or segments or frames, depending what layer you're operating at, until they're acknowledged by the other side. So it ensures they'll get through. Now with stop and wait, which we saw before, only one message can be outstanding at a time. Here's the time sequence diagram for the normal case where nothing is lost. You can see the sender sends a frame and it numbers it, number 0, and that comes back, and then we're happy. The sender knows that frame has made it to the receiver, so the sender can move on and send the next frame. That's frame 1, and an ACK will come back for it eventually, and so forth. There's a big limitation of stop and wait, however, and that's the fact that only one frame can be outstanding in the network at a given time, at any time. Now, this is fine if we're talking about a local area network, because the propagation delay over a local area network is usually small enough that that sending a single packet fills that network, it uses it well. On the other hand, imagine an internet path where we might have a bandwidth delay which is much greater than one packet. In this case, the packet will only fill a very small portion of the network path and will be using the network inefficiently. This is similar to the picture you can see here, in which there's just this small packet in the midst of a long network path between two hosts. So let's take a look at how much of a limitation this is. Imagine that we have a network with a rate of 1 megabit per second, that's the capacity of the network, and the propagation delay is 50 milliseconds. So the round trip time will be 100 milliseconds. How many packets a second can we transfer reliably over this network using sliding window? Using stop and wait, which will turn out to be a sliding window of size 1. Well, I can see by inspection that if it takes 100 milliseconds, that's a tenth of a second to send a bit to the other side and back, then at most we'll be able to send 10 packets a second. Now, if every packet is 1250 bytes, chosen so that's 10 kilobits, that is going to be an information transfer rate of 100 kilobits a second. That's not much considering that the network path could handle a megabit per second. So we're only using a fraction of it. We're using about 10% of the network path's bandwidth. Suppose we upgrade the link to be 10 megabits per second because we just want everything to be faster. How many packets could we send? Again, the answer is 10 packets a second. Why? Because they were constrained by the round trip time. The bandwidth really didn't affect them at all. This is going to be the same, 100 kilobits a second. And now it's actually going to be more like 1% of the capacity instead of 10%. So for our fast and long networks, stop and wait really uses them inefficiently. Okay, so sliding window generalizes stop and wait and considers that to be the special case of a window size of 1. With sliding window, we'll allow a window of up to W packets to be outstanding at any given time. By the way, I'll talk for the sliding window about either frames, packets, or segments as is convenient, since this algorithm could be used at either the link, network, or transport layers. We're really using it at the transport layer, that's what TCP does. But since we're building on ARQ and we saw that at the link layer, you'll still see frames, and I'll sometimes talk about packets. Now, with a sliding window and a window of size W, that means we'll be able to send W packets per round trip time. The pipelining here that we're getting by sending multiple packets at once is what's improving performance for us on the network. To use the entire network path, so if I have a rate of 10 megabits per second, to use all of that, then I would want the window to be large enough so that I could send so that it is the same as 2BD expressed in packets. The reason for this is that we said you can send W packets per round trip time. A round trip time is really 2D. If we want to send it the bandwidth, the full rate, then we want to send B bits per second for those RTT seconds. Multiplying it all together, we get 2D up here times B for the bandwidth, which is 2BD. That's the amount of data that can be transferred over the path in one round trip time. So if we set W to that, we'll be able to send at that rate. Let's see what kind of window sizes this implies to get it working. So what window size W would we like to use to fill up the network, to use it to its capacity? For the examples before, now with a rate of 1 megabit per second and a delay of 50 milliseconds. So we would like W to be equal to 2BD, that is twice the bandwidth times the delay. I'm just going to multiply the bandwidth first, that's 10 to the 6 bits per second, and twice the delay is 100 milliseconds, so that's 100, 10 to the minus 3 seconds, so that's 100 kilobits. Kilobit. Now expressed in packets, if a packet is about 10 kilobit, that's 1250 bytes. This is about 10 packets. So to use the path fully, we needed to have a sliding window size W of about 10 packets rather than the one packet in stop and wait. And this is what you might imagine, since we worked out before, we're only getting to utilize about 10% of its bandwidth. So we were off by a factor of 10. Now, what if we increase the rate to 10 megabits per second? Well, I could do my W equals 2BD calculation again. This is a W. And actually, the only thing that's happened is the rate, which is the B in this equation, has gone up by a factor of 10. So it's going to be 1,000 kilobit, or approximately 100 packets. So you can see that I would need a reasonably sized sliding window to fully utilize this link, and the sliding window would just have to get bigger for faster and longer links. Okay, so here's all of this tidied up, and hopefully I got all of the math right. So let's now talk about the sliding window protocol in a little more detail. We've just said that there are these W packets outstanding, but how exactly does it work? Actually, there are many variations of the sliding window protocol, depending on exactly the way you want to handle the buffering, the acknowledgements, and the retransmissions. I'm going to sketch for you two versions. One is called Go Back N. This is the simplest version. It's not terribly efficient when there are errors, but it's quite simple and you don't have to do much at the receiver or sender. And I'll also talk about a version called Selective Repeat, which is a little more involved, especially at the receiver. But on the other hand, it gives us slightly better performance. Or actually, it could be a lot better performance in the case when there are errors. So this is what happens at the sender. Now, the picture below is showing you the buffering as a function of the sequence number space. So sequence numbers go up to the right here. So this is the segments of data go along to the right here in this picture. The sender is allowed to buffer up to W segments of data until they're acknowledged. So this is information that's been sent and not yet been acknowledged. The sender needs to buffer this because if it's not acknowledged, the sender is going to have to retransmit it, so it better have a copy. We'll express the sliding window with a couple of state variables. One is going to be LFS, that's the last frame sent. That's here, so it's the highest numbered segment which has actually been sent out but not yet acknowledged. The other variable is LAR, the last acknowledgement received. So that's the number of the highest in-sequence acknowledgement which has been received from the other side. And our sliding window allows us to, it has a buffer of up to W packets, so we can have a difference between LAR and LFS, that's the number of packets we've sent into the network that haven't been acknowledged, of up to W packets. You can see here is the sliding window here, and we actually have 4 packets out in the network, the window's 5, so actually we could fit one more. All of the segments before the left side of this window, we're finished with them. They've all been sent through the network, acknowledged by the other side. We've got the acknowledgement. They're done. They're finished. And to the right side of this sliding window, there's segments that we can't yet send because our window is not big enough. Okay, so this is the sliding window. It evolves as we send new packets and receive ACKs. So a couple of things could happen here. What could happen? Well, one thing that could happen is the transport layer could accept another segment from the application, and that would be this segment here. And in this case, it can go ahead and send it. Why? Because we only had 4 packets outstanding in the network, and our sliding window size is 5. If we send this one, now we have 5. And you can see I've updated LFS here. I haven't updated LAR because we haven't received any acknowledgements. So now our window is full. At this stage, we can't send any more segments, new segments, into the network until some of the old segments which are in the network are acknowledged. Here's something else that can happen. We can receive the next higher acknowledgement. Now, you might have noticed that LAR has moved along. We actually received an acknowledgement for this packet here, this segment here. So LAR now points here. I've not colored that pink anymore because we can free that buffer and throw it away. So in fact, now we only have these 4 segments outstanding in the network. And you can see that this sliding window is still size 5, but it's slid to the right. That's why it's called a sliding window. It moves along. That's opened up space for us to send one new segment into the network. And there you are. That's how the sliding window is operating in the normal case at the sender. You can see it moving along, sending new segments into the network as old segments are acknowledged. Let's look at what goes on at the receiver, because we just saw the sender half there. And recall I was going to describe 2 different variations for you. The first variation is go back in. And it's very simple. It's actually the simplest sliding window receiver implementation. Here, the receiver only keeps a single packet buffer, segment buffer, to put the next segment in. So it passes, when it gets the next segment, the right segment, it passes it up to the application. So the application sees data in order. All we need here is one state variable, LAS, the last ACK sent. And what we're looking to do is receive a segment which is the next one beyond that. So this is what happens when a segment is received. We look at the sequence number. If it is the next one, then we accept it. We put it in the buffer. We pass it up to the app as soon as the app can take it. We update LAS. This is now climbed up by 1. And then we send an acknowledgement to the other side to say, yep, got LAS plus 1. If the sequence number is anything else, then we can simply discard it and not worry about it. In effect, there has been some kind of error. If it's something else, then a segment has been lost in the network. And the sender is going to work that out and retransmit the lost segments. We'll see that in a little while. Well, now let's look at a different version of the receiver for a selective repeat receiver. This is a receiver that does a little more work, but can use the network capacity more effectively when there's loss. So here, the receiver still passes data up to the app in order, but it buffers out of order segments to reduce retransmissions. So instead of having a buffer of size 1, it's going to have a larger buffer, and it will take segments in there even as they're not the next one, and it will hold on to them. So that way, when it later gets the segment that was missing, it will be able to send those segments up to the application in order. The ACK number we use is still going to convey the highest in order segment that's received. So it's still like LAS. It's that bottom edge of the sliding window. Plus, depending on the variation, it's quite common to send hints about which out-of-order segments have or haven't arrived. This is going to allow the sender to do a better job by understanding what packets or segments might have been lost. TCP actually uses a selective repeat design, and we'll see some of the details later on when we get to TCP. But let me say a little more about selective repeat at the receiver yet. I haven't really said how it works. Here's how it works. It has a buffer for up to W segments. W is the same size as the sliding window. That's the largest number of segments which could be outstanding at any time. And we're going to use the same one state variable, the last acknowledgement sent. When you receive segments, if they fit in the window from the next segment, LAS plus 1, or actually any of the next W segments from +1 to +W, then you buffer them. You put them in the buffer you have. Then you look at your buffer and you see if you have any segments in order, starting at LAS +1 and onwards. If you do, you pass up those in order segments to the app and you update LAS to push it up to the highest segment which has been delivered to the app. And then you send an ACK for this LAS, regardless of whether it's a new LAS because it's moved or it's the old LAS. If it's the old LAS, you're really making the channel a little more reliable by repeating the acknowledgement, so that the sender, even if it's lost some ACKs, since every ACK here is really telling you that you received all segments up to and including this segment, if we get any of them, we have some idea what's going on the other side. We don't have to get them all. Okay, so now we've seen the receiver a little bit. We've seen the sender in the normal case. We haven't seen the sender with retransmissions. What happens when there is loss? Well, this is what happens. In the case of the go back N sender, we can simply use a single timer to detect losses. If a segment is not acknowledged after some timeout, then we assume that it's lost. In that case, all segments after it will have been thrown away by the receiver. So we simply start resending the buffered packets from LAR +1, the next acknowledgement which we wanted to receive. So we're going back N. We're basically going back the whole window, up to the whole window. On the other hand, in a selective repeat sender, because we're buffering packets or segments out of order on the receiver on the other side, we can retransmit them individually. So we can have a timer for each different segment, and when that goes off, we can retransmit that segment if that segment hasn't been acknowledged. The hope here is that we'll resend fewer of the segments, because we might time out and send one segment, but if many other higher segments have been received by the receiver, pretty soon we'll get acknowledgements telling us that these new segments have been received, so we won't need to resend them. Okay, so now you've seen the sliding window operation for a couple of these variations. One more detail I need to tell you about the sliding window is the sequence numbers. Remember, for stop and wait, we simply needed two sequence numbers, 0 and 1, and we can alternate between them. That's not going to work for a sliding window size W, because there can be more than 2 packets in the window, and we need different sequence numbers for every packet in the window at least. So how many sequence numbers do we need? Well, for selective repeat, if we're sending up to W packets, then they can be outstanding in the network at one time. We need at least W sequence numbers for these outstanding packets. Now we can also, at the same time, the network can be carrying acknowledgements up to W them for earlier packets which were sent with earlier sequence numbers. Altogether, W plus W, we need at least 2 W sequence numbers. Turns out with go back N, you can need fewer, because we won't have all of those ACKs outstanding at a time. We can only have, an ACK for one thing outstanding at a time. But it doesn't worry too much, because usually we would not get too tight on the number of sequence numbers we need. Typically, sequence numbers would be implemented with an n-bit counter. That's a number that would simply climb up to some power of 2, and just as it is about to get there, it will wrap and go to 0 again. So for instance, an 8-bit counter might count up to 255, 253, 254, 255. That's the highest number you can represent with 8 bits, and then it will wrap and go down to 0, 1, 2, 3 again, and so forth. So it's a modulo counter. As long as we have enough bits to cover the range here, we'll be fine with our sequence numbers. And finally, just to show you a little more about how sliding windows work, we're going to look at a sequence time plot for the sliding number sequences. This graph shows the evolution over time on the y-axis of the sequence number. Time on the x-axis of the sequence number on the y-axis. Now if you look at these curves, this blue curve gives you a line for the transmissions of the sender. And you can see here that the sequence numbers are going up over time. Over time, it's sending newer, more highly numbered segments. There's also another staircase here, and that's for the receiver. These are the acknowledgements coming back. And you can see that after some delay, the ACKs come back for the same number of packets that were already sent. This delay here, sorry, this is when the receiver sends the ACKs. This delay will be D, or the round trip time on 2, because it will take about that long for the segment to go through the network for it to be acknowledged. So that's how you read these diagrams. And now something funny is happening here. We'll look at that in just a minute. Okay, so let's look at it. This is a hypothetical sequence number plot for a go back in scenario. If everything's going fine and there's no loss, we have these two parallel lines or staircases. They're going in fine steps going up. We're sending and we're being acknowledged a short while later. But now something funny happens here. What happens here? Well, we must have loss. That's because the acknowledgement number stops going up. So something's been lost and there's a hole in the receiver. There's some, well, since this is a go back in scenario, the receiver couldn't get the next ACK, and so it's not sending further ACK. So this ACK number is not climbing. What's going to happen then? Well, when maybe this segment was sent, there's no ACK that comes back for it. After some amount of time, this is a timeout, the receiver will work, the sender will work out there's a problem. This timeout is going to be approximately the RTT. I mean, that's the minimum it could be, because that's the shortest amount of time you could take to send a packet and get an ACK back from the other side. So a timeout needs to be longer than that. The RTT is the minimum. But you can see here, if 1/2 was the delay, this is about 2D, which is the RTT. After that time, the receiver, it's hard to work through these things. After that time, the sender will time out and it will start sending these things again. So up through here, these are all retransmissions. That is, they're segments which we sent previously, we're now sending them again. And after another short delay, across here at the bottom, the receiver will start sending acknowledgements for them. And it looks like we get those acknowledgements because we keep climbing up here and there's no more loss and we keep going. So as you can see, there's a lot of information in this time sequence diagram if you know how to read it. This is just one scenario for the possible evolution of a sliding window. There are many others, but I hope from this, this lecture you have a sense of how the sliding window works. Oh, and you can see here I've cleaned it up, and hopefully I've gotten all of those inferences from what's going on correct. G'day viewers. In this segment we'll talk about flow control. Flow control is an addition to the sliding window to deal with the problem of making sure that the receiver can handle the data that the sender is sending to it. So it's going to provide a way to slow down an over-enthusiastic sender. You might wonder whether this is a real problem. Do we need to worry about receivers not being able to handle data fast enough? Well, yes, actually. So the sliding window is already using a lot of pipelining to make sure we keep the network busy. But what we want to do with flow control is make sure that in doing so, even though we're keeping the network busy as we can to use it all, we're not inadvertently overloading the receiver. You might have, for instance, a small mobile phone that's got to be a little wimpier compared to some big powerful server in the cloud, which could send data at it possibly faster than the phone could receive. We'd like for our protocols to be able to handle this case. Okay, so let's zoom in on the sliding window and how it works at the receiver. So this is a receiver where we have buffering for up to W buffers for out-of-order packets. Now what is going to happen in the normal case is that we'll have a sequence number. This is here, LAS, the last ACK sent. That is going to be the highest in order acknowledgement that's been sent. And as we receive new data, it's going to go into the buffer and then we'll pass it up to the app. The app will actually pull the data out of that buffer and we can slide our sliding window and go ahead. How does the app actually pull the data out of that buffer? It turns out, we can relate this to sockets, it's done with the receive call. So an app needs to call receive. to get the data out. Hopefully it called receive before because it was expecting data and it's just waiting to get it. But let's see what can happen under this model. Suppose that a couple of segments arrive from the network, but the app is a little slow calling receive, so the transport can't pass them up to the application right away. Maybe the app was busy for some reason. Well, two segments come in, that's these two here. Okay, so they're now full. My LAS is going to go on to here. Right, so this is now LAS. However, we can't really slide the window yet because we haven't been able to offload these two segments and pass them to the app. As soon as we've done that, we're fine and we can move the window along. But if the app's slow, we can't send them along yet. What happens? Oh, so here's a cleaned up version of that diagram. And the conclusion here is we can't slide the window just yet. What happens now if before the app gets its act together and calls receive, more segments come in from the network? Here you can see another 3 segments arrived here. They went into the buffer, we had room for them, we updated LAS, great, but we still haven't passed them to the app yet. Now, this actually means we're in a very unfortunate situation because if more new segments arrive from the other side, we don't have a place to buffer them. We'll have to throw them away. That doesn't sound very good. But luckily for us, the app now takes 2 segments. So that must have been these 2 segments here. They are now shown as white because the data is being passed up to the app. So this means we can slide the window along from its left edge being here to where it is now here. And now we have another couple of buffers available for new segments coming in from the other side. Phew, that was great, just in time. But you can see we got lucky in this scenario, and with a slow receiver we could easily get unlucky. What we would like to do with flow control is come up with a mechanism whereby we avoid these kinds of losses at the receiver. And we can do that by simply telling the receiver how much buffer space is available. So what we would like to tell the receiver is that, for instance, here there are 3 buffer spots available. That's this win, the flow control window, which is the number of acceptable segments or the buffer size there. We want to tell it that. And not information about W, which the sender knows anyhow. And this win number of acceptable buffers, they're measured from LAS, from where you sent the last act, because they're the next higher segments which could be received. So all we'll do with our flow control protocol is simply send that information back. As well as the acknowledgement, we'll send this win information, the flow control window. The sender will then use the lower size, the smaller size of the actual sliding window W and the flow control window win. And it will pretend that the effective size of the sliding window is this size. Either of these factors could be the limiting factor. For instance, we could be limited by the amount of space in the flow control buffer at the other side, or if we had a big fat buffer, we could be limited by the size of the sliding window that the sender is using. So either of these could be the minimum. So I'll now show you an example of flow control just to put it all together. And this is a fairly long example, so it'll take us a little while to go through it. It's also a TCP style example. Here we use a sequence number and an acknowledgement number for the sliding window. These are both measured in bytes, they're byte positions. The flow control window is carried in a variable called win. And the invariant that we need for flow control is that the byte sequence number plus the length of the number of bytes we carry in a segment needs to be less than the ACK number plus the flow control window. Because if it's larger than that, it may not fit in the buffer on the other side. The receiver here also has a 4 kilobyte buffer, and it's a circular buffer. So the network fills it up round and round and round, and the application reads from the tail end of the buffer going round. So let's see how it works. The beginning, then we have the app sending 2 kilobytes here from a sequence number of 0. So that goes into the buffer. What goes back? The ACK goes back. This ACK is for 2 kilobytes because that's now the end here of the buffer. the next place to write into it. And our window has gone down to also 2 kilobytes because that's what's left of the 4 kilobyte buffer. Okay, that's fine. Now after a little while, the app does another send of 2 kilobytes. What happens then? Well, we filled in this buffer, so you can see the write head has gone around to the beginning of the buffer again. And the ACK that's going to come back is going to acknowledge the end there. We got to 4K of data has gone through. The window, however, is now 0. There's no space left in the buffer. So the sender at this stage, right here, actually from the very beginning here, when it went through, it knew that it had filled up the buffer on the other side, and so it was waiting for information from the other side to say there's a little more space. It hasn't received it yet, so the sender is blocked at this stage. Sometime later here, our buffer is full. We haven't done anything with it yet, but sometime later here, the application will do a read. It will read from the beginning of the buffer through, so it will read up to here. That's 2 kilobytes. If that's the case, we now have 2 kilobytes free. So we will, I'll just draw over that one. We did send that back. But now, after the application reads data, we're going to send another ACK back. This ACK will have the same acknowledgement number because no new data has been received from the other side, but the window will be updated to say, hey, there's now 2 kilobytes of free space in this buffer. When the sender receives that here, the sender knows that it can actually send some more data if it wants. It feels very happy and pleased about this, and it decides to go ahead, and now it sends another 1 kilobyte of data from the sequence number of 4K. That 1 kilobyte of data goes into the buffer there. So we filled it up just a little bit there. And you can see we now have 1 kilobyte left. So if I was to go a little further here, then you would see an ACK. You can do the math here for 5K. And a win, what do you think it will be? It should be for 1K because that's all that's left. So both of those will be on here. Great. Okay, well that's the end of our example, and now you've seen how flow control works. G'day viewers. In this segment I'll talk about how to set the retransmission timer. So this is a fun little topic. All we're trying to do is set that timer to decide when a segment is lost and when to retransmit. But it turns out that to do a good job of that, we need to be able to adapt to the conditions on the network path. Here's the overall context for our topic. We're using a retransmission strategy as part of the sliding window. And the way in which we detect loss and hence decide to retransmit is by using a timeout. So we simply set a timer when a segment is first sent. And if an acknowledgement comes back, this is the normal case, then everything's good and we can cancel that timer. However, if the timer goes off, it means no acknowledgement has been received. We decide that the segment most likely has been lost and we retransmit it. So that's all the timer is used for. The difficulty that we're going to talk about in this lecture is how to set the value of that timeout. It turns out that it's important to set it to an appropriate level. If it's too short, if it's too long case first, then we'll end up wasting the network capacity. Because by the time the timeout is gone, our network path may have been idle for a long time when we could have usefully sent information. On the other hand, if it's too short, we'll decide to retransmit early when actually the packet had got there, it's just that the acknowledgement was coming from the other side. So these early retransmissions add load to the network when maybe the round trip time had already gotten high, and they're also somewhat inefficient. So we'd like to avoid both of these cases. So how do we find this value that's just right? Now, it turns out that it's fairly easy to pick a value on a LAN. That's because the round trip time is usually fairly short. It's also fairly fixed and predictable. In the internet at large, however, it's much harder to pick a reasonable retransmission timeout. And that's because the RTTs can be much larger And they're also, it depends, they can also be short, and it's also the case that the RTT is much more variable over time. Both of these factors make it difficult to pick an appropriate retransmission timeout without erring on the side of being far too short or far too long. Well, let's look at a little bit of data to see that issue. Here's some data I took by using the ping program to send packets along the path from Barcelona to Seattle and back to Barcelona. And you can see on the y-axis here, we have the round trip time in milliseconds. And on the x-axis there, we just have time in seconds. Wow, this data goes up and down. It's a little surprising, isn't it, to see? So actually, there's a lower bound somewhere around here. This would be essentially the propagation delay. Plus maybe the time to transmit a packet, but if that's small compared to the propagation delay, this is mostly the propagation delay. So this is the minimum time that it could possibly take to send a packet along that path and get an ACK back. I keep saying packet, but here I'm really talking about segments because we're in the transport layer. Nonetheless, a message on the internet. There's also a lot of variation. Sometimes the round trip time from sending a packet and getting the ACK back is short. It's near the minimum, but at other times it shoots up, and you can see it bounces around quite a lot. This variation comes from many possible sources, but most likely from queuing. When packets get queued inside routers and they compete with other traffic from different flows, and it takes them a while to cross the network. So the round trip time really does jump around. For here it's moving from around 200 milliseconds to almost 900 milliseconds. So that's a substantial variation. Let me clean that up there. And this is the original data. So now we would like to pick those timeout values. What should they be? Well, here are just some fixed values I could pick. If we pick something down on the low side here that covers much of the data and is not much higher than the propagation delay, you can see that it still loses out a lot of the time. All of this area here, we would be deciding that packets were lost and retransmitting them even though they'd gotten through. It's just the delay in the network was higher. This probably means that the network is busy, so this is not really a very good time to be sending a lot of extra traffic. So we could use a higher timeout. On the other hand, if we set our timeout to the maximum we see over a period of time here, we're really, if a packet is lost due to some reason, corruption, we're really spending a lot of time in here and here, unnecessary time to decide that something's happened to that packet. So neither of these are good. What we would like to do is adapt our choice of timeout to the actual network conditions. So over time, we would like to move from low to high, back to low again. That's what we want to do. How are we going to do that? Well, I'm glad you asked. We're going to use an adaptive timeout. Now the math looks a little hairy here. Don't worry, actually, it's fairly simple when you get used to it. For this adaptive timeout, we will simply keep smoothed estimates of the round trip time. So that's going to be like a moving average, just to keep its average value. And we'll also keep an estimate of the variance in the round trip time, because not only is its absolute level changing, but also how variable it is can change over time. So we update these estimates with a moving average. Let's look at this first one here for SRTT, that's the smooth round trip time. This equation says that the way we update the smooth round trip time estimator over time is we take 90% of its former value, that's the 0.9 times, and we feed in 10% of a new sample. That new sample is just the latest round trip time measurement we have. And this has the effect of, this is like a low pass filter, it's really averaging it and throwing away a lot of the ups and downs. We'll also run a similar estimator for the variation, and for this we simply keep 90% of our estimate for the variation from the last time, that's this factor, and then we fold in 10% of a new sample. And the new sample can just be the difference between the round trip time we just got and the smooth round trip time, because that's some estimate of how much it's jumping up and down. This is technically the deviation. Once we have these estimators, they sort of tell us roughly what's going on with the round trip time. And we can then set a timeout to be some multiple or combination of these estimates. The idea here is to come up with something which gives us a good prediction of the highest round trip time we're likely to see in practice right about now. The estimate that TCP uses, in fact, is the smooth round trip time plus 4 times the variance. It's unlikely to vary the round trip time by more than about that. Well, let's see how this works. Okay, so the blue curve here is our data, and I've overlaid 2 other computations based on the data on there. This line, this higher line here is the smooth round trip time. And you can see that it tracks the blue line just without all of the extrema there, so it's the smoother line in the middle. This line down the bottom, S-var, is tracking the variance in the round trip time over time. And you can see the variance is sometimes fairly low at the end here, but sometimes the variance jumps up and it's quite high, and this is when the signal is going up and down. So our estimator for the timeout is going to be the smooth round trip time plus 4 times the variance. And we hope that that will somehow be something like this. Let's see. Well, here it is. Well, you can see actually it did even a little better than my line. Here's the timeout, so the smooth round trip time plus 4 times the variance. And you can see that on the whole, this stays above the blue curve, but it comes down and it lowers itself so that at times when the blue curve jumps up, it's really not that much higher than the blue curve. So it's fairly tight. Yet it is shooting up fairly rapidly at a time when the round trip times seem to be climbing. Now it looks like just very occasionally our predictor could actually be a little low. If that's the case, we would end up doing an early timeout. However, that's pretty rare. Okay, so just to sum up, these adaptive timeouts are pretty cool actually. They're fairly simple to compute and they do a good job of estimating a reasonable timeout value based on the real round trip time. So they track it. You could see in the previous slide that the estimator went up and down as appropriate. It has little headroom, so it's usually not much higher than it needs to be, so we'll detect losses fast. Yet it also makes errors rarely, so it's not usually lower than the actual round trip time. So we should expect to have very few early timeouts. And even though we don't know it yet for sure, I can tell you that it turns out to be important to have good robustness and performance to have a good round trip time estimator in practice. Okay. G'day viewers, in this segment I'll tell you about the Transmission Control Protocol. And yes, this is it. This segment is about TCP and how it works, the one you've been waiting for. TCP implements a streams transport service that's accessed by sockets, and it's the protocol that's used to transfer the vast majority of content that's used on the internet today. So all of these devices implement TCP as well as IP. Okay, here are some of TCP's features. I'm going to go through some of them a little bit. However, you're already in a position to understand the bulk of them because they use the concepts that we've worked up to at this stage. TCP provides a reliable byte stream service. I'll talk a little more about what that means. That's the service interface. In terms of implementing it, that service is implemented using connections. Okay, we know how they work, how we set them up and tear them down. The reliability is provided with a sliding window that uses an adaptive timeout. Check, we've seen how that works, the sliding window and adaptive timeout. I'll tell you some of the TCP specific details of it though. TCP also includes flow control to help slow receivers handle fast senders. Well, we've seen how that works too. So these are the features that I'll cover just very briefly in this segment. We will next time, later on, we'll also look at another topic, congestion control, which is implemented by TCP. This is to match the sending rate of the sender to the available capacity inside the network. This is a major portion of TCP, but we're going to treat it as another topic just because there's so much there. So really I'm mostly talking about reliability functions today. Okay, so this reliable byte stream model. In a reliable byte stream model, as you've surely guessed, message boundaries are not preserved between send and receive calls. So the bytes that are sent down from the sender they are delivered to the other side reliably and in the same order, so that when you read them, you get what you would expect. But the units in which they're sent down, there are no message boundaries that are preserved. Just as an example of that, you can see here the sender is makes 4 calls to send, and it sends half a kilobyte with every call. So 2 kilobytes are sent to the network. On the other end at the receiver, it would be possible to make a single receive call and receive all of those 2 kilobytes at once, depending when they came in and when the timing of the calls, what the timing of the calls was. This is what I mean by message boundaries are not preserved. It's really a stream of bytes that we're sending from one side to the other. A reliable byte stream also gives us another opportunity to combine things. This byte stream is bidirectional, so we're able to transfer data in both directions. Because of this, on segments, TCP segments that are sent in the network, we can piggyback control information going in one direction with data that's been sent in the opposite direction. Control information is information like the acknowledgement number, for instance. So as you can see here, there is a data segment that's been sent from A to B. It's carrying information. That's great. As well as that, it's also carrying here a little bit of control information, ACK numbers, for the reverse stream of data that's been sent from B to A. That's the packet down here. And similarly, that segment down there is also carrying control information, the ACK, for data that has just gone in the reverse direction from A to B. So these segments are combining information from both directions. It's called piggybacking. It's quite clever. So what we'll do, just to see a little bit of TCP, is we'll look at the TCP header. This is a good way to see the features of protocols. Here's the header shown in this picture here. First up, it has ports. These identify the apps which are using the transport service. We talked about ports previously when we covered the socket API. Here in the header, they carried as 16-bit identifiers. Okay, well next comes the sequence and acknowledgement numbers. These are used to implement the sliding window. TCP uses a selective repeat style of sliding window, and the sequence and ACK number really carry byte positions rather than segment numbers. So that's one difference right there. I can tell you a little more about the sliding window, just in terms of how TCP implements it. The ACK that comes back is what is called a cumulative ACK. It tells us the next expected byte number in sequence. So if you like, according to our Fermat terminology, this is just LAS plus 1. It's telling us the next byte that's expected. In addition, and optionally, TCP acknowledgements can contain selective ACKs. And these are some of the hints we mentioned, sometimes used with selective repeat, that try to tell the sender what's going on at the receiver in terms of its buffer state. SACK blocks in TCP can specify up to 3 byte ranges that have been received beyond the cumulative ACK. So an ACK that's going back from B to A might, for instance, say, "Hi, I'm an ACK, and I'm ACKing up to all bytes have been received up to byte 99, and the next byte I expect is 100. That's the cumulative ACK. And in addition to that, I also happen to have received bytes 200 to 299. So you can see there's a bit of a hole here. We don't know what's happened to bytes 100 to 199 yet. At the sender, TCP uses an adaptive timeout strategy, retransmissions based on this adaptive timeout, to resend the data when that timeout goes out from the highest acknowledgement number, the next expected byte onwards. However, and this is the clever bit for TCP, TCP uses a variety of heuristics to infer loss quickly so that it can resend the data and avoid these timeouts. And it does that by using information in the ACK stream. There is a 3 duplicate ACKs rule of thumb that's used to find loss. Now, what's that all about? Let's see an example, and I think it'll become clear. Okay, so here is an ACK going back. This is just the first ACK for ACK 100. Suppose next we get an ACK for 100 again. That's a duplicate ACK. Our cumulative ACK is not moved, so we've sent the same value again. And in addition, maybe we get a SACK block saying, oh, not only have I got up to 99, so I expect 100, but I've also gotten 200 to 299. Next ACK, number 3, that's another duplicate ACK, because it says the cumulative ACK is now still at 100, but looks like I've received some new data. It's just it was further out. And finally, there is the 4th ACK here, or the 3rd duplicate ACK. It says I'm still at ACK 100, but I've now got also bytes 200 to 499. Well, at this stage, you don't have to be a genius to think to yourself, well, I guess that bytes 100 to 199 have just been lost. That's what happened. That explains this whole. The sender uses this heuristic to decide that that data range has been lost and resend it, hopefully before the timeout goes off. 3 duplicate ACKs is used as a little bit of trade-off because we don't actually know for sure if that packet is late in the network or lost. It could have been late just because it took a slightly different path through the network. So waiting for 3 duplicate ACKs provides a little bit of robustness against some packet reordering. And you can also see here, by the way, that if I simply had the ACK numbers and none of these SAC blocks, I could also make the same guess that the next thing beyond 100, that's probably what was lost and sent it. So TCP uses these heuristics. We'll see a little more about it when we get to congestion control because this overlaps that subject. Okay, so what else is in this header? Well, not too much actually. You can see here there are some flags that are used to set up connections. These are the SYN and the FIN flags. And there's also a reset to abort. These are simply flags because these messages also reuse the sequence numbers and acknowledgement numbers. For instance, to set up a connection with a SYN, the sequence number here is used as a parameter instead of having to carry it elsewhere in the packet. And there's also a window size you can see here that's used for flow control. Like SequentACK, this is measured in bytes rather than in segments, and this is the number of bytes of buffer space remaining, or units of buffer space remaining relative to the value of the ACK. Okay, so that's it in our quick tour of TCP. Now it turns out that there are many quirks with TCP that you can learn about if you study TCP in detail. But in some sense, these are all in the details. We've gone over the main ideas so that you should be able to understand how the sliding window connections and flow control, the key bits of TCP, work. The only bit we haven't really talked about, which is key to the functioning of TCP, is congestion control. And that's a subject we'll get to in the next unit.
Hello network students, welcome to week 2 of quiz sections. So today we have with us Will Scott. Will is a graduate student at the University of Washington and he is a former employee at Google, and he's an expert on all things to do with Google. So today we are going to talk about some tweaks and some optimization that Google does to the regular network protocol stack, and Will is going to tell us about that. So Will, why don't we start with, why are these tweaks required? TCP is a 20-year-old protocol, so isn't TCP/IP a solved problem?
Yeah, so let me prefix my answer by saying that I didn't work on Google's TCP stack, but rather worked on some of their actual products. But I mean, when you think about TCP, TCP is a very broad protocol that is responsible for most of the traffic that goes across the internet. But traffic that is going on inside of a data center is going to look very different from the traffic that goes between your home computer and that data center, right? The computers are much closer together in that packets are going to get to their destination much faster, like a matter of milliseconds, or 1 millisecond, something like that. And also that there's a lot of bandwidth between those, right? Data centers are going to have a gigabit connection between any 2 computers. It's going to be fast. That's like at minimum. And so one thing that you're going to see is that in TCP we've got this slow start mechanism, which sort of probes the connection, sees how much bandwidth is available, and that's something that you need on the internet because you don't know how much bandwidth you've got. But in a data center, you've got much more of that guarantee of what your connection looks like. And so you can set your parameters so that you largely skip that, right? You start with a large window to send so that for most of your connections, they're going to send before you need to wait for any of your acknowledgments to come back to you. And so that lets you be more efficient. And that happens because you have a better sense of what traffic you're going to be sending.
All right, so can you tell us about Anycast? What is Anycast, and how does it work, and how does it help us?
Sure. So Anycast is a way where you can have multiple hosts that all respond to the same IP address. So if you've got a piece of content or a service, like for instance Google, but you can think of any piece of content, and you want hosts around the world to be able to get to that content quickly. One of the problems that we have with the model that we understand so far is that all of the hosts are going to have, all of the computers around the world are going to have to go to one place to get that content, right? The IP address identifies one machine. And that's sort of suboptimal in that you don't really want the computers in Europe to have to go to the US to get their content if you've got data centers in Europe. And so there's a trick that gets played, and it's called Anycast. And what Anycast allows computers and services to do is that they can advertise the same IP address from multiple places. So the BGP protocol, the Border Gateway Protocol, which I believe has been discussed in your lectures, talks about how an AS, an autonomous system, is going to advertise a block of IP addresses that it owns. And so Google can, from multiple places where it peers with other autonomous systems, it can advertise that it owns and has a route to the same block of IP addresses. And so when your host goes to send packets to that IP address, it'll follow the path to the closest Google data center, and so it will end up following that shorter path. And Anycast gets used in a lot of places. It gets used by the root DNS servers and by many sort of replicated, widely available services. It's a common trick that gets played to allow for this locality in global internet services.
Thank you, Will. So before we talk about DO-sensitive DNS and what Google does with it, can you give our students a very brief primer on what DNS is, because we haven't studied the application layer yet?
Sure. So DNS stands for the domain name system, and it's the internet system that lets you resolve a domain name to an IP address. So the google.com or the washington.edu or the coursera.org name that we type into our browser and get used in many applications, when you think about the internet packet and the IP header that you've learned, there's no place for that to fit, right? The destination is one of these IP addresses, like 128.208.4.252 or something like that. And so the DNS system is a set of servers. They form sort of a tree, and the thought is it's a way to resolve one of those names, like washington.edu, back to an IP address that you can route to.
So what does Google do differently from the DNS you just described?
Okay, so one thing that you'll notice with Google, if you look up their record, is that they tend to set the time to live field very short, like something like 5 minutes, or even 1 minute. And what that does is it tells sort of intermediate DNS servers that they shouldn't cache the result very long, that Google's IP addresses are very volatile, that they'll change quickly. Another thing you'll notice is that when you ask for Google, you'll get something like 10 IP addresses back, not just one, which gives your computer some additional freedom in load balancing. But I think the caching is sort of one of the interesting points. DNS ends up caching a lot. There's a lot of sort of intermediation between Google's DNS server and you. Your ISP, your local network tend to cache. And so Google isn't able to directly say, you should visit this IP address when you want to visit us. And that ends up making their traffic management issues tricky, because there's these intermediate systems that they can't control in between the clients and them. Mm-hmm. Another thing that you see from them to try and prevent this is the use of CNAMEs to alias their domain names. And so what they'll do sometimes is that a domain that tends to have logged in users will actually be an alias for some longer, more personal domain. And what that does is it means that your client will sort of save that, and in the future it'll look up that specific domain, and that lets the DNS server route you to the data center that has your data. so that they don't have to move it around to a different data center if your traffic comes up there.
So it seems like the gist of these optimizations that we saw was that in today's internet, the content is more important than finding the content, is more important than finding the right host. So if suppose in a hypothetical scenario, if the internet were to be redesigned and built up from the bottom up today, what do you think would be different?
Yeah, that's a good question. And a lot of thought went into the internet, and we've come up with something that's really cool. I mean, I think one thing that we've noticed, right, is the internet was purposely designed with all of the functionality pushed out to the edges, and that's given us a set of properties. We have really good evolvability. We can evolve protocols without having to change the intermediate, the core routers, and we also get good properties of reliability and availability. But there's other things that end up not working as well in that model. Things like quality of service. So that's when, if you want to watch a video and you want to sort of set up that channel and say, I really want to make sure that the video keeps coming at the same rate the whole time and guarantee that. Or mobility, if you want to be able to move your laptop to different points in the network and have the connections not lose. The internet isn't set up to handle that very well right now. So I guess to answer your question, I think we're at a point in the internet now where maybe we have a better sense of what it's doing now and are happy with that. And so that means maybe we can start pushing some of the functionality back into the middle. I think we're seeing that already with middle boxes. We've got this proliferation of smart machines in the middle of the internet. I think in a ground up design, you'd probably see this as well. Also because we've got a lot of big company players, and that definitely makes their life easier if they have more intelligence there.
Thanks a lot. And thank you for listening to the quiz section, and goodbye.
Thanks.
G'day viewers. In this segment I'll talk to you about congestion and the topics we're going to cover to control it. So we're still in the transport layer, having a little more fun. We've talked about reliability in the transport layer, and now it's time to cover congestion control, which is another major component of it. And we'll also find that this is a topic that's not confined to the transport layer. We'll go back and talk a little bit about how the network layer affects congestion as well. So congestion is like a traffic jam that occurs inside the network. In this segment, I'm mostly going to talk to you about what congestion is and where it comes from. And I'll then briefly mention some of the topics that we're going to cover as we develop mechanisms that control congestion inside networks and prevent it from occurring. So here's an earlier slide so you can just recall what goes on inside routers and switches. Routers and switches have some amount of internal buffering for contention when multiple input packets want to go to the same output. So in this diagram I have a switch in the middle here, or a router. I have the inputs on the left and the outputs on the right. There's buffering inside the router because, for instance, I might at a particular moment in time want to send traffic from 3 different inputs to a single output. Well, in that case, not all of the packets can go on the output line at the same time. Since they've come into the switch on the input line, then they need to be stored somewhere inside the switch. And this is just temporarily until they can go outside the output line. In this picture, there's a simplified view of the internal structure of routers that will be sufficient for our purposes. We can just imagine it as though every output line, every output port has its own queue. So you can see here there are 3 different queues inside the router by the output ports to handle traffic. And as traffic comes in from the input, it goes to the right output and it may be queued. Here are packets queued inside these queues, just because we might have gotten more packets from the input than we could send out the output immediately. And you can see mostly these queues are empty, except for one of them is getting kind of full, and that queue, that output link, is becoming congested. Most of these queues, they could be run in different ways, but the typical implementation of a queue, which we'll consider to be the case unless I say otherwise, is a FIFO queue, or a first in, first out queue. That simply means that as packets or segments come in, they're placed in the queue in the order they come in, and they're sent out such that the first one in the queue is the first one out. And when this queue is full, new packets can't fit in, so they're discarded. So you can see here that the buffering inside routers is actually beneficial. It's there to provide queuing to absorb these short-term bursts, just when 3 input ports wanted to send to the same output port at the same amount of time. So it's beneficial. The routers wouldn't work without them. On the other hand, you should also be able to see that if there is a sustained overload or a long period when the input rate is persistently bigger than the output rate, then those queues will fill. There's nothing else they can do. And when they fill, they will overflow and we will begin to lose packets inside routers. This is congestion. This is how congestion occurs. Now, it's also the case that there's no getting rid of congestion. You might imagine if we just made every link have the same capacity, then everything would be fine. There'd be sort of no mismatches. But congestion is a function of the traffic patterns, because I keep using the example of 3 input ports sending to the same output port. Even if all of the links have the same speed, we'll still need some buffering in routers. You'll also have buffering if, for example, the input ports are faster than the output ports. So you might have 3 packets arrive rapidly, and if they're going at a slow link, we'll also need buffering for that case. Well, that's congestion, but let's think a bit about what happens when it occurs. What is its effect on performance? And this can help us understand why it's actually bad. We know there's a little loss. So let's go through this. I'll go through both the graphs on the left and the right. On the left-hand side, we're looking at the effect of on good put as we increase the load on the network. Good put is simply the amount of traffic, desired traffic, that gets through the network. You could think of it as almost synonymous with throughput. So the x-axis here is offered load. As the offered load increases, what would we like to happen to the good put or throughput through the network? Ideally, it should rise exactly with the offered load. As that goes up, we expect the throughput in the network to go up. And of course, when the offered load reaches the capacity, the highest amount of data that could go through the network, then we would expect that even if you offer more load, the good put can't go up any further. This is an ideal curve, but really the traffic is statistical. It's not very smooth. There are fluctuations. Sometimes we will have queues that overflow. And in that case, the more realistic curve is something like this. So this one was ideal. This is desired. In that there's a slight degradation. You can see there's a bit of a gap here, and in that the performance is falling off a little bit as the load increases. That's because some number of packets are lost as there are fluctuations and some of the queues overflow. As we increase the load too close to the capacity, it gets more likely that we'll lose more packets. So the gap here is growing. On the other hand, what can happen with congestion, and this is where congestion is really bad, is our throughput can go like this, or our good put, can go like this. This is congestion collapse. Now it can be, and this is why I've shown good put on the axis here rather than throughput. Good put is desired traffic that comes through the network. So if you have retransmissions of the same packet through the network 7 times, you only get it to count once as useful information going through the network. In the collapse scenario, because packets are lost, we're retransmitting them. And it's possible, if the protocols don't work very well, if they're not designed for very high levels of load, for us to end up retransmitting packets lots of times and having them lost many times, so that even though we're sending a lot of packets, less useful information is getting through the network, and the network is in a state of collapse. This, in fact, is something that happened in the internet in the early days. So we need to be careful as we're entering congestion here, and as we go up to very high levels of load, bad things can happen inside the network. What about for delay? That's another really measure of performance of the network. Okay, here's the offered load of 1, the maximum. Now, the ideal delay would be something like this. That is, it would be a constant low value that's really the propagation delay across the network. You can't do better than that. However, what we find is that as the load gets closer and closer to the capacity, there's more queuing statistically, and that's going to increase the delay. Initially, and until we get close to the offered load, we will have output rates that are greater than the input rates, and so we would expect there to be almost no queuing. In that case, the delay is really not going to go up much at all. However, as we get close to congestion, those queues are going to start to build. And as they start to build, the delay will build. And as we get very close to the capacity, those queues will be full nearly all of the time, and our delay will go up and up. So our delay goes something like this. Actually, in theoretical models where there's no limit on the router buffer size, they can go right up to infinity as your offered load reaches the capacity. The point is that as we approach congestion, the delay starts to climb up. So here's a cleaned up version of this picture, and you can see that operating the network in a congested state is not good. That's what I would like you to take away. We begin to lose packets, so we have to retransmit more. And we're also adding delay to the packets through the network. So we're not getting any more useful information through, and we're having to spend a longer amount of time to send it through the network. It's a lose. Here's the slide just to summarize some of those effects. Congestion occurs as the offered load rises and those queues start to fill. And it's bad. Delay and loss rise. They can both begin to rise sharply as we get close to the capacity, as the offered load gets close to the capacity. Throughput can also fall because of this loss, and goodput can fall even more if we're sending retransmissions many times, just trying to get packets through the network. This is all bad. So we would like to operate the network before we get to a congested state. We still want to be able to use all of the capacity of the network, so it's a bit of a dance to try and do this, to use all of the capacity yet not congest the network. Okay, so I've actually been talking so far mostly about congestion. That's a problem. The task we're really trying to accomplish, however, is not so much to deal with congestion as to allocate bandwidth. The network has different bandwidth resources inside it on the links, and really its whole purpose, its whole reason for being, is to allocate this bandwidth to different senders to allow them to communicate with receivers. So the problem for the network is one of bandwidth allocation. A good bandwidth allocation should be efficient and fair, and this is going to capture our notion of congestion. An efficient allocation means that we're getting to use most of the capacity in the network. Those links are not idle, we're getting to use them. However, we're not running the network in such a way that there's congestion and a lot of queuing, because we've just seen the bad effects that occur because of that. A fair allocation is one in which every sender who wants to use the network gets some reasonable share of the network. So no one is precluded from using the network. We sort of add this as a secondary condition because you don't want to be efficient simply by choking senders which are problematic for congestion. Now, I'm going to talk just a bit about the bandwidth allocation problem in general now. We'll see solutions to it in the coming lectures. But I'd like to make a few general points for you to remember about it and keep in the back of your mind, because they're important for the solution. One key observation I want to make is this, that to allocate bandwidth effectively, both the transport and the network layer need to work together. That's interesting, isn't it? Because previously many of our mechanisms have been confined to a single layer. Here we need two. Why? Well, we need the network layer because we've seen congestion is something that manifests itself inside routers. That's the domain of the network layer. So only the network layer can directly see congestion and tell someone that it's occurring. On the other hand, the transport layer is the layer that is really injecting the traffic into the network on behalf of applications. It's the layer that's causing the congestion by offering the load. So it's the only layer that can really control this congestion by controlling the offered load. So they're both going to play a part. You might also wonder why this is hard to solve the bandwidth allocation problem. After all, it seems like if you just have a link of a certain value and senders want to use it, we could simply divide the bandwidth and call it quits. Well, it's a little harder than that for several reasons here. Now, the actual number of senders and how much traffic they're sending and even where they're sending to is something which is constantly changing over time as people surf different web pages, go and get a coffee, watch a movie, go out, and so forth. So the workload of the network is something which is always moving around. We don't have any static picture to divide it. What's more, there's no single pie to divide. Different senders, depending where they're sending, can have a shortage of capacity in different places in the network. Where those places are is going to depend where they're sending to, so it's something that can move around too. And not only that, but like our routing formulation, where no one had an overall view of the network, the same case holds here. There's no single party who can see the whole network and look at all of the traffic information and say, here's what we should do. So everyone is just going to have to work based on their partial knowledge of the network. This is a distributed system problem once again. You can see this is quite an interesting and challenging problem. That's what makes congestion such a fascinating topic to study. Okay, so we still haven't got to the solution. It's going to take us many lectures to go over how TCP solves the bandwidth allocation problem. But I do want to give you just a little bit of context for the solutions we'll look at. Much like the routing problem, this is going to be one in which we come up with solutions in which all of the different hosts instead of routers this time, who are sending traffic into the network are going to need to adapt their load on the network based on their own view of the network. So all of the senders are operating independently and concurrently. Nonetheless, we want to design the way they operate and adapt their load such that the network as a whole arrives at an efficient and fair allocation when you sum up all of the independent actions of these senders. And since the offered load on the network is something that's changing all of the time, this adaptation is never actually going to end. We would like it to quickly converge to a good operating point that's fair and efficient, but as the traffic on the network changes, the bandwidth allocation is also going to change over time. Okay, so I've now told you about congestion and framed the problem, so we've covered the nature of congestion here. In the coming segments, we're going to go over a little bit more about what we're looking for in a solution to the bandwidth allocation problem, and then we're going to see different kinds of mechanisms we can use to solve the problem. AIMD is something which will come up as a desirable kind of operating point for allocating bandwidth, and then all of these other topics really have to do with how TCP comes up with a solution to the bandwidth allocation problem. It's a crucial part of its function. Okay, let's see how it all works. G'day viewers. In this segment we'll talk about the fairness of a bandwidth allocation. So our topic is really the question of what's fair anyhow? What does it mean for a bandwidth allocation to be fair? And in particular, we'll talk about the max-min fair allocation. So just a little bit of context before we dive into fairness. We've talked about trying to solve the problem of bandwidth allocation to give different senders bandwidth through the network to communicate with their receivers. We want any allocation that's good to be both fair and efficient. Efficient we talked about when we covered congestion, and we talked about using all of the network but not operating in a congested state. Fairness I didn't really explain. I just said that all senders should get some reasonable share of the network. What exactly does that mean? That's a pretty vague statement. Now, in this segment, we'll learn what it really means to be fair. And I'll give you one caveat while we go into this, and that is that fairness in networks, as in life maybe, is overrated. In practice, it's going to be more important to use the network efficiently than it is going to be precisely fair. Fairness will still matter in some sense, but not at a very high level of precision. Okay, so we have these two different considerations, efficiency and fairness. One of the first things I want to tell you is that they're sometimes in conflict. It's not clear that we could always have both. That's one bit of bad news. Consider this example network. Now here we have three hosts shown in the picture, A, B, and C, and we have three traffic flows. One is simply going from A to B over this link, which has capacity of 1 unit. One's going from B to C over this different link, BC. Again, it has capacity of 1 unit. And one flow is going all the way from A through B to C across those two links. And to solve the bandwidth allocation problem, we need to decide how much bandwidth, how much traffic we will allow to go along each flow. Well, suppose we care about fairness. What should we do? We could simply give all of these flows an equal amount of bandwidth. That way they'll all be treated the same. If we did that, since the limit is 1 unit across each of these links, the best we can do is assign a half unit to all of the different flows. A half to AB, a half to BC, and a half to AC. Because if we do that, you can see that the flow AC goes through B, so we'll have half a unit across each of these links. When we sum it with the other flows, we get up to the total of 1. So in this way, we're actually using all of the network. We've used all of the capacity on both links. Everyone's got the same amount of flow. So we've certainly been fair. In this case, the total amount of traffic that the network carries, which is a measure of its efficiency, is 1.5 units, 3 halves. Okay, well, what if we care about efficiency? If we care about efficiency, this is what we would do. We would want to maximize the total amount of traffic that can go through the network. That's our measure of efficiency. Now, just by inspection, I can see that we can increase the traffic going through the network by simply assigning 1 whole unit to AB, 1 whole unit, that's 1, to BC, and nothing, 0, to AC. In this way, we are able to to grow the total amount of traffic through the network to be 2 units, 1 plus 1. That's bigger than 1.5. So we're operating the network more efficiently. Really, we've done so by penalizing AC. That unfortunate flow happened to go through 2 links, so it was kind of competing a little more for network bandwidth than the other flows. And so if we just set it to 0 and give the bandwidth to the other flows, we can send more traffic through the network. So you can see that fairness and efficiency can leave us at different points. And nonetheless, we're going to want a little bit of each of them and not go to the extreme of caring about efficiency and not caring about fairness. Now, it's actually a little worse than I've been letting on so far, because not only are fairness and efficiency in conflict, but it's not clear what we really should mean by fair. I said equal per flow. Okay, why is that fair compared to other things? For instance, really the reason that there was a difference in our allocations between the first fair one and the next efficient one is that this flow, AC, went through 2 links, so it was using more of the network resources than the other flows. Why should we give it the same amount of bandwidth then? Maybe since it's using more network flows, it should be penalized more, and we should give it a third of a unit and give the other flows 2/3 of a unit, because then everyone will be using the same sort of amount of packet hops or something across links. In addition, so that's one consideration for fairness. In addition, we could look from a host point of view, not a flow point of view. Host A is actually getting to send 2 flows worth of traffic. So host A is sort of getting to send twice as much traffic if we give an equal amount per flow than host B. Well, that doesn't seem right either, so it's not fair in that sense. So as you can see here, fairness is a pretty slippery notion, and it's not clear how we should best define it. Now, I'll also tell you what I'm sort of arguing about this fairness and efficiency is that what we really want to do is avoid starvation. So that allocation for efficiency where AC didn't get to send any traffic at all is not desirable, because we're precluding that flow from using the network. It should be able to use the network to some extent. It turns out that it's really not terribly productive to argue about exact notions of fairness and differentiate between them. And we'll stick with our equal per flow. You can see that there are potentially some problems here, but approximately equal per flow is generally going to be good enough, and that will certainly avoid this starvation problem. Okay, so equal per flow it is. I'd now like to tell you what equal per flow means in a more complicated network setting. We looked at a very simplistic example, and it turns out that it's a little hard to generalize from that example to what equal per flow means across a network. I'll tell you why. So let's start out with a little bit of terminology. The bottleneck for a flow of traffic is the link which is limiting the bandwidth. So for instance, if I have that flow, this is going from A to C through this network, it's going across two different links. Now note I've changed the capacity of one of the links in this network so that it's 10 units. It's a fast link. The former link between A and B is still slow at 1 unit of capacity. For this flow, AB is the bottleneck link. It's the place that's limiting the amount of capacity we could assign to this flow, and it's also the place where congestion is going to occur. That link is going to be congested. So the link AB is congested, meaning that the queues will build up just before it in A, trying to get on to the network. So that's what a bottleneck is. In examples which are more general than the first one we looked at, you'll note that different flows can have different bottlenecks. That is, different flows can be limited by different parts of the network. Here we looked at the other flows in the example. If we look at AB and BC, they go over different sets of links, they're disjoint, so they're going to have different bottlenecks. For AB, the bottleneck link is literally that link AB. It limits the flow to 1 unit of capacity. For BC, it only goes over one link, so that's the bottleneck link. But that link limits the capacity to 10 units. So it's different. It's a different place in the network, and it's a different amount of capacity we have that is at the bottleneck link. So it's no longer possible to have a very simple picture where we evenly divide the bottleneck resources amongst flows. We need to do something a little more general than that. And the more general allocation that's going to give us equal use by flows at the different bottlenecks is something called max-min allocation, a max-min fair allocation. It's going to be an allocation that maximizes the minimum that flows get. This is why it's called max-min. Now, intuitively, to generalize our equal per flow allocation, we could describe it in this way. All flows that are bottlenecked at a particular place in the network should get an equal share of that bottleneck link. That's what our max-min allocation is. This definition is a little circular though, because bottlenecks are caused when different flows send different amounts of traffic. That's what causes a link to be full and reach capacity and a bottleneck to appear. So we can define a max-min fair allocation in a way that's less circular, but is a little puzzling, like this. A max-min fair allocation is one in which increasing the rate of one flow must decrease the rate of a different flow which was already smaller. Wow, that's a little tricky. But if you come up with a point which has that allocation, then it will be the case that you have maximized the minimum flow. And then for the second smallest flow, you've also maximized what it can get out of the rest. And for the third smallest flow, you've then maximized the amount it can get out of the rest of the network, and so forth. We're going to look at an example, and that will hopefully make some of this strange concept just a little clearer. So I defined a max-min fair allocation in a bit of a puzzling way. I didn't tell you how to find that allocation. Here's a procedure you can use to find that allocation. It's a pretty intuitive one. You just imagine we have all of these flows going through the network, each flow from a source to a destination. Just imagine pouring water into the network along these flows, raising the level of all flows, and we'll see what bottlenecks they run into. That will help us find a max-min fair allocation. So if you start with all of the flows with rate 0, then you pour water along the flows by increasing the rate until you run into some bottleneck in the network. Now, whoever is part of that bottleneck, you can't increase them anymore, so hold their rates fixed and go back and increase the rate of any other flows which are not bottlenecked until they find a new bottleneck which will appear. Then subtract them and increase anyone who's left, and so on. We'll look at an example just to see how this works in practice. So here we have a network. There are 4 flows. For example, we're going to call them A, B, C, and D. The A flow is really sending from A on the left to A on the right. The B flow from B on the left to B on the right. But you can see these different flows go through different links. So they might potentially have different bottlenecks. We'll assume here that every link has the same capacity. We'll just call it 1 unit. Okay, so let's imagine we want to find the max-min fair allocation. So we start pumping water along all of these flows and raise the level. They start at 0, a tenth of a unit, 2/10 of a unit, and raise. And what's going to happen? Well, as soon as we get to 1/3 of a unit, flows B, C, and D will fill up this link here. Let's just move ahead. Here it is. So now everyone, A, B, C, and D, is sitting at 1/3 of a unit, and we bottleneck this link here. This means that we can no longer increase flows B, C, and D. They're fixed. There are, however, still flows left. The only flow that's left is A. So we will keep raising A until we reach another bottleneck. How far can we raise A? Can we raise it at all? Well, actually, there's a little bit of spare bandwidth left on this link that's not used. It's at 2/3 of a unit, so there's a little left over. So we're going to raise A, and what will happen? We will reach this point. We can raise A until it has a rate of 2/3 of a unit of flow. When that happens, we'll be bottlenecked on another link. And then A can no longer increase. And there are no flows left, so we're done. We have an allocation. Here's what the allocation is that we ended up in, just to remind you. A had 2/3 of a unit, B, C, and D had 1/3 of a unit. So you can see, even though it's equal per flow, not everyone's going to get an equal amount. Now, in this allocation, 2 links were maxed out, between R4 and R5, and between R2 and R3. Some of the other links had unused capacity. That capacity simply couldn't be used in the network while still having a fair allocation. I'll just write down what it is so you can see it. Just looking between R1 and R2, we have 1/3 of a unit of excess capacity that's not used. Between R5 and R2, we have 2/3 of a unit. So we're really not using that link very much at all. In fact, if we were building that network and we had this traffic flow, we could maybe make that one slower and it wouldn't slow anything down. And also between R5 and R6, we have 1/3 of a unit that's left over in our network. So this was as efficient as we could make the network while still making it fair according to max-min fairness. And finally, just for fairness, I want to point out that the fair allocation will change over time. Before, we considered a fixed picture and we were just trying to maximize the flows individually. But in this picture, let's look over time, as time goes along, to the right, what happens to the bandwidth allocation. So you can see here just an illustration of how bandwidth allocation can change over time. The beginning of time, flow 1 is the only flow that's actually using the network. So it's going to get 100% of a link. Just imagine these flows are all going over a very simple network. At time 1, flow 2 starts. So that means that flow 1 and flow 2 are going to share the network. Flow 1 will get half a unit. Everyone goes on. At time 4, flow 3 starts. Now flow 3 gets a small unit of bandwidth. We don't know why. Maybe it's bottlenecked somewhere else. Maybe it just doesn't have that much traffic to send. But at any rate, that means, since it's using less than its fair share, if it was using the same link and it wanted to send more, flows 1 and 2 are going to divide the bandwidth that's left. So flow 1 will get now a little less. Flow 2 will also get the same amount. And they're going to go on until something else changes. What changes in this case? Flow 2 stops. In that case, flow 1 will take up the slack of flow 2 so that we have an allocation which is as efficient as we can, uses as much of the network, but is fair. For some reason, flow 3 is just limited to this amount, maybe because of a different path. And there we have it. Okay, so I've just cleaned that up. So now we know what a max-min fair allocation is, and fairness in allocations. We haven't yet looked at mechanisms which will find in a network when senders operate independently, which will arrive at a good bandwidth allocation. We'll go to that next. G'day viewers. In this segment we'll talk about the additive increase, multiplicative decrease algorithm. So our general topic here is bandwidth allocation. Additive increase, multiplicative decrease, or AIMD, is one control law which has attractive properties for bandwidth allocation, which is why we're going to look at it in detail. Before we do that, I just want to remind you of some context for where we are on bandwidth allocation. What we're trying to do here in our network is allocate some of the capacity of the network to senders. And we want an allocation to be efficient in that it's going to use all of the network, but not more than is there and cause congestion, and fair. We've already talked about fairness. Now, any solution here is going to use feedback from the network layer, because that's how we'll find out if the network is congested or if there's spare capacity. And it's also going to use the transport layer, because that's the layer that controls the load that's often into the network. We know all of this before. What we don't know is just how we should actually perform a bandwidth allocation. There are actually lots of different ways, if you're designing the network from scratch, that you might allocate its bandwidth. You could use a design which is either open loop or closed loop. Open loop simply means that ahead of time you simply come up with an allocation, you make reservations for how much bandwidth the different flows are going to get at a certain route or at a certain time, and then it's done. Closed loop is where we're using feedback to adapt and vary the amount of capacity which different flows are assigned over time, depending on what's available in the network and who else wants to send. We could have allocation mechanisms that are more host-based or more network-based, whereby whether they're host or network-based, I really mean which party is responsible for setting and enforcing the allocation. Is that something the network should do, or is that something the host should do? This has implications, by the way, for how the scheme works in different situations. For instance, if the network is enforcing it, the network's really in control and users can't undermine the network. If the hosts are setting the bandwidth allocations in some ways, then really they better behave in a good way for the network, or they might have an adverse effect on the whole network, and there's nothing much the network can do about it. So these things matter at a high level. And also in terms of the allocation, we can have an allocation expressed either in terms of the size of the sliding window or as an absolute rate, such as 1 packet per second directly. Both of these are going to provide us with ways of controlling the amount of network capacity that's used by a sender. TCP in this sort of schema or framework is a closed-looped, host-driven, window-based bandwidth allocation scheme. And that's where we're going to look, because we're mostly going to study TCP. This is the scheme that's been successful and is used in the internet. Okay, so this just says that where we're going to look. Now, as far as the network layer and the transport layer are concerned, the network layer is going to return feedback on the current allocation to the senders, and we're going to assume that the network layer will at least tell the senders if there is congestion or not. So a binary signal will do. That's this. The transport layer is going to adjust the sender's behavior. We've said that here we'll use a window, a sliding window, and it's going to adjust it in response to the feedback. How the senders decide to adapt the window over time, what the rules for the adaptation is called a control law. And that brings us to AIMD, additive increase, multiplicative decrease. AIMD is a control law for doing this adaptation. And it's a control law which has some attractive properties because it can help us get to an efficient and fair allocation. In AIMD, hosts additively increase the rate by adjusting the window size, say, by adding something to it, while the network is not congested. That's the AI part. And then hosts multiplicatively decrease the rate by changing the sliding window, reducing it, when the network enters a congested state. And that's it. This algorithm repeats, additively increasing until you run into congestion, then multiplicatively decreasing to get away from it, on and on and on. And that's AIMD. TCP uses the AIMD algorithm. All of the TCP different mechanisms really exist to implement AIMD. Now, just to see why AIMD is any good, let's use the AIMD game to see how it works. Here's the game. The game is to consider a very simple network. There are these two hosts, host 1 and host 2. You can see here they're attached to the network and they're sharing a link here, a link of 1 unit. This is the bottleneck for both of those links. So somehow host 1 and host 2 are going to have to agree amongst themselves who gets how much of that different link. But the rub, and this is where it's a little tricky and follows the way bandwidth allocation works in practice, is that host 1 and host 2 can't talk to one another directly to sort that out. they might not even know who the other party is, who they're sharing the link with. If there's just one other person or 10 other people, and so forth. So somehow they're going to have to work out their bandwidth allocation without talking to one another directly. All they have to help them work things out is that the router or the network is going to provide binary feedback, a 0-1 signal to tell the host whether the network is congested or not. So the AIMD game takes place on this plane. This plane represents all of the possible bandwidth allocations. So a point here, for instance, has a bandwidth allocation of, it looks like, about 0.5 to host 2 and what's this, 0.1 maybe to host 1 on this particular point. And all sorts of different points on that plane just provide different amounts of bandwidth to host 1 or host 2. There are several key different features of this diagram. So we've talked about a fair and efficient allocation. What are they? This line, this is like at 45 degrees, the y equals x. This is fair. And it's fair in this simple setting because along this line, host 1 and host 2 get an equal amount of bandwidth. Maybe they both get 0.3 units or 0.4 or 0.5. Whatever it is, it's fair. This other line here is the efficiency line. This is an efficient network allocation. This is the line such that the host 1 and host 2 values sum to 1 unit. So x plus y is equal to 1. Now, since 1 is the total allocation, if host 1 and host 2's bandwidth together sum up to 1, they're using all of the network capacity and the network is operating efficiently. Down here at this point I did, they add up to 0.6. So we've kind of left 40% of the network capacity on the table. We're not running efficiently. The intersection is the optimal point that's both fair and efficient. This is where we want to get. And the plane beyond the efficiency line is congestion. Congestion occurs as soon as you go into this territory. You can't sustain any point that is above here because you're sending more traffic into the network than it can handle. It will all get dropped on the floor. So, and what I also have to tell you is what AIMD looks like in this diagram. If we take a point, let's just take a point here, additive increase is going to add a fixed amount of bandwidth to both hosts. So that's going to take us along the line at 45 degrees. We're adding, let's just say 0.1 to host 1 and host 2. It takes us up there. Multiplicative decrease, on the other hand, is going to lop a fraction, the same fraction, off of both host 1 and host 2. We could, for instance, reduce their bandwidth allocations both by 25%. Now, if one of them had a larger bandwidth allocation with multiplicative decrease, it's going to lose a bigger portion than the other one. It turns out that a multiplicative decrease portion effectively takes you back on a line towards the origin. You can see from here, for host 2 had a smaller amount of bandwidth here. So on this line towards the origin, it lost just a little bit. Host 1, on the other hand, had quite a large allocation. So it, down this line, lost a lot more. So they're both losing proportionally to their magnitude. This is multiplicative decrease. Visually, it's a line pointing towards the origin. So here is that game cleaned up for all of the points, and I've written the equations for some of the lines. At this point, you might be wondering what the game is and whether it's any fun at all. Well, here's how it works. To play the AIMD game, you pick a point, any point along here, as a starting point. It's up to you, it's part of the game. And then you change the allocation according to the rules of additive increase, multiplicative decrease, and you see where you end up. Let's see what happens. From here, what's going to happen? Well, we additively increase, and that goes up at 45 degrees. Eventually, we will become congested, and the network will tell us that it's congested. For all of these points, the network was saying not congested, not congested, not congested. Sometime after we cross it, we'll say congested. We could do it immediately, but often we'll move in more sizable increments, so there'll be a little bit of going to and fro. At that point, we do the multiplicative decrease. Oops, that's my somewhat shaky line down to the origin. Now we're below it. We do additive increase again. Multiplicative decrease, additive increase, multiplicative decrease. Can you see where we're going? It's a little hard, but see, these are pointing towards the origin. We're heading towards this point. If you play the AIMD game, from any point, you will end up at a fair and efficient allocation. Let me just clean that up a little bit so you can see it. These different lines for multiplicative decrease should all be pointing towards the origin. So you can see that their slope is changing. Okay, so AIMD, the point here is that it will always converge to a good allocation no matter where you start. That's pretty handy in a scheme. If we also look at what's happening for any particular host, host 1 or host 2, over time, this axis is now time, not the other host, and we look at the allocation of the rate, that rate will be going through a sawtooth pattern. It will go up, that's the additive increase, then it will suddenly go down all at once. That was the multiplicative decrease. And here it will go up again, additive increase, multiplicative decrease. And that must mean that the place we wanted to get to, this was probably the efficient allocation. Right in the middle, fair and efficient. Right there. This sawtooth pattern, this is what we're getting when we have it looks like the multiplicative decrease might be 50% here and the additive increase is just something that happens slowly over time. But this is a sawtooth pattern, and we'll see later that TCP produces a TCP sawtooth, which is the sign of an AIMD allocation. Okay, so I'll just talk briefly about some of the properties of AIMD. I've been hammering in that it converges to an allocation that's fair and efficient when you run it, no matter where you start from. It might not seem very interesting on that small topology, but this is going to hold for more general topologies and larger numbers of flows playing this game together, even though everyone is acting independently and only with a little bit of feedback from the network. They don't know who they're competing against, they don't know who has how much other bandwidth, they just know if the network's congested or not. They follow this rule, AIMD, everyone ends up at a good allocation for the network. It will seem more interesting to you if you actually try on that game some other control rules. If you try multiplicative increase, additive decrease, or any of these other combinations, multiplicative increase, multiplicative decrease, or oops, and the other one that's missing that I shouldn't say here is additive increase, additive decrease, then you'll find that none of these other allocations converge to a good operating point. Some of them just go to and fro, others diverge, so they actually move away to a worse allocation. And we're doing all of this requiring really very little, just this binary feedback from the network about whether it's congested or not. So AIMD is quite useful. Just to finish up this segment, I'll talk very briefly about feedback signals. We said the network gives you feedback, but I never really said what kind of feedback that was. Well, there are several different possible signals that you might use to get feedback from the network. They all have their different pros and cons. One of the signals you might lose is simply packet loss. If packets are lost, that's really a signal from the network that it's congested because the queues are filled up. That's how packet loss occurs. Packet loss, and I've listed here in the middle column just some examples of transport protocols that use this signal as part of their congestion control scheme. Packet loss is good in some respects. It's a pretty hard signal to get wrong or miss because it's hard to build a router that doesn't drop packets under overload. Eventually it has to. The con, the disadvantage of this scheme is that you hear about congestion late. So you really hear about congestion after it's happened and the queue's full and a packet's dropped, and even a little after that, because it takes a little while from the ACKs to work out, or timeouts to work out that something's gone wrong. Alternatively, you might use packet delay. We said as you approach congestion, the delays through the network tend to jump up. If you did this, you would get to hear about congestion more early. That's good. The downside is just that you need to infer congestions from the timings, and it can be a bit of an implicit and a noisy signal. because delay depends on lots of things. So we're not really getting a very clean signal from the network. We're just having to work a little hard to hear it. Finally, you might also build a network in which the routers directly gave you an indication and just told you by sending a message that, hey, the network's congested. In this way, you would hear about congestion early as the router could find it. The downside is just that now we actually require routers to do something to help us with the feedback signal, whereas delaying packets or dropping them was something that they sort of had to do. It was no extra work. In the middle columns here, I have examples of just transport protocols that use all of these different approaches. It turns out that over time, congestion control is diversified, and there are many different flavors of transport protocols. For instance, TCP Reno and Cubic TCP, which is used in Linux, are mostly based on packet loss as the signal. Whereas Compound TCP, that's now the TCP which is used by default on Windows, uses packet delay information as a congestion signal. And finally, using a scheme we'll look at called explicit congestion notification, TCP can use router indications of congestion. So there are all sorts of different congestion designs. Okay, but our point for right now is about the AIMD scheme, and shortly we'll look at how TCP goes about realizing AIMD. G'day viewers. In this segment I'll talk about the history of TCP congestion control. So we've talked about congestion control in general, including the additive, increase, multiplicative, decrease control law. In the following segments we're going to dive into the details of TCP in particular to find out how it implements congestion control and comes up with a bandwidth allocation. Before we do that, however, I thought I'd just tell you a little bit about the history of TCP congestion control, because it's a colourful story involving congestion collapse, new mechanisms to control it, and a diversity of mechanisms which we've reached today. So in the late 1980s, the mid to late 1980s, as the internet grew, the earlier designs for TCP in fact used a fixed size sliding window. Some machines, for instance, used 8 packets. This worked reasonably well for reliability, but as you can see here, something strange happened as the ARPANET grew. In particular, the network got into a state called congestion collapse, where the links were all very busy sending packets, but the end-to-end good put or useful information which went through the network plunged through the floor. Here's a picture from before about congestion collapse. We really got into this situation where the queues became very full. There were many retransmissions which were clogging the network, and because of most of the information in the network was in fact retransmissions, the good put or the useful information fell by orders of magnitude. So the network was no longer performing very well at all. This was a great mystery at the time, a bit of a puzzle as to how the network could have gotten into this state, why it seemed to be stable and persisting, and of course what could be done to ensure that the network would run properly. Enter this man, Van Jacobson. Van Jacobson is widely credited with saving the internet from congestion collapse in the late 80s. He introduced many of the principles of congestion control that we talk about to this day, as well as coming up with practical solutions in the form of new versions of TCP, TCP Tahoe and TCP Reno, other well-known versions. These versions of TCP didn't use a fixed size sliding window. They used a dynamically sized sliding window, adjusting it to operate the network and control to control the allocation of bandwidth in the network and avoid congestion. Van Jacobson's well known in the networking community, and he's done a lot of other pioneering work that you might have heard of. Some of the tools we've used before, like Traceroute, for instance, were developed by Van Jacobson. And you can see a few other things here. He's also worked on IP header compression and multicast tools. So TCP Tahoe and Reno really try to avoid congestion collapse under some pretty heavy constraints. The task here that Van Jacobson took on was really to avoid this congestion collapse without changing any of the routers in the network or even the receivers, just by upgrading the logic, the protocol logic at the senders. If you could do this, and he could, it has a tremendous advantage over other schemes in that we don't have to replace and go and fix the whole network. We can just update a little bit of software on the hosts at the edge of the network where they're sending traffic into the network. So it's great if you can do it. And the idea which he came up with to be able to do this did a couple of things. One of the things it did was it fixed the timeouts. And we've looked earlier at the adaptive timeout that took into account the mean and the variance. But in addition to this, the real key innovation that Van Jacobson introduced was the notion of a congestion window on top of the sliding window. We talked about a flow control window which changed dynamically to prevent the sender from overflowing the receiver. The congestion window is the same kind of adaptive sliding window which changes to prevent the sender from overrunning the network. It prevents the sender from filling up those queues in the network and causing loss. We just need to work out what this, how this congestion window should behave. We already know part of the answer in that we would like the congestion window to produce additive increase, multiplicative decrease changes in the bandwidth allocation because we know that will get the network to a good point. TCP Tahoe and Reno use a set of mechanisms to adapt the congestion window to implement AIMD. And they do this using only packet loss as the signal from the network. This is very clever because, of course, the routers in the network already lost packets when they were overloaded. So that signal already existed, hence there was no need to update the routers in the network. Now TCP has many different mechanisms in it which collectively implement AIMD. In fact, TCP is one of those protocols where there's no real clean specification. The specification is the implementation, so it gets a little hairy. In what follows, we're going to go through the main mechanisms, but understand that I'm not trying to tell you all of the fine little details because, well, many of them don't matter because they could have been done differently. It's just a little hard because the specification and the implementation are completely intertwined in the old internet. But we'll look at several different behaviors as important. Actually, we've already looked at this one, the adaptive timeout, where we kept an estimator for the mean and variance and then formed the timeout as some multiple of them. What we'll look at in the following segments are mechanisms for what's called ACK clocking, slow start, fast retransmission, and fast recovery. They're all very colorful names, but they describe important concepts which help TCP to realize that AIMD sawtooth and arrive at a good allocation. And here are just a couple of slides on timelines to give you some sense of TCP history before we dive into it, so you'll know which bit we're really covering. TCP first existed, I guess, when Sirfin Khan wrote a paper on a protocol for packet network interconnection. This really proposed the precursor, a protocol which eventually split into TCP and IP. And you can see the split is complete by about 81 when we have RFCs for these different protocols. In this period, really the emphasis was on getting the basics of the architecture right and focusing on reliability to make it actually work. For instance, the three-way handshake we looked at in TCP was proposed in 75. And by 83, the internet, or the ARPANET, had a flag day and changed over such that TCP was used as the main protocol for some of this end-to-end transport across the internet work, rather than the earlier protocols. So TCP was up and running in what would become the internet. This is the prehistory. Starting in about 86, as the internet grew and began to be used more, congestion collapse was observed. So the protocols worked for reliability, but the performance was terrible under some circumstances, which really was this strange situation that everyone wanted to understand and then fix. Van Jacobson is the guy who devised a very practical solution to them and released it onto the internet. It became part of the standard software base, and so then all of the hosts on the internet were able to work together and achieve a fair and efficient allocation, reasonably anyhow. Fairness is, maybe only approximate. And this happened in 88, first with TCP Tahoe, and then quickly with TCP Reno in 1990, which finally implemented AIMD. Now, if we proceed a little bit along the history, well, for maybe the first 10 years or so, we went through a phase where work on classic congestion control was further refined. TCP Reno eventually shifted to New Reno, which used slightly better heuristics to recover from losses. A little later than TCP Reno, a mechanism called SAC, which we've already looked at, selective acknowledgement, provided cleaner information about packet loss to make these versions of classic TCP run more effectively. But in addition, Threads also got started on some other kind of work. TCP Vegas was one of the first schemes which used delay-based feedback from the network instead of packet loss. This has some advantages if you can do it. And we also looked at router support. Sally Floyd in about 94 introduced explicit congestion notification where routers would send indications of congestion to hosts at the edge of the network. These two schemes introduced new capabilities which over time have had a big impact on congestion control. You can see here actually that it's taken quite an amount of time. It's only really in the 2000s that some of the impacts of delay-based and router support schemes have been felt on congestion control. And we're really now in a phase of diversification, where there is no single form of classic congestion control, but many different kinds of congestion control, where people have come up with slightly different algorithms that they prefer. In Linux, we have now TCP Cubic from an earlier TCP BIC design. These are really descendants of New Reno. They use different algorithms, so they're not really AIMD exactly. They're something slightly different, but they're based on packet loss. On the other hand, we have other algorithms which have really begun to use some of the delay-based schemes to be able to scale more effectively and maintain good performance for fast networks. Fast TCP is one of those, and it's based on sort of control theory to make sure that it will scale well. And Windows uses a form of TCP called compound TCP, which uses delay-based feedback as well as packet loss. In addition, there are all sorts of variations on congestion control that are going on. The IETF has concluded work on a protocol called TCP LEDBAT, which is a little strange, but this is all about background TCP transfers, which soak up excess capacity, say for your big downloads or your Dropbox syncs and all of that, yet they don't get in the way when someone else is trying to actively use the network. Now this is all very interesting that we have this proliferation of schemes. Oh, and also these modern schemes are capable of using both SAC and ECN router support. That's sort of been adopted into all of these schemes. The situation is quite interesting because now we have this diversity of algorithms and they all need to work together to help the network achieve a good operating point. So it's a little like having a family of different actors, and we can begin to ask how they all get on and whether they're a happy family. Whereas the situation was simpler before, when we just had classic TCP congestion control running against itself. Anyhow, we are mostly going to look at the boxes in pink. So we'll study classic congestion control and leave out some of this messy picture where there are many different kinds of variants of TCP as congestion control is diversified. So on with the show. Good day, viewers. In this segment, I'll talk about ACK clocking, a behavior used by TCP. So sliding windows have a self-clocking kind of behavior called ACK clocking. In this segment, I'll explain what ACK clocking is and why it's beneficial. First of all, just recall the basic features of a sliding window, and you'll see what I mean by an ACK clock. In a sliding window, every time we get the next ACK, normally this is the next in-order ACK, it advances the sliding window and allows for a new packet to be sent into the network, or a new segment to be sent into the network. So in effect, the ACKs are clocking out the data segments. This is what we mean by an ACK clock. You can see here packets going across regularly and ACKs coming back with the same spacing. And every time an ACK comes back, it's a strobe or a clock which allows the sender to release a new packet into the network, assuming there's no loss, this is. You might wonder what all the fuss is about. What I've described so far is simply how sliding windows work after all. Well, let's look at an example to illustrate the benefits of ACK clocking. So consider what would happen in this network. In this network, I have two hosts that are connected to one another over a two-router network. Note that I've got a fast link on either side, and there's a slow link somewhere in the middle. This is going to be the bottleneck link. The host can't see this directly, but somewhere in the network there'll be a bottleneck which will slow their traffic down. The sender on the left sends a burst of packets into the network. So you can see there are 5 packets which are injected rapidly in succession. What will happen? Well, the segments, as they make their way through the network, they were sent in a burst over the fast link, but they can't go out that quickly over the slow link. This means that some of them will be buffered. Here they are, inside the buffer. And as they go over the slow link, they'll effectively be spaced out. Why is that? That's because if you had a fast link and you could send a packet every microsecond, say, on a link that was 1,000 times slower, you could only send the same packet, the same number of bits, every millisecond. So they'll have to sit around and wait for a lot longer, and the packet will be more spread out on the wire in some sense. So as we imagine these packets going further through the network, let's think about what happens. They've already gone from a burst to being spread out. That's what the slow link does. It spreads things out in time. Now, as they go back onto a fast network, however, this timing will not necessarily change. It can be unchanged. There might be one in the buffer here, but the other ones are going to be spread out in time with the same spacing. And every time one arrives here, we'll send an ACK back to the other side. So the ACKs, maybe I'll do it here, the ACKs that are coming down here are also going to have this kind of spacing. Here's a cleaner version of that. The key point is that the ACKs are maintaining this spread or spacing of the packets, and this spacing is coming from the slow link, the bottleneck link. Well, these ACKs are going to go through the network. As they go over this slow link, they will maintain their spacing. The slow link spreads packets apart until they're going slowly enough. But if they're already going slowly, they don't get to spread apart anymore. It's like a maximum speed limit. The fast links, you can drive fast. If you hit a slow link, you get slowed down to that speed limit. Well, if you keep that slow speed, when you come back around, you don't get slowed around anymore. So these ACKs are going to continue through this nice slow pace through the network to the other side. As they get to the other side, they will gate out new packets, but these new packets won't go out in a burst. They will come there spread out with the same timing. Let's look at a cleaned up picture of that. You can see here the ACKs arrive back here with this timing. At that timing, the ACK served as a clock which gated out a new packet, and these packets, these new packets or segments, were still spread with the timing. Now the amazing thing about this is that the segments are now being sent at just the right rate to go over the bottleneck link. They're going to fit, because the timing came from the bottleneck link, it's right, so that a new packet should arrive at the gateway, if there's not a lot of other interference from other flows, at roughly the right time that it can be sent out onto that link. So we now expect that there will be no big queue building here, and the packets will simply go out onto the slow link because they'll be arriving at about the right order. So in effect, the sender is now sending at about the bottleneck link. So there'll be no queuing, all without actually having anyone tell it what the capacity of the bottleneck link was. Well, this is the benefit of ACK clocking. ACK clocking here effectively will help the network to run with low levels of loss and low levels of delay. And it's working as follows. The network, when we sent a small burst, it smoothed out the burst of segments, and it smoothed them out so that they were spread at about the bottleneck rate. The ACK clock mechanism from the receiver all the way back through the sender transferred this same timing from the bottleneck link back to the sender. The sender then, because of the sliding window property, used that ACK timing to be able to send out data segments that weren't in one big burst. They were spread out at about just the right rate that they would go over the bottleneck link without a lot of queuing. So by using this ACK clock, we have nice smooth traffic that's well matched to the capacity of the network. That's what's amazing about ACK clocking. TCP uses a sliding window, and because of that ACK clocking, because of the value of this scheme. As I've said in a previous segment, TCP is going to use a sliding window to control how much traffic is in the network. TCP's version of this dynamic window is called a congestion window. And just like a flow control window, the sender, well, actually in this case it's the sender, whereas the flow control window is controlled by the receiver. This sliding window will be adjusted by the sender so that there won't be too many packets in the network. It will match the sender's capabilities to the network. ACK clocking is going to help us to do that. You might wonder how it's controlling the rate of what's in the network, since we're talking about a congestion window. Here's a key observation for you. The rate at which you send is related to the size of the congestion window, or the sliding window we're using in this case. With a sliding window of size W, you can send W segments every round trip time, assuming there's no loss. Well, our sliding window is size CWIND, so we get to send CWIND segments every round trip time. If you divide them, you'll find roughly the rate that's been supported by that window size. So TCP is going to send using only small bursts of segments, which the network will smooth out. This is how we'll keep our traffic nice and smooth and keep queues from building and congestion from forming. TCP is going to use these small bursts, and the network is going to smooth them out, and we'll use ACK clocking to keep everything smooth. And we'll do this using adjusting things and using only packet loss as the signal. Anyhow, so this is ACK clocking. You now know what it is, and we'll see how we use it in subsequent segments. G'day viewers. In this segment I'll talk about TCP slow start. So recall that we're trying to get TCP to implement an AIMD control law, because this will give us a good allocation that's efficient and fair. Slow start is one of the mechanisms that TCP uses as part of its additive increase mechanism. So here's just a little more background context before we go into the details. I've said that TCP is trying to get to an AIMD control law. The way we're going to use it implement it in TCP is to have the sender implement a congestion window and adjust the size of the congestion window. This controls the rate indirectly. The rate we'll get is the congestion window divided by the round trip time. We're also going to use feedback from the network in terms of packet loss to understand when there's congestion. And our problem of using AIMD to adjust the size of the congestion window is really difficult for TCP, because we want TCP to be a solution that works across a very wide range of RTTs and rates for links in the network. So it's going to be difficult just to pick a number and have it go to any of those rates or any kind of constants. We have to be a little careful about. The problem in implementing additive increase directly with the congestion window, which slow start will solve, is this. We want to fairly quickly get the size of the congestion window to be somewhere near the ideal congestion window, which will give us the right rate. If we're hovering anywhere near there and oscillating back and forth, that's where AIMD ends up, then we have a good bandwidth allocation. But that ideal can vary greatly depending on the RTT and the rate of link. So we really don't know a priori what it should be. If we took a guess, we could easily be way too small or way too large. Any fixed size sliding window is going to be problematic, because not only will it be either way too small or way too large, but it's also very rough on the network. It just injects a burst, which can lead to queuing and packet loss. The whole reason for using a congestion window in small bursts is that we're nice and smooth on the network. So we can use our congestion window with additive increase, using small bursts to additively change the congestion window, make it bigger and bigger and bigger. In this way, we'll have smooth traffic running with the ACK clock that we're seeing at about the right congestion window, eventually when additive increase increases the congestion window to where we want to. But it might take a very long time to get anywhere near CWIND ideal and become efficient. And that's because the network could simply be one for which this is large compared to a step size we'll have to conservatively choose. Slow start is the solution to this problem. Slow start doubles Cwind every round trip time. So it's adapted to the round trip time already because we can measure that. By doubling the congestion window, we have exponential growth here. So 1, 2, 4, 8, 16. The growth is initially fairly slow, but rapidly becomes very large. That's what exponentials do. So this means that it will reach large values very quickly in a small amount of time, but it will initially start off more softly. So it will tend not to overshoot so much. We can see here slow start compared, and that's this exponential curve, oops, maybe not very good drawing there, to two alternatives. So slow start will reach up to this ideal level here much more quickly than additive increase, which will take a very, very long time to get to this ideal value. And on the other hand, slow start is going to reach there fairly quickly, not as fast as the fixed allocation, but on the other hand, it's adapted traffic smoothly to the network. So we'll avoid a lot of enormous bursts of traffic. So slow start is a pretty good compromise between these two things. You'll note, by the way, that it's not very slow in how it increases the size of the sliding window. It's only slow by comparison of jumping from 0 to the maximum window size in one step. But we're not quite done. So slow start can exponentially increase the window size to get to about the right neighborhood. But eventually, packet loss is going to occur. At some stage, the window will be too large, we'll be sending too much traffic into the network, the queues will build, packets will lost, and the network will be congested. When that happens, we'll get a timeout. Because we're lacking an acknowledgement, we'll know that a packet's been lost. Now, at this stage, it's too late. We're already congested, and in fact, the loss happened quite a while ago. It just took us a little while to find out. So that means that Cwin is too large. What we'll do instead, next time that we begin to increase the congestion window from the beginning and ramp up, is that we'll switch away from our doubling solution, our slow start, to additive increase, which we wanted all along when we're in the vicinity. So this way, we'll additively increase and more slowly adapt the congestion window somewhere around the right value. Now, in terms of how TCP adapts the congestion window, it works something like this. You expect a loss when the congestion window is about twice the bandwidth delay product, because that's how much information can fit in the network. Plus, there's a queue size. We could also store some packets in the queue. So we will create this new variable, SSThresh, slow start threshold, and we'll set that to be half of the size of the congestion window when you detect loss. Because when you detected loss, we'd already gone too far. By setting it to half, we're sort of being a little more conservative. And here's the combined solution you get, which is what we use instead of additive increase to quickly get the congestion window to about the right place and then additively increase for the last part of the segment. You can see here that we slow start until we reach this slow start threshold, and then we're going to additively increase. And we'll spend most of our time in the additive increase phase, not in the slow start phase. And you'll note that the ideal is here. We'll probably additively increase past that until eventually we cause loss somewhere up here with a higher congestion window. And at that time, we'll get some timeout and we'll know that we've gone too far. I can show you some timeline graphs just to get the hang of how slow start works, the double and followed by additive increase. Here's what slow start looks like on a timeline. So we have the sender on the left and the receiver on the right. Here is a data packet being sent, and here is an ACK coming back. We want to double the congestion window every round trip time. Well, a neat way to do that is to increment the congestion window by one packet every time you get an ACK. In this way, every one packet in a window becomes two packets in the next window. So this is why we're doubling. So when we get this ACK here, we could double our congestion window from 1 to 2, and, add 1 to the congestion window, add one packet to the congestion window. That will let us send two packets. because we added one to the congestion window, and we also got another packet ACK, so that lets us send 2 new packets. Each of those will cause ACKs to be returned, and you can see here every time we receive an ACK, we send 2 packets. One for the new one that we can send because an ACK arrived, so the sliding window could advance, and one for increasing the congestion window. And you can see here on the right hand side, if I divide the time into round trip times, we have 1, 2, 4 packets going there into the network. After that, we've reached twice the bandwidth delay product and the pipe is full, so any other packets would have to be stored in router queues or somewhere else, and eventually they would cause loss. And now for a contrast, let's look at how additive increase is implemented with packets. Here we're starting from 1. You would normally slow start somewhere, but for the sake of a simpler example, we'll slow start from 1. So with additive increase, we would like to add 1 packet to the congestion window every round trip time. So here's a round trip time. On the right, I'm just dividing time as before, and you can see we're still sending packets and getting ACKs back as before. The first time we get an ACK, a round trip time has gone by, so we add 1 to the congestion window, and we get to send 2 packets. The next time though, you can see that we're only sending 2 packets in response to the last ACK there, right? And that's what's allowing our that's what's allowing the congestion window. That's where the congestion window is growing, and the reason why we're adding 1 packet to the congestion window over time. Now, just in the same way we added 1 packet every C-wind to double, there's also a heuristic for adding 1 packet to the congestion window every C-wind. Sorry, before I meant if you add 1 packet every time you get an ACK, you will double the congestion window every RTT. Now we only want to add 1 packet to the congestion window every RTT. Well, in an RTT, you should get ACKs for about C-wind packets, because there are C-wind packets every round trip time. So if you just add 1 on C-wind, fraction of a packet, to the congestion window every time you get an ACK, you'll end up in about the same place. I'm skipping a little bit ahead to the implementation, so let me just move to that and tell you. What I would like you to take away from this diagram is simply that every round trip time, the congestion window is going up by 1 packet. So for most of the packets, the ACK simply triggers another packet, but occasionally we're sending 2. That's a small burst, which the network will smooth out. TCP Tahoe implements slow start followed by additive increase. And it does this using the slow start and additive increase rules as follows. For slow start, we start with a congestion window of 1, or you could start with some other small initial value. Modern implementations have recently, to get things going quickly, started using 4 or even 10 packets as an initial congestion window. And you add 1 packet to the congestion window every time you get an ACK. So we're doubling the congestion window over time. For additive increase, once you pass the slow start threshold, we'll get to that in a minute, you also increase the congestion window over time. But you don't do it so quickly. We want to add 1 packet to the congestion window every round trip time, but we don't want to keep a separate round trip time timer. So instead, what we do is we add 1 on C-wind packets, that fraction. We can do this because congestion window is measured in bytes, so you can have, 4.25 packets. That's a congestion window that big. We add this fraction to the congestion window every time we get an ACK. And since there are about C-wind packets every round trip time, we're adding approximately 1 packet every round trip time by using this heuristic. It's not exact if you do the math, and that just doesn't matter. Now we have the rules for these 2 phases. We have to work out how they relate. Well, remember we use this switching threshold, SS thresh. Initially you can set it to infinity, so you just slow start until you cause loss. In the future, when there's a reasonable value of SS thresh, when the congestion window reaches this threshold, we change from slow start, where you double, to additive increase. When you get a loss, you set slow start threshold to be half of the congestion window that caused the loss. So the first time, eventually we'll slow start until we cause loss. We'll remember where that congestion window was, set slow start threshold to be half of that. Now, in the future iterations, we'll be able to slow start up to about the right value and then slowly additively increase to spend most of our time at a reasonable congestion window that's sending traffic at a reasonable rate into the network. And finally, another rule here is that after you've timed out, you go back and you slow start from all the way from a congestion window of 1 or your other small value. That's one thing you may wonder about, actually. The misfortune of timing out and starting again with slow start. After all, we wanted to implement additive increase, multiplicative decrease. We're doing the additive increase bit, but you would think after loss we should simply multiplicatively decrease the congestion window and keep going. That is where we want to get to. The problem here is that we detect loss with timeouts. Now when you do that, timeouts, because they have to be conservative, are usually sufficiently long that all of the packets that have gone into the network have been ACKed already. We've received whatever ACKs there are, and in fact our ACK clock has now run down. So we no longer have any nice clock which will help us send packets into the network at a nice, smooth, gradual rate that won't cause queues to build up. If we simply kept a big congestion window and started, we would send an enormous burst of traffic into the network potentially and cause a lot of loss. Instead, if we use slow start, that's a way to start from nothing when the network's gone quiescent and to ramp up our ACK clock and our congestion window fairly quickly to about the right value. So if we're going to fix this and really get to AIMD, then we need some way to detect loss before a timeout. And this is what we'll see next with other TCP heuristics that are used in TCP Reno. G'day viewers. In this segment I'll tell you about the TCP fast retransmit and fast recovery behaviors. So this is the second part where we're going to look at how TCP implements the AIMD control law. We're already seeing the AI part, of which slow start is one contributing factor. Now, by looking at fast retransmit and fast recovery, we're covering the multiplicative decrease, or MD part. And I would also say, hang in there. We're almost there in terms of TCP congestion control. And congestion control is, I would say, the most complicated behavior of TCP to understand. Okay, so just a little bit of context again, just to refresh your memory. We're trying to get to this additive increase, multiplicative decrease control law. It has good properties. We're doing it by having the sender control a congestion window, increasing or decreasing it. That's indirectly controlling the rate. We've seen in the previous segment that the sender can use slow start to rapidly increase the congestion window to about the right time while still using an ACK clock to keep the traffic reasonably smooth. And it can then use additive increase around about the right congestion window. This is all good. The only problem was we then detected loss when it finally occurred with a timeout. And by that time, the ACK clock has run down because timeouts are relatively large compared to the time it takes to ACK a packet. So the sender needed to slow start all the way again. We haven't got to the multiplicative decrease part yet. And going all the way back to essentially starting from a congestion window 1 seems a little extreme. We can do better. The way we're going to do better is by using more information in the ACK stream. In fact, by looking at the ACK stream, you can usually infer something about loss. Let me show you how. TCP uses this cumulative ACK, if you recall. The cumulative ACK gives the highest in-order sequence number that's been received. When there's no loss, it will just steadily advance from one sequence number to the next. As the data segments are sent, the ACK will come in and it will just rise, counting up. When there's loss, there'll be a hole in the sequence numbers at the receiver side, and the cumulative ACK will get stuck at some value. The ACKs will then repeat the highest in-order sequence number that's been received. These ACKs are called duplicate ACKs because they're sending the same number over and over again. And if you think about it, these ACKs actually give us hints about what has arrived, or rather what data hasn't arrived. So they tell us every time we get an ACK, we know that some new data arrived, but we know that it wasn't the next segment, because if it was, the cumulative ACK number would have risen. So there's a good chance that, in fact, it is the next segment just beyond the one that's been acknowledged that has been lost. The fast retransmit heuristic uses this sort of inference to work out that a packet has been lost, which packet, and to retransmit it. So in particular, when the TCP sender receives 3 duplicate ACKs, it treats this as a loss event. It says, aha, loss has happened in the network, and it will immediately retransmit the next expected segment beyond the ACK value in the cumulative ACK, because it thinks that's the one that's been lost. 3 sounds a little arbitrary. Why 3 duplicate ACKs, not 2 or 4 or something? Well, some small number like this, and 3 is just a small number, allows a little bit of tolerance for packet reordering that could occasionally happen in the internet. This will cause duplicate ACKs also, yet it still detects any loss which actually occurs quickly. We can see the heuristic working here. You can see the ACK stream coming in, 1, 2, 3, 4, 5. Now we get duplicates. Here's a duplicate, first duplicate, 5. Well, so a packet arrived on the other side, but it wasn't 6. Or this ACK would have gone up again. 5, still haven't got 6. 5, still haven't got 6. This was the 3rd duplicate ACK. I'm going to circle this because right here we would resend 6. Right? We'll assume that that has been lost. And you'll note that after that we're still receiving duplicate ACKs, because even though we've sent 6, it's going to take a little while for 6 to reach the other side and the cumulative ACK to advance and us to hear back a bigger cumulative ACK. We can see some of those effects on the time sequence diagram here. We have again the sender on the left and the receiver on the right. Now ACKs have been sent merrily. Also, let me see. So this text is actually showing the receipt of information. Okay, so the sender and receiver labels are important. So in fact, this coming in is ACK 10. And you can see the ACKs are going up normally as they come, and they go up 10, 11, 12, 13, and for the last ACK 13 that's received, that's ACK 13 there. I'm just going to do this to make this figure a little clearer. Then we actually send data 20 here to the receiver. Before that we would have sent data 19, 18 and so forth. But now look what happens here. First duplicate ACK, ACK 13. Uh-oh. So we can't advance the window, so no new data goes out. ACK 13 again, same thing. ACK 13 now. This is the 3rd duplicate ACK. So fast retransmit hits and we send 14. And now after that we're going to get more ACK 13s until eventually the ACK comes back, and that's not going to be an ACK for 14, that's going to be an ACK for where we were already. Previously we had sent all data up through 20, but 14 was lost. Now that we've got 14, our cumulative ACK can jump to 20, and we see here the ACK jump to 20. So the hole's been filled, everything's good again, and now we can continue sending packets. Okay. However, hang on, let me just finish our fast retransmit. So fast retransmit can repair a single segment loss, and it can detect that this segment has been lost very quickly. This is usually before the timeout goes off, because it's about the shortest amount of time it could possibly take before you could even hear information from the other side about the loss. However, you might have noticed that we're not finished yet. After the fast retransmit segment, we had some quiet period where we were just sort of waiting, twiddling our thumbs for the ACK to advance, even though we were getting new ACKs in that were further duplicate ACKs, and we weren't sending out packets. And we didn't actually get to multiplicatively decreasing the congestion window yet, so we're not finished. We can do more with these ACKs. In fact, we can infer not only what packet is likely to be lost, but something about what packets are likely to have already been received on the other side. And we can do this by looking at further duplicate ACKs. What's going on is that every time we get another duplicate ACK, we know that something has arrived. We know not only that it was not one beyond whatever's there, or the ACK number would have changed, but most likely it will be. It's got to be something we sent, so it's likely to be the segment numbers beyond the loss. And if loss is relatively rare, it's likely to be the segments in sequence just going on and on and on. So what we can do is we can advance the congestion sliding window. If the purpose of that window was to control how many segments were in the network to make sure the queues didn't overflow, then we know from the ACK that a packet has left the network, so it's okay to advance that window and send a new packet into the network. We won't increase the load in the queues. The new packet that we would send into the network are just new data packets as we expect further out into the future. So we can turn some of these insights into the fast recovery heuristic. Fast recovery works with fast retransmit. First you do the fast retransmit. Then, and we haven't got to this before, but now we do, now you multiplicatively decrease your congestion window. You do this because we're not going to slow start. We're going to just do the multiplicative decrease and then get back to the nice additive increase. Now, in fast recovery, as further duplicate ACKs come in, just imagine that they're really the ACKs for whatever you expected in the normal sequence going forward. So if you like, you're keeping a shadow congestion window, which we're just going to begin to move along and inflate so that we can send new packets into the network because we know packets are leaving the network. So when we do this, when we pretend these duplicate ACKs are really something high that we expected, then we will allow new segments to be sent into the network in response to the ACKs. Eventually, after a good round trip time has gone by, our ACK number will jump as we fill in the hole. At that point, we can reconcile these two different views of this inflated window or shadow ACKs where we're pretending there's something else, and the acknowledgements we've received in the packets we've actually sent. Okay, so you can see on this diagram, here we would do something like this. We've got the ACKs coming in, 5, duplicate, 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 here. So we'll do the resend, 6 here. Now we're getting further duplicates. After a little while, we've halved our congestion window, we've multiplicatively decreased it, so it's smaller, so we might need to let some of the packets drain out of the network. But at some point, let's say here, while our ACK has not jumped, we would like to send new data as ACKs come. So I'll say send, I don't know, 10. I will just pretend we're up to 10 now. So that's what fast recovery is going to let us do. Here's a time sequence diagram to go over it a little bit. We have the sender on the left and the receiver on the right as before. So now I'm just showing the bit for where ACK 12 came in here. And we'll go through the sequence. You get to ACK 13 where you get a duplicate, duplicate, third duplicate. At this point, we'll do several things. We'll do the fast retransmit. That's the data 14. That's to fill in the hole on the other side. And we'll now set our SSThresh and to the congestion window over 2, and we'll also change the congestion window to the congestion window over 2. So we'll multiplicatively decrease the congestion window. Now, because it's smaller, some other packets may need to leave the network. But with fast recovery, eventually, as we get another duplicate ACK in, we will send packets out here. So more ACKs advance the window, and you can send new segments before the ACK jumps. Sometime later down here, the ACK jumps, and at that stage we can exit fast recovery. We know what's over the other side, we know what's sent. We can make sure that our congestion window is okay. And you can see just here on the other side, just by using fast recovery, we managed to get an extra bit of data into the network before our hole was filled at 14 and it was all ACKed and everything. So fast recovery will help us send more data through the network as well as to keep that ACK clock going. Okay, so in conjunction with fast retransmit, fast recovery allows us to repair a single segment loss quickly. We can work out that something's been lost, we can retransmit it. While that is going and we're waiting for the ACK back, we can continue to send packets and keep everything going. When you put all of these pieces together, they allow us to realize additive increase, multiplicative decrease. So we're now adjusting the congestion window up and down according to this formula. We're not using timeouts if we're just dealing with single packet losses. That's great. And we're not using slow start after loss because we keep the app clock going and we just multiplicatively decrease the congestion window. These mechanisms are implemented in TCP Reno, was the historic version of TCP that came out in 1990 that put all of these pieces together: slow start, fast retransmit, fast recovering, as well as some of the better timeout estimators that we'd seen before. And the multiplicative decrease factor that we use here is a pretty hefty one of a half. So we halve the congestion window on a loss event. This will sort of allow, even if there are two flows, new flows come in, it will sort of allow two flows to quickly each get half of the bandwidth. So it will accommodate fairly large changes at one go. When you put all of those mechanisms together, here's how the congestion window goes over time. It goes up with a slow start. We cross the slow start threshold and we're in a nice additive increase. That's what we wanted. Now when there's loss, we're going to go down and do a multiplicative decrease. We would find loss quickly and we would maybe go down immediately. We halved our congestion window, so we had to wait for a few acts to exit the network. Then we're back to our additive increase. Eventually you'll get too high, halve again, and so forth. And this is the TCP sawtooth that we're following. We've kept the act clock running all the way through these loss events without doing any version of slow start. And this is the behavior that classic TCP produces. You can see here it's actually driving the network into congestion, filling up the queues, and then recovering gracefully. So it sort of has to probe the boundary of congestion to find out just how much bandwidth there was in the network. Now we're going to stop there for understanding congestion control. We've seen how classic TCP congestion control has been implemented. Modern congestion control goes beyond it in many small respects. I'm just going to briefly mention some of them. So we've got to Reno. TCP Reno can repair one loss per round trip time using its mechanisms. If you were unfortunate enough to have multiple losses per round trip time, you would end up needing a timeout to recover from them. Then we'd have to start again with slow start because we've timed out and our act clock is broken and so forth. A common version of TCP that's deployed in the internet today, perhaps the most popular, is a classic style mechanism, is TCP New Reno. That's Reno with further heuristics that allow it to repair multiple losses in one round trip time without a timeout. So it's still using inference, but it's doing a slightly better job, and it can often do a little better in terms of repairing things. But one step beyond that, that's an even better idea, is something called SAC, TCP with selective acknowledgements. We actually looked at the selective acknowledgement option earlier, as well as the cumulative ACK. They add information about the byte ranges you've got. Once you've got these ACK ranges, there are ranges of bytes that have been received that are carried in the acknowledgements from the receiver. The sender no longer needs to guess which packets may or may not have got there. The receiver's telling it. So this is much cleaner and more straightforward in terms of trying to work out what might be lost and retransmitting it. You can retransmit without the guesswork. So SAC is the option that is increasingly used in modern TCP. It's simply a matter of deploying it and turning it on. So now we know how TCP congestion control works in routers that lose packets. G'day viewers. In this segment I'll tell you about explicit congestion notification. So our topic is how routers can help hosts to avoid congestion. We've talked about the network layer needing to work together with the transport layer to avoid congestion and come up with a reasonable bandwidth allocation. So far routers have been helping by, well, dropping packets, which is not very helpful. It's some kind of signal, but it's a little bit implicit. With explicit congestion notification, routers are going to send an explicit signal to hosts saying that there is congestion. And this is a kind of congestion control or a form of support for avoiding congestion, which is being rolled out, deployed in the internet today. So mostly this is a mechanism that's not used yet, even though it's been around for a long time. And its time is coming as it's deployed more and more. So to understand why explicit congestion notification is useful, let's consider the difference between congestion avoidance and congestion control. If you think about it, with classic TCP, actually it's not avoiding congestion. The way it finds out where to set the congestion window is TCP really, by increasing the congestion window, drives the network into congestion. Then it does a pretty good job of recovering. So TCP is actually causing congestion. And it has to do this because it needs to seek some kind of loss, which only comes through congestion, to know when to slow down. Okay, I mean, it works pretty well. But, you know, if you want to build a good network with low delay and low loss and whatever, wouldn't it be better to actually avoid congestion? This is what we would like to do. We would get better performance, low levels of loss, lower levels of delay, you know, while still getting the high throughput. We just need to find a way to do this. This is the real question. How can we do this? With classic TCP and routers providing packet loss signals, we really couldn't do this very well. Well, maybe there are options. With explicit congestion notification, we're going to build supporting to routers to help us avoid congestion. And this will get us to a better place. This is something that's going on in the internet. So to just understand a little bit about how routers could help, I want to remind you of this slide from the beginning, almost, of when we talked about congestion. We talked about the network providing feedback via a signal, and there were several different kinds of signals shown here in this column. The first one was packet loss. This is what classic TCP used and many forms of TCP use today. Well, most forms of TCP interpret packet loss as congestion. We said this is a good mechanism in that it's hard to get wrong. You can't build routers that don't drop packets when congestion is occurring. But the downside that I'm talking about now is you hear about congestion late, after it's already occurred and done the damage. Well, there are two other signals that we can use instead. Packet delay, because delays will begin to go up as soon as congestion is approaching, and router indications or explicit notifications of some kind from routers telling you that there is congestion occurring. The big benefits of these two approaches are that we hear about congestion early. And they're a little different in some ways. Packet delay is a bit of a signal that can fluctuate, so we need to work on how to infer congestion from it. And exactly how to do this is not so clear. I'm not going to talk about this, although if you're interested, there are various kinds of congestion control around that do use packet delay. Instead, what I'll talk about is a simpler and cleaner mechanism whereby we use router indications, messages from routers that congestion is coming. The downside here is simply that we need router support, which is why it's taken so long to deploy. But once it is deployed, we'll have a fairly clean way of recognizing when we're driving the network into congestion. So this mechanism whereby routers provide congestion indications is called explicit congestion notification, or ECN. The idea is, it's fairly straightforward. The idea is that the router is going to detect the onset of congestion by monitoring its queue. Instantaneous queue size can fluctuate a lot, just like our RTT data could fluctuate a lot. So the router can use some kind of moving average over it to get an estimate of the average queuing time. That should be near zero. If that begins to go up, it means that a persistent queue is beginning to build and we might be getting near congestion. When this happens, the router here will know that we're near the point of congestion, and it will then mark the packets that are going through it which are experiencing congestion. Marking is simply turning a bit on the IP header. So it's just flipping a bit is marking it. Now there were some bits in the IP header, if you go back and look at them, which are used to do this, the ECN bits. Now, when a host receives this packet, when it goes through the network and arrives at the host will know that it has been marked, and it will know that that packet experienced congestion. What the receiver will do is it will say, well, this congestion, I need to tell the sender about it, because congestion, previously we detected it with a packet loss. Here marked will be considered to be the equivalent of having lost a packet. It's just we're hearing about it ahead of time. What the receiver will do then is that it will send this congestion signal back to the sender. Now, actually the congestion notification is carried on the IP layers because it has to be done in the network, so it's a network layer protocol. When the mark arrives at the receiver, this information is passed up to the TCP layer, because it's the TCP layer, the transport, which will need to respond to congestion and interpret these marks and do something about it. So at the TCP level, in packets that are going in the other direction, ACKs and so forth, we will send this congestion signal back to the sender. And the sender here, I'm just going to write sender and receiver. The sender here will get that congestion notification. If there'd been an actual loss, it would have worked out from the ACK stream that there was a loss. Instead, there's another side channel whereby it gets these congestion notifications. But it treats them as equivalent as a loss in that it will half its congestion window and do all of the slowing down and so forth. So TCP really doesn't need to do anything new with explicit congestion indications. It just needs to treat them as loss. And with that, we're pretty much done with ECN. The advantages of ECN are that routers are able to deliver a clear signal to hosts of congestion. The congestion is detected early. This means the sender can react to it before it causes loss and excessive delay. So we're getting a better quality of network service by avoiding this congestion. And you might have wondered about whether, why these bits were flipped on packets as they went through and congestion notifications were carried, congestion signals were carried from the receiver back to the sender. But what we've done here that's kind of clever is we've sent these congestion indications while sending no additional packets in the network. When the network's getting congested, it's not generally a good time to be having routers generate extra packets, which are another source of traffic. So we're simply using bits on existing packets so we don't amplify the traffic. The disadvantage of all of this is really the deployment question. That we need to upgrade the routers to produce these indications and the hosts to make use of it so that TCP will operate a little differently. It's not until you've got them both upgraded that ECN will be deployed and used on the internet. And it's a little bit of a chicken and egg situation, since you could wonder whether to upgrade the routers if the hosts haven't been upgraded or the hosts if the routers haven't been upgraded. But we're getting there, and in the future you can expect that TCP-style congestion control will use explicit congestion notification from routers, as well as selective acknowledgements. And that will make it just that little bit better than most of the versions of TCP congestion control that we've seen. And now you know how congestion control works. G'day viewers. In this segment I'll give you an overview of the application layer material we'll cover. Okay, so first of all, congratulations are in order again. We're moving on to here, the application layer, having covered all of the lower layers of the network so far. And the application layer is where all of your favorite applications live. The web, YouTube, Dropbox, whatever it is you like. So in this unit, we're going to learn about some of those applications, focusing mostly on the web, as well as we'll use the domain name system, which translates host names to IP addresses as an example of an application too. All of these applications are really building distributed network services, you might think of as things that use the network, that is, on top of the services of the transport layer, which we've covered already. So just a little bit of a refresher before we dive into the details. Here's our protocol stack again, just spelled out in a little more detail. And I want to draw your attention to this blob, which is really an app or an application. Now, interestingly, inside it, there's an application layer protocol. I'll often use app and application layer, the application layer protocol, and all of those things synonymously. That's fairly loose, so really the app is the program. It contains an implementation of an application layer protocol. Here, HTTP is the application layer protocol. App layer protocol. That's part of the application. And I've also drawn the lines just to remind you of where this functionality is typically implemented in systems today. So the application, including the application layer protocol, is something which usually runs at user level on traditional operating systems. And in the operating system, we have TCP/IP and everything below the application level, essentially, down to some of the lowest layers, the link and physical layer, which can be implemented as part of the NIC in hardware, the network interface card. Now, one thing I want to call your attention to here is that application layer protocols, they don't necessarily need a GUI. So this is why, from our point of view, something like the DNS, the domain name system, which we'll get to later, but I'll tell you now, it translates host names to IP addresses. That is an application layer protocol from our point of view, even though it's something that doesn't really have a user interface and you might not otherwise be aware of it. You might think of it more as a network service. I'll also give you just a little bit of a refresher on the protocol layering, how it manifests itself in terms of structure on the networks. The only real point I want to make here is that typically many application layer messages will be relatively large. So here's our long HTTP message. This was an image in a web page coming back or so forth. This won't fit in a packet. So to be carried across the network, it will be split into multiple packets. Or segments, if you like, transport segments, where a TCP transport segment is typically carried in a single packet. So we'll loosely use packets. So you can see here that pieces of that HTTP message are sent, one piece within each different packet. So there are extra headers here. Of course, the application layer doesn't see all of this because all of this dividing things and putting the headers on is in the TCP and IP layers below the application layer. The application is using the services of the transport layer, so it's just seeing a byte stream if we're using TCP in this case. Okay, so that's just the protocol layering to relate it to some of our basic concepts. Now let's move on a bit towards applications. Okay, well, one of the difficulties with talking to you about applications is that applications are a very diverse set of things. An application does, well, whatever it is you want it to do. So these apps vary widely, and their communication patterns vary widely too. I can tell you that whatever their communication patterns are, and they do vary, they're going to need to build them on top of the services the transport layers we're already providing. So I've sketched 3 examples for you here, just to think about the different kinds of communication patterns. Now on the left here we have the web, and the real communication pattern need for the web is a series of variable length and reliably transferred request-reply interactions. So this is where you fetch a web resource, and you typically do this many times. There's a whole series of them to build a web page. This kind of communication pattern is going to be built on top of TCP in the case of the web. TCP already gives us the reliability and the variable length messages as part of its byte stream. So we'll need to build a series of request-reply interactions on top of it. That's the web. A completely different example here is in the middle. So the domain name system, its need is for, it says here, short, reliable request-reply exchanges. You'll have to trust me because we haven't seen the DNS yet, but it's going to send a series of very short messages to ask for these translations. Because it really needs to send short messages rather than a variable length and possibly long byte stream, it builds on top of UDP. So and you can see I've shaded this box as a little mix between all of the grey and the pink, because I would actually like to point out that DNS is something that would like message reliability but not a byte stream. So it's a little stuck in terms of the transport services. It sort of wants something in between TCP and UDP, right? We wanted the reliability but not the byte streams. That didn't exist as a transport layer service, so DNS at the application layer will build it, the reliability itself. So it's really almost building a bit of a transport layer because we didn't have such a good fit. And on the right-hand side, I have an example of Skype. Skype also builds on UDP. Skype is really just a stand-in for a popular real-time conferencing application that's sending around audio and video between live participants. The reason to build on top of UDP normally is that there's no need for reliability. The communication needs to be real-time, so if the information doesn't arrive quickly by a deadline, there's no point retransmitting it so that it can arrive later for the sake of reliability, because everyone will have already seen a glitch in the conversation and moved ahead. So Skype somehow needs to implement a real-time stream delivery communication pattern on top of UDP. So these top boxes that are in the pink, or the grey and the pink in the middle, are the network communications that these applications are going to implement. And we'll look at some of them in a lot more detail. What else can I tell you about applications in general before we dive into specific applications? Well, one other thing I can tell you is, that I can remind you of, is one of our reference model slides from the very beginning. You remember this old OSI reference model? You might have recalled that it had these session and presentation layers between the transport and the application. Now, we're not going to follow a strictly layered model and have any of these layers in our applications. Nonetheless, I'm pointing this out because both sessions and presentations are very much two relevant concepts, and most applications will express them in one way or the other. They won't be coded in a strictly layered fashion as in this protocol stack, but there are still things which are worth thinking about within the context of applications. So let me give you a quick slide on each of those. So what's a session? A session is really, it says here, a series of related network interactions. And they're done in support of a common application task. Now, often because we don't have a strict session structure, this task will be informal rather than explicit. But I'll give you a couple of examples here. In a web page, simply viewing a web page, you end up fetching a whole series of related web resources, the text of the page, associated images and style sheets and so forth. So the session is this overall page fetch, which is made up of the many component fetches. A different example would be a Skype call. A Skype call involves a session because it often won't have simply one stream of information flowing over UDP. It will have a series of related activity. In a call, for instance, you might have audio and video and chat messages, and they all need to be coordinated and used together in support of a common goal, that conference call. Okay, what about the presentation layer? Well, the point of the presentation layer is, as it says here, apps need to identify the type of content as well as encode it for transfer. That's what the presentation layer concepts are all about. So some applications might only want to deal with one kind of content, but for many kinds of applications, if you just think about the web, that application will deal with many different kinds of content and want to handle them in different ways. If there are multiple types of content, we're going to need to say what kind of content is carried and what kind of message. And again, I'll just give you a couple of examples of how this is often done in practice. A very common standard on the web, and it's used elsewhere too, for specifying the type of media are the so-called MIME types. Originally, this came from email. Multi-part internet mail extensions is what MIME stands for. But it's really more relevant these days for the web. An example of a MIME type is image/JPEG, and there are many more that you've probably seen in different places. Text/HTML, for example. These MIME types or media types identify the type of the content. So often application layer protocols will carry meta information, such as these MIME types, to describe the content they're transferring. As well as the content itself, there's also something distinct called a transfer encoding. Just because you've got a particular content like an HTML file, it doesn't tell you what format is going to be sent across the networking. For instance, one common transfer encoding might be gzip. You might decide to gzip the contents. Or you might not. If it was a JPEG image, gzipping it probably wouldn't do much good. So that's a transfer encoding. Now, and I would also point out that often these application layer headers tend to be simple and expressed in a way which is fairly easy to read, rather than compactly packed, say with a binary encoding for reasons of efficiency. That's because these headers are usually small compared to the contents, and a great amount of value can usually be obtained by making them easy to see. For instance, when you debug it, you can just look at the contents of the messages much more easily. Okay, so Internet applications. I said that they are many and varied. In fact, one of the few things you could say about Internet applications in general is that they're always changing and evolving and growing. This timeline just gives you a sense of the dominant Internet application and how it has changed over time. In the beginning, around 1970 or 1969, we really started with Telnet as an application. This is a remote terminal to a remote computer. Today we would use a more secure version called a secure shell, but nonetheless Telnet was a very early dominant internet application, along with file transfer as a utility. Email in various forms was actually the first killer application of the internet that took off very soon after the internet, or ARPANET at that stage, began to grow. And email was the dominant application for quite a while. Then we began to get to other richer kinds of content. Network news, if any of you remember that, it's a precursor to the web, a different form of content where really text was being sent around, but news groups was one sort of interesting other kind of content which rapidly increased in volume. But all of this was completely dwarfed when the web came along in the early 1990s. And the web itself has grown through several different phases. It's initially started off with clients talking directly to servers. But as very popular sites became more and more popular, content distribution networks were really embedded into part of the web infrastructure. And the traffic that was served by content distribution networks dwarfed much of the other traffic. In the middle here, there's another kind of application which became very popular for a time, still is, peer-to-peer file sharing with protocols such as BitTorrent. As digital audio and video and other kinds of content proliferated, there was a need to transfer them, or at least many people would transfer them without using any kind of centralized infrastructure, clients helping themselves. That's this peer-to-peer system, which we'll eventually see some of. The web itself has also these days grown very much in the direction of video. So the bulk of the traffic on the internet is probably video that's been streamed across the web, with slightly different protocols. In all of these, it's always called the web. Everything is the web. But as we go up these steps, often the way the protocols are used changes slightly to support the different kinds of usage. So the web is certainly a big application which has many pieces to it. And what's next? I don't know. Your guess is as good as mine. Maybe it'll be some kind of content caused by all of this Dropbox traffic. Who knows? Maybe it'll be something else entirely. We'll see. But the one thing that is for certain is that there will be something new up there, and it will transfer more and more traffic. This is how the web evolves. If you are interested in finding out a little bit more about the evolution, really, of the way we use the web, the different applications, there are all sorts of resources out there you could take a peek at. I've just provided some pointers here to some that I look at fairly regularly. Akamai runs a State of the Internet report quarterly that gives you some data on the traffic they serve and what they see that's going on. Cisco also annually publishes a visual networking index, which contains forecasts of how internet traffic is growing and changing. And Mary Meeker is also well known as an analyst who pulls together different sources of information and gives you her view of where the internet is heading. Out of all of these different sources of information, there are some points that I think you could take away for where we are right now in the web, and I'll just highlight them briefly. And in some ways this is about traffic, but all of this traffic is very much driven by applications. That's why I'm talking about it now. So today, the growth of the internet is still robust. It hasn't capped out or anything, it's still very much growing, especially in the dimensions of video, wireless, and mobile traffic. Most of the traffic from the applications we have is video today. It's the majority of the bytes that are sent over the internet. And predictions are that if current growth rates continue, we'll be at 90% of the traffic on the internet being video within just a handful of years. Of course, the way the internet works in those handful of years, a whole new application could come along and dwarf everything so far. Wireless traffic is also growing. Wireless traffic is right now just a little less than half of the internet, but it's soon predicted to be the majority of traffic will come from wireless links to the edge of the network. Mobile traffic, which comes from smartphones, is still a small portion of the overall traffic, around 15%, but it's growing quickly. All of these dimensions are growing. And interestingly, there's also been observed growing amounts of attack traffic, large denial of service attacks and other kinds of infiltration. So this much of this has come from China, if you read all of your newspapers, but there's also a fair amount of attack traffic that comes from the US and Russia. So the web is also evolving very rapidly, not simply different internet applications. And here's a visualization I just wanted to show you. This comes from evolutionoftheweb.com. And you can see here this really pretty amazing graphic picture shows some of the different technologies, not simply HTTP that starts on the very far left in 1991, but as we go ahead over time, different browsers appear, starting with Mosaic, then Netscape Navigator, Opera, and Internet Explorer. And there's a whole proliferation of different technologies here. Different kinds of HTML, scripting with JavaScript and Java and Flash, HTML progressors and so forth. And as we go to the right, not only do new kinds of internet browsers, not only are they developed, but sorry, I'm just stunned by the mess here, as different kinds of web technologies that are now present in your browser are all developed. Okay, so out of all of this picture, the part we're going to look at, that I'm going to talk about as relevant to the network, is simply this path. This is HTTP and its evolution. Nearly all of the rest has to do with the execution of content on browsers and servers and the kinds of content itself, like HTML, and that's a little bit wide of our purview. So we have a lot to look at already just with HTTP, but it's only a small part of the picture. Okay, so we'll look more at applications in some of the coming segments. We've gone over the evolution of internet applications, and now we're going to select just a handful of applications to look at. First, I'm going to tell you about the DNS, the domain name system, because that's really a crucial service translating the host names to IP addresses that we can use. Then I'll switch to the web by telling you about the Hypertext Transport Protocol, HTTP. And we'll just have much to discuss about the web, including how different kinds of caching works and content distribution networks. We'll also get to peer-to-peer systems such as BitTorrent at the end, just really to provide an alternative to show you a protocol that's a little different than HTTP. And finally, not in this unit, but later on, we'll get to real-time applications such as voice over IP. And I'll separate out that last application and treat it differently when we cover quality of service, because in that respect it's quite different than the other applications. Okay. G'day viewers. In this segment I'll give you an introduction to the domain name system. So our topic for this lecture and for the next lecture is the domain name system, the DNS, as you might have heard it called. The DNS is responsible for mapping between host names, these nice human readable names for computers, and their IP addresses, as well as other associated functions. In this first segment, I'm going to give an introduction to the concepts of the DNS and focus on the namespace itself and naming different hosts. So let's start with just the idea of names and addresses. Names here are really high-level identifiers for different resources, whereas addresses are these lower-layer identifiers, which provide typically a way of locating a resource. Now, really there are multiple levels of addressing and naming that can go all the way down to the bottom here, starting from the high level to the low level. For instance, a full name might be a high-level name, which might be mapped to a lower-level address, such as an email address. But this email address itself could also be thought of as a high-level name, which could be mapped to a lower-level address, such as an IP address, and then an Ethernet address to find it. Resolution, or lookup, is the process of mapping a name to its address. So if all of this sounds a little formal, you might really think of it as just being like a phone book, in the sense that that is a directory, and you use it to look up a name to addressing information about it. In a phone book, you might take a name like Andy Tannenbaum to an address where you'll be able to contact him. In the DNS, we'll more typically take a host name written like this, flits.cs.vu.nl, to an IP address, such as an IPv4 address here. Now, before the DNS, in the early ARPANET, the way that we mapped from host names to IP addresses was just with a file called host.txt. You just needed a copy of that file. So it was regularly retrieved by sites from a central location at what was called the NIC. Here NIC stands for Network Information Center, not your network interface card. The NIC was, just the body in charge of the network, so you would copy an authoritative version of this file from the NIC and distribute it to all the machines. Names in this space were initially flat, just the name of your computer. Galar, Vegemite, whatever you'd like. but they became hierarchical, such as lcs.mit.edu, starting in about the mid-80s. As you might imagine, this first initial scheme, copying the authoritative file from the central information repository, was neither very manageable nor very efficient as the ARPANET grew into the internet. It wasn't very manageable because there's one central location and you need to coordinate with it to get your information into the network, and there are possible naming conflicts, especially when everything's flat and so forth. It's not very efficient because there's a bit of a delay getting that information there and before everyone's copied down the file nightly so they can contact you. And it's also not very efficient simply because that whole file has been transferred repeatedly to everywhere on the internet, whether everyone needs to contact everyone else or not. So the idea of the DNS, which emerged, actually I'm not quite sure when, the mid-80s, I would guess gradually. The idea with the DNS is to provide an automated system that performed this mapping between the host names and the IP addresses without this central repository that everyone had to coordinate with. So we still want to be able to perform this same translation as though we were looking up a local file, but we're not going to have the local file anymore. I haven't told you exactly how we're going to do it yet because we're going to get to a lot of that later in the second part. Now we're just going to go through the namespace. I'll say here that the goals, really just at a high level, they're to make the administration of names easy to manage, especially amongst all of the different multiple parties that are involved in the internet. Having to get these parties to coordinate and agree on naming conflicts would be a pretty big job, so we would really like to come up with a system that makes it easy to manage administration of names, even when multiple parties are involved. We'd also like the domain name system to be efficient. Here, efficient means a few different things. It means good performance, so that we can map quickly between host names and IP addresses. This is necessary because the first time you contact a site, for instance, you'll need to work out its IP address to contact the server and retrieve a page from that site. So any latency here is contributing to latency as you surf the web. It's adding to page load times. We'd also like the DNS to be fairly lightweight in that you require a few resources or few hosts to be able to run it, so it's efficient in that sense. Well, the approach that we're going to get to eventually is to use a distributed directory service, or at least that's what we're going to design and implement, a distributed directory service. It's going to be based on a hierarchical namespace, such as the lcs.mit.edu, because that's going to provide a natural way to break up the namespace and distribute it to different hosts. And to tie all the pieces together when everyone has a different portion of the namespace, we're going to use an automated protocol. That's the DNS protocol. So just maybe to step back and emphasize the difference between a host.txt file approach and this approach that we're moving towards. In host.txt, you had a copy of the entire internet namespace in your computer to use. With the DNS, there is no one large file with all of the internet namespace. It's distributed. So you just use a protocol, the DNS, to access the portion of it that you need at a particular time. Well, I'm getting ahead of myself. So let's just begin from the beginning and talk about the DNS namespace. This is what the namespace looks like. It's hierarchical, so that means it's an upside down tree if you like. Here's the root, it's this dot, it's called dot, although we typically omit the dot when we write names, as you'll see in a minute. So there are many branches out from this root. I'll just highlight one here, the one that goes to the edu domain. All of these top ones, this first layer, are what are called the top level domains. That's this row here, such as edu. And after edu, again, since it's a tree, from these top level domains we divide and have other names there. Under edu here I've just shown one particular name, Washington, washington.edu, the University of Washington. But there'll be many other branches of .edu, one for MIT, one for Berkeley, Stanford, and so forth, all of the other universities. And we can continue this for as many different layers as we'd like. Under washington.edu, the namespace here just happens to be distributed into a couple of branches shown here. One for the CS, that's the Computer Science Department, another one for Eng, the engineering. the School of Engineering, and there would be many other different branches in any university, of course. And within CS, I've just shown one branch here for a particular computer called Robot. The reason I've highlighted some of these branches is just to get down to the end, so there'll be all sorts of other ones off the tree here. But for the path at the end, we would write this host name. This would be robot.cs.washington.edu. That should look like a familiar host name to you, not the particular name of it, but just the, let me make that a little clearer. Just the particular form of names. So you'll note that the name there is, we gain it by going up the tree towards the root, from the leaf back to the root, of course. And you'll also note that, the dot, logically there is a dot at the end here, that's the very end. Usually we can omit this as common convention. Well, so let's talk about the namespace a little more. So there are, I'll just tell you about some of the top-level domains. That's sort of where a lot of the action is in terms of some of the interesting news articles you'd read. Now, this tree, the domain namespace, is administered by a body called ICANN, the Internet Corporation for Assigned Names and Numbers. ICANN was formed in about 1998, and it really came into existence as the Internet grew because there was a lot of attention around matters such as naming. Naming, it turns out, is a very financial, political, and international topic. Everyone gets very involved in it. And particularly as the internet began to transition from an American institution, an American administered institution, to a worldwide international asset, some of the administration became a little more general with ICANN serving as the body. So ICANN here began to administer the top-level domains, or TLDs as they're called. Initially, when the internet was young, from the beginning of the DNS, there were 6 TLDs. Well, pretty close to the beginning anyhow. .com, .edu, .gov, .mil, .org, and .net. You're probably familiar with most of these already. In fact, they're most of the TLDs that you might see, although I would remind you actually that since ICANN took over, there has been a process for adding more TLDs. And in fact, a series of other TLDs, we must have around 14 or so, have been added, starting from about 2001, with TLDs such as .aero for the aerospace industry, .museum, and so forth. These are little used compared to some of the other ones, but who knows where they'll end up ahead of time. The most recent addition to get us to the 22 was .xxx for the sex industry in 2011. And as you might imagine, this was a little political. It took, or controversial. It took years to come into being. And now that it exists, we'll see if it gets used. Many of these different top-level domains have different usage policies. These 22 ones I'm talking about are what's called the generic TLDs. Generic just means that they describe a whole category, and the usage policy is going to depend on the category, what it was intended for and how it's administered. For .com, for instance, well, it's really for companies or commercial institutions, but anyone can get a .com address. You just have to pay your $10 or whatever it is to a registrar to serve the name. On the other hand, other top-level domains like .edu are for approved educational institutions, and presumably not anybody can get a .edu address. As well as these generic top-level domains, there is also a much larger list of country code domains. There are around a couple of hundred of these, or 250 or so. These are 2-letter country codes which come from a standard list of countries. This is not invented by the internet. It's more administered by the ISO, so by international bodies. So these 2-letter country code, they might be familiar to you. They're things like AU for Australia and so forth. And recently, starting in 2010, these country code can also be written using internationalized scripts, Chinese characters, Arabic characters, and so forth. Now, while these TLDs were really intended for country usage, this is why everything in the UK ends with UK, for instance, or in Spain, ES. many of these country codes have been widely commercialized. For instance, Tuvalu is a small island. They happen to have .tv. So they've sold the rights for .tv and they partner, I think it's with VeriSign. Because of course .tv is a domain name that many TV stations might like to acquire. And actually this island makes a small amount of money over it. They would like to make more money over it. There's actually a little bit of controversy over it. But they get a feed of money from the naming of .tv. Another one you might have heard of is .fm for radio stations. These are the Federated Islands of Micronesia, I believe, something like that. You might have also seen quite recently there's been a flurry of domain hacks. For instance, Instagram with the .am. This is really the .am being a country code, Armenia, but been reused as a way to spell Instagram just with fewer letters than beginning in a .com. Similarly for Google, goo.gl. The GL stands for Greenland and so forth. So as you've just seen from surfing the web, these country codes are really beginning to be exploited in all sorts of ways. And presumably some money for that licensing flows back to the country itself. Okay, so we've talked about the DNS namespace. That's this tree. We haven't yet gotten to how we would divide this up for distribution. So I want to get to that because that's the heart of really how the DNS operates. This namespace is divided up into zones, and a zone is simply a contiguous portion of the namespace. It's the portion of the namespace we're going to serve with a DNS server. So for instance, a zone could be this. This is like everything under the acm.org domain. Even though there are subdomains there, one zone contains all of that information. We'll put that all together in some file that can be accessed. Here's another example. In Washington, just for the picture here, we might have everything under Washington and the Washington domain and the eng.washington.edu domain, but not the cs.washington.edu domain, which would be handled by someone else. So what this really means is that CS has been delegated from Washington to a different zone, and CS is in this zone with the robot. And really this would be because the computer science department runs its own, administers its own zone and serves its own zone from its own server. So these zones, right now they're just a different way, they're a way of dividing up this namespace into pieces. And I've just circled a few to show you the different kinds of pieces that might exist. Edu is a zone too. So what that zone will know is anything in there which is really just the links to the other zones. So there are links between all of these pieces. One zone, if there's something low, will have a pointer to the rest. Okay, so the zones here are important because they're the basis for the distribution. So there is going to be, for instance, just recalling that picture, the Edu registrar administers the .edu zone. The University of Washington administers the washington.edu zone, and the Computer Science and Engineering Department at UW administers the cs.washington.edu zone. All of these zones, or each of these zones, has a name server that hosts the information in the zone, and that's who you're going to contact for all of the information about the zone. If you want to find out about a computer inside cs.washington.edu, for instance, you would contact the CSE department's name server because it's going to know about it. Now for this to work, any zone needs to, so what's going on there? Any zone needs to include contacts for delegations. So the zone washington.edu, if is going to need to include contact information for the cs.washington.edu, simply so that if you contact it looking for information in there, it has a forward pointer to say, well, I don't know what's inside cs.washington.edu, but I do know who you should contact to ask. Okay, so these zones are descriptions of portions of the namespace. But what does a description look like? What can be in it? Well, I'm glad you asked. A zone is comprised of a set of DNS resource records. And these resource records are the things that give information such as the IP address of hosts. There are different types of resource records. Each different type has a different purpose and it carries different kinds of information. Now the ones we might care about most easily or be familiar with is the A type of DNS record. The A stands for address, so an A record tells you, the value of an A record tells you the IPv4 address for a particular host name within a domain. Similarly, you might not be surprised to learn that there's an AAAA, it's pronounced Quad A record. That's the IPv6 address of a host. The Quad A name was chosen simply because the length of an IPv6 address is 4 times as long as an IPv4 address. And there are a few other names, types of record here. One of the most important is the name server record. This will tell you the name servers that this will provide contact information for the name servers for the domain. So it will tell you who they are and what their IP address is will be elsewhere in the file. Or it'll tell you the name server for a delegated subdomain. So this is how you can have a pointer in your zone to the subdomains which have been delegated. And there are various other records which are useful if you're running the DNS, but we don't need to worry about too much. I'll just briefly mention there's something called a CNAME, canonical name for aliases. So you can have multiple names for the one computer. You might have galar.cs.washington.edu might be a machine. The name www.cs.washington.edu might actually be, the same IP address as Galar. They're just 2 different names. They're convenient. There are also different records if you want to find the mailers, the mail exchanges for a domain to deliver mail to a domain. And all zones start with an SOA, a start of authority record. It gives you key parameters about the zone, like how long the information is valid for, and who the name server responsible for the zone is, and so forth. Let's see a little bit of an example. Here it is. And we'll look at this example, and then this will conclude an introduction to the DNS, and then I'll dive later into how DNS servers use this information. So here is our nice zone file. Now it's interesting, this is written out in a textual form. Originally these files were written in a textual form, so we still have that sort of historical representation. This is the external representation that you and I can read. When this file is loaded into a DNS server, it could be in any representation, it doesn't matter. But this is a tabular kind of format that's fairly readable. So it starts just with a comment here saying this is the authoritative data, the real data for this zone or for this domain. And there are various records. Here's our start of authority domain. It's going to have some key parameters. But most things in it will then be things like the A address. Here are A records. They have the IPv4 addresses. Here was an NS record. It had the name of a name server. So star.cs.vu.nl is the name server for this domain. We can also find out, so the IP address for star is here, because here's the A record for star within cs.vu.nl. This other information is information such as the time to live or validity information. I forget what 86400 is. That might be the number of seconds in a day or something like that. And IN just means internet zone. And I think that I'll leave it at that for a DNS record. What I would like you to take away from this first part is simply that we have this that we have this hierarchical namespace for the DNS. We use the hierarchy to distribute it into zones. And each zone then has all of this information. What we're going to see next is how to use these different all of this different zone information to actually perform the translation in a distributed way. Okay, let's move on to that. G'day viewers. In this segment I'll complete our look at the domain name system or DNS. So in the first part of looking at the DNS we talked about the distributed namespace. In this part I'm going to focus on how we perform resolution and map host names to IP addresses. So just as a quick recollection, here's where we were. We talked about the distributed namespace or the hierarchical namespace, which you can see in front of you. And we talked about the use of zones or contiguous portions of the namespace as the way that we were going to separate it into pieces that we could distribute to different machines. Every zone, which is a circle or an outlined region in this picture, is managed by one or more name servers. So now, here's what I want to really move on to. The DNS protocol and DNS resolution. So the DNS, as well as being a system, the DNS is the name of a protocol that lets any host on the internet resolve or map a host name, which in our terminology is a domain, in the hierarchical namespace to its IP address. The way that it's going to work is, well, you can probably imagine it, and we'll see an example in just a minute, but I just would say now, if a host doesn't know anything about what the IP address of this host name is, it can always start at the root, at dot in the namespace. If it goes to that zone, it can then work its way down following the forward pointers to delegated zones until it gets to the zone that has the right host record in, and it will there find the IP address. So let's see how this works, because it probably sounds a little mysterious, but it works in pretty much the way you would imagine, going down from the root. So let's just imagine that we have a client here, or an originator of the request here, that should say flits.cs.vu.nl. What it wants to do is it wants to resolve robot.cs.washington.edu. That means it wants to find the IP address of this machine. Must be a popular machine. It's been turning up a lot in our examples. Must have some great content. But to contact it, we need that IP address. So what does Flits do? Well, I'm going to write over some of these steps. First step is that Flits will send a query to its local name server. That's this machine here. This is some machine that's just on the campus maybe, and it's serving all of the machines in the computer science department as their name server. It's going to help them with these translations. Now, if the local name server is just doing this at the beginning and it knows nothing about robot.cs.washington.edu, it will do what we suggested and go to the root with a query saying, hey, I want to find out the IP address of robot.cs.washington.edu. What can the root name server do? The root name server, well, is sending a reply here. The reply says edu. What that really means is the root name server is going to say, well, I don't know what the IP address of robot.cs.washington.edu is, but I can tell you who the name server is for .edu. And you can go and ask them. Please go away. So the local name server then knows who to contact for .edu, so it tries its luck and asks .edu, what's the IP address of robot.cs.washington.edu? Well, .edu, again, it doesn't know the answer, but it's a little more helpful. It can at least provide a pointer to washington.edu, who you ask. Washington.edu is going to say, well, you know, I don't know, but here's a pointer to cs.washington.edu. And finally, when you ask cs.washington.edu, what is the IP address of robot.cs.washington.edu, this name server can answer it because that domain is within its zone. It has not been delegated. It will send back the IP address. And the IP address will then be at the local name server, who now has the answer, and it will send it back. In the last step to Flits, it'll say, well, here's the IP address. Wow, so that's an example of all of the steps that could be involved in translating that name. Well, let's talk about that example a little bit and see what was going on. One thing that I would like you to notice is that there were two kinds of queries that were performed in that example. The first was a recursive query. Here, Flits, for instance, asked the local name server what the resolution was, and the local name server then recursively performed all of the steps to get the complete answer and replied to Flits with the complete answer, rather than any of these little steps. This is called a recursive query. The other query were the other steps. These were the iterative queries. Here, when someone asked a name server in an iterative query, if the name server didn't know, it didn't then carry on further queries to find out the answer and return it. Instead, it just immediately returned the best answer it had, the pointer to the delegated subdomain, and called it quits. It was not involved in the query resolution anymore. This is an iterative query. And you can see that we needed several iterative queries to be able to come up with the answer to a recursive query. So the iterative queries were where the local name server was making queries to all of the other name servers individually. I'd like you to think for a minute about just the differences between the recursive and iterative queries. Why should we have both? Why shouldn't we always make queries iterative or always make queries recursive? That's a good thing for you to think about in terms of the design of networks. So think for a moment, and I'll tell you the answer. Okay, you ready? So here's the answer. So there are advantages to both, of course. That's why we're going to have both. What are they? Well, the advantage of a recursive query is that it lets one party offload administration and work for another party. So the recursive query here lets the local name server offload a burden from the client so that it can be this is sort of like an IT practice, and similar to the way routing was not done by hosts, it was done by routers. We can move the smarts to this local name server, have IT people who know what they're doing administer it so it can work very well and use it as a point of management, then have very little going on in the clients. They will then only need a very simple query interface to communicate with the local name server. And there's less work on the clients. It also potentially can provide better performance because the server can cache resolutions across a pool of clients. So maybe if some other client next to you has been asking for a host name of something that you were interested in, when you ask for it, your local name server already has a resolution it can use. So there are a few benefits here. Okay, that's good. Well, why then would we bother with iterative queries? Well, the advantage of an iterative query is that it lets whoever is receiving it deal with it and look up the answer, send it back, and then forget about the query. No extra information or timers or anything needs to be maintained for a longer interaction. So it's very lightweight on the receiving end, an iterative query. This makes it easy to build some of the high-load servers. If you think about the root server or the .edu server, for instance, these servers can be receiving a very high load of queries because there can be very many clients all over the internet which are using these servers. So we would like to reduce what these servers have to do to handle a query so that they can scale more effectively. With an iterative query, the root's not doing any more than the minimum amount of work for you. It's pushing the work back to the local name server. So between both of these techniques, we're locating the bulk of the work on the local name server. I'll also talk about caching. So the resolution I showed you so far was the full sequence resolution. So we know it can work, but it doesn't look very fast in that there might be a lot of round trips to machines all over the internet to be able to translate that name. If possible, we would like the latency of resolutions to be as low as possible. Why? Well, because this latency directly adds, in some cases, to the page load time. Because before we can load a page on the web, we need to get the IP address of the server to contact. So if the DNS time is long, it can lead to lengthy page load times on the web. And of course, everyone wants the web to run quickly, so it works well. As well as there are other services too. So generally, we would like this, other applications that depend on the DNS too. So we would like the DNS to run with as lower latency as possible. Now, the obvious thing we can do here is cache. We can have the local name server remember past translations between host names and IP addresses. That way, when the same host or other hosts that are using the name server want to know the translations again, the name server can quickly return a cached copy. So for this to work, there are a couple of steps we take. First of all, responses that come from name servers carry a TTL or time to live field, which says how long information can be kept in a cache and used for. If the information is very stable, this time to live field might be long. If the domain is in flux or you need to go back and consult it, it might be kept quite short. It's fairly common for TTLs to be hours or a day, for instance. And in addition, caching in the DNS is interesting because we can cache partial answers that come from the iterative queries. So, for instance, when I resolved robot.cs.washington.edu, we learned information about a variety of servers, not just that IP address at the end, but we also learned the name servers for .edu, washington.edu, and cs.washington.edu. So all of that's information that can be cached and used for future queries. Let's see an example. Okay, so let's suppose that Flitz now wants to resolve the IP address of edu.washington.edu. eng.washington.edu. Well, it's previously done some resolutions. They're going to help. So let's just imagine the steps. First of all, the client asks the local name server, here, I would like the IP address of eng.washington.edu. What does the local name server do? If it didn't know anything, it would go to the root. The root would tell it edu, and then it would go to edu, and edu would tell it Washington.edu, and so forth. But we've already done that on the way to get to through cs.washington.edu. So the local name server can shortcut this process because it already knows the name server for Washington.edu. Therefore, assuming this information is still valid in the cache, so it's been looked up within the recent hours or a day or something, but if it's valid in the local cache, the local name server can send the query to the UW name server for Washington.edu, and in this case, eng.washington.edu was in that zone, so it can be answered by that name server, who will return the IP address to the local name server, who can then convey it. And you can see here, we've cut out a lot of steps. So we potentially made the resolution much faster. Okay, so that's caching. Caching is really quite important for improving performance of the DNS. I want to talk just a little bit about some of the name servers at either end of this process, the local name servers near clients and the root name servers at the top of the tree. So the local name servers, we said that a client contacts a local name server. So that means a local name server is typically run by your organization, by IT people in your organization, in your enterprise, or it could be provided as part of your ISP service. This all depends on how your computer is set up. You could be running a local name server on your Linux host, say, or your host right now. Or your access point at home might also be running a local name server, which is then talking to your AP. This would maybe provide advantages by caching information for machines inside your house, which is available locally and quickly inside your house. It's also possible to use alternative systems for your local name server. Google, for instance, runs a public DNS, and you can configure your machine to use Google as a local name server. And you can look up on the web and read about it. Google suggests there are several advantages of doing this. They're trying to make the web faster. If you're interested, just Google it, and that way you can play around with it and see how some of the name servers work. One point for us, though, as part of this system, if we're designing it, is that clients need some way to contact their local name server. So how are they going to know how to contact their local name server? Well, you can see I've already provided the answer for you here on the screen. I should stop doing that. But what happens is that the name server is something which is typically configured as part of DHCP. So when your host is assigned its address and other parameters, those other parameters usually include the IP address, maybe name of the local name server, so that you can contact it and use it. Okay, what about the other end, the root name servers? Well, they're fun too. As you can imagine, the root name server, that's dot at the very top of the tree, is pretty important for the DNS. I mean, if the root was taken down, we wouldn't be able to perform name resolutions. Well, not to worry. The root is served by 13 server names. They're called, so you can see it's not just one machine. It's replicated. There are at least 13 logical names there. They're called a.rootservers.net through m.rootservers.net. Now, this is important because every host, every name server, every local name server that wants to be able to answer queries needs to have information about the root, what their name is and what their IP address is, so they can contact the root and begin this resolution process. That's handled by using a configuration file. So it's just part of the configuration of local name services to provide them a file. It's by convention, it's called name.ca. The CA stands for cache, so if you like, it's the cold information you put in your cache at the beginning of time to bootstrap it and get it going. Now, it's also the case that even though there are only 13 root server names, there are around 250 root server instances that are distributed around the globe. These machines together provide a highly reliable and reachable service for the whole internet because they're crucial for internet service. There's a very interesting trick here. You can read about it in section 529 of your text, Anycast. I'm not going to go into it in much more detail here because we just don't have time, but it's quite interesting. Many of these 250 server instances are reached by what's called IP Anycast. This is essentially a trick, a very clever trick, where multiple different physical locations around the internet advertise the same IP address. If you just assign them all the same IP address, what's going to happen? Will the internet break? Well, no, actually. What routing will do is it will take you to the closest place that IP address can be reached. So it will effectively route you to the closest replica of that IP address. This is called Anycast. And we're getting a bit of a performance gain by going to the closest one, as well as getting replication, which is good for reliability. And I'll just point out that these servers are reachable via IPv4 as well as IPv6, of course, so that the IPv6 internet will work. Okay, well, let's get have a little more fun with these root servers. I've just told you there are lots of them, A through m.rootservers.net. This map, taken from the rootservers.org website, gives you a snapshot of just how the root servers were deployed quite recently. So you can see that they're spread all around the world, and there are all of these different servers. So it's really quite an amazing infrastructure that's been built up. Now, as we wrap up all of the resolution, I'd like to go through the DNS protocol a bit. We've seen pictures where all of the queries and responses are sent, the messages are sent, but we haven't really talked about them in much detail. So now I'll just tell you a little bit about the protocol. So it's a query response system. That's the queries and the responses we saw in the previous pictures. This protocol is built on top of UDP. Typically, it uses port 53. These messages need to be reliable, and we just have UDP, which is unreliable. So the implementation of the DNS implements ARQ, automatic repeat request, for reliability. So you can see here is a client sends a message. That's the request or the query, and back later comes the response. Everything worked here, nothing was lost. If something was lost, the client, using its ARQ, would eventually time out and retransmit. This means that the server is stateless. The server just gets these queries in and processes them. It doesn't need to run any timers to see whether someone's got a message or not. If this response didn't get through for some reason, it's like the ACK, then the client will send the question again. So this is very handy for building high-performance servers, that they can process a message, then forget all state about it. At the client, however, we need some way to link together a query and a response, so you know which ones are paired. This is done by placing a 16-bit identification number on the messages. So you can see here both the query and the response in this example happen to have an identification value of 1, 2, 3, 4. Okay. What else? Service reliability. So I showed you how the query response between a single client and a single server. The DNS is a system that should be reliable, and we provide reliability by using replicas. Here are shown that there are 3 replicas, A, B, and C, for a given domain. A client here can contact any of the replicas with a query and get a response. All of these replicas contain exactly the same information. What that means, and of course when they return information, they return lists of translations or resolutions, including lists of all of the name servers for the domain. So when B provides replies there, or when someone's told you about the domain, they've told you that all A, B, and C are name servers for that domain. That means that if B goes down for any reason, it's unplugged, it's blown up, whatever, then a client here can simply contact A instead, say, for a query and get a response. So clients will choose different name servers to contact, and they'll typically rotate their choices, or the servers will rotate information that they send out. This also helps to distribute the load, as well as providing reliability. So that's a nice feature of the DNS protocol. And finally, let me just say, one topic that is kind of notorious sticks out in that I haven't mentioned it yet, is security. Security is a major issue for the DNS. That's because if the DNS is compromised, then you'll end up contacting the wrong computer to get information. Imagine, for instance, you're trying to log into your bank and you're contacting the wrong computer. This is not good. Security was not considered as part of the original protocols, but as the internet grew and many parties began to exploit it in different ways, security has become more and more important. Nowadays, DNSSEC, or the DNS security extensions, are rapidly being deployed and used. They've been under development for a long time, and now they are partially deployed, and their use is really beginning to take off. I just mention it now because it's an important part of the DNS system, but it's a topic that we're not going to look at until later. When we get to security, later on we'll look at this and other topics. So that's DNS resolution. G'day viewers. In this segment I'll provide an introduction to HTTP, the Hypertext Transport Protocol. So HTTP is the basis for the modern web because it's the network protocol which is used to move web resources that make up web pages between all of the clients and servers, or servers to clients maybe I should say. In this segment I'll give you an introduction to HTTP and talk about where it fits in the context of the web. And then later on we'll talk about the performance of HTTP in more detail. Okay, so beginning with the web, I guess. The web, this man is credited with the invention of the web. It's Tim Berners-Lee. He developed the web when he was working at CERN in Geneva, starting in about '89. From that time onwards, he and his collaborators came up with the first browser, server, and the first implementation of the HTTP protocol, which holds all of these pieces together. Within just a few short years, the web was popularized by the browser Mosaic, was a different implementation of the system, which had in some ways a more graphic user interface, and it really took off as it captured people's imagination. And very soon after that, Netscape was founded. The first World Wide Web conference, the first International World Wide Web conference happened in '94, and we were away. Very soon, the web became the dominant internet application, and it has been since about the mid-1990s. Tim Berners-Lee now directs the W3 Consortium, so that's the World Wide Web Consortium that standardizes the behavior of the web. Okay, so now we know a little bit about where the web came from, or we've refreshed our memories. Here's the overall context for the web and how HTTP fits, because it's really HTTP that we're going to look at. You can see here, there's the web browser in the middle, and the web browser is using the HTTP protocol, sending requests and getting responses to talk to web servers and to fetch web resources. Now, we're used to looking at web pages. Here's the page over here in the left. But I assume you know that a web page is really a set of related web resources. There might be the HTML text, the images, CSS style sheets, JavaScript that holds it all together, and so forth. So while we're used to looking at entire web pages, the HTTP protocol is really designed to deal with individual web resources, and it's the browser's job to knit them all together into the web pages and provide us the experiences that we're after. Just drilling down a little bit, we talk about the context for HTTP more. I've drawn one of our familiar protocol stacks here so you can see where it fits in. So we can see here HTTP. It's this request response protocol. So you can see it, browser sends a request to the server replies with a response. HTTP is implemented on top of TCP, typically running on port 80 is the well-known port that most web servers sit on. Now, because it runs on top of TCP, TCP is providing a byte stream for long messages and reliability. So great, HTTP gets those features. What it really needs to implement now is the request response series of interactions to build a web page. And I'll just note that, as usual, I've shown the browser here as an application on top, but really HTTP is typically implemented in a user level program. So the app, if you like, probably has an implementation of HTTP somehow folded in, maybe via a library, and the browser code itself. Okay, so this is the operating context for HTTP. Let's just look at how a web page is fetched to, again, just learn a little more about the relationship between HTTP and web pages. So I picked an example URL for a page to start with. Here it is. It's a page on Wikipedia for Vegemite. So if I write out the URL, you can see that it has several parts. The first part is the protocol part. That's HTTP. We're only interested here in HTTP URLs because they're the ones which are fetched with the HTTP protocol. If this was something different, a different protocol would be used to fetch it. And then the remainder of the URL has two components. One is the server component. That's really telling us which host. So you can see this is a DNS domain name. It's the name of our host, the server. And the part after this, well, that's the identification, the name of the page that resides on that server. So we go through several steps for a browser to be able to retrieve and display this page. And I'm listing them all here just so we can go through them and get a sense of where HTTP fits in. This is more than HTTP. In fact, the first step is often to resolve the server host name to its IP address using the DNS. We've seen how this is done with the DNS. We need this to be able to contact the server. Once we have the IP address for the server, we've got to set up a TCP connection. HTTP runs on top of TCP, so we can't do much till we open the TCP connection. After we do that, we can send our HTTP request. Now we're getting to HTTP proper. And then, once having sent the request, the browser will wait to receive the response from the other side, from the server. It will simply be sent on through. And then there is a large step here. I've started just because to indicate that there's a lot of complexity that goes in here. This step is really the fetching of embedded web resources. If you have a page which has 3 images in, well, you would have to go and fetch those pictures to be able to display the page. And you need to fetch them before you can render or display the page. The reason I've started is that this step is very complicated today in modern browsers because some of the resources that we can fetch are not simply static content to display, but they're programs such as JavaScript. Browsers need to execute those programs. In the course of executing those programs, they may discover that they need to use HTTP to obtain further resources for display. So pages have really become not simply a static picture that we're moving around, but real running application code, as it were, a real dynamic system. And finally, after this process is finished and a page is displayed, if it ever finishes, that is, because you can continue to interact with the page, at some stage there'll be a cleanup step, and we'll tear down maybe any TCP connections which are no longer being used. Okay, so this is the overall web page fetch, and HTTP is used as part of it to get every web resource. How that happens is going to depend on the execution of the content. And just for the sake of completeness, since I've started talking about programs and web pages, let me briefly go over static and dynamic web pages. This is actually not terribly relevant to HTTP, the protocol, which is what we're focused on in a networking course, but it is of course very relevant just to how well the web works. So you will surely have heard of static and dynamic web pages and understand somewhat about the differences. I'll go over that. In a static web page, the file contents are unchanging. They're whatever the contents of the file were. An image would be a good example. Maybe you get that from a URL and that's just what it is, the contents of that image. The contents of a file, which is the image. Dynamic web pages, on the other hand, are the result of program executions. So, and this program could be executed on either the server, the client, or both. The common languages that we see today are, and there are actually many that can be used, so these are just examples of very popular languages today. JavaScript, running on clients, and systems like PHP running as part of the server. So here, this figure just illustrates how dynamic web pages can fit in. To fetch a dynamic web page, you might just make an HTTP request as usual. The request doesn't care if it's static or dynamic. Now, when this request gets to the server, a program here would be run that would often consult a database and the input parameters you provide as part of the HTTP request to construct the output page. That's the output of the program. It would then go back to be displayed on your browser. However, the contents that comes back may include a program. This program would be run on the web page. Even if it doesn't cause any other content to be fetched right away, as the user interacts with the web page, you may trigger the execution of further parts of this program. And this program could then go off and request yet more content from the same server or a different server. Again, that content could be produced by a program, by consulting a database, and it could then be sent back to the program, and it could then affect the user interface. So you can see in this way, we've turned the what used to be simply a static page, like a newspaper or something, into an interface that evolves as the user interacts with it. It's really a running application. HTTP is just the part that's used over here, so it's not terribly concerned with how these programs are run. Now, the HTTP protocol itself, since I'm going to tell you a bit about it, I'm going to start just by giving you this timeline to show its evolution. HTTP has been around since the very beginning of the web. You can see here the first versions were used around 91 maybe, something like that, was when a version called 0.9 was popularly used in browsers. So this was pre-1.0 HTTP. And that version very quickly gave way to version 1.0, which came under development. Actually, it wasn't until like 96 over here that HTTP 1.0 was standardized. So before that time, different browsers all had pre-standard implementations. Really, a de facto HTTP 1.0 was evolving based on common usage and what was important. And it was standardized after the fact. You can see in the middle here, well before it's standardized, Netscape added cookies as a feature to the way the protocol worked by adding new headers. This allowed stateful behavior on some clients and servers. It's very useful for many things in the way the pages work today. Also around this time in 94, some of the first versions of SSL were developed. SSL and also TLS as it's known today are part of what makes up HTTPS, the Secure Web Protocol. This is a very interesting subject, but again, as with some of the other security subjects, it's something that we're going to defer until later. So I'm not going to talk about HTTPS now, just HTTP. So version 1.0 was developed over a period of a few years and standardized, eventually around 96. By the time it was standardized, work had already begun on, right about then, people began to move ahead to HTTP 1.1 with other new features that we'll look at, including what's called persistent connections. And HTTP 1.1 was then standardized, I think it's probably this arrow here, with RFC 206A, and then later revised a bit. So you can see that along this path, HTTP 1.1 has been developed, and that much of this activity here has happened over a relatively short period of time. This has been the flurry of activity that developed some of the initial versions of HTTP. And after that time, we've had about something like a decade of relatively stable usage of HTTP. Now, the web certainly hasn't stood still in that time. Actually, this other bubble in here says that there has been a huge proliferation of many different types of content, different media types, different browser and server scripting technologies. But these technologies have had only a minimal impact on HTTP. So it's stayed fairly stable for quite a while. The implementations in browsers, really, it's the deployment of the HTTP 1.1 features, which have happened increasingly over this period. More recently, however, the clock has again begun to start ticking on HTTP, and I'll tell you about a new protocol called SPDY, S-P-D-Y, just briefly in the following segment. SPDY is a protocol that's now implemented in Chrome and Firefox by default. It's forming the basis of what's become called HTTP 2.0, which is an ongoing effort just to slightly improve the HTTP protocol to make the web faster. Okay, so I've given you an introduction to the context of the web and the HTTP protocol. To complete an introduction to HTTP, I want to tell you about some of the features of the protocol. And we're just going to talk about the messages. You know it's a request-response protocol, but nothing about what the request and the response looks like. So I'll talk about that a little bit, and in a subsequent lecture we'll talk about HTTP performance and see more about how and when the requests are sent and what that means for performance. Okay, so the HTTP protocol, well, originally actually it was a very simple protocol. It still is in some ways a request-response protocol. It's just had more and more options and features added over time. Many of typically the headers, originally the way they all started, is they're text-based commands and text-based headers. This is actually very convenient for debugging the protocol and observing what's going on. One fun thing that you can do, this makes an excellent lab, is to try it yourself. You can pretend that you're a browser and try and fetch a page and see what happens. You can do this just by running the Telnet program on one of your clients, any system. It's not so easy maybe on Windows, but on most systems you can get a Telnet program and run it. You can simply, to pretend to be a browser, connect to a host, such as nen.wikipedia.org on port 80, and then you can send an HTTP request. Here's an example of an HTTP request. Just get and give it the URL and the HTTP version to make it work. Actually, if you try this, it's important that it be followed by a blank line before the server will respond. Once you issue this request, the server should look it up and it will return an HTTP response, which will have headers, and it could be the content itself, hopefully, or it might be codes telling you where it's gone or something else like that. But this is a fun thing to do. Okay, so the HTTP protocol, it's request response. Let's look at the request first. The request is simply a command or a method, which is the name for a command. And there are, well, it looks like there are several different possible methods here. Two of them are really very popular and are the ones which make up the bulk of HTTP requests. And I've shaded them here. You can see there's a GET method. Well, that's the command you send if you want to get a web page. You just send a GET request. There's also a POST method. This is the command that's actually used if you want the client or the browser to be able to upload data to the server. When you're writing a mail message, for instance, on a web interface and you want to be able to send it, or some other kind of document and so forth. This you need POST as well as GET to be able to write, to be able to develop real applications that have a user interface and can do useful things. These are the two main methods. You can look up all of the other ones in the RFCs, but these are the two ones you really need. The response returns, along with the various content, which hopefully you're asking for, status codes, which tell you what's going on. The code you want to get is a 200 something. This is a success code. It says, yep, it worked, and here are all of the parameters for the content and hopefully the content itself. Or maybe even code saying the content hasn't changed, so it's okay. You might get other kinds of codes, and you might have seen these in some places. 404 is a well-known error message, page not found. So you may well have seen web pages that say error code 404 when you're trying to access a URL that's not there. That 404 comes from the HTTP spec. It's one of the status codes. You might also have seen some of these other ones, internal server errors, forbidden. You typically won't see, although these are quite important, redirection codes like 301. Redirection would mean this page is moved from here to another URL. Maybe when you used a different server name than you're meant to use to access the content. If this code comes back, your browser will actually get it, realize it's a redirect, and try and retrieve the content from the new location on the web. That's why as a user you probably don't see this code much, but it's quite important in practice. And finally, both the request and the response can include, as well as the content itself on the response, they can include many headers, which just describe the context of what's going on and provide more detail to go with the request. Here are some examples of headers. Typically they're text fields with a fairly simple format. An example of one is content type : text/HTML. The content type header is telling you, surprise, the type of the content that's been returned in a response. Another header would be cookie : lect equals 84-HTTP. Now I just made that up, but that's an example of a cookie that might be sent from a client to a server to tell it some state it has, maybe about the lecture you're watching right now. There are dozens and dozens of different HTTP headers. You can look them up in the spec. I've just summarized some of the groups of them in this table. So many of the headers describe browser capabilities. So these are sent from the client to the server. They might describe, for instance, what language and kind of content encodings you will accept. The user agent is also a popular one. So the browser will tell the server what kind of browser it is. just because for implementation reasons, the server may want to return different responses depending on the browser. Yeah. Okay, so there are also many caching related directives which are sent in both directions, from the browser to the server to specify, well, some of the contents, its situation, what it already has, and from the server to the browser to specify how returned content should be treated for caching purposes. Examples of headers here, actually I'll get to some of these in the next lecture when we talk about caching, but they're things such as when the content expires, what date, or when it was last modified, a timestamp from the server for when this version of the content was created. There are also context information which is sent from the client to the server. I mentioned cookie is a state that the client is holding, which the server wants to know about to implement stateful interactions. There are all sorts of other things. Referrer tells you the page that the browser was previously on when a link was clicked to visit this page, so it's providing context. Actually, it's misspelt there. It should be R-E-F-E-R-R-E-R, but this is a misspelling in the standard, so this is what's stuck. And finally, there are probably all of the headers that you were thinking about. The content delivery headers that are used from the server to the client to describe the content itself that comes back with the response. We talked about content type, maybe to say it's image/JPEG or something, but there is also the content length, the encoding, how it's being encoded for transfer, languages, cookies that the server is telling the browser to now maintain and set for the next time it wants to contact it, and so forth. So, in a nutshell, we've now looked at the basic operation of the HTTP protocol, requests and responses using all of these different formats. In the next section, I'll move on and talk about the performance of the protocol as we see how it's used in practice. G'day viewers. In this segment I'll talk about the performance of the HTTP protocol. So we've covered an introduction to the HTTP protocol and heard about its requests and responses, but I haven't said anything yet about how well it performs over the web. That's what we'll begin to look at in this segment, and in particular I'll go over a couple of options for arranging requests and responses, so-called parallel and persistent connections. Now, for any discussion of HTTP performance for loading web pages, we need to understand what we really mean by performance. What is it we're trying to improve? For the web, the most direct thing that we would like to improve is page load time, or PLT. This is the time from when a user clicks on a link to summon a page until something useful appears in your browser. So it's a very user-centric measure. It's what people usually care about when they're designing websites. Note that it's actually different from situations such as when all of the content has been transferred in your browser, for instance. That's not really what matters. Or even the lifetime of the HTTP connection. Again, that's not really what matters. For the user, it's really the moment from when you click until you see something useful on the screen. And there are subtle differences between all of these different definitions. Unfortunately, for us, in terms of understanding it, page load time depends on many factors. It depends on how you structure your page. You may choose to have many embedded objects, different pictures that are part of the page, which are fetched by separate HTTP requests, or not. This would affect how quickly the page can be loaded. The page load time depends on the details of the HTTP protocol itself, as well as the TCP protocol. We'll see that TCP factors like time to set up connections and slow start behavior actually matters, depending on how HTTP mixes and matches between requests and TCP connections. And of course, the page load time depends upon the network itself. And it will turn out that it depends not simply on the bandwidth of the network, but it also depends on factors such as the round trip time. Oh, and I forgot to mention here, just that page load time is not just a hypothetical metric which is useful in theory. It's known to be useful in practice in that there's been much quantitative work, especially around online e-commerce. And sites find that small increases in page load time can actually decrease sales measurably. Amazon has a lot of data on this, for instance. So they very much care about keeping a good page load time to keep all of their customers happy. Okay, so now we want to understand how page load time works, or at least what kind of page load time you could expect from different versions of HTTP. So let's begin at the beginning with the earliest versions of HTTP. And the simplest thing you can do is to send one HTTP request and receive a response for it on one single TCP connection. If you have other requests to make, use other TCP connections for them. This is how that would work. So imagine that I'm trying to request a page, fetch a page, and it has the main body of the page and maybe a couple of inlined images. Well, first of all, I would set up a connection for the page. This is the connect. Then I would send the request. Then I would get back the response. At that stage, I might have the body of the page. I'd look at it, I'd see that there are inlined images. Well, I would then set up another TCP connection for the inlined image. This is the request and this is the response. And then I'd send a request again, get back a response. Actually, maybe it's a fairly big response because it's an image, but I would be done with it eventually. Then I'll set up the third connection, send the request, get back the response, and you can see where I'm going. So this is one TCP connection, two TCP connections, three TCP connections. This design was actually very easy to build to begin with because TCP is essentially giving you everything you need. On the other hand, it gives a fairly poor user experience in terms of page load time, as you might imagine. So let's dive into that. First of all, let me clean up the diagram so you can more clearly see the connection setup. It's just some delay for that. And the request and response. Now, so why does this give poor page load time? Well, there are several reasons. If you think about all of this behavior here, you can see that this is inherently sequential in the way we've structured it. So none of these steps are going on in parallel. We just have to wait for them all to happen one after the other. This is the case even when we're talking to different servers. Now you think one of the reasons you'd have a network is that you could talk to multiple servers at once and overlap activity between them. You can. We're just not doing that here. And because we're sending only one request per TCP connection, this means that we have all of the overheads of a TCP connection for every request. So in particular, we have like 3 connection setups, when if these resources all came from the single server, we would only really need one TCP connection set up to it. More than that, we're also suffering from TCP slow start at the beginning of each of these responses when a larger volume of data tends to be returned. TCP needs to start slowly and then ramp up and rediscover the speed of the network. We don't have a single connection that's up and running and we keep sending the data down it. Instead, we're doing 3 things independently. So for all of these reasons, we're not making very good use of the network. You might want to just stop the video in just a moment and think for yourself about how you would go about improving this. Improvements are certainly possible. That's exactly what we're going to see. But it takes a little bit of thinking to understand how you might come up with the improvements. So why don't you see if you can come up with some of the options that we'll get to. And I'll mention just the broad approaches on the next slide. You should be able to see, just to start thinking about what's wrong with this, that in this picture the network is not used effectively because only some blocks here are shaded in grey when I'm actually using the network at any significant rate to send back the information. The white time, the network is mostly idle. Actually, even in that grey period, slow start is going on, so we're not using the network very well. So there's a lot of inefficiency there to be gained. This picture gets worse, if you think about it, when you have many embedded resources that are part of a page, because we'll then have many more connection setups than we would otherwise have. And it's also worse, not only if you have many resources per page, but if you have small resources per page. Because for these small resources, we're not really ramping up, a big data transfer in these shaded periods to amortize all of the costs of connection setup and slow start. If each of these individual gray areas was a very large object, well, maybe it wouldn't matter if we had a few overheads to go with it. But if they're small files, then these overheads can really add up. So here's that slide that just outlines some of the categories of approaches we might go about for improving page load time. And we're going to get to most of these in more detail over the coming lectures. The first approach is simply to reduce the amount of content that we need to transfer. You could imagine doing this in a few ways, and this is something that's still very much popular today. It used to be that you would try and reduce the size of the images that you'd have on websites just to avoid unnecessarily large images, for instance. That's something you can do. If you wanted to, you could use better compression formats that are suited to the kind of image you have, so they're going to make it smaller. You could gzip some of the contents. As far as smaller images goes, for instance, note that a server might want to send a different version of an image depending on the client. If you have a big browser running on a computer that has a big screen, you might actually want a fairly detailed picture. On the other hand, if you're operating on your smartphone, there's really no point sending a high-resolution picture. So the browser would actually like to know from the client which situation it's in these days. That helps you send the appropriate content. So that's one approach, send less content. And there are opportunities for that. Another approach is to change the HTTP protocol to make better use of the network bandwidth. This is what we're going to get to in this segment, and I'll tell you more in a moment about how we might do that. And then there are other big approaches that we'll get to later. So another big category of approach would be to leverage repeated visits. For many web pages, it's the case that for a popular web page, you don't visit it just once, you visit it many times. If maybe you visited it every single day. If every time you visit it, all of the contents of the page is sent across the network, we're transferring the same information many times. What we could try and do is change the HTTP protocol to avoid these repeated transfers. This is called caching. And we'll look at caches and other devices which perform caching, such as web proxies, in a subsequent segment. And then finally, here's another category that you might not have thought of. And you can use this for popular content. You can move the content from the server, which might be remote, to locations that are closer to the client. This is going to have the effect of reducing the download time. This is the strategy that content delivery networks use, and we'll get to see that later on. Okay, but for now, let's dive in here and look at how to change HTTP to do something different than that single request per TCP connection sequential style we just saw to get better performance. What can we do? Well, here's the first thing you might think of doing, and that is to run parallel TCP connections. Why run one TCP connection one after the other, when in fact there's no reason you can't write a program to open many TCP connections at once? So here's what we would do. You would have your browser run, say, 8 instances, some small number, more than one, of the HTTP protocol in parallel. Each of these instances would have its own TCP connection and would send one HTTP request over that one TCP connection. These TCP connections are just happening in parallel rather than sequentially. You need to change a browser to do this. Interestingly, you probably wouldn't need to change a server. Servers are already used to being able to handle multiple concurrent connections. Usually these are connections from different clients. That's why they were built to support that, since you don't want to sort of block one client while you're serving another client. You'd like to be able to serve many of them in parallel. If that's the case, then the server can already serve multiple requests from the same client in parallel. It just drops out. Now, what you might wonder is, how does this strategy of running HTTP connections in parallel help us? I mean, after all, if this could simply be a different way of slicing up the pie. Instead of giving each user 100% of the network for 1/n of the time, you could give n users 1/n of the network for all of the time. It would all add up to the same thing. I hope I got the numbers quite right there, but I think you know what I mean. Giving someone all of the network for a small portion of the time versus always using the network but only getting a fraction of its capacity. If this was the case, it really wouldn't matter if we performed our requests sequentially or parallel. They would take the same amount of total time. But this is not the case, because the key observation here is that the single HTTP connection wasn't actually really using all of the network that much. It wasn't using all of the bandwidth. That's why we had a lot of white on the figure before. During the connection phase, we're really just waiting around for the two ends to synchronize themselves. We're not limited by the network bandwidth. That means if we run our connections in parallel, they're not going to be slowed down by very much, because now they're actually making use of something that they weren't using before. If that's the case, we'll pull in the last one to complete, and that will reduce the page load time, so we'll be better off. So parallel connections are something which is widely used in practice. But there's something even better that we can do, and this is called a persistent connection. Now, parallel connections help, but they're not a panacea, they're not ideal in a couple of respects. Actually, the important respect here is that something that's a little odd about these parallel connections is that even though they're all coming from one client, they're competing with one another for the network resources. So by writing a parallel client that maybe ran 8 connections at once, that one parallel client might appear to the network as though it has the same load as 8 sequential clients, because that's the behavior that it's providing. If that's the case, we're sort of multiplying the number of clients which are trying to use the network at the same time significantly, as far as the network's concerned. And the effect is to exacerbate the network usage. Usage tends to be more bursty, and this leads to larger amounts of loss, which then have to be recovered by all of the protocols. In fact, if you think about this, while we're downloading 8 connections in parallel, one of your connections might cause loss for another 3 of your connections, which will then have to realize it and deal with it. So the network doesn't operate very smoothly here. The alternative which we can use, which gains us many of the performance advantages of parallelism, yet is more effective in terms of network usage, the usage is more well suited to the network, is what is called a persistent connection. Here, what we do is we simply make one TCP connection to the server. We don't make 8, we just make one. And then we use this one connection to send multiple HTTP requests. So let's see how that would work on some of our time sequence diagrams. Here we are. So let me just draw in just for reference, here's how it used to work when we had our first scheme with the connections and then request response. So connect, request, response. And I'm just doing that repeatedly. Let me just do 3 of those. And actually I'm also just going to indicate a bigger volume coming back on these responses. Okay, so for persistent connections, here's how it would work. You would, first of all, you've got to make your TCP connection. You can't get around that. Now you send the request. Now you get back the response. Okay. Looks just as usual. However, now we've got back the page and we found there are a couple of embedded inline images. What do we do? With a persistent connection, we don't close this TCP connection and open another one. We send the second request on the same TCP connection and we get back the response. Then we send the third request and we get back the response. Now this is better in several respects. You can see we only have one TCP connection. It's a little hard. I'll clean this up in a little while. Actually, why don't I just go through the options and then we'll talk about why it's better. You'll notice that there's on this persistent connection, I only had one TCP connection, and then I sequentially sent the request response pairs. There's something even a little better we can do, and that is this option. I'm going to make a connection. I'll do the initial request and get the initial response back. You can't do much before that. Now, at this stage, we've got back the body of a page. and it has 2 inlined images, say. What we can do now is send both requests right away. Why wait? Just tell the server what you want right now. As the server gets these requests, it can start answering them. It'll answer the first request first, maybe. Then it'll answer the second request. So really the answers for these 2 requests have been combined together. We're not waiting this extra round trip time sort of here to be able to send the request there and get the response back. So let me just clean that up. Here it is. And now I'll discuss it a little bit. So you can see in moving from the 1 request per connection to the sequential requests over here, we benefited from having only a single TCP connection. Yes, that's good. So we would expect sequential requests to be better. We're actually doing better than that though, because you'll notice for some reason I shaded this gray area to be much shorter in time than it was on the first one. What's going on there? Well, what's going on here is that, let me just write no slow start. What's happening here is that we already have a connection up and running, and we don't need to perform slow start for it once again to be able to send more content. So we're beginning to use the network quickly to all of its capacity. So we should be substantially better off under this model than the previous one. And you can see that we can be even better still as we move to this model. Here, the difference is that those 2 requests here have been gone out at the same time. And so now the information comes back to back. We don't have the gap. Right? So I'll tick that. This gap over here has gone. And we're somewhat better off. So by performing all of these steps, we're beginning to use the network much more effectively than we would otherwise. And parallel persistent connections are what is used in modern web browsers today. Just to finish, I want to discuss HTTP 1.1 with persistent connections a little more. Actually, here, so it says these persistent connections were one of the major changes which were introduced going from HTTP 1.0 to HTTP 1.1. Pipelining is an optional mechanism in this standard. Initially, they were just persistent connections and pipelining wasn't implemented. Over time, pipelining has come to be implemented more widely. And so now we have persistent pipeline connections in browsers. This helps the page load time for all of the reasons that we just went over in the previous slide. Now, I would actually like to be able to give you some figures and just say, well, how much benefit you get from all of these different techniques. That's very hard to do in the abstract though, because the page load time benefits you get are going to depend on the structure of the pages, including how long all of these contents are, as well as the network itself. Nonetheless, we would expect to get many of the benefits of speeding up the network transfer, maybe not all of parallelism actually, but we come up with a workload which is much easier on the network in terms of causing loss and so forth. Persistent connections aren't all roses, however. They do raise a couple of issues for us to think about. One issue that you have to think about if you implement it is how long you keep a TCP connection open. It's fairly easy for me in my example to say, well, I have this TCP connection, I keep it open, I send the 2 requests, which I happen to know over there, and well, then I could close it. But in reality, a browser and a server wouldn't know whether to expect any more HTTP requests to the same server or not. It just depends on the contents of the page that they don't know yet. More, and whether the user interacts with the site. More might be coming or it might not. So typically browsers and servers will hold persistent connections open for a very short amount of time, and if there's no continued activity, close them. Particularly if a server is busy, it won't want to keep extra connections around. And you might also wonder whether it's possible for persistent connections to be slower than parallel connections. Well, the answer is yes, they can sometimes be slower. Why is the question? Well, to think about this, consider what will happen if you have a web page which has many small components in. In that case, the network will be mostly in slow start because it won't really have the time to get up to full speed. With persistent connections, we're going through a slow start once, With parallel connections, we're also going through the slow start, but all of the connections are slow starting in parallel. So if you like, it's a faster slow start. Because of this, actually the TCP connection details often matter for web page load performance. And one thing you might do is configure your TCP to use a larger initial window size. This is a common practice on the web today. Okay, so that's all I have to say about persistent connections, and you now know how requests and responses are sent over TCP connections. G'day viewers. In this segment I'll talk about HTTP caching and web proxies. So we've talked about the performance of HTTP just for requests and responses, fetching content. HTTP caching is an important technique which can be used to improve performance by enabling the local reuse of content. And in this segment I'm going to tell you how it works. So the motivation for web caching is that users often revisit the same page. They're looking at the same content. When this is the case, there's a big win that's waiting to be had by simply reusing the local copy. That is, if you remember what the page looked like the last time you visited it yesterday and it hasn't changed today, or most of it is the same, such as many of the images, because the site looks the same, then we can reuse all of that and avoid transferring that content over the network. This is called caching. And so you can see in the picture here, I have the client over on the left in this case, the server on the right, and what's new here is this big cache. We're going to try and draw web resources from this cache rather than from the server across the network. Now the key question when you have a URL that the browser's been instructed to fetch by the user, the key question that we need to consider with caching is, when is it okay to reuse a local copy that you happen to have in the cache? If you have an entry for the URL that you're trying to fetch, great, everything sounds good, but you've still got to know when you can actually make use of that copy. That copy might have changed on the server, in which case you don't want to present the old information. But it might also be the same as what's on the server, in which case you would like to use it so that you don't transfer it across the network anymore. So, how are we going to do it? Well, there are a couple of different options. Let's see them. The first option that you can use is to try and locally determine whether the content copy that you have in your cache is still valid. Valid means that it has the same contents as would be returned to you by the server if you were to request it again. How are we going to do that though? This is sort of getting a little circular. To do that, we would really like to use meta information which came from the server when we retrieved it last time. For instance, if the server includes an expires header which gives a timestamp and says this copy of the content is valid until this date, well then our test to determine whether the local copy is valid is simply checking the time and seeing if the document has already expired, and if it hasn't expired, it's good. This would be wonderful if there was always an expired header. There isn't. Sometimes browsers will fall back on heuristics. This is not ideal in that these heuristics could get it wrong, but usually it's helpful in terms of performance. So a heuristic is just a rule that provides a guess. So if you were the browser and trying to guess whether content was a copy of content which is in the cache was still valid or not, you might look at several factors. One rule that's used is if the content is of the kind that looks like it's cacheable, meaning it doesn't have any headers, any meta information that says it's not cacheable because it was produced dynamically, for instance. So if it's cacheable, and if it's freshly valid, you got or validated a copy of this with the server recently, like maybe a few minutes ago, and it hasn't been modified recently. The copy you got, it might have header information to say when this content last changed. Say it changed a year ago. Well, if it hasn't changed for a year and you just got a copy a few minutes ago, chances are it's going to be okay and it won't have changed. So this is a heuristic that browsers might use. They can be wrong. In that case, the page you're looking at can be different than the page which is on the server, and there's a small amount of inconsistency. Mostly they'll be right. When you use these local determinations and you end up with a copy that's still valid, the advantage is that you get the content right away. So you get it with near zero latency, and with zero network cost. So this is definitely a win where you can do it. In fact, it's a huge win. And you can see that I've just drawn the box around everything local. The cache and the client are all local behavior, so the network's not even involved here. It's in terms of cutting down on network usage, it's the best we can do. But even when we can't locally revalidate the copy because we don't have an expires header and we're unwilling to guess, there's also there's a second strategy we can use, which can greatly help by reducing the amount of information we send over the network. And that is to revalidate the copy with the remote server. Revalidating the copy involves talking to the remote server and asking them if the copy you have is still valid. If it is, then you've won even though you contacted the remote server, because you don't have to transfer the information across the network again. Well, how are you going to ask the remote server if your copy is still valid? One way you can do it is based on a timestamp. When you downloaded the contents, it probably had a timestamp saying when it was last modified. You can ask the server if this URL has changed since this last modified timestamp. If it has, you'll have to get a new copy. If it hasn't, well, the copy you have is still valid. Alternatively, instead of timestamps, sometimes headers are used which are based on the contents of the resource itself. This can be done with an E-tag header. It stands for entity tag. It might be a hash or other indication of the contents of the file. And this is information that, again, you could send to the server and say, well, I have this copy. Is there anything more recent than this copy? Assuming that you can contact the server and validate the local copy you have, then the advantage is that you get content after about one round trip time. It will be at least a round trip time to send a message to the server and to hear back, yes, you can use it. But in this case, even though we've waited a little longer than with the local case, we've transferred essentially no information, very little information across the network. We haven't had to do the large transfer of 0.5 megabyte of information to move the resource again. So these are both big wins. Now, I've talked about two different methods, but actually these methods are used together. So here's what it looks like when you put these different pieces together. Here's the sequence for a user trying to browse a URL, and if possible, we'd like to use cache copies. So first of all, we get the request when they type something into their browser. What you can do first is perform a local check on your cache. This is checking the expiry. Do we have a valid local copy? Suppose that it can't be determined that you do. If you do, you're done. But if it can't be determined that you do, then we're going to revalidate our copy with the server. The way you revalidate the copy with the server is to do what's called a conditional get. It's a get because we'd like to get the resource, but it's conditional because we only want to get it if our copy is not valid. So we would send header information such as describing the copy we have, when it was last modified or what its contents was. If in fact our copy is still valid, the server will respond with a not modified code to tell us that the copy we have is still valid. And in that way, we can simply get the copy out of the cache here and display it. On the other hand, if the page has changed, then the server in this lower path would respond by sending a full large response. So I'll write large. And this is small in terms of content, so we'll win. Either way we get it from the cache or it gets sent and then we display it. So that's how web caching works. As well as web caching, so far I've really talked about caching inside the browser. I'd like to talk about another web entity which can be used for caching and for other purposes, and that's something called a web proxy. So a web proxy is an intermediary that you would place near a pool of clients, and it would act on behalf of those clients, providing web transfers for those clients when they're interacting with remote servers. So what will happen here is that all of the clients will send their requests through the web proxy. The proxy is then in a position to act as a big cache. So the benefits that it will provide for the clients are that it can run a bigger cache, and it can also provide a little bit of sharing across users. We'll get to that too. As well as security checking. Actually, a big reason for proxy caches is really the security checking and organizational access policies rather than plain caching. These access policies, this security checking might involve things like scanning the contents that are sent back to make sure that it's not full of viruses or other nasty things you can pick up just by surfing sites on the web. So a proxy is something that might be run by your local IT organization in your enterprise. They've set it up and they'll manage it to provide a better service, a more secure web service or more secure web experience than you and I and everyone having to maintain their own computer and inserting all of these different security checks. Now, the organization also benefits in that it can provide, or enforce rather, organizational access policies. Your organization might have policies about what kind of sites you can surf through the corporate firewall, and if you try and surf other things, then those connections just won't go through. Your organization might even have policies about what information you can send outside of the company, just to try and prevent confidential information from leaking. So proxies perform all of these different services, and this is why they're sort of useful from an IT perspective. The reason we're mentioning them now is because of this caching role. A proxy provides a local point at which caching can be provided for a pool of clients. This provides a few benefits for the clients. So first of all, the size of a cache at a proxy can typically be larger than at individual clients because it's probably a more powerful machine that's been set up and is managed by your IT organization. More than that, there is a shared cache, shared across users, I mean. So if you and I work at the same organization and you've recently been surfing some sites and I browse them later, I can benefit from your surfing because I might get a copy from the cache that you pulled in the first time you visited the site and it had to be fetched. I can then get the copy from the proxy rather than having to go to the remote server. However, caching in a proxy, as with caching in your browser, is limited in some ways. Caching is generally not effective for secure content. If you've retrieved something with secure protocols like your online bank interface, we usually don't share or cache and share that information across users. That would create more security problems. Caching is also limited by dynamic content. Many pages, if they're produced dynamically, they will depend on all of the program inputs and state of the database, so they're often not cacheable. If you want to look at them again, you have to recreate them. And caching is also limited by what we call the long tail, in that while there's some popular content that can be cached well, there's a very large number of unpopular pages, and these comprise a significant fraction of usage that caches can't do much about. So let's see how web proxies really work just with this picture. So you can see here, I have the pool of clients here. Here are all the clients here. And they might also have all of their browser caches already. They could get a hit on that and that would short circuit things. But if they're trying to request things that they can't satisfy from their browser cache, what they will do is they will send all of their requests to the proxy. So the client needs to be configured not to talk to remote service directly, but to send all of its requests to the proxy. All of your web browsers have built-in functionality for doing this. The proxy will then be able to consult its cache in much the same way as you would check a browser cache, and it will be able to share the contents of this cache across users when there are no security issues. And if you miss in the proxy cache, then you'll have to go all of the way to a remote server and back. Now, since the proxy is close to you, it's really within your organization, you would expect to get a much faster hit if you simply request content from that proxy and it's able to supply it locally than going out to the internet. So that's a proxy, a web proxy, and it's providing another level of caching, as well as all of these other kinds of filtering to provide a better web experience. G'day viewers. In this segment I'll provide an overview of content delivery networks. So CDNs for content delivery network or a content distribution network provide an effective way to distribute content to many clients on the internet. They're both more efficient in terms of how they use the overall network bandwidth, which is good for the network, and they provide faster delivery of content to clients. For these reasons, CDNs have become an important part of the Internet architecture today. So as a little bit of context, CDNs emerged in the mid to late 1990s. Really what happened during this period was that the web was taking off and the traffic volumes grew tremendously, more quickly than the network could be expanded. And this caused various problems. It caused problems for very popular servers. As these servers became very popular, the traffic volumes close to the server grew and grew, and it made it very difficult to provision large servers. The volume of traffic going through all of the networks congested the networks in turn, and there was the need to provision more bandwidth. And finally, for all of this, it gave a rather poor user experience because of congestion and because of pages growing richer and larger all of the time. So in this setting, everyone was really looking for a way to improve the web experience, often by looking at different kinds of caching. But CDNs emerged really as an idea to improve the efficiency of content distribution. The key idea is to place popular content near the clients and somehow hook the clients up to the content that is replicated near them. If we can do this, and CDNs really use a trick today to make this work, a very clever trick. If we can do this, then we'll be able to help with all of those three issues above, as we'll see. So here, actually, this is some slide that I showed you in the very beginning of this course, just about the benefits of content distribution. Here's the architecture as you might imagine it before there's any content distribution networks. In this example, we have here a source on the left, sending to 4 different users on the right here. And you can see that to send, we send through here, 1 copy from the source, another copy from the source, another copy from the source, and another copy from the source. This takes altogether 4 by 3 or 12 network hops, where a network hop is something like this, sending the content from one hop to another hop, between any hops. That's how much work the network has to perform. And you can see that the server has to do a lot here in terms of sending a lot of information out. Well, let's look at what happens when we do use content distribution networks. Here's a CDN architecture. What we've done is inserted this replica here, and now this replica can hold a copy of the content and redistribute the content from that point. And so, of course, what happens is that the source can simply send to this point, and from this point, we can send out to the users who are nearby. So we've taken the amount of network effort needed down to 4 plus 2 or 6 network hops overall. So it's twice efficient in terms of the overall network. But it's actually even better than that from the point of view of all of the parties. Let's take a look at that. And here are the kinds of benefits we get, assuming that there is very popular content that many users want. I'll get to this on the next slide. If we have popular content and we have this replica in place and we can arrange for all of the users to use it, then we see the following benefits. We see reduced server load. So that's a benefit right here. You can see the source only needs to send 1 copy out to this replica. And this might not be such a big deal with 4 users, but imagine hundreds of thousands of users all wanting a copy of this content. Then we're going to greatly reduce all of the effort on the source. We're also reducing the network load. So you can see that just if we look at points within the network, like here, for instance, maybe as we get close to ISPs, if these are ISPs at the edge of the network, then the amount of upstream bandwidth they need has fallen greatly also, just in the same way that it has for the server. Maybe it hasn't fallen quite as much, but it's fallen a lot. And finally, we obtain an improved user experience. This should manifest itself as decreased page load time. So the users here on the right should be better off. Why should they get a better user experience? Well, generally, so what they're doing now is they're downloading content from a replica that is closer than the remote server. This is generally faster for several reasons. If you remember from our discussion of web page performance, the round trip time matters because connection setup is involved. If you're setting up a connection to someone who's closer, the ITT will be smaller and you'll be able to do it more quickly. Moreover, We're just going over this local link here. We're not going over remote links. So this means that no bottlenecks further out in the network will be able to slow us down. It's only the local link near the edge of the network that could be a bottleneck. So if we can arrange for this architecture, this CDN architecture, to come into existence, then we'll be much better off. But that's assuming popular content. So let's just revisit that for a moment. Is there very popular content to be distributed? Well, yes, you and I both know the answer is yes, and that there are hugely popular things out there on the internet. What I'm going to do is just tell you a little bit about the distribution of popular content on the internet to put that into perspective. It turns out that, well, some of you might have heard of Zipf's law, named after George Zipf, who's shown here on the right-hand side. Zipf was a linguist, and Zipf's law relates to the relative frequency of words in a language. The most popular word, I guess that would be the or something in English, we'll give that relative frequency 1. The second most popular word is half as popular as the most common word. The third word is a third as popular. The fourth word, a quarter as popular. The fifth word, a fifth as popular, and so on. So the popularity of the kth item, shown here, is 1 on k compared to the popularity of the most popular item. This law, or relative ranking of frequencies, turns out to be something that is very common in the real world. So it is not simply the relative distribution of the frequency of words in a language. It also describes well, the popularity of video rentals. When we used to have video stores, online now I guess, the distribution of incomes, how they fall off. What else? The size of cities, many different things, the size of the population of cities, many different things roughly follow Zipf's law in terms of their distribution. Now, and what this means for us in networks, and the content does, I mentioned video as an example, but other popular websites too. What this means is that there is a small number of very popular items. These items, if we can put them in the replicas, will save an enormous amount of work, because essentially everyone was looking at them, or a large fraction of the internet was looking at them. But Zipf's law also tells us, you might be somewhat surprised to learn, that there is also a very long tail out here, and that tail matters because while all of this other content is unpopular compared to the popular stuff, there is a lot of it. This is sometimes called the long tail. You might have heard that expression. And the idea is that the weight of the long tail is significant. When you add it up, it's going to matter. It can even dominate the popular items. So even if we're able to sort of use caching techniques on all of the popular items, we're still going to need a lot of network bandwidth for the unpopular ones. That's what I'm saying. We would really like to optimize for both of these cases. For CDNs, however, the good news is this. There are many popular items, so we can use replicas very well. Well, this begs the question of how we're actually going to do it. I'm sure you've got the architecture down now. The question is just, how do we cause content to be distributed in that way? We saw something that gets a little close. I mean, if we just have browsers and servers, we don't have a content distribution architecture yet. If we put in the caches at browsers and at proxies, well, we're a little bit of a step closer in some way. A cache is a replica of the content. Now, if we just have a browser cache, well, we've got a replica there, and we're saving when the same user goes back to visit the page. But we haven't helped all of the other users who are nearby. Well, if we have a proxy cache, actually now we're caching across all of the users in that organization. So we're doing a little better. But we maybe haven't helped a lot of other clients who are nearby. A proxy cache only helps someone in your own organization. So neither of these methods really help all of the nearby clients to use the closest replica, nor do these methods really help with the deployment. There's something that sets of users have to do for themselves. So if you're a business and you want to be able to deploy these replicas to improve your site, well, you're a little stuck. You would need to wait for the world to deploy all of their proxies. Instead, we would like a way to be able to place these replicas ourselves. So for a site that wants to improve its experience, it could place replicas essentially all around the internet, distribute some of these worldwide, And we would like these replicas to be for use by all nearby clients. So a client should use the nearest replica. That's where we're going to get the advantage. How do we do this? I still haven't told you yet. Well, the answer, I'll tell you now, is that it's done by the clever use of the DNS. So the DNS mapping between host names and the IP addresses of the replicas is what's going to make it work. Let's see a little more. Here's the architecture overall for the content delivery network. I showed you before, so we have the origin server up here on the top. And before, we'd really sort of been looking at going to one replica and the clients associated with it. But just here for clarity, I've shown you that there are other replicas here and here in widely geographically distributed locations. And we would like the client to contact the nearest replica. So this client here is going to fetch a page from this replica here because this client is closest to Sydney. Whereas another client over here is closest to Amsterdam. So that's where it will fetch a copy of the page from, that replica. That's what we want to arrange to happen. Now we just have to do it with that clever trick of the DNS. Well, here's how it works. To contact a site and get the image off the site, you need to use the DNS to resolve the name of a server that has the content you want into its IP address. For content delivery networks, we upgrade the DNS server so that DNS resolution of a site, of the host name for the site, gives different answers to different clients. The answer, of course, that we want is to tell each client the site that is nearest the replica. Right? So that's what we want to do. So you can see here, if there are clients in Sydney and they want to access a certain site that has been replicated around the internet, they will they'll issue a query to the DNS somehow, and here is the DNS server for the CDN. This bit has been upgraded. The clients haven't been upgraded. The DNS will answer, and what the DNS server knows here is it knows who's asking for the translation. So in particular, you could look at the IP address on the DNS query. That would tell you actually probably not the client, but the client's local name server, which should be close to the client. Look at the IP address of the name server. You can use internet mapping techniques to try and work out what's closest. And for the Sydney client, when it's asking, the right answer that you want to tell it is to contact the Sydney node here, because that's closest to it. On the other hand, when you get a request from someone over in Amsterdam, you're going to be able to work out from the IP address that's on that DNS request that this node is actually a long way away from the Sydney replica. The answer you want to send back is the IP address of this replica in Amsterdam. Now, what you could imagine doing if you wanted to work out how some of this mapping works is when you've got a query from a node, you could ask all of your replicas to ping it or trace route to it if you wanted, and just see how many milliseconds each replica was from it. And over time, you could build up a map of where the different IP addresses were and work out how to provide the right answer more quickly. So the whole trick here is that the DNS server for the CDN is a special one that provides a different answer for all of the different clients to connect them to the nearest replica. You might think this is a little bit of a cheat in that when we talked about the DNS before, we had a file where you had the IP address of a DNS name, and it was the same for whoever was asking. But there was no requirement that it be the same for whoever was asking. And we actually don't break things really by returning a different answer in response to different clients. So this, if we simply do this, then we've accomplished our content distribution network. Now our clients in different places will contact the replicas. We still need to, from the origin server, distribute the content to these different replicas, but we can do that with the system we put together fairly easily. And it's also the case that the site that's served by this CDN, well, we'll have to have a special DNS server for the host name for that site to do this processing. But that's exactly what CDNs do. And finally, to close with CDNs, I'd just like to remark on their business model. Essentially, CDNs come up with a very clever business model. This was pioneered by Akamai, which was founded at about 96 and was well underway by the late 90s. And the observation for a business model here is that placing a replica of a particular site at an ISP is a win-win situation. You help both parties. So you can both improve the site experience, well, that should be worth money to the consumer site, and you can reduce the bandwidth that's needed by the ISP where you're placing the replica. Well, that should be worth some money to the ISP in some form. For this reason, because deploying these replicas are really win-win, CDNs have become an integral part of the internet architecture. And I would add, in terms of deployment, maybe one of the reasons their deployment took off is it's possible to deploy this replica simply by upgrading the DNS servers for the particular domain managed that's run by all of the replicas without changing any other ISP software and without changing any of the user clients that were running browsers to use the web. So without changing them, we managed to redirect them to these nearby replicas, which is pretty cool. Okay, so now you know how CDNs work. G'day viewers. In this segment I'll talk about some of the future directions for HTTP. So we've covered all of the topics that I wanted to cover for HTTP, and you should have some appreciation for how the protocol works. But the web's not done, of course. It's going to continue to move on and pages will get more and more complex, and there'll always be the need to make the web faster over time. The question for us is, well, how's it going to happen? What's going to happen to the web protocols to make them perform more effectively than they already do? What I'd like to do in this segment is just have a very brief look at some of the work that's going on right now and some of the options. So since this is really work in progress, you'll have to look back later to see what's happened to the actual web protocols. One of the first things we can do is take a closer look at modern web pages. Now, over the past small number of years, some very good tools have been developed to help us understand what happens when you actually load a page in a browser. Recall we said it depended on all sorts of things. Well, this is an example of what's called a waterfall diagram. There are many tools that produce them. Support's built into popular browsers, such as Chrome, for instance. And this is some of the output which comes from a popular open source tool called Web Page Test. And if you just Google that, you'll be able to find out where you can run it on the web. This is a very complicated looking diagram. I'll go through it in a bit. But it is produced, it's a fraction of the waterfall diagram that's showing how http://coursera.org is loaded by Firefox, running over a network with 5 megabits per second download speed, emulating cable, from Virginia recently. So all of those things matter. You change any one of those, you would end up with a different picture. Okay, anyhow, so what does this diagram mean? Well, here's time going across. Well, this is time. So really going across, you're looking at sequential activity. Going up and down, you're seeing parallel activity. These are all of the different web resources, and where they overlap, there is parallelism in the network. There's not a lot of overlapping yet. Things are always going to kind of follow this curve where they fall off like this, somewhat like a waterfall. Because you usually can't get the later resources until you've learned that you need them by fetching some of the earlier resources. Now the color coding here is fairly complicated. The key at the bottom tells you a little bit of what's going on. I don't claim to understand all of this diagram, but we'll still walk through it a bit. Let's look at the very beginning. So this is where we start at time 0. The first thing we do when we try and look up Coursera.org is this is the dark green code, so a DNS lookup. So we actually have to do a DNS lookup to find out the IP address for Coursera.org. Then there's orange, there's an initial connection, a TCP connection to it. And after the TCP connection, it's mostly green, so that means that we're spending most of the time waiting to get the first byte back from the server. So we set up the connection, then we have to send a request and wait for the server to send a response. So just like the TCP connection setup, there's at least a round trip time delay here. This whole event took 274 milliseconds, you can see here. And I can see here it actually returned to 302. Now I know just from looking up HTTP codes that that is a redirect. And so the answer to this, and on the real screen you can dig down more, the answer to this redirect would be that the server would be telling the browser to go and visit another URL. In this case, it's telling us to go here to switch over to HTTPS rather than HTTP to be secure. That's the little lock, and that we should visit www.coursera.org, that server. So Coursera.org was really a shorthand for this www.coursera.org. Okay, so now we want to go and visit this server, and there is a DNS lookup. Oh, by the way, you can see I'm skipping some of these ones, the GoDaddy ones and the DigCirc. This is a lot of other behavior related to HTTPS, I think, to verify or revalidate certificates online. This is just one of the other weird things which live in browsers. There are many, many strange things that live in browsers. I don't really understand it yet, so I'm not going to go into it. I'll just stick with the regular page load. So now we do another DNS lookup. This is all adding sequential time, and we have to make a connection there. Now there's a purple. That's actually SSL negotiation. We haven't gotten to that yet, but you can see that the modern web is mixing in a lot of HTTPS, even when you try and get something with HTTP. So this was a really just like a connection setup to make sure everything was okay. And eventually there's some gap. I'm not sure why there's a gap. Maybe because of other activity. It's very hard to know without having the browser tell you what was going on. There's probably not enough information here for us to do other than guess. There's a delay until the first byte, and then the first byte must come in. The reason you don't see that is that would maybe just be a tiny blue bar at the end, because maybe only a kilobyte of information was needed. At any rate, after this, you can see that later on, there is a little bit of first byte and content delivered for other things. We have a CSS resource, style sheets, and JavaScript resources. They come in. Oh, it looks like we needed another DNS and another TCP connection setup. That's because another domain's involved here. This would be maybe the CloudFront for Amazon hosting, this long URL. So once we've got the Coursera beginning, we then contact other Amazon servers or whoever is hosting the page to get it. So that's why we need more DNS and more connection setups. Then there's a little bit of waiting and content begins to come through. It looks like we maybe have just one connection here. And we're then sending We're then sending multiple different requests here, probably over the same connection. So we have some kind of persistent connections. And eventually we're getting up to speed. Something's beginning to use the network and we're seeing content come through. Now the loading process continues, and we would have to look a lot more carefully to know what's where, at all of the content that comes back to understand why it unfolds in this way. There's a blue line about here. This line here is the document complete line. This means we've actually gotten in everything that's needed in the initial page. Actually, the rendering of the initial page started back here. So our computer started to display it on the screen, but it could have changed and might need to be updated until at least the document was complete. After the document's complete, you might wonder what could possibly be going on. Well, scripts could be running on the page, which causes other information to be fetched, as well as the strange things that happen inside web browsers. For instance, I happen to know that this next one here, this is favicon.ico. This is just a little icon which is fetched by the browser to display in the bar the site in your URL bar. So it wasn't part of the page contents. And then there's a lot of other stuff which might be scripts or information being loaded by programs running in the page. And the page will continue to evolve. So as you can see, a web page load can be quite complicated. In fact, it's a lot more complicated than I've shown you. Here is the full picture for downloading the Coursera page using the same settings that I had before with this web page test tool. So you can see that there's actually a lot of activity here after the document complete. We're loading in probably a lot of pictures, looks like, and other things, and scripts. The whole web page itself is comprised, or at least everything we see here, which happens to make the page, is comprised of 23 requests. It's around 1 megabyte of data, and it takes 2.6 seconds to get to the end of it. when we don't have anything cached. It's actually shorter if you do a repeat load and you have some things cached. Moreover, this is actually not a terribly complicated web page. It's not unusual to see 50 requests or even 100 requests on many web pages. So as you can see, some of these modern web pages are really very complicated. There's a little bit more, just to look at the bottom bit of this graph. There is an indication of just how our CPU and bandwidth are used throughout this process. The bandwidth looks like something like this. So this actually means that for the first second or so, we're really not using the network bandwidth very much at all when you're setting up connections, different kinds of connections. So we're not using the network bandwidth to its fullest extent. It looks like for the next second, though, we're using nearly all of the network. That's really good. Actually, I'm a little surprised and skeptical that that's really the case, but that's what this line is showing us, that we're using the network. The CPU utilization also jumps around a bit. You can see the CPU is doing a little bit of stuff. Now, I wouldn't be surprised, sometime after the start rendering, you can see it sort of jumping up around here. That's because we started rendering, which is often a CPU-intensive operation, around here, and as the document was complete and we really needed to finish drawing it, more CPU's activity is spent. If you're interested in this, you can investigate some modern web pages yourself. It's really quite startling just to find out what's going on inside a web page. One thing that you will find is that, unfortunately, and this is what makes web performance a difficult topic, the waterfall diagram, which is showing us the details of what's going on, and hence the page load time, which is the end of the waterfall, depend on many different factors. In fact, you might be somewhat surprised to learn that the waterfall diagrams look very different for different browsers. Try it on some of the pages with just different browsers and you'll see. You would think if all of the browsers were implementing the same protocol, you might get roughly the same behavior. But they are very different because implementation strategies matter greatly in terms of achieving good browsing performance. They're also different, as I noted, between reviewing the page, a repeat view, and a first view. What I've shown you is the first view, and actually maybe a repeat view would make more sense for something like Coursera, where you've been there before. And you even find that, in fact, the page load time often depends on the local computational resources that you have available, as well as the network. And the reason for this is that script execution and rendering both need to happen as well as network activity to be able to load and show the page. So wow, modern web pages are quite complicated. Hopefully just some of those figures gave you an appreciation for that, and you can look a little more yourself. The question that I just want to talk about briefly here is, what are we going to do looking ahead? Pages are only getting more complicated over time. Every year it seems that the size of pages, the number of components they include, get more and more complicated. And they're also getting not only larger, but more dynamic and more secure. So more programs are being run, and we're using HTTPS further, which complicates caching more. The question for us is really how we're going to design the network system here to reduce the page load time, or at least keep it as low as possible, because we know that's important for people to use the web. Well, no one really knows the answer here because this is ongoing research, but I'm going to briefly talk about a couple of options which seem really quite useful. The first option is really better use of the network. And if you like, you could think of this as just as HTTP 2.0. How can we revise HTTP beyond 1.1? What brilliant ideas are there which will make page load time better? And the second topic I'm going to talk about is actually a little different. Might get you thinking, and that's about coming up with better structures for the content. Because even though HTTP is a separate protocol than the content, it turns out the way the content is structured has a big impact on the page load time. And here I'll talk about some server extensions. Okay, let's dive into those two. Now, first of all, this protocol called SPDY, S-P-D-Y, pronounced Speedy. SPDY is an experimental protocol which is now being tested and deployed. It runs in browsers such as Chrome and Firefox. I think for modern versions of these browsers is actually the default protocol. So instead of HTTP 1.1, your browser will try and use the SPDY protocol to talk to servers. And if the servers also speak it, it will use that protocol. It's forming the basis of an ongoing effort that's just sort of getting everyone excited now to revise HTTP again. I said, if you recall, that it had been stable for really most of a decade. Well, now it's time to move it from 1.1 to 2.0 to try and improve performance. Well, exactly how can Speedy do that? Speedy has a set of features, each of which maybe helps somewhat. How effective these features are together or individually is a little up in the air because it depends a lot on the web pages, so people are gathering data. Speedy has features such as, just to pick something that's fairly easy to understand, compressed HTTP headers. The headers have gotten bigger over time. They didn't used to matter much. Now they're a lot longer. Compressing them can reduce the bandwidth and help. The biggest change for Speedy is this first one. It has multiplexed or parallel HTTP connections on a single TCP connection. Recall we saw parallel TCP connections with HTTP on them individually early on, and persistent connections replace that. In a persistent connection, you have one TCP connection and then sequential HTTP request responses. They might overlap a little bit for pipelining, but they're not all happening in parallel. With Speedy, the next step in the evolution is to perform these HTTP requests in parallel and to allow the client to change the relative priorities of the parallel downloads. This is so if a client has 3 requests outstanding, they can all come in at once and the client can tell the server, hey, I think the second one is actually more important, so send that, try and send that first, and then send the rest. And it could change its mind later. Another feature which is very interesting for HTTP is what's called, is a very interesting extension of HTTP for Speedy, is what is called server push. Normally the model is that a client requests a resource and the server simply responds with it. With server push, when a client requests a resource, the server may respond with that resource and also push other related resources, as in, here, have these too because I think you're going to need them and ask me for them in just a moment. It can be somewhat difficult to work out how to effectively do pushes because it interacts with caching. You might already have copies of some of these resources. So it's ongoing work to work out how to use some of these features. But nonetheless, I think the insight that I'm interested about here is really changing the structure of HTTP. This is probably what needs to happen to be able to improve the performance significantly. Okay, so that's all I'll say about Speedy, but you can read more about it on the web and look at it in your browsers. Let's turn to the server now and the mod PageSpeed extension. Here the observation is that the way pages are written, the way they're structured, affects how long it takes to download them. In fact, if you're developing, if you're authoring web pages or developing web tools or websites, there are many books that you can buy here that tell you about best practices authors and developers should use so that their pages will load fast, using small pictures, putting bits first, trying to avoid blocking JavaScript, doing all of these different things and so forth. So far, if you're authoring the page and following a best practice, you're a person doing that. The idea here for mod PageSpeed, or more generally for other approaches that are going on, for other projects that are going on, is to have the server implement these best practices and have it essentially rewrite, or you could think of it as compiling pages. So if you think of the page as really just a description of the structure of the content, the server can work out how to lay it out in the way so that it will load fastest. This is kind of what compilers do when they have programs and they optimize things, and we're probably better off leaving it to programs as soon as we work it out how to do it. Mod PageSpeed is an extension that goes in the server which performs this rewriting or optimization task by restructuring your content, something that HTTP can't do by itself. I'll give you just a little more detail on mod PageSpeed. It is an HTTP server extension, so it's part of a software module that's installed with your web server. Its purpose is to rewrite pages on the fly. So when you request a web resource, it will generate it, but then it might restructure it and change it before returning it to you. And it's going to try and give you a copy which will be structured so that it loads as quickly as possible. How does it do that? Well, with all of its rewrite rules. Here are just some examples of the rewrite rules to give you a sense of the things that can happen. It can rewrite the page by minifying JavaScript programs. This means reducing them by throwing away unused bits of code that are in JavaScript files, by changing the JavaScript itself to replace long variable names with short variable names so that the JavaScript code is as compact as possible, so we're going to need few bytes to transfer it. That's one thing it could do. It could also flatten multiple levels of include. For instance, in style sheets, one style sheet can include another. And if you have several levels of includes, every time you get a style sheet, you just learn you have to go and fetch another resource to find out what the whole style sheet is. The server could fetch them all and inline them all together. This is what the flattening is. And these are really compiler techniques you can think of, various inlining techniques and so forth. The server might also resize the images to suit the client, depending on what client is asking. And actually, there are many, many more. It's difficult for me to explain some of these rules to you because they really depend on a lot of the ins and outs and very specific situations in the web, which people know about and would like to avoid. In fact, there are hundreds of specific rules. But more than the actual rules themselves, the reason I'm mentioning this is I think this approach of having the server rewrite your content and restructure it is a promising one. Okay, so now you know about a couple of directions for the future development of the web to speed up the page load experience. Check back much later to see what's actually happened with the web. G'day viewers. In this segment I'll talk about peer-to-peer content distribution systems using BitTorrent as an example. So peer-to-peer content delivery is interesting to us because it provides an alternative to client-server content delivery using CDNs. And it's an alternative that runs without dedicated infrastructure. That's what makes it interesting. We're going to look at these systems just to understand a little bit about how they work using BitTorrent as an example. And I'm really just going to give you a quick overview of these systems so that you've seen what they look like. So here's a little bit of context for where peer-to-peer systems came from. We've seen delivery with traditional client-server methods which have scaled up over time to become content distribution networks. These systems are efficient and they're able to scale up delivery for very popular content, and they work quite effectively. They're also quite reliable, and that's because they're a managed infrastructure. People pay for content delivery, so you can hire people to carefully administer all of these systems and run them well and make sure they provide good service. But traditional models, this CDN system, have some disadvantages too. And the two real disadvantages that come to mind are, first, the need for this dedicated infrastructure. It has to be provisioned and carefully managed. All of that costs money, so we're paying maybe quite a lot, maybe more than we need to, for this content delivery. And second, there is an element of centralized control or oversight. Whoever has set up the CDN is really in control and able to make decisions about what goes on that CDN. Now, that may present problems for some people for many reasons. You might not be interested, for instance, in some large internet companies such as Google or Facebook delivering all of your content and having a very good idea of what's going on. So if you care about privacy, peer-to-peer might be more interesting. Other people have different examples, of course, such as downloading illegal content. So for peer-to-peer, the real goal of this technology is to provide delivery without the dedicated infrastructure or centralized control that we've seen in these other systems, while still retaining the advantages that we got from a CDN. So we still want to be efficient to deliver content at large scale when there's very popular content, and quite reliable in providing a system that's really very usable all of the time and provides good performance and is always up and so forth. This all sounds great. The key question is just how on earth are we going to make this work when all we have is a pool of clients who want to exchange information amongst themselves with no dedicated infrastructure to help them? Well, the key idea here is that we're going to have the participants help themselves. The participants here are called peers in the system. That's why it's peer-to-peer technology. Peer-to-peer took off very shortly after some of the early systems, such as Napster, demonstrated a peer-to-peer system in 1999. This was really used for stealing music or downloading illegally copied music. It seems to become defunct because it was shut down. There was a flurry of activity on different peer-to-peer systems, including BitTorrent was one of the fairly early ones. It was developed around 2001 and it quickly became very popular. It's probably the dominant peer-to-peer system today, and it shifts a substantial fraction of the internet content. So it really sees very widespread use. Okay, so let's just talk about some peer-to-peer systems in general, and then I'll move on to BitTorrent. So for peer-to-peer in general, for delivering content, there are a few challenges that we're going to have to deal with just because of this very different setting than client servers. The real problem we have here is there are no servers on which we can rely for anything. So this means that all of the communication to deliver the content is going to be between the participants or peers. This is why it's called a peer-to-peer system. That's the communication pattern, not client-server. So all of these peers are going to have to organize themselves somehow into coherent architecture to accomplish the task of content delivery. Well, you might be able to work out how to do this if you just have a group of friends at a small scale. But we would like these peer-to-peer systems to scale up to large scale, hundreds of thousands of clients working together to distribute content amongst themselves, for example. At this scale, there are a few problems, and I'll just go through them here. The first problem is that of limited capabilities of the participants. So all of the participants, the peers, are just, they're clients that want to download the content too. We don't have the luxury of provisioning highly powerful, high-end servers that can distribute content to many clients or end clients. Everyone's just a client in some sense. While they may range in their capabilities, we don't have the luxury of deciding exactly who's going to be how powerful. So the question then is, how can one peer, which might not be a particularly high-end peer, be able to deliver its content to all of the other peers in the system if they want to download that content? That's one issue. Another issue is that of participation incentives. The peers are really helping one another, at least that's what we want to happen. But if as a peer all you really want to do is download the content, you want to get a copy of this file, we haven't yet really worked out why it is that you're going to bother sending copies of that file to everyone else to help them out, since that's not really what you're trying to do. And the third issue is that of decentralization. With a managed server infrastructure, you know who to contact to find out where the file is. With a peer-to-peer system, the set of peers is changing over time. It's just whoever wants to be involved in the download and spreading of this content right now. So it's not clear in this system how you would go about finding out who to contact to get a copy of the content. So we would like systems that work well when they're very decentralized. No one's in charge and all of the members of the system are constantly changing. So these are actually three substantial challenges to deal with. Well, there's a roughly an approach which we could use to deal with each one. So to overcome the limited capabilities of an individual peer, we can still enable one node to distribute its content to all of the other peers by simply making a distribution tree. This is like multicasting, or really sort of like what a CDN is doing over time. So if you just imagine the source node here has content and everyone wants to get it, well, we could get it to all nodes by having the source send only 2 copies to these 2 nodes, and these 2 nodes each would send only 2 copies. And there actually, I've reached all of the other nodes in the network. Let me just clean that up. Here it is. You can see by following that distribution pattern, no node did a lot of work, yet we got the file to everyone in the system. Of course, with this tree, I have a small picture here, but we could scale up to a very large number of nodes using this technique. So, and actually we wouldn't have to go through very many levels to get to a very large system because of the way we're growing exponentially. So this kind of transfer is typically done not instantaneously, but with replicas over time. So each of the other nodes that you're sending to, like here, a replica of the file, it started off here, a replica has been stored here, and sometime a little later it'll be transferred to these other 2 nodes. Now this approach means that in some sense the capacity of a peer-to-peer network is self-scaling with its size. If you have more nodes in the system, well, you have more capacity to distribute the content to all of the nodes themselves. So it certainly has the potential to be able to work and deliver content to all of the nodes. In terms of participation incentives, I'll note that the peers here play two different roles. The pink arrows here, like these arrows, are downloads to this particular node that's shaded in grey. Let's just call this one the peer that we're interested in looking at. So this is really the node helping itself. It's downloading the content that it wanted all of the time. At the same time, because it participates in a peer-to-peer system, this node is doing some other work. These are the blue arrows. Oh, I forgot a pink arrow there, doesn't matter. These blue arrows, from the point of view of that same node, are uploads to other nodes. These uploads don't help it directly at all. They're really doing other nodes a favor. So this is the dual roles and why it's called a peer. It's performing, if you like, the roles of both the client and the server. To encourage participation in a network, we can try and couple the two roles together. Essentially, we can try and create a system where nodes are working together so that one of them is sort of saying, well, I'll upload content to you if you upload it to me. If they both do that, and we can create a system that works that way, then we'll encourage a bit of cooperation and they'll all satisfy their goals. Of course, we just have to come up with a protocol to do that, and that's part of the trick. And finally, in terms of decentralization, nodes, even though the set of nodes are changing, the peers in the system need to be able to learn where to get the content. To solve this problem, we're going to use something called DHTs, a distributed hash table. Some of you might have heard of DHTs, maybe not. DHTs started as an academic line of work in the academic community about 2001 with work on systems called CORD and CAN, you might have heard of. They turned out to be all of the rage in the networking research community. There was a huge amount of work on them, there still is. They are some of the most highly cited networking papers of all time. Now, I don't really have time to tell you how these new algorithms work. If you like, I'm sure you can read about them a little further. Actually, in your text, there's a section on the distributed hash tables in the same section as peer-to-peer systems, which will explain how one of them, CORD, works. But what I'm going to tell you now is simply what a DHT does. So a DHT is essentially an index. You can look this up for their name to find out where the peers are. That's what we want to do. Now, it's a distributed index, so the index is spread across all of the peers, and it's fully decentralized and efficient. These are the properties we want. So what does all of this mean? Well, I guess I'm repeating this a little bit, but let me just say a DHT is an index that's spread across all of the peers, so it's distributed. The index provides a mapping from, say, the name of a file or something you want to get to the set of peers who currently have pieces of it that you could contact. And any peer who's in this system is, by using the DHT algorithms, able to look up this index and find out who the peers are to contact to get a copy of this file. So an index is a very simple thing. It turns out to be difficult to do in a way which is fully decentralized. Even when the peers are changing, it is still very efficient and fast to look up. That's the magic of DHTs, but I won't go into it. Okay, so let's move on to a BitTorrent to see an example of a peer-to-peer system. So BitTorrent is the main peer-to-peer system that's in use in the internet today. It was developed starting in 2001 by Bram Cohen. Here he is, shown on the right. Finally, we found someone younger than myself to show you a picture of. That's great. BitTorrent, after its introduction in 2001, grew very rapidly. And it sends a very large amount of traffic because it's used to transfer very large files. Movies, for instance. Copies of movies are moved around. As a result, today, BitTorrent traffic constitutes a significant fraction of all internet activity. So this is one of the main kinds of traffic on the internet. And it's used for much legal as well as illegal content. Maybe I should actually say illegal and legal content, depending on what you think is mostly transferred with BitTorrent. So just to switch to a little closer to the BitTorrent terminology, data is delivered using these things called torrents. A torrent, you might imagine, is just a big gush of data that's going to give you the file you want. The BitTorrent system transfers files in pieces, so it's going to break up a file into pieces. because by using many pieces in parallel, this parallelism is what is going to give us a high level of performance and let you get a fast transfer rate, even though the individual peers might not be very fast themselves. It's notable for its treatment of incentives as part of the protocol. What this really means is that the protocol does actually consider incentives and try and do something about it. We'll see that in just a minute. And in terms of decentralization, some of the early versions weren't really decentralized. They used an index which was stored on just another server that you had to find and know about. But the most recent versions have now switched to using decentralized indexing technology using a DHT. Okay, so here's the architecture. Oh, sorry, actually, before we get to the architecture, here's the steps to download a torrent. And then I'll show you a picture and we'll go through these steps again. This is what you do. Step 1, start with the torrent description. You've got to know what you want to download. Maybe someone, your friend, mails you a link or a description of a torrent and says, check this out, it's great. Okay, once you've got this description, step 2 is to find out the peers you can contact to get the torrent, to download the file. You can do this either by contacting this special tracker to join the set of live peers and get the list of other peers that are currently downloading the file. This list will contain at least a seed peer, a special node which is initialized with a copy of the content to bootstrap this whole process. This is the older centralized way. Alternatively, you can use this decentralized, fully decentralized DHT index, look it up under the name of the torrent and find a set of peers who you can contact to get a copy of this file. Now you know who to contact, the peers. And what you begin to do is start trading pieces with them. These peers, everyone's trying to download the same file at the same time, so everyone trades or swaps the different blocks they have. As you contact different peers, they may have some different blocks, and you may have some blocks they want. So you begin to trade them until you get the complete file. And as you do so, the incentive rule is that you're going to favor peers that upload to you rapidly and choke peers that don't upload to you rapidly by slowing your upload to them. So somehow you're providing a little bit of feedback. People who are helping the system by downloading to you, well, you'll also provide them good service. People who aren't really helping you, going to try and cut off service to them. That way, if they're not helping anyone in the system, no one's going to give them good service. I've talked about that a little bit through the steps, but I think they'll become clearer when we just look at them a little more and talk about how they solve the challenges. So here is a peer-to-peer system, and you can see I've circled one peer we're going to look at, but all of these other nodes are peers too. Peer, peer, peer. So all of these peers are trying to download the file, receive the torrent that is, at the same time. So they all have the same goal in mind. One of them here, the seed peer, already has a special copy of the content. That's to get the system going. Someone has to have the content after all. Now in the initial versions of BitTorrent, the way it works is once you have a description of the torrent, it's metafile that just says what it is you're trying to download. In this, there is information about who the tracker node is. If you then contact the tracker node, what's going on here? You can get the list of live peers. So that will have like 1, 2, 3, all of these nodes. It will tell you who they are, so you know who the peers are. And then you proceed with the BitTorrent protocol. You contact a randomly chosen set of peers, like maybe these peers, to trade chunks with them. You'll ask what pieces of the file they have, and then you will try and download those pieces from them, and they will also be asking you what pieces you have. And as you're talking to multiple different peers, you'll get multiple different pieces, and you'll be able to trade them with other pieces. And this way, everyone will be helping everyone. And some peers eventually will leave this system when they have the new file, but other peers will arrive. Especially if many peers are trying to download at the same time, there'll be a large set of people available to help everyone else. So let's just revisit those challenges and see how it all works, how we've met them. In terms of dealing with the limited capabilities of an individual peer, we've dealt with that by dividing the file into pieces that can be downloaded in parallel. This peer here that we're looking at is downloading from 3 different other peers concurrently. That means if these other 3 peers are very wimpy, well, we're able to get a download from all of them. So the rate at which we can download is the sum of this. It can be quite fast. our infrastructure can be providing us a fairly good rate because of this parallelism, even though the capabilities of each individual peer is limited. In terms of participation incentives, I talked about this technique of favoring the peers which are uploading to you, you upload to them. On the other hand, we choke peers that aren't uploading to us. So this peer here, this unfortunate peer, is shown as choked by all of the other 3 peers it's talking to. It's these stops here. This is the choking. And this other peer must be choking because the rotten peer here with the X's, I'll say rotten, it's not really helping out, or unhelpful might be better. This unhelpful peer is not providing downloads to all of the other nodes. And so they've cut it off, and they're favoring other peers. This is going to provide an incentive for everyone who has any content to trade to actually trade it. If you don't have anything because you're just beginning, other nodes will give you a basic level of service, but your download will take a very long time unless you're willing to help everyone out. Okay, and finally, in terms of decentralization, well, when we switch to the fully decentralized model, the DHT index is spread over all of the peers. So a small piece of it you can see here is implemented as part of every peer. Together they are implementing this DHT, this overall index, using the DHT technology. So any peer that can find another peer can join the system and look up this index, and will end up carrying things to form part of this index. So it's fully decentralized, and we've made our goal of knowing how to get around without having a well-known central server that provides information. Okay, so that's peer-to-peer systems, and BitTorrent is an example. Peer-to-peer systems are interesting to us as an alternative to CDN-style client-server distribution of content. They certainly have some potential advantages if they can do away with dedicated infrastructure and decentralization. They also have some challenges to meet to do that. It's probably not as easy with peer-to-peer technology as it is with a managed, carefully provisioned infrastructure. So if we can make it work, we're in good shape. But there are still some problems to solve to make them work very effectively. At this stage, today, CDN technologies are probably more mature. Nonetheless, P2P technologies are coming along, and DHT technologies too, and over time, we're finding that they're more widely used in systems. And these are the technologies that are adopted in different kinds of content distribution systems. Actually, P2P and DHT style technologies are used as part of the Skype system and as part of Amazon's system, Amazon's cloud computing services. So I think in the future what you can expect is more and more hybrid systems which maybe use some peer-to-peer style techniques along with a carefully provisioned infrastructure, for example, rather than having solely all of the clients do it themselves. Okay. G'day viewers. In this segment I'll introduce quality of service. So here's a protocol layer diagram to tell us where we are in the course, and we've now already covered everything from the physical layer up to the application layer. We're now going to talk about quality of service, and that's a topic that, as you can see here, spans several layers. It goes all the way from the application layer, because the application needs to be able to tell the network what it needs, down to the network layer, because the network is the layer which ultimately provides different kinds of network service to applications. So the topic of quality of service relates to the kind or type or level of service that a different application or user on behalf of that application receives from the network. Now, we're going to end up defining that in a way which depends on the particular application. So we might be talking about whether we want a certain amount of bandwidth, high or low bandwidth from the network. Or an application might actually not really care about bandwidth very much at all. It might care more about low levels of delay and loss, as we'll see in an example in just a moment from the network. So we'll look at this topic, and I also want to flag here this point. That quality of service is an important issue for the future of the internet. In the internet today, we really don't have much in the way of quality of service support. We get what's called a best effort service from the FIFO routers in the network. In the future, we're likely to see improvement in terms of quality of service, with various mechanisms being deployed to provide stronger levels of quality of service, higher guarantees of quality of service for different applications. But a lot of that's in the future, and we're just at the beginning of that. So we'll look at what happens today and where things might head in the future. So first of all, I should talk about the internet today, and that's this best effort service. So the term best effort, that's what you get from the internet today when all of the routers are FIFO routers. And here's a picture of a router down at the bottom of this slide. And if you recall, the way they work is packets might come in on different input lines from different places into the router, and they queue up in a queue to go out a particular output link wherever the routing sends them. And it might just be the case that for this particular output link I've indicated, a queue builds up, just because a lot of traffic wants to go out that link. This leads to congestion, and the packets that go out this queue are delayed because of the excess queuing, and if the queue overflows, some of them are lost. So the applications here compete for bandwidth, and the queuing can add the delay and the loss, just depending on the traffic patterns and what the apps want to send. The best effort service provided by these routers will do its best to deliver all of the packets, but there's no guarantee of the particular amount of bandwidth, delay, or loss you'll get. Often it might be fine, sometimes it might not. So that's the internet we have today. But sometimes best effort just isn't enough. You might want different kinds of performance guarantees if you needed a minimum amount of bandwidth to make the application work, and so forth. So that's what quality of service will try and provide. Now, we've got to be a little careful though. There are some things we can't do because they're just impossible. We can't guarantee more bandwidth than the network can actually provide, or lower delay than it takes for messages to actually cross the network. So we can't do the impossible. However, what we can do is control how the bandwidth is allocated to different applications, and because we control the way the bandwidth's allocated, we'll also control properties that come from that, such as the variation in delay and the loss. And by changing the way the bandwidth is allocated, we can come up with an allocation which is maybe a little better, and we'll do a better job at giving different applications what they most want from the network. Well, let's see an example of that, how that might work. So for my example here, I'm imagining that you're at home. Here's your home setting on the left, and you're talking to the rest of the internet across your access link. This access link is going to be the bottleneck. It's the limited bandwidth portion of the network, and so queues will build up on the routers on either side of this bottleneck. Now at home you're running two applications, and you're running them both at the same time. Skype, and Skype, this will just be a voice over IP call, so not a lot of bandwidth, and BitTorrent. And we're running these at the same time, but note that we want really different things for the different applications. Skype cares most about getting low latency communications and probably low levels of loss. This is so your Skype call quality will sound good. Your call won't sound choppy or broken up. And BitTorrent, on the other hand, doesn't really care about a bit of variation in delay. BitTorrent wants to grab as much bandwidth as it can. A bit of delay or loss, it's just fine. It's trying to do a bulk transfer, which is why it needs all this bandwidth. Okay, so let's see what happens when we run these two applications with FIFO routers. Well, the two applications are going to send packets. In this direction, they'll build up this queue here, and in this direction, they'll build up this queue here as packets queue to get onto the bottleneck link over the access link here. Now, the two applications will compete over the link, and as they compete, and the Skype sends a lot of traffic, queues are going to build up. Well, what will happen when queues build up? Nothing particularly good. In fact, as queues build up, we'll see increased levels of packet delay, and we'll see some levels of packet loss. This means that Skype is a little bit out of luck. The Skype call quality is going to fall because of the interference caused by BitTorrent. And if you've ever tried running a Skype call at home while running something like BitTorrent, you know what I mean. It can be pretty bad. If you're trying to Skype or even watch a bit of video and while you're doing something else, it can really interfere with your application. The quality goes way down the drain, even if you are getting some bandwidth. BitTorrent, on the other hand, will be mostly unaffected. Skype will use a little bit of bandwidth, but it wasn't using much, so BitTorrent is actually doing pretty well. But Skype's not. So what could we do? Well, there's actually not too much we can do with what we've seen so far. About all we could do, since we've just seen routers and links and other things, is we could add another link to the network. We could somehow split the access link into two different links, and for an apples to apples comparison, we'll say that each of them has half the bandwidth. Could be some other fraction, but let's just say a half. And we could change the routing so that the BitTorrent application goes over one of the access links and Skype goes over the other access link. This would be a fair bit of bother to go to, but let's just see if it's going to do anything to solve our problem. Okay, well, now the Skype packets, they're queuing here. There's very few of them, so they basically go on the link right away. And the result is that the Skype call quality is good. Skype sees low levels of delay and low levels of loss. It's happy. Good call, we're happy. On the other hand, what about BitTorrent? Well, BitTorrent will work well and saturate this link here, but it's basically lost half of the bandwidth available to it. So BitTorrent is not doing nearly as well as it did. And we've come up with a fairly complicated network just to try and fix one of these, and we really haven't fixed the whole problem. Could we do better? Well, I'm glad you asked. In fact, we can do better. Here is a brilliant idea that we might try, sort of. And quality of service will take us towards some of these things. Here's the idea. Let's just use the one access link and the routers adjacent to the access link here. These are the access routers. We're going to modify them so that we're going to tag the Skype packets with a VIP tag, very important packet, I guess, and we'll modify the routers here to give Skype packets priority on the link. So you can see here I've shown that the BitTorrent packets are queued, they go in a queue, but if a Skype packet comes, it just goes straight onto the link. Well, and to do this, we have to change the router. So we're changing the way a router works to do this. What's going to happen if we do this? Well, guess what? Now we're happy for both of the applications. We get a high call quality for Skype because the Skype packets see low delay and low loss. And at the same time, we get a high throughput for BitTorrent because BitTorrent gets all of the bandwidth that's left over that Skype's not using. So in fact, if Skype is not running concurrently with BitTorrent, BitTorrent would get all of the bandwidth. And that would never happen if we divided our access link, for instance. So BitTorrent is getting as much throughput as it can. The point is that both of these applications win. And we can do this because they were after slightly different qualities. One cared more about delay and one cared more about throughput. So we rearranged what the network was doing to better support both of those applications. That's pretty cool. And that's an example of what you can get from quality of service. So backing up to quality of service from that example, what quality of service is all about is allocating the bandwidth in different ways than we would get with FIFO routers in a way that's going to improve the application performance for the various applications. We might, for instance, want to guarantee a certain level of bandwidth to an application if it needed that much bandwidth to run, like for instance streaming video, you might have a minimum rate, or we might care about delay as we've just seen. And it may be the case that you can do a better job of satisfying multiple apps with quality of service mechanisms. You might be able to make all of them happier than they would otherwise be. That's pretty good. And I want to note here that I use priority as a simple motivating example. That's not used in networks, really. Networks use mechanisms which are slightly more general and generally more useful. And we will explore those ideas as we look at quality of service. And I'm thinking of things like fair queuing and weighted fair queuing. We'll get to what that means later. Okay, but one point I've got to make here is that to provide quality of service, what quality of service actually is sort of depends on applications. So we need to know what it is that applications require of the network. Do they care more about getting a high bandwidth, a low delay, a low variation in delay, low loss, or maybe something else entirely? We need to know before the network can possibly provide it. This table here just gives us a way of thinking. I've shown some example applications and the different kinds of things they might want of the network to get you thinking about it. So the network qualities we're looking at are bandwidth, delay. Jitter here is maybe a new one. I'm not sure if I've mentioned this. Jitter just means variation in delay. So it's not the absolute delay, which just, there's a minimum delay for the signal to travel down the wire. It's the variation in delay that's going to come from things like queuing in the network or taking different routes. And there's also loss, because we might get packet loss. Now, this table lists the stringency with which an application requires any of these network characteristics. A high stringency, so high in this table, means you have a strict need for the quantity. For bandwidth, a high stringency means you want a lot of bandwidth. For delay, a high stringency means you want low delay and low loss, right? The more difficult one to provide. And we can see here that different applications really do have different needs in terms of these qualities, which is what makes quality of service interesting, of course. Email, for instance, doesn't really need much of anything. It needs some bandwidth and a bit of delay and loss, and eventually your mail will get there and you'll be happy. File sharing, well, it doesn't have strict performance guarantees, but it does want a lot of bandwidth, so you can get your file there in a reasonable time. Other things may have different qualities. I've listed here audio on demand, like a podcast or so forth, benefits from a highly stringent control over jitter. So you want low variation in delay. That's so you don't get fades, and we can use techniques so that when we start streaming, you get a nice continuous smooth playback. On the other hand, things like telephony, which is interactive, it's not a podcast through two people talking to one another, not only do you want fairly low variation in delay, but you also want fairly low delay because we have a highly stringent requirement on the delay characteristic. And video conferencing, well, much like telephony, but I've said here that we have a highly stringent need for bandwidth because video is just going to require more bandwidth out of the network. So the point from this table of takeaways is different applications have different needs, and you can think a little from the application to understand what they are. Great, well, we're going to dive into quality of service in some of the coming lectures. Before we do that and I give you a table of contents, I want to tell you about one caveat. The caveat here is that quality of service only matters when there's actually a bottleneck in the network somewhere. If there's no bottleneck, then there's no queuing and there's no loss, and everyone's getting as good a performance as they can from the network. There's really no opportunity here to improve the performance characteristics that the applications are seeing. Well, this does actually lead to one possible approach to quality of service, or maybe I should say an alternative to quality of service. And that alternative is to, instead of building quality of service smarts into the network, simply build a network with heaps of capacity, so you'll never have any bottlenecks. This is a simple alternative, and you can do it and you can try and do it. In fact, that's what a lot of the internet has been based on at different times. But while it's a simple alternative to quality of service, and it works, if you can get it going in the early days, it's actually not a terribly effective approach for a couple of reasons. The first is that it's not really very cost effective. There's nearly always some bottlenecks somewhere in the internet. Maybe it's not in the ISPs, but it's in the backbone links and so forth. In that case, it would cost a lot of money to build a network that really had no bottlenecks. Even for an ISP, providing a network to ensure that you have no bottlenecks inside it can be quite an expensive proposition. So if we can make quality of service work, we may end up with a cheaper network. So it can be not cost effective. And the other difficulty is that over-provisioning gives you no guarantee. It might work on a sunny day when you have your normal traffic levels, but under an attack scenario or growth that maybe you didn't predict, well, things might not behave so well. You have no guarantee that applications will continue to receive the performance they need to run in the way users expect. That's why we'll talk about quality of service mechanisms and see how to actually add some of that to the network. We're going to go over several topics. I've talked about the different application requirements that they might have for different kinds of qualities. That's what we mean by quality of service, the different requirements for applications. Next, I'm going to talk about, in the coming modules, different ways of handling applications that you might think would need quality of service that we handle in the internet today. Real-time applications like voice over IP, and also streaming media applications like playing video over the internet. We clearly do them in the internet today. Well, how do they work and how well do they run? And after we cover that, I'm going to go down this progression talking about different mechanisms we can add to the internet to provide stronger guarantees of quality of service. These range from mechanisms called fair queuing that we'll get to and ways of shaping traffic to architectures for providing quality of service. Differentiated services is one architecture, and the strongest forms of quality of service we'll see, which are not deployed today, are providing rate and delay guarantees to individual applications. Okay, so on to quality of service. G'day viewers. In this segment I'll talk about real-time transport, in which information needs to be sent across the network in a timely fashion to meet a deadline. So when I say real-time transport, I'm really talking about something like a VoIP call, where voice or a video call, if video has been sent over the network with timing deadlines. And the reason it has timing deadlines is there's a person waiting at the other end to hear that call. So this is typically live information, and it's also interactive here, whereby two or more parties are communicating, so we need to turn around information quickly. You could just think of a telephone call. We're just trying to do it over the internet. What we're going to talk about in this segment is how we can provide real-time transport to run that VoIP call using the best effort service of the internet. And the technique I'll tell you about to make it work is the playout buffer technique. So the real challenge here is how to deal with network delay. We'll just think about one direction of transfer, even though in a real VoIP call, information is being sent in two directions, and that's important for understanding the timing deadlines. So in the one direction, we'll go here from a microphone over on the left of the picture through the network to a speaker over on the right-hand side of the picture. Now, the way these real-time media work, voice samples in this case, is being produced at a constant rate at the source. It's going across the network and it's then going to be consumed at a constant rate at the receiver. The network is in the middle of all of this. So the network is going to add delay as packets go across it, so the consumption must be at a later time than the production. And the network also needs to have enough bandwidth. If we can't get the data through the network, well, you're not going to be able to make that VoIP call. But even when there is enough bandwidth, we need to deal with the delay. So let's think a little more about the delay through the network. A key attribute of this delay is that it's variable. This graph here, this curve, the blue one here, it's meant to show you the delays, the network delays of sending information across the network. Now the network delay itself is going to have a few components to it. It's going to be the basic message latency, that's what's shown here. This is really the propagation delay and transmission, prop plus TX delay. So they're fixed delays that it just takes to send a message that distance over a wire. In addition to that, there's also going to be some queuing delay because these packets are queued up in FIFO queues in routers, and when those queues get big, there is going to be more delay. This graph here shows a PDF, or probability density function, of the delay. So it's really showing the fraction of packets which experience which delay. The biggest delay, the biggest fraction of packets experience about this delay here. You can see that many packets experience delays around here. And these are delays which are somewhat bigger than the basic latency that we get from sending the message simply over that distance. Because we're adding a bit by the queuing, but not too much. However, a small fraction of the packets, and that's out here where the fraction is lower, are experiencing delays which are much greater. So all of this addition from here out to here is queuing. Extra delay from queuing. Okay, so this is what network delay looks like when you send things over the internet. If you took a lot of samples, you would end up drawing a graph a little bit like this. The variability that you get when you send information across the network and you look at the delays at the other side is something called jitter. That's actually important for a lot of our VoIP calls. And you might imagine why, because it complicates playing out a VoIP call. If you get a message sample of voice which arrives at a particular moment, then at the next moment, this next sample should arrive, but suddenly it takes a lot longer for some unknown reason, because it got caught in a queue. Then the next one comes out much more quickly. Maybe it even arrives sooner than the other one. This kind of complicates play out a little bit. So let's think about play out, because that's really what we're trying to accomplish here. This is a different kind of graph, which is drawing the timestamps for media on the y-axis versus the actual clock time. And so you can see this line here, sender generation. That is a constant rate. That line has a constant slope, so it's going up at a constant rate as media is being produced at a fixed rate at the source. Now, what would ideally happen here, this is the ideal, it's not what we have, is that when you produce some media, say it's this sample here, when you send it across the network, it's going to take some amount of time to go across the network. That is this distance here that's labeled network delay, so it'll take a while to come out. On the other side, if the network had a fixed and preferably small delay, such as this delay here, then we would end up receiving samples and we could play them out at the receiver as we receive them along this curve here. This is really what happens in the telephone network. We have samples going into a pipe. There's no queuing inside the telephone network. They come out and they're ready to go to the speaker on the other side. And hopefully the delay is kept small. So this is what we would like to do. But of course that's not what we have. Let's think for a moment about what we have when we send messages across the network and we get that variable delay. Well, here maybe is the line for just the basic message latency. That's this latency here. You're not going to beat this. This was the latency, not the overall network delay. So it's going to take longer than that for the information to come out the other side. And it's also going to be a little variable, as we saw in the graph. So maybe we'll get a curve like this. Something like that. I don't know. I made it up. You can see here the difference between the time at which the media is produced, and if we just go across horizontally to here, this is when it arrives at the receiver. So this is the network delay. For that particular point, it's quite long. And you can see down here, it's shorter for a different sample down here. Why? Well, we just got a little lucky there and there was less queuing. So we're going to get something like that. Here's a cleaned up picture. Here, a cleaned up version of that picture. And you can see, so the blue curve is the important one to remember because it's media arrival. Now we've got to work out what to, and so this is when the samples from the VoIP call, they were produced and sent at a constant rate. This is when they're arriving at the receiver. It's a little bit all over the place. Now we have to work out how we're going to play them out. And what we're going to do to play them out, the technique for handling real-time transport on the internet today, is to use what's called a playout buffer. When the media arrives, we'll put that media in the playout buffer, and we'll then draw from the top end of the buffer and play things out at a constant rate. So the media is going to sit in that buffer, and that buffer's purpose is to smooth out the variable network delay. Right? Really, the dimension of this buffer is really about jitter. It's for jitter. If the network delay were constant, when information arrived, we would only need a buffer of, one sample, and we could send it straight to the speaker. But there's variability when it arrives. That variability is the variation in delay, or jitter as we've called it. The buffer is there to smooth it out so information can sit in the buffer and be drawn at a constant rate at the other end. Let's look at that in terms of our other graph, which just shows the media samples over time. Here was the generation at the source. They went across the network. So there was at least a minimum latency to go across there, and then there was an additional latency. This is meant to be all horizontal here, due to queuing. And you can see some things arrived quickly, some took a little longer. We then put them in the buffer and we play them out according to this curve, which is a line at the same slope, so they've been played out at a constant fixed rate equal to the source rate. Now what this means is that the pink area in here really represents how long samples stay in the buffer. That's its purpose. The buffer ought to handle that variation, and so if you get there early, you spend a longer time in the buffer. We can also see there's a deadline. If you arrive later than the playout date, that's here, then the media is not much use. The conversation has to go on. You can't pause it. That would be very awkward. You don't have any samples, so you might just sort of play a little bit of a noise or something. It's like there's a little bit of a glitch. But this information is arriving too late, and actually it's not useful. It might as well have not arrived because it's not going to help us play out any of this media. The time to play it has passed. So this is what a playout buffer, the effects it produces and how it works. We're also, now let's look at a playout buffer in this other graph. Here we're back to our PDF that's showing the fraction of network delay for the different packets. Here's the PDF curve again. What we're effectively doing with the playout buffer is choosing some upper bound on the network delay that we're willing to tolerate. Some things will have a larger network delay, or there might even be lost packets. I guess they're equivalent to having a very large network delay over here of infinity. Some number of packets will be in this tail of the PDF. For those packets, it'll be too late to be used in the playout buffer. So we are making a bit of a trade-off by setting this point. We're picking the largest acceptable network delay to pick this playout point. Here's a little more for how you can think about this trade-off. And this should be fairly intuitive just from looking at those pictures. If we choose to allow a larger network delay to be acceptable, then we're going to end up with a larger buffer. And of course, we're tolerating a larger delay across the network. Well, sorry, it's not that we're tolerating a larger delay, we're playing things out after a larger delay. So we're adding to the time it takes for the information to go across the network and be played out. On the other hand, we'll end up with less loss. More information will arrive by its play out time, we'll have it, it'll be great. If we choose a smaller network delay as the largest acceptable network delay, then we'll use a smaller buffer. We'll have a smaller delay in terms of when the information is played out relative to when it was sent across the network. However, more packets, a larger fraction of packets, won't arrive by the deadline and they'll be treated as loss. And what's implicit in what I'm saying above here is that if packets don't arrive by the deadline, typically we'll treat them as loss and not try and recover it. The reason for that is recovery takes time. You need to tell the other end that something's been lost and it needs to be retransmitted. And usually for a real-time interactive scenario, there's simply not time to tell everyone to hang on and to go back and get the information. So packet loss is simply skipped over and we'll do without it. That will then just be a little bit of a glitch in the conversation, or there'll be a little bit of an or something like that, and it will be okay. So this is a playout buffer, and how a playout buffer works to provide real-time transport across the internet on top of a best effort network service. We should talk a little bit about an overall VoIP or Skype call, because we've seen a key component of it here, the media playout buffer, how to provide real-time. But there are a few other components of a real-time session, something like a call, like a Skype call. There's the playout buffer technique to provide real-time transport. There's also actually carrying the media across the network. It has to go in the packets in some kind of format. I'll tell you a little bit about that as we work with RTP. There's also session description information, and this really has to do with the format of the media. There are many different kinds of codecs or possible encodings of voice and video. They all have different trade-offs in terms of their quality and their bit rate and other parameters, just for the kinds of components you have available to play them back. There are different alternatives. The format of information can be specified with standards such as SDP, a session description protocol. I'm not going to talk about that in these slides. This is really just a bit of descriptive information. What I will talk about, though, is the final missing piece here, and that's something for call setup. We're just talking about the media so far, but you don't just start sending voice samples to someone across the internet. First you call them up and you set up a call before you send the media. This is the call setup or the signaling with a protocol such as SIP that I'll talk about in a minute. Now, I also want to point out that a real-time session, such as a VoIP call or a video call, can have many other attributes to it beyond what we're talking about. As well as audio, you can have video together in the combinations and even other data. And you can often have multiple parties, a group call, mobility as people move around and so forth. These are all important features. But in what we're talking about, to keep it simple, I'm really just concentrating on an audio call across the network. So let's talk about that, and we're going to go through just some of the pieces of our scenario here. And the purpose really is to pull it together so you have an overall sense of how it works. What I'm going to do is move from the bottom up. So we've talked about the playout buffer. Now let's talk about the information that goes in the playout buffer. That's the media. How are we going to carry it across the network? Well, media is often carried with a protocol called the Real-Time Transport Protocol, or RTP. It is really quite a simple protocol. It's providing a little bit of a wrapper. You can see the header of it here. And RTP really carries media samples across the internet with this format, all inside a UDP segment. So it's just really a packaging of the right information. The header here tells us what a lot of the right information is. I've shown the header here. The media comes after it. And there are a few features to note which you would think are pretty useful for real-time transport. There's a payload type. This tells you the media format, so you know what kind of information follows. There are various standard formats. You might have heard of MP4. I'm sure many of you would have heard of MP4. Many fewer of you would probably have heard of a standard such as G11, which is just a way of encoding audio samples without the kind of compression that MP4 gives you. So it's a simpler standard for voice calls. And it's quite widely used. As well as the payload type or the media format, there's other information. Some of the key information is this information here, the timestamp. This is crucial for knowing when to actually play out those samples, right? So this is something that didn't exist in UDP and is really crucial for the real-time transport of media. And finally, I mentioned there is this sequence number. This is really a RTP packet number, but it's going to help us work out if we've got the packets in the right order, if there are packets that are missing and so forth, what's going on, to allow us to deal with a little bit of loss. There's other information in here. I'm not going to go into it. You can look at a little bit more information in your text if you would like, but it allows for synchronization when you have several streams that are part of the one call and other things which are pretty useful for multimedia. Okay, so now we've done the media itself. What I would like to talk about now, just to complete our picture, is the signaling for the call setup. The signaling for many VoIP clients out there on the internet is done with a protocol called SIP, the Session Initiation Protocol. This is an open standard for establishing voice and video calls on top of IP and managing them in various ways. It's just as I've said, but just to make clear, it's about the signaling. The media itself is carried with RTP as we've seen. I also want to point out, just to be clear, that this isn't Skype that I'm talking about here. Skype uses a proprietary protocol for all of its signaling and even carrying of media. So it's something whose format is not definitively publicly known. So actually I can't really talk about it. But SIP and RTP are widely used for many VoIP clients out there. Here's how SIP works for the call setup signaling. It sends fairly simple messages, so it's really a little HTTP-like in that you send a simple command. These are often done with text, and you'll have a little status code reply. I'll show you how the call setup sequence in a moment. The SIP messages, interestingly, run on either UDP or TCP. Kind of interesting because one's unreliable, the other's reliable. So, but SIP was done in a way to be a little agnostic to what's below it. And also in this picture, I'm just going to talk about two clients, one of whom is calling another one. But actually, if you look at the real SIP standard and how it's used in practice, there are often parties who can come in between here who relay the information. These can be proxy servers and registrars. They help connect all of the pieces when you're trying to find out where someone's actually located because they're on their computer at home instead of at work or vice versa, yet you still want the call to go through. They don't matter for our simple setup. So for our simple setup, let's just say the person on the left is calling the person on the right. What happens? Well, the first message that gets sent is an invite. And after the invite reaches the receiver, we'll get status code information back. Actually, the first optional message that goes back is something to tell you that it's ringing. So this way you can get your media player on the left-hand side can play a ringtone to tell you that your message has been received at the receiver and it's now ringing on the media player. Assume they pick up, then you'll get an OK, meaning the call is on. So here someone has answered the call. And just to complete the handshake, there's also an ACK that's sent in the other direction. At this stage, both clients are connected to one another, and you can see I've already drawn in here the flow of media via RTP packets in the middle. Our call is going in a way, and we're happy and having a great conversation. Eventually, someone will decide they've had enough and hang up, and when that's the case, one side will send the other a message called bye, goodbye. Let's just say, so this is a hang up here. Either party could have decided to hang up. This is just what we have here. And there'll be an ACK, I think. I think there's an ACK for this, or maybe it's an OK. All right, OK. Not quite sure. We'll see. Let me clean this up. OK, it was OK. Great. That was the answer. So here's the overall scenario, and we've now seen all of the pieces that are needed to put together a voice over IP call, from the signaling itself, which is separate, to the media, the voice samples which are sent across using RTP to the playout technique. So now you have an idea how to actually implement and run a real-time transport over the internet. G'day viewers. In this segment I'm going to talk about streaming real-time media across the internet for playout. So our topic is really watching videos over the internet or the playback of real-time media. And we're going to do this using the best effort internet as a network service on which to build rather than changing that service. So that means that what I'm talking about now really corresponds to the way that popular sites like be it Coursera, YouTube, Netflix, pick your own favorite one to put in. I'm talking about how all those sites are able to stream video across the internet for you to watch. This is obviously something that's huge network usage in the internet today. And it's interesting for us just to contrast with how the Skype case or the VoIP case works, because the two are quite different. So let me start there with the two cases of streamed media for playback and interactive media is in a conference call. The stream case is considerably less demanding. Here's the stream case. You can see from the picture it's a little different. I do have the speaker over on the right hand side, but I have simply a file that I'm reading from on the left-hand side rather than a live source. Moreover, there is only a single direction to consider. Now, in the picture before, I looked at a single direction just for simplicity, but there really were two directions, and this was an important reason why we needed to minimize the delay, so that when you were talking to someone else and they were answering back, the delay was kept low and the network didn't get in the way. Here, we're looking at a single direction, but that's it. There is only this single direction. Given that this is the case, the low delay is really not essential here. It really wouldn't matter if the video you're watching was delayed by a couple of seconds. It would be ruinous for a telephone call if it was delayed in only one direction by an extra couple of seconds, but not for your streaming video. It is still generally desirable to keep the delay low for streaming video, but that's really about affecting the startup, so that when you get started, you don't have to wait a long time for the streaming video to commence. It's not about the interactivity. However, because this is a real-time playout on the other end, we're still going to need to handle the bandwidth and jitter issues in the network. So let's go on to those issues. As with the interactive case, the hardest thing to handle is really the delay. And here, the key component for us is not so much the delay, but the jitter. So as in the interactive case with VoIP, the solution to handle the variation in the network delay is to use this playout buffer right here. When media arrives at the receiver, we'll put it in the playout buffer until it's playout time so that we can play it out at a constant rate. This buffering is still needed here to smooth out the variation in network delay. It's not needed, so that's its primary purpose, as in the case of the interactive call. There is a difference, however. So let me get to that here on this next slide. Now recall that we are reading the information from a file and sending it across the network. We're not reading it from a live source. That means we can read it as quickly as we can read from the file and send over the network. So if the network has ample bandwidth, we might well find that we're filling up this buffer more quickly than we're playing it out, and the buffer is becoming very full. If we were to continue, we would end up buffering perhaps a very large amount of data at the client unnecessarily. So what most media players will have is something called a high watermark. At this high watermark, when the buffer is quite full, they'll simply stop requesting the information from the server and give it a break so it doesn't have to read it out its file and send it across the network. If you stop pulling media at this high level, then the media down here will slowly drain out of the network and we'll end up going back, down, emptying this buffer as we play it out until we reach this low watermark. At that time, that low watermark has a good indication that now you should start asking the server at the other end of the network for more information from the file to put in the buffer. The low watermark shouldn't be at the playout point right at the head of the buffer, because obviously it's going to take us a little bit of latency to be able to send off the request and for the answer to come back. So that's why the low watermark will have some space, some buffer space, rather than be right at the front. And similarly, why you would expect a high watermark to be somewhere above, perhaps where you to be somewhere above where you're going to stop making a request, because a little bit of information may be coming in response to your previous requests. So we've talked about the delay issue. Now let's talk about the bandwidth issue. Often in these streaming video scenarios, video can be streamed from a server to many different clients, and they have many different kinds of network connections which support different service rates and amounts of bandwidth. So to handle the available bandwidth, it's quite common to have encoded and to send the file in one of a set of encodings. It's possible to encode the same video or voice in several different ways. Choosing higher quality encodings will give you a nicer picture and result, but require more bandwidth. The files will be larger, so they'll require network bandwidth to be more network bandwidth to transfer. Similarly, you could use a lower quality encoding and save more bandwidth. What you can then do is select the best encoding which will fit across the network given the available bandwidth. Just to give you an example of how that works, I've shown you some pictures that show the variation in quality versus size for JPEG encoding. JPEG is all about a still image. For video, this would be MPEG or something else, but it's just easiest to show you a JPEG example. The same analogous procedure is used with video. So on the left here, we have a high quality, and you can see 15:1 is the compression ratio. So we've greatly compacted the picture. It still looks really good though. As we go down, 23:1, 46:1, you might not even be able to see any difference at 23:1. At 46:1, at least on my screen, there are some blocking artifacts appearing here. And by the time we get to 144:1, this is like horrible. I wouldn't want to watch it. Don't know about you. Horrible. However, it is almost 10 times smaller than the original high quality one. So you can see here we can choose a trade-off point that's going to have the best quality we can handle for the amount of bandwidth which we have available to the client at the other end. And as internet video has been used more and more over time and technology progresses, we've tended to use larger and better quality pictures that will fit. And now in some cases you can download and stream high definition TV movies rather than the standard definition or small versions. So what else is a little different about the streaming media case than the interactive conferencing case? Well, one thing that is quite different is just the transport protocol we can use to get the information there. In particular, should we stream over TCP or UDP? This is a bit of a funny question in that most of us, at least networking researchers, are used to thinking of real-time information as being synonymous with the usage of UDP. If you use UDP, it's just a glorified packet, so this is a great way to minimize the message delay. And that's what you would want to use for interactive real-time sessions like your Skype calls. However, for streaming, it turns out that TCP is typically used for sending information, even though it will have a larger delay. It will generally have a larger delay because if anything's lost, TCP will go back and get it before releasing the information that comes after that. So it may look like your information delivery suddenly stops for a while and then continues. So the delay can be larger, sometimes quite a lot larger. Well, whereby a lot is seconds or sub-seconds, not minutes. So it's not really a lot larger by the scale at which we watch videos or the length of videos. But TCP is very popular today for streaming media rather than UDP for several reasons. The first is that, as I've been saying here, the load delay is not as essential. It's useful to keep it low to be able to start the video quickly after you hit click, get the information to begin playing, enough in your buffer to handle the variation delay and begin playing. But, as long as it's fairly low, it'll be okay. It has the benefits that loss recovery is simplified. TCP is handling the loss recovery, so we don't have to worry about it as part of presenting the media. So we'll never have to skip over some missing slides in the presentation or fill in a little bit of audio with just some white noise or something like that. Moreover, in terms of deployment, TCP, and especially if you're using HTTP on top of it, it's very easy to deploy because it generally passes through people's firewalls and NAT boxes and everything quite easily. So it's the internet is really set up for it. So it's easier to be able to deploy it everywhere than it is to use UDP. Okay, so just to complete our picture of streaming media, what I would like to do is talk about the other components that are missing. We've talked about the delivery of real-time information. I've told you that it's mostly done with TCP, but you're still going to use a playout buffer, just with high and low watermarks. But there's a little more to streaming media players. We've mostly talked about this. Now, and we've talked a little bit about the media transport, just with TCP or UDP. What we haven't talked about yet is the signaling. We still need some way to set it up. Usually you will set up a call or you'll set up a streaming media session before the server can just suddenly black all of the video data down. We need a little bit of call overhead for signaling. And I want to say a little bit more about the media transport to go beyond TCP or UDP and talk about protocols on top, application protocols, which you use for streaming media. And really I'm going to say a little bit about the use of HTTP and a protocol called RTSP. I'm not going to say too much, however. You will have the basic ideas already in understanding how to adapt to different levels of bandwidth and jitter. And this is actually a very fast evolving area. In fact, the HTML5 standard now includes a video player. So everyone's going to have to work out how to get video to that player now that it's almost a standard part of the web. And the protocols which cause this to happen are all evolving, and there are different proprietary protocols, and they'll be standardized more over time. And finally, just before I go over a couple of ways to deliver the media, I want to point out that I'm really talking about the streaming of media to an individual party. That's the way it mostly works in the internet today, where we use something like a CDN to get the media close to all of the viewers, and then individual sessions between a CDN node, or CDN replica rather, and the nearby viewers. There are other advantages to be had if we're all watching, say, a live event at the same time. But while they're interesting things, I'm not going to go into them in this video. Okay, so let's look at these two alternatives for just some of the higher layer protocols for putting all of the pieces together. One way that you can stream video is with a protocol called RTSP. This is a design which used to be fairly popular, and in this sort of system you were able to tie a media player into your web viewing. What would happen is you typically click on a link where a video was mentioned in your web player, and what this would do is it would start the process by getting, using HTTP, a meta file describing the video. So that's this request. You run a web page and someone clicks, and then you make an HTTP request for the video and you get it back. Now, the HTTP response doesn't actually contain the video. This might be a gigabyte or something, and you don't want to transfer all of that before beginning to look at it. It really contains some meta file. And the meta information is typically that the protocol used to play out the video is with RTSP, so you might have seen URLs with the form RTSP://, and then other information about what server to contact and what the file name is. At this stage, the browser hands off an RTSP URL to the media player. The media player, if this is RTSP, will then send a media request and set up a session and do the negotiation with the media server. And then all of your media response will come back, whether it's via TCP or UDP, often as RTP information carried over those two. And at this stage, we'll have the usual playout buffer technique and we'll be done. So RTSP here is really the protocol which is used to do the call signaling with the media server and to pull all of the information over, stopping when you reach the high watermark and resuming when you reach the low watermark. Here's a different way, a completely different way of streaming media. And I'm mentioning this other way of streaming media using simply the existing web protocols, HTTP, because this method of delivering streaming media is the method that has become quite popular nowadays and is widely used for streaming media clients. It's supplanting all of the RTSP methods. The method here is that you simply use HTTP really. The first step is to use an HTTP request to simply get some of the meta information. This is an index. So you can see here I have the GET request. And then the information that comes back as part of the HTTP response is going to be the index. That's going to really give you a list, if you like, of many different HTTP URLs which could be got, each of which is going to contain a small amount of the video at a different time step and in different encodings. What your video player will then do is make many HTTP requests, each of which will get a small bit of the information, then put it in the playout buffer for playout. And so you can see that's why there's a GET media request. And they just keep going and media is returned. Now, in addition to simply getting some media for the first second, for the second second, for the third second, and putting them all in the playout buffer so they can be played out, your media player will need to make decisions as to what kind of encoding of video to get. The server might have half a dozen different encodings of video at different bit rates. So the media player will adapt the choices of what quality of media it gets for each different time instant. And it can do that based on just the past history of buffer occupancy. If it's getting low quality video and it's pulling in quickly and it's getting ahead of when it needs to be played out, it might decide to get higher quality video, which will come in a little more slowly because it's in terms of time, because it's larger. But if you can play a higher quality video, it's generally better. So your media player will be responsible for adapting between there. And you can see I've tried to indicate a thicker line here, so we'll just call it higher quality, higher Q. So maybe that was a second of video just at a higher quality than before because the media player has decided it's the way to go. So this is the method which is being worked out right now and used for video players on the internet. The standards are evolving, and you could look up something called DASH, which I think stands for Dynamic Adaptive Streaming over HTTP. Apple has proprietary versions, Adobe has proprietary versions, Netflix has proprietary versions, and so on. And they're all beginning to be standardized. This system is interesting because it very much fits into the existing web protocols. We're really just using HTTP here to knit everything together just with a media player as output. That media player can be embedded as part of our web browser, especially with HTML5. This is also quite good on the server end. So this is the server, and this is the client. It's quite good on the server end too, because the server is really just another HTTP server, another web server. It's not maintaining call state for the client. This client is really just pulling the bits of video it needs. This makes it quite easy if the client, for instance, wants to skip around to the other end of the video. As long as it's got the index, it will know what to ask for, and it'll be able to jump to that end, and the web server really doesn't have to care about what client it's talking to and where they are. It will need to check the request just to make sure you're allowed to watch this video, but other than that, it can give you a video from anywhere in the movie. Okay, and now we're done. When you put these pieces together, you see how the information can be transferred for streaming media, and we use the same kind of variation of a playout buffer to be able to play it out in real time. G'day viewers. In this segment we'll learn about fair queuing, one of the building blocks for quality of service. So our topic is sharing bandwidth between flows, one of the key topics for quality of service. What we're going to learn about in this segment is fair queuing, or more specifically weighted fair queuing, which is one of the key building blocks for quality of service and an alternative to the FIFO queuing that we've seen up until now. Well, let's start with FIFO queuing to make sure we understand it before we improve on it. With FIFO drop-tail queuing, packets are queued in first come, first out order, first come, first serve, it's sometimes said. It's essentially a regular queue, as you and I know. The queue also has a rule that new packets are discarded when the queue is full. You could discard packets in the queue or packets, the oldest packets or something like that, but typically what's done is that you discard the newly arriving packet when the queue is full. And this is the typical queuing model or scheduler which is implemented in routers today and widely used in the internet. When we share with a FIFO queue, what's really happening is that multiple different users, or really we'll typically talk about flows of traffic. A flow of traffic is a series of related packets that come from a user, and usually they'll represent some kind of application, some meaningful application unit, such as a Skype video call, or a BitTorrent session, or web surfing by a user, or something like that. So I'll use that word flow, you'll see will come up often. At any rate, these flows all are trying to go to the same output link, which is run by a FIFO scheduler. What's going to happen? Well, we sort of know what's going to happen in that this is what the best effort internet service is all about. We have to, apps have to compete, and their traffic, the flows, will share the bandwidth and delay and loss via this FIFO queue. So if we sort of revisit it from our point of view right here, what I would say is that the bandwidth allocation, you see how much bandwidth a different flow gets, depends upon the behavior of all of the flows. It depends upon everyone's behavior. To describe this picture, on the left-hand side we have the inputs. These is actually, it could all be coming in on one link or more, but it consists of multiple different flows. And I've logically separated the traffic from three flows, the grey flow, the pink flow, and the blue flow, so you can see there's traffic from all of them, but they're all flowing in. And what will happen inside the router is they'll all be queued in a single FIFO queue for transmission onto the output link on the right-hand side. The order in which they're queued is the order in which they will arrive. And it just so happens here that it happens to be pink, pink, grey, pink, pink, blue, pink, pink, blue, and so on. That's just the arrival order that happened to be here. This means if there's a lot of pink traffic and some of the blue traffic might miss out. It just depends. Now, over the long term, how much bandwidth of the output link the different flows get is going to depend on how they implement TCP, and they share the bandwidth over the long term. Different flows are also going to cause other flows amounts of delay and loss. Even TCP sharing, it's certainly only sharing over the long term, because in the short term you could get lucky or unlucky. And even over the long term, TCP has what is called an RTT, or round trip time bias. Flows with a short RTT tend to get more bandwidth than flows with a large RTT because they react more quickly. The upshot of all of this is that the behavior that one flow sees, the bandwidth it sees, depends upon the behavior of everyone else. And if there's an aggressive user or flow in here, or more than one, they can easily crowd out another well-behaved flow so that it can get less bandwidth and see more delay and loss than otherwise. Maybe than it should if it's not been aggressive in the network. What we want to do now is come up with a better way of queuing to improve fairness. And I'm going to start looking at that way of queuing by talking about what I'll call round-robin queuing. With round-robin queuing, the idea here is that instead of keeping one big FIFO queue, we're going to break the queue up and have a different queue per flow. So if I have 3 flows here, then I have 3 different per flow queues. And as my inputs come in, I will put them into the right queue, into the flow 1, the flow 2, or the flow 3 queue. So now we've split up that one big flow inside the router to many smaller, that one big queue inside the router to many smaller queues. What I'm then going to do for the output link, here's the output, is I'll go round and round these queues. Every time I have an opportunity to send a packet on the output link, I'll take from the next flow in turn. Maybe I'll draw from flow 1 and then 2 and then flow 3, then go back to flow 1, 2, 3, and so on. And I'll look every time it's an opportunity to send a packet. If there is a packet there in the flow queue that I'm meant to be looking at, great, it will get sent. If that flow queue is empty, though, I'll just advance on to the next flow queue and eventually we'll go around and come back, and then hopefully there'll be a packet from the other flow. The queue could be empty simply if there's a flow that's not sending very much traffic. Well, let's see what's going to happen here. What I really want to do is work out the output order. Well, actually, it shouldn't be too hard, so let's just think about it. If I go round robin, I should get a packet from flow 1, and then flow 2, then flow 3, then flow 1, then flow 2, then flow 3, and so on. So on the right-hand side, I have the earliest one or the first one sent. And we're just going to keep repeating. So I don't even need that question mark because it's fairly simple here. So that's what we should see. Let me just clean that up. And we have that graph. Now I have gone through and done the same thing. Actually, my writing on the previous slide wasn't quite correct because I only had 2 grey packets. So if I go through and label it, I've got 1, 2, 3, 1, 2, 3, and then I have no 1 because I have no other grey packets. So I get to send flow 2 and then flow 3. Then I have no flow 3 packets, so I just send packets from flow 2 onwards. And eventually more packets should arrive. Now, one thing to note is that the output order is now no longer necessarily the arrival order. It won't be, in fact, if the link is busy and there's some amount of queuing. We can't see the arrival order in this picture. It could have been not quite anything, but we can't see whether all of those pink packets arrived all at once or not. In this picture, we could imagine, if you like, that all of the packets shown there arrived at time 0, and then I'm drawing the order in which they're sent. And again, this end is the first away on the output link. So you can see this pattern is different than the previous pattern with the FIFO one, in that we have improved the fairness in some respect. If you consider a packet at the beginning of the grey queue now, it really doesn't matter whether all of these packets came before it and are just hanging around or not. This packet at the head of the grey queue isn't going to have to wait for a large number of pink packets to go through. It will get to go through every time around the cycle. It will have an opportunity to send. So it's fairer. These flows which are sending less traffic are now seeing less delay and less loss caused by a flow which is sending a lot of traffic. So that's this point. It's better. So flows no longer see uncontrolled delay or loss, is how I stated here, from the other flows, even if those other flows are very aggressive. So even if another flow, if you like, you could consider that flow 2 here goes berserk. Flow 2 goes crazy. Even if flow 2 goes crazy, it really can't slow down traffic from flow 1 and flow 3 going out the output link. If there is a packet from flow 1 or flow 3 waiting in their queue to go, they will get to send 1 packet every 3 output packets, regardless of whether flow 2 goes crazy or not. So this is definitely a step in the right direction in terms of fairness. However, it can be quite imbalanced. So if our goal was actually to divide the output bandwidth of that link, maybe it was a 150 megabit per second link and we wanted to give 50 megabits per second to 3 different users, we haven't really succeeded with that goal. And the reason is because we haven't factored different packet sizes into account. It's the case that this wouldn't matter if packets were all basically the same size, but it's the case that packets can be significantly different in length. You might have 40 byte small packets carrying different samples, or 1,500 byte larger packets, or even more depending on the network technology. So this is 1 to 2 orders of magnitude difference. So we can easily be talking about dividing the bandwidth not into thirds, but giving someone a 30th part or a 300th part instead of a third, which is really not what you wanted to do. So what we're going to do, and I've now finally gotten to the fair queuing part of this, is we will introduce what's called fair queuing. Fair queuing is an improvement on our round robin queuing, which was a straw man, if you like. And what fair queuing is going to do is approximate bit level fairness. So this really will allow us to roughly divide 150 megabit per second link into 3 50 megabit per second links. What we'll do is we'll come up with different rules instead of taking one packet from each flow queue in turn. Instead, for all of the different flow queues, we will approximate a virtual finish time for the packet at the head of the queue. We'll compute it. And this finish time will be in terms of a virtual clock. The virtual clock is defined to be a clock that ticks once when all of the queues which are non-empty have gotten to send 1 bit. Why? Well, we'll just find that this is a simple way of thinking about it that's going to give us the right order in which to send things. So we will send packets in the order of their virtual finish times. If you have a lower virtual finish time, you should get to go first. However, we're not going to aim for perfection in approximating fairness. In particular, we're not going to preempt packets that are being transmitted. So if I have a big packet that's been transmitted of 1500 bytes, and halfway through it a small packet comes in, and because it's very small, maybe it has an earlier virtual finish time, I'm not going to stop or abort the transmission of the 1500 byte packet just so I can send the small one. I'm going to send complete packets at a go. Okay, all of this might sound a little mysterious, but let's just try and work through the formulation and an example to see how it would work. To do that, I need to present you with a bit of notation. Here's the notation. So let us define arrive J of F to be the arrival time of the jth packet for flow F. Length of J of F is the length of that packet. And then the thing we're trying to, so that was length of J of F, and these are just inputs, these first two. What we're trying to compute is the finish time for J of F. Now, this looks like a little bit of a complicated formula, but it's not too bad. Let me work through it. If you just ignore the max operation and the arrive for a start, then we're saying something like the finish time of J of F is the finish time of J minus 1F, the finish time of the previous packet that is, plus the length of the current packet J of F. Well, that makes sense, because we said this virtual clock ticks once every bit is sent from every packet that is waiting, from every queue that is full. So you get to send 1 bit from your queue every tick of the virtual clock. So if you've got a packet that's length bits long, it's going to take you length ticks on your virtual clock to send it. So the finish times are advancing by the length of the packet. But what's this max operation all about? Well, the max operation just says we're going to take that length of the packet for virtual clock ticks, and we're going to start from either the finish time from the previous packet or the arrival time of the current packet, whichever is later. The reason for that is that if you think about when the packet is going to get sent, we can't start sending its bits until either the previous packet was finished. If it arrived early, it just has to wait around and it won't even get to be sent, or shouldn't even be considered until the previous packet is gone. Or if the queue was lying idle, the finish time of the previous packet wasn't really relevant, we just start again when the new packet comes. You don't get any sort of credit for not having used the queue for a long time. Let's talk about an example to try and work that out. So let's suppose for this concrete example, here are our flows again, flow 1, flow 2, flow 3. Now I've drawn the same picture so the packets look the same size, but for fair queuing here, let us consider that flow 1 and flow 3 are sending 1000 byte packets, whereas flow 2 sends small packets of 300 bytes each. If this was round robin queuing, we would take one packet from each queue in turn, 1, 2, 3, 1, 2, 3, 1, 2, 3. But we're trying to take the packet sizes into account. So what will fair queuing do? So we want to work out the output order here. Well, here's first again. Well, what's it going to be? To do that, we need to compute the finish times. That's how we determine the output order. Okay, let's have a go and try and do that. To do that, we'll start with the finish times of, I'll just define finish of 0 for any flow to be 0. So we're just going to start everything at time 0 on the virtual clock. And I'm going to assume that all of the queues always have something to send. So the terminology for this is that the queues are backlogged. There's always something in it. So we never just have an empty queue. We're waiting for things to arrive. If you like, you could think of this as just all of the packets in the queue for a flow just all arriving at once. Or it wouldn't actually make any difference as long as the next packet arrived before the previous packet had been fully sent. So there was always something in the queue. That's this condition here. It doesn't matter other than us just thinking that there's always a bit to send. There's always a packet to send in each of the different flow queues. Okay, let's compute the time for finish 1 F1. That is the finish time of the first packet on the first flow. Now the finish times are just the finish times of the previous packets plus the length of the packet. Since the queues are always backlogged, this max condition with the arrival is not going to come into play just yet because there's always something to send. So the finish time of the first packet will be 1,000 because it's 1,000 long. And then the second packet will be there, and the finish time of the second packet will be 2,000 in our virtual clock ticks. You get the hang of this, I bet. For the finish time of the first packet of the second flow, well, it will be 300 because it's 300 bytes long. Starting from 0, you add 300, you get that. The finish time of the second packet in that flow will be 600, then 900. We're adding another 300, and so forth. And similarly, the finish times for the third flow are going to be the same as the finish times for the first flow because those flows had packets of the same size. And again, the arrival factor doesn't matter here in this particular example because the queues are backlogged, there's always a packet to send. So look at these arrival times, look at these finish times, and we're going to send packets in order of the finish times. So can you see what order we'll send things in now? Looks like we're going to send the lowest one is this one, then this one, then this one. So that means 3 packets from flow 2, and then let's say this one and this one, they're the same, so the order doesn't matter. A packet from flow 1 and a packet from flow 3. Then this one, and so forth. If I draw that as a picture, it should make a little more sense. This is the first end. And you can see we're sending packets from 2, 2, 2, 1, 3, 2, 2, 2, 1, 3, 2, 2, 2, and so on. This is what we want to do, in fact, for fair queuing. And the reason for this is flow 2 has the smaller packet, so it should get to send about 3 1/3 packets before anyone else gets to send one of their packets. And that's actually exactly what's happening. In this example, you could work it out fairly easily, just because I said the flows were always backlogged and the numbers were fairly clear. In a more complicated example, the fair queuing expressions would tell you the order in which packets should be sent so that they will always remain approximately fair. However, before we get there, I need to introduce just the final bit in this formulation, and that is to take us to weighted fair queuing. In fair queuing, what we've seen so far is a way of dividing the bandwidth of a link into n equal portions when there are n flows. We can also split it up into n slightly different portions if there are flows where some of the flows don't have packets waiting at a particular time. Then the arrival factor would come into play. But so far, all of the different flows have been treated equally. With weighted fair queuing, we generalize fair queuing. This turns out to be useful so that we can assign a weight, or an importance if you like, to each flow, each different flow. So all of the flows can have a different weight. A higher weight gives you more bandwidth. So for instance, if you have a flow of a weight of 2 for your flow, then you get twice the amount of bandwidth. You're going to get to send twice as many bits over the same period of time as the flow with weight 1. And so you can see how we can prioritize things using this weight, relatively prioritize them. To do this, we need to update our formulas for computing the finish time. And the only change we need to make is this change shown here in pink. We need to factor in the weight. So what we do is we take the start time at which we can start sending the packet, and instead of adding the length, we add the length divided by this weight. This weight is a normalizing factor. If the weight were 2, it would mean you get to send 2 bits every virtual clock tick. So instead of adding length, the number of bits we want to send, we'll add length divided by 2, because that's the number of virtual clock ticks. So using the weight factor in this way normalizes everything in terms of the virtual clock and helps us understand what's going on and the order in which to send things. Well, here's a more complicated example. I'm not going to work through it now in this short lecture, but it's an example. It's taken from your text. You could look through, you can work through this example yourself. The table here has all of the input data you need. These are the inputs. The packets when they arrive and what their length are, and you can compute the finish times, and from the finish times the output order in which they should go on the link. Note, if you do that, this queue here on which packets C, E and G arrive has twice weight. So C, E and G. I just put a 2 there to note that they have a 2x bandwidth multiplier. And so if you worked it through, you'd see a few interesting things. You'd be able to work out the output order, make sure that you understood this concept. And you'd also see things happen like packet F will actually get to go before packet D, even though it arrives afterwards, just because of fair queuing, just because of when we're expecting the end times. The end time for this one is longer. So I'll leave you to work through that. So we've now seen weighted fair queuing. Weighted fair queuing has a lot of potential for quality of service. I hope you can imagine how we can use it to just prioritize and protect different flows. By using the per flow queues, we've already provided some protection. So one flow could go berserk and not affect the other flows by adding extra delay and loss to them. And by adjusting the weights, we can also prioritize different flows. If I have a queue with a high weight like 10 and another queue with a low weight like 1, then you can see how I can preferentially favor some traffic. I might, for instance, put Skype traffic in the queue with a weight of 10 and BitTorrent traffic in the queue with a weight of 1. That way the Skype traffic will get to go, will get preference. It's not actually absolute priority, it's just you could send 10 times as many of those packets, or they would drain 10 times as quickly and keep the queue small, so they would probably get sent fast compared to the BitTorrent. Actually, these weights are often more useful than strict priority, because strict priority can starve out a queue if there's ever any higher priority traffic. Okay, but just to wrap up this lecture, let me just say, in case weighted fair queuing sounds a little mysterious, that we haven't yet seen a complete quality of service solution. Weighted fair queuing is a powerful building block, but for any kind of complete solution, we need to do a few other things. For instance, we need to determine how to assign packets to different flows. I mean, what is a flow? Could it be a user, an application, or a TCP connection? We will then need to assign different weights to different flows. We need a higher weight for Skype if we want to favor it over BitTorrent, otherwise we haven't necessarily done very much. And also, I'll just point out that actually weighted fair queuing can be difficult to implement at high speed when you have many concurrent flows. So this affects how we might want to use it. We might want a relatively small number of flows. So in some of the next lectures, we'll begin to see ways of building complete solutions using weighted fair queuing to give us quality of service in the internet. G'day viewers. In this segment I'll talk about traffic shaping. Traffic shaping is about constraining the flow of traffic, both in terms of parameters such as the average rate or bandwidth it needs, as well as other parameters such as burstiness. And it's particularly useful in quality of service because constraining traffic can help the network make good on any promises it makes. In this segment, we're going to look at token buckets, a particular kind of traffic shaper which are widely used as a key building block for quality of service. Okay, so a little motivation first. So traffic shaping is about constraining traffic flows in terms of their properties, or really the load which traffic flows which come from users or applications can place on the network. We can limit them in a couple of ways. Just limiting the total amount of traffic by shaping it enables us to make bandwidth guarantees, because if we shape traffic, we can control how much traffic is in the network, and that way we can be sure that we'll meet the promise about so-and-so having a certain level of bandwidth. We can also limit not only the average rate of traffic, but also the burstiness. Limiting the bursts of traffic helps us to be able to avoid unnecessary queuing and loss within the network. So again, it can be useful for quality of service. The big question, though, is how we should actually go about shaping traffic. From the network's point of view, it might be desirable for traffic to be as smooth as possible, because that way we'll avoid unnecessary bursts and loss as queues fill up. But on the other hand, if you think about real apps generate varying traffic. They just do. As you surf the web, or as you use a remote desktop or something, or as media is compressed in different ways, the traffic that's sent into the network is often quite variable. So it's unrealistic to think that applications will smooth out their traffic. Here's a little bit of motivation just to understand the differences between patterns of traffic that applications might inject into the network. This graph shows the bandwidth on the y-axis versus time on the x-axis. And there are two flows shown just to show very different behavior that they might exhibit. Flow A is a good old smooth flow. It sends steadily at a rate of 1 megabit per second over a period of 3.5 seconds. Flow B, on the other hand, sends at a low rate and then occasionally shoots up and sends at a high rate. Then back down, and then occasionally it shoots up again. Now, Flow A and Flow B clearly have very different behavior as far as the network is concerned. But they actually have the same average rate, which is 1 megabit per second. So we can see from this example that the average rate alone is not a good descriptor of behavior in terms of what the network can expect from traffic flows. So how should we go about describing traffic flows to the network? Well, what we'll do is constrain two parameters. We're going to constrain the average rate because this matters in a long-term sense. It relates to the amount of bandwidth or capacity that's needed in a network. To carry both of these flows, we need to allow for a megabit per second for them within the network over a longer period of time. We'll also want to describe or constrain the burstiness of the different flows. Flow B is harder to carry in a sense with only 1 megabit per second of network bandwidth, because when it's above it, it's sending bursts into the network, which will end up in queues somewhere, causing delay and potentially loss. So we might want to limit the burstiness, or at least know how big it is so we can handle it. However, simply using these two characteristics rather than the average is already very useful. The two characteristics are much more expressive than the average because they allow a variety of different flow patterns to be characterized and distinguished. On the other hand, these two characteristics, we've gone from 1 to 2, it's still a relatively simple model for the network to work with compared to all of the infinite variety of traffic patterns that could be sent into the network. So without further ado, let's go to the RB token bucket. The token bucket is a traffic shaper which has two parameters, that's the R and the B, to constrain the traffic. And the R and B constrain the traffic as follows. The R parameter constrains the flow of traffic to have an average rate of no more than R bits per second. The B parameter constrains the traffic to have instantaneous bursts or traffic that is injected into the network over and above the average rate, the long-term rate of R, bursts of no more than B bits. So that's the limit on the instantaneous load which can be placed on the network by the traffic flow. Now we have this picture here of the bucket. So a token bucket is usually explained in terms of a bucket analogy. So here it is. Now change the writing here to reflect the bucket analogy. To implement a token bucket, think of having a bucket with capacity or size B bits. That's how much water or how many tokens or credits it can hold. The bucket has been filled up by a tap that runs at a rate of R bits per second. That's how quickly water or tokens or credits are going into the bucket. The way you then use the token bucket is when you want to send, to be able to send, you need to be able to remove tokens from the bucket or draw that amount of water out of the bucket. If you want to have a packet to send and there's enough water in the bucket, you take it out and you're able to send the packet on its way. If there's no water in the bucket, however, you can't send the packet. It's outside of the token bucket specification, so the traffic is not constrained according to a token bucket. Token buckets are useful because they're able to constrain the greatest or largest amount of traffic from an RB source that the network can expect over time. So let's just imagine that we have traffic that's coming from an RB token bucket source. What kind of traffic could that impose on the network? Well, we do know something about it from the RMB parameters. This line here, sorry, let me draw that again, this line here, this is meant to be R times time. This is the long-term rate, maybe that's a little better, over time. So it's just as time goes by, it's going up at a rate R. This is the average rate, so we expect traffic to go into the network this fast over time. Now at any particular time, the traffic could burst and it could send B bits over and above that long-term rate. Of course, it can't send two bursts back to back and go even higher. If it bursts, it's going to have to wait for a while until it gets back down so that it's sending no faster than the average rate. But if we add the bursts together, we have an upper line, which is RT plus B. That line indicates the maximum load that this traffic could place on the network. The real traffic might go something like this. You can see the traffic went along at its rate for a little while, and then suddenly around here it crept up fairly quickly. So it was sending faster than the average over a short period of time, and it sent quite a lot of traffic into the network and got near the upper line. Then it had to send slowly, more slowly than the rate, and do pretty much nothing for a while until it got back down closer to its long-term rate. So an RB token bucket source is constraining the traffic that an application can send into the network. And here's that picture cleaned up, just so that you can work through it a little more clearly. Okay, so that is an RB token bucket. A token bucket can be used in two different ways. They can either be used for shaping or policing. Shaping is about modifying the traffic near a source. So that's the traffic that's injected into the network. We can shape it to fit within an RB token bucket profile. The way we do it is as follows. We run the RB token bucket at the source, and as packets are generated at the source, we pass the packets as they're generated into the network when there are tokens in the bucket that we can use to send them. However, if we have a packet that's generated and we have no tokens in the bucket, then we have to delay or queue the packets at the source until our token bucket has more tokens, and we can then use these tokens and send the packet into the network. In this way, the token bucket is able to let the user condition their traffic to meet some kind of contract that's been agreed between the user and the network as to how much traffic the network will handle well. Policing is a different usage for a token bucket. Policing is something which is done within the network, within the edge of the network or at a network boundary. And it's done to verify that a source of traffic that's come from a user meets an RB token bucket profile. So we do it as follows. At a network edge device, this might be a router inside the network, we run the RB token bucket. And as traffic comes through, we meter or charge that traffic by taking tokens out of the token bucket that corresponds to the traffic. And if there are tokens there, then we let the traffic into the network. The traffic is in profile. On the other hand, if traffic is trying to come into the network and there is no tokens in our token bucket to fit it in, then that traffic is out of profile. And the network might do something nasty to it. The network might demote or discard the packets. Discarding is just throwing them away. They were out of profile. They were beyond what was agreed for an RB token bucket. Demoting is something that can be used in a quality of service scenario. We might have these packets which correspond to an RB token bucket. They might be a video call, and we might mark them as high priority, make sure they don't get lost and get them through. Anything in excess of the RB token bucket profile might be demoted by being marked as purely best effort. The network will let it through if there happens to be bandwidth at that time, otherwise it will get dropped. So it won't be treated as well. It will be demoted. But a token bucket used for policing lets the network check the traffic that comes in to verify that it meets a contract which has been agreed by the user, and to separate out anything in excess of that contract, so it can decide what traffic to treat well and what traffic does not need to be treated well. Okay, so that's token buckets. We've seen how token buckets can constrain traffic. This can help both the user and the network. The network is able to limit the traffic that's coming into it so that it can meet any promises about preferential treatment for some kinds of traffic. And the user is still able to inject a wide range of traffic. It can flexibly make traffic while still conforming to some RB token bucket. The token buckets themselves don't provide any kind of differentiation or quality of service to traffic. That kind of differentiation to handle some packets well so they go ahead of other packets is going to require special treatment at routers within the network. And that special treatment will be provided with building blocks such as weighted fair queuing. In the following segments, we'll look at how to put together token buckets and weighted fair queuing to implement quality of service solutions. G'day viewers. In this segment I'll talk about differentiated services, which is one vision for quality of service in the internet today. Okay, so in differentiated services, what we're really trying to do is provide a small number of different classes or grades of service. So this is a premium and regular service, network service if you will. And it's one kind of quality of service which is gradually being deployed in the internet today. For motivation, let's return to our classic scenario of a user who's sending Skype and BitTorrent traffic at the same time. Actually, they're just examples of kinds of traffic. Instead of Skype, you might imagine remote desktop and gaming traffic and so forth. I really have in the picture here down on the left the pink packets and blue packets, and they require different kinds of service. You can see the blue packets are marked as priority VIP packets. Maybe your gaming or remote desktop or Skype traffic is more time sensitive than your other traffic and you would like it to receive preferential treatment. What we're really after with differentiated services is to work out how we'll be able to provide that kind of preferential treatment. And what we're going to do, as you might have suspected all along, is combine some of the building blocks that we've known about because we've seen them in earlier lectures. So where we want to get to is this idea of being able to treat different kinds of traffic, the different grades, differently in the network. We're only going to have a few different grades of network service. I've called them here gold, silver, bronze. You could call them anything you like. We'll see some different names in a moment. Obviously, for the different kinds of service or the different grades of service, they're going to get better or worse treatment inside the network. So some with the gold will receive preferential network service compared to the silver and the bronze. But of course, to get that from your ISP, you probably have to pay for it. And then all we need to do to complete the picture is map the traffic from the different applications we're running to the appropriate kind of service we would like them to receive in the network. So here's the overall architecture. And you can see there are three important pieces here. The first piece is that the user is marking the packets with the service they would like the packet to receive. So all packets that come from Skype might be marked to receive gold level service here. So this is done right here at the edge of the network by the user. The packets then go into the network, and then we have steps 2 and 3. In step 2, the network right here is policing the traffic that is entering it at its boundary as it goes into the network to make sure that it's appropriate. Appropriate would mean that you're not asking for too much high priority traffic, and really essentially that you're getting what you paid for. And we'll see how we use token buckets to do that. You can see all of the pieces are coming together here. And the third piece is within the network itself, so within the ISP here, we need to actually provide the different kinds of service so that gold service comes out ahead in some respects of silver and bronze service. And we'll do that by using weighted fair queuing at routers. And there are other schedulers that could be used too. But in this overview of differentiated services, I'm really just going to take a quick peek and show you the most basic option. So let's go through each of those three different parts of the architecture in turn. First, marking packets. How are we going to mark these packets? We actually sort of need to flip some bits on them and carry them through the internet so that different routers will know which packet belongs to what kind of service. Well, very fortunately, there are some bits in the IP header. This is the IPv4 header, and they're inside this differentiated services field. They're also in the IPv6 header in a traffic class field. These bits carry a 6-bit DSCP, that's a differentiated services code point field, which specifies the kind of quality of service the packet should receive inside the internet. Actually, these bits have been rebranded some number of years ago. Originally, they were called the type of service bits, and they were able to specify whether the packet should receive low delay or high throughput, all of this sort of stuff. But no one really knew what to do with quality of service in those days, and so they languished. So they've really recently been relabeled so that they can be used for something that's closer to their intended purpose. But luckily they were there, because IP header space, at least for IPv4, is some of the most scarce and expensive real estate in the world, I guess. Okay, so now we know the bit fields where the marks go, we need to work out what to put on them. Well, in the differentiated services architecture, there are many possible different DSCP markings that could be put on a packet to request a different kind of service. Actually, it really depends on what the network operator is going to provide here. Differentiated services is really a toolkit, and you can make up all sorts of quality of service offerings. So your network ISP will decide what handful of services they'll support and exactly what they will mean. But I've shown here in the table just some different common differentiated services names. One kind of differentiated service is just a service that has a code point of 0. That's the default forwarding service, and that is, surprise, best effort. So you get just what the internet already does. This is appropriate for what's called elastic traffic, and that's traffic that can be spread out over whatever time is available. So BitTorrent is a good example of this. It's a bulk download. It just goes as fast as the network has spare capacity for it. And beyond this kind of service, I have 3 other services here which represent kind of more stringent qualities of service. So where the network will actually do a little more than best effort. There's one kind here which is assured forwarding, is the name that's used. It's a little unclear exactly what this is, but we can think of this as some kind of enhanced forwarding. It's not best effort, it's enhanced effort. There are many different DSCP values that are used here. I've shown a typical range for different grades of this service in different ways. But the need that this service provides is traffic that has some kind of average rate that it requires and that the network is going to provide. Streaming video is a good example of this, because you would like a certain rate so that you can get through the right quality of your video, but maybe you don't care particularly about the exact delay you get because it's a streaming scenario. Beyond this, we have expedited forwarding. This is for real-time traffic, like voice over IP or gaming and so forth. This is traffic for which you want the network to provide low loss and low delay. And then finally, there are other more historical kinds of forwarding values. In this field, old precedence values from previous uses of the field can be used. And they really specify different priorities of traffic. And I've just shown an example here, network control traffic. This is high priority traffic. A good example is traffic which is sent by the routing protocol between all of the routers to help maintain the routes. Well, you'd really think the network should treat that as high priority and deliver it so the routers can work out which way to send all of the other traffic. So you can see here that quality of service can actually be useful for running our own network. Okay, so now we have all of the markings and we know something about what they mean. All we have to do now really is have traffic be marked by the users. Now, exactly what application is marked with what DSCP value for service is a matter of local policy. It depends on how it's configured in the user network at the end. And the reason it's local policy is it depends on your objectives. I picked an example here. Should gaming traffic be marked as expedited quality of service or not? Well, I don't know. If this is you at home, yeah, absolutely, because you want a good gaming experience and latency really matters. If this is your business at work, they might not be really thrilled to be paying for extra money for all of the premium service that they're buying, for that to be used on gaming traffic. They might think their VoIP calls are more important. So there's a matter of local configuration. In either case, it's done on the user side as traffic goes into the network. This could actually be done on the host itself, as part of either the operating system or the application. This is actually quite helpful when you can do it, because really it's the application or the local operating system from which the traffic is generated that has the best idea what that traffic actually is, and hence what priority it should get. Or it could be done by a device inside the network, a kind of middle box as traffic is going through. You might use the heuristics, like the ports on which the TCP or UDP traffic is going, to decide whether it's high priority or not. This is actually a little tricky to do inside the network, because if the traffic was encrypted, for instance, it might be a little difficult for the network box to tell what kind of traffic it is and how important it is in terms of quality of service. So there's another twist which makes it difficult. Okay, step 2, policing at the edge of the network. What's this all about? Well, this is really about two things. The network at the boundary, as the traffic comes into the ISP network that's going to implement quality of service, it needs to check that incoming traffic to see that it meets whatever service contract has been agreed with the user. For instance, you would not want to, if you were the ISP, allow more expedited traffic or packets with expedited markings into your network than you've already agreed to accept from the user, and more particularly that the user has already paid for. If they haven't paid for it, you might just not want to give them expedited service. And more than that, you might also do a little housekeeping. You would only pass in allowed quality of service markings. For instance, users should not generally be passing routing traffic into the network. So if they have any markings for network control traffic that should be treated as very high priority, these markings might be scrubbed, because you're only going to allow that kind of traffic to be generated inside your network. You're not going to give that high priority to the different users. Now, policing, just to tell you a little bit about how policing is done, you might have guessed the answer already. It's done with a token bucket. We simply run a token bucket machine, and that way we can assess the rate and the burstiness of traffic. And we can decide whether too little or too much traffic of a certain kind is coming in. If too much is coming in, then we can simply demote the traffic which is out of profile. We could discard that out of profile traffic if there's too many high priority packets coming in. But what is often done instead is to demote it. If a user marks all VoIP packets as high priority, and for some reason there's a lot of VoIP traffic, and so there's too much high priority traffic, more than they paid for, what the network can do is it can demote and change some of those markings, and it can remark that high priority traffic to be just best effort traffic. That way, if there's enough bandwidth in the network, it will get through. And if there isn't, it won't get through, and the user will find they're not getting the service they want and have to buy more service or use the network less or something. And actually in DivServ, other kinds of demotions are possible too. For instance, these packets might be prioritized for a different kind of loss. If you've got too many high priority packets, you might let the extra ones in, but mark them as the ones which should be dropped first. So that's policing. What about the third component, forwarding? Well, here we really have to work out how the packets are going to be treated at routers to provide the different kinds of services. And the answer is that the routers inside the ISP network will use weighted fair queuing as a scheduler instead of FIFO. If we use weighted fair queuing and adjust the weights appropriately, we will get different kinds of service. Now, when we talked about weighted fair queuing before, we talked about different traffic flows going into a queue and drawing from those queues. Here, the different traffic flows are the different kinds of service. So we'll have a different queue for premium, regular, best effort, expedited, and so forth. And what we'll do as traffic comes in to a router is we'll use the markings on the packet, the DSCP code points, to map the traffic to the appropriate queue so it'll get the service it wants. We're just going ahead to look at that in a little more detail. Here is a picture of a router here, so you can see what is going on. And we have three kinds of service here. I have expedited forwarding, default forwarding, and assured forwarding. So they're going to be 3 different queues. Packets as they come in, we'll look at the markings on them and put them in the right queue. And a weighted fair queue scheduler is used here. And you can see that I have different weights placed on here. The expedited forwarding has the highest weight. That means that we're going to draw up to 8 packets from that queue for every 1 packet we draw from the default queue. So if there is any traffic in this queue, it will go through preferentially more quickly. And assured forwarding is somewhere in between. It's got a higher weight than the default best effort traffic, but not as high as expedited. So there are a couple of things to note here. The first is that the services, the way differentiated services work, is services are defined as per hop behaviors, so they're behaviors at a router. There's in fact no guarantee of the service you'll get when you stitch many routers together and look across the network, the entire network. It should be better, but depending how many routers you go through, we don't know exactly what it will be like in terms of guaranteed rates and delays. And the other thing is, as you might have guessed, to make expedited forwarding worth it, you need to make sure that there are only small amounts of high priority traffic on your network. So it's not like we can make all traffic be expedited traffic and expect to get better service. If we want it to get better service, we really need to make sure the queues here stay small. So even though it has a higher weight, we'll only want a small amount of traffic to go through. So that will be the VoIP for the VoIP call, not your streaming video, for instance. Okay, so now we've seen those 3 components of the architecture. That's what there is to differentiated services, and you've seen how we can put the pieces together to treat your Skype traffic differently than your BitTorrent traffic. Now, quality of service in this fashion has been rolled out gradually across the internet, but it's pretty slow going for a couple of reasons. And this is sort of one of the unfortunate things about quality of service. The first is that it provides value, the most value, really when it's deployed across the entire network. It doesn't do you much good if quality of service is deployed across your ISP, but not the ISP of the person you're talking to. So you're not going to get appropriate handling in their network. So, this is sort of one of those situations where if you don't have it everywhere, you don't necessarily see the great value. The second problematic issue is that quality of service is fairly tightly tied to pricing and economics. If we don't have some kind of pushback, then there's really no reason all applications and users shouldn't say that all of their traffic is high priority. I mean, I don't know about you, but my traffic's certainly high priority. So I would just like to configure my router to mark everything high priority. That won't work, obviously. We need some kind of pushback here. Often that pushback will end up being reflected in pricing somehow. And this just complicates the rollout of quality of service in the internet. For this reason, the deployment of quality of service has been quite slow and difficult, but it's ongoing and we should expect more of it in the future. G'day viewers. In this segment I'm going to talk about rate and delay guarantees for quality of service in the future internet. So we've talked about differentiated services, which provides different kinds of treatment, preferential treatment for different kinds of traffic flows. But in this segment, we want to go beyond that and talk about how you would guarantee performance for different traffic flows across the network. This is to provide a kind of hard quality of service where you get firm guarantees for your kind of traffic, regardless of what everyone else is doing. And it's something that might be used in the future internet one day. For a little bit of motivation, just consider what we've talked about so far. We've gone through Skype scenarios and BitTorrent and so forth. But sometimes what you would really like is a guaranteed service. And this is a service that's more like the telephone network. In the telephone network, when you put bits in, it's as though they go through a pipe, they come out with a well-known rate and a well-known delay. In fact, you get this minimum rate, well actually you get a fixed rate with the telephone service, and a maximum delay, again it's fixed with the telephone service, regardless of what everyone else is doing with the network. Why might you want such a strong service? Well, you might want it for different kinds of hard real-time users. For instance, consider here that you've got a robot at the other end or something you're controlling. It's not going to be too good if control traffic to or from this robot, can't get through just because someone else is playing their video, or does get through when it arrives a few seconds too late when you were meant to turn the corner a while ago. If you're really going to be able to operate that and other services over the internet, as well as classic services like voice over IP under very stringent delays, then you would like to have a network that can deliver these strong guarantees. Now, the question really is just, how can we do this? I mean, actually, can we do this effectively? You could certainly build your own network. You could provision a dedicated service. I mean, almost set up a different wire or a different network for this traffic where you wanted the guarantee. That would give it a certain rate, and if you fix the path, you'd get a certain delay, and especially if no one else could use it. But that would be expensive. I mean, the whole point of networking the way we do it with the internet, and we use statistical multiplexing and packet switching, is to share the bandwidth. That makes networks much more cost effective. So the real question here is, can we have a statistical multiplexing style network where we use packet switching, but at the same time get some hard guarantees? So we could make it look to this device here like it really had its own guaranteed network. Well, the answer is yes, and I'm going to show you how to do that. At least I'm going to sketch this kind of quality of service in the coming slides. So I'll just go through the various components. Before we look at rate and delay though, there's one point I need to make. That's about admission control. So the setup here is that we have a flow F, and we want to be able to guarantee a rate. It should be at least R megabits per second. It might be more than R if no one else is using the network and we can get more traffic through, but no matter what happens, we want at least R. Similarly, the delay should be at most D seconds. It might be less than that because no one else might be using the network, so we might get our traffic through with a minimum of queuing. But even if everyone else is going crazy, our delay should not exceed D seconds. Now, to do that, we've got to decide, if someone comes along and says, hey, I have this flow and I want this rate and this delay, we need to decide whether we can admit that flow to the network or not, and whether we have to reject it. This is what's called admission control. It's really like using the telephone network. When you make a call, if you're able to get a dial tone through to the other side and someone picks up, the network has accepted your call, and it should be sending traffic through with a fixed delay and making sure you get the bandwidth you need, at least in the classic telephone network, before it was all implemented with voice over IP. Now, on the other hand, it's possible sometimes that you might try and ring through. If you've ever tried to ring through on Mother's Day internationally in the old days, you just might not be able to get a dial tone on the other side. The network would be blocking your call. There's not enough capacity for it to admit your call and make sure it can give everyone the bandwidth that it's promised. So it would reject your call or block it. This should happen infrequently, where you don't have a very well designed network and you're not going to have very many customers. But it could happen. The key point here is that to be able to make guarantees at all, we need admission control, because we need some way to control the load in the network. Otherwise, we could get overloaded and not be able to meet our guarantees. So assume we have admission control. Now I want to move on to rate and delay guarantees. How are we going to do it? First of all, rate. And we're going to consider a delay at a rate guarantees, at a router, one router. And then we'll move along the network path. So here's our router. It's down here. It's in our usual box. Now we have a flow here, flow F, that I want to concentrate on. The router has a weighted fair queuing scheduler. You're just going to need a scheduler that's more complicated and more powerful than a FIFO scheduler to be able to provide any guarantees. We have, going out here, a link that has 100 megabits per second of bandwidth. It says there. So I would like to know what kind of rate guarantee we can give flow F through this one router. What do you think? Well, there's weighted fair queuing. There's some number of other flows. We're not quite sure yet. We can see that this flow has a weight of 10 and the other flows have different weights. Well, what could we do? Actually, I need to tell you a little more before we can really work out a rate. So let's consider, first of all, the case where we simplify weighted fair queuing and we just have n different flows here, including flow F that we care about, and each of these flows has weight 1. Okay, well in this scenario, if you remember your weighted fair queuing, you would expect that each of the flows is going to get an nth share of the bandwidth under load. That means if all of these queues are full, each flow is going to get 1 out of n packets, 1 out of n times it's going to get to send its packet. If the other queues aren't full for some reason, someone's not using their share, everyone else will get more, but you'll get to send at least one out of every n packets if all packets are the same and everyone has weight 1. So if you like, we could divide the 100 megabits per second into n shares and everyone's going to get one of those. That's the case where there are n flows with weight 1. So now let's see if we can do our weighted fair queuing example. Suppose now our flow F that we're interested in, it has weight 10. And we don't know how many other flows there are here. Actually, it turns out it doesn't matter. But we do know the sum of the weights of all flows is 100, I say here. So here are all of the other flows. Actually, I mean all flows, including flow F. If we sum up all of their weights, that's equal to 100. That's what we know. Well, if flow F has a weight of 10 and the total weight is 100, actually flow F is going to get 10 on 100th parts out of every 100 packets, say they get to be sent. Flow F would get to send 10 of them times 100 megabits per second. That's 10 megabits per second. So flow F would be guaranteed a rate of 10 megabits per second in this scenario. Let me just clean it up here. Here it is. So if you think about that, you might have to go back and review your notes about fair queuing. But given that the weight of this flow F is 10 and the total weight is 100, what it means is that we're going to get 10 out of 100 shares of the output bandwidth in terms of bits. And 10 out of 100 shares, or 10% of this output link, is 10 megabits per second. So yay, we have a guarantee. Let's see if we can get a network guarantee now. Because I don't want to guarantee a single router. I want to guarantee across the whole network path. You can see the whole network path goes through here. And so far, we've just done this one router here that's shaded in pink. However, you should realize, if you think about it a bit, that if we make the same condition at every particular router, I mean, if I have a guarantee of 10 megabits per second at the first router here, and 10 megabits per second here, and 10 megabits per second here, I will get 10 megabits per second along the whole path. So what we want to do is, for every router, set the weights to make sure you get 10 megabits per second, say. So I've written this a little more generally here. The condition for every router to get R megabits per second is just that you set the weight appropriately. So you need to make sure that the fraction of the weight, fraction of the total weight, that is the weight that we give to the flow F, divided by the total weight at that router. I here is the number of different routers, so this is going to hold at every router, times the output link should be should be equal to R, and that will give us equal or more to R, and that will give us at least R megabits per second, no matter what the traffic patterns are. So you can see here you could have 10% of a 100 megabit per second output link and you get at least 10 megabits per second, or you could have 20% of a 50 megabit per second output link, and you get 10 megabits per second. And if you got this at every router, you will get it along the path. Okay, so now we know how to get a rate guarantee. What about a delay guarantee? This is actually the trickier case, so let's move on to this. And really, we want to know about the queuing delay. The delay we're going to get is going to be at least the propagation delay and the transmission delay to packetize things, to send individual packets as they're stored and forwarded at every router. That's a minimum. You're just not going to beat that because the signal has to propagate. Our question is, how much larger than this latency is the delay going to be because of queuing? Given that we already have this situation where we've made a rate guarantee, it'd be wonderful if we made a rate guarantee and that meant if we'd set all of the weights correctly and we were getting at least our R megabits per second, that meant that we incurred no queuing, say. Well, that's not the case. If you think about it, you should realize that the queuing delay you're going to get at a router depends upon the characteristics of the traffic flow. Now, I might be getting R megabits per second through the router. But if my traffic, the instantaneous rate is going to go up and down, just depending on the statistics. If this is a robot, it might be generating traffic at different rates depending whether things are being moved or not. Well, if the rate exceeds r megabits per second over short intervals, whenever it exceeds that, the queue inside the router may well grow. If other people are using their shares and we're only getting our minimum, the queue will grow. If the queue grows, the delay will grow. So the queue built and the delay is going to grow. So the insight here is that if you want any delay guarantee, which you can state conclusively, then you need to shape the traffic to enable a guarantee. To do that, we need to constrain the burstness. And I think you know how we're going to do that. It says so there, we're going to use token buckets. Great. We knew they were useful for something. So here's our token bucket picture. So what we're going to do is assume that the traffic flow F is shaped according to an RB token bucket. What that means, if you recall your RB token bucket, is that we will get a long-term rate of R megabits per second, and we are, in addition to that, allowed to send a short-term burst of up to B bits, as long as we don't exceed that rate over time. So if we send a burst, we're going to have to slow down after a while to recover. So now let's think at one individual router, what kind of delay guarantee do we have if we change our traffic so that it is now shaped by an RB token bucket? So if you like, what's coming in here is an RB token bucket. And we have the same setup inside the router. We have the different flows and we have a weight here. It happens to be 10 here, and we have 100 megabits per second output link here. So we just need to work out what delay we're going to get out. What do you think? It's actually difficult to think about what delay we'll get out. It really depends on the details of exactly what packets are sent when by the source. Now, what we can say though is that the worst case for delay is going to be if someone sends a burst and the traffic arrives all at once. They just go blat, and a burst of B packets arrives all at once. If they were spread out more over time, they're going to cause less of a queue to build up, and it's going to be not so bad in terms of delay. So the worst case is sending as fast as you can traffic all at once. That's this burst B. Well, if that arrives at the router, it's going to fill up the queue. Say it arrives instantaneously, the input link is really fast, and we might fill it up to here. That last packet, that's going to experience a queuing delay of up to B on R seconds. So the burst size divided by the drain rate, it's going to take that long for this packet to go through the queue and get out of there on the link on the other side. So that's the worst case delay that can be experienced. Since we just blew our burst all at once, we can't make this queue any bigger. It can only fall over time. So no one else is going to get a bigger delay. So B on R is the worst case through a single router. What about the delay across all routers on a path? Because again, I care about the delay not just for this router, but for all of these routers. And you can see I've shaded them all in pink because I care about the delay across the entire path. Well, actually, this is kind of tricky to work out. This is difficult for us to do in detail. And the reason for this is that all of these routers, so as I go through one, I might get a delay, another one, I might get another delay, and it's going to add. So unlike the rate case where they just all had to be large enough and we really cared about the minimum you get along the path, here for delay it's additive. So all of the routers are going to add their delay. Now we could just say, okay, one router, it can't be any worse than B on R. So for the whole path, if you've got n routers, it's n times B on R. But that can be quite a large number. So this can be a very loose balance. It's not really very useful in practice for coming up with a good guarantee. So I'm going to give you an intuitive argument in the following slides about the delay band we'll get, which is going to be much better. It's actually a kind of cool argument too. So observe that if the traffic is perfectly smooth at rate R, there's no burst coming in, then you don't get queuing delay at any of the routers. So if the traffic is perfectly smooth, we send one packet in here, there's no queue, and so it goes out immediately into the next router and then the next router and the next router. Here, from the source, we send another packet, but we don't send it immediately. We wait so that we're pacing out the packets at rate R. That means that by the time the second packet comes in here, the first packet is cleared out of the queue. So the second packet goes right to the beginning and it's ready to be forwarded again. And so on at the next router and the next router. So we're in good shape here. We're getting no queuing delay. So no queuing. The only latency that we'll end up with is the old propagation and transmission delays to send packets along this path and through all of these store and forward routers. But no queuing. That's great. Well, that was the best case. What about the worst case? What about if we don't smooth traffic, but we send a burst? Let's send that horrible burst. So the burst goes right in here into the first router. All of these packets come in at once. Rats, that's pretty tricky. So we said that you can pay a queuing delay of up to B on R going through this router. Now, here's an interesting observation. Suppose we do that. Well, the traffic might go into the router as one big burst, but it's going to come out smoothly. If smoothly, in the worst case, it will come out one packet sort of appropriately so that it's been sent out at rate R. Why? Well, because we guaranteed that rate. It could come out a little faster, but in that case we won't get the whole queuing delay of B on R. It'll come out nice and smoothly at rate R if everyone else was using their bandwidth and we were just getting our R megabits per second. So if it comes out at rate R, then guess what? It's not going to queue at the next router. No queuing. So it will then go on to the next router where there's no queuing and so forth. So the interesting observation here is that because as you pay for the burst it's smoothed out, you only pay for the burst delay once. It might not be this router I've chosen here. You might end up paying for some reason in the middle router or the end router. Or you might pay half across two routers, but you don't pay for the burst more than once as it's delayed and smoothed. So interestingly here we end up with this situation. The delay, that is the queuing delay across all of the routers is B on R, the same at a single router. And of course our delay then has these various latency terms to set along the path, plus the B on R queuing. Pretty cool, huh? Okay, so just to recap, we've now come up with a strong quality of service result, which if you were designing a network could let you provide hard rate and delay guarantees. To do that, we needed all of these pieces. We needed a network with traffic which was shaped according to RB token buckets, and we needed routers which implemented weighted fair queuing scheduling rather than first in, first out. And we had to adjust the weights, and from all of those weights we could compute the rate and the maximum delay we'll get across the network. So we got those delays even though we have a network with statistical sharing, so all other traffic sources can take advantage of whatever packet, whatever bandwidth is available just by packet switching. So when we do all of this, we end up with these guarantees and the guarantee is for the minimum rate. You might get more if someone else isn't using the network, and the maximum delay. You might get a better delay if there's less traffic that's in the way. And it's important to realize when I say guarantee, I really mean a guarantee here regardless of what the other flows are doing on the network. Doesn't matter if they're crazy or not, you still get to meet your guarantees. So that is how we can provide strong quality of service in a network. G'day viewers. In this segment I'll introduce the topic of network security. So network security is an interesting topic for us because it really spans all of the layers. And the reason for that is that each layer can introduce its own risks in terms of security. So as we look at the different material in this topic, we're going to cover all of the different layers. Our focus as we work through all of the material in this unit is really about different kinds of security designs that protect against different kinds of threats. Often the mechanisms we look at in the designs will build on cryptography. It's a very powerful set of techniques which can be used to provide different kinds of security properties. So I'll tell you a little bit about cryptography, but really our focus is building on it. And I also want to stress this, that what I'm providing you with is just a brief overview of the topic. And we're doing that because security is an important topic these days in networks, but it's usually handled as part of other courses. You can take whole courses on security. So we can really cover relatively little in the time we have available. I'm going to go through some of the material fairly quickly, and it's really to raise your sense of awareness on the topics and the issues and give you a sense of it so that you can follow up and take a complete course if you're interested. Okay, so the first concept that we'll come up with in security is that of a security threat. Now, this is really a very important part of understanding security. And the reason is this, that we all talk about security. Have you read the papers lately? There's bound to be something about security. But security is really a little bit like performance in that it means many different things to many different people. There's many different kinds of security. So if we want to have any kind of sensible discussion about security and different protocols and so forth, we need to define carefully the kinds of properties we want in terms of security. And this is often given as what's called a threat model. We state either the properties we want or the different kind of threats that might cause those properties to fail. So that is, it says here we're going to list the dangers and the attacker's abilities in terms of breaking the security of the system. And this is necessary because without an understanding of the dangers we're trying to protect against and the attacker's abilities in terms of getting through them, we really can't make any kind of sensible assessment of the risk that's involved in the system. Just to give you an example, so here are some example threats in this table. And really one reason I give you this table too is to give you the sense that security is not all about encrypting messages so no one can read them. That's the first thing we think of when we say security. That's really this threat here. The threat is given over here in this column. The threat is that someone else will read the contents of your messages. Really, the attacker here is an eavesdropper. So the first threat that's listed here in this model is that an eavesdropper will be able to read the contents of our messages. And the ability they have to do that is simply to intercept messages. Exactly how they do this, we don't know, but we assume that they have this ability. So they're out there somehow able to tap into the network, really just to listen to what's going on. This is what we would often think of as classic security, protecting the system. But there's actually much more. You might think of, for instance, intruders who are inside your system because they're at a compromised host. And the threat is really the ability to tamper with the contents of messages that are sent from your machine. There could be other threats too that we're not going to cover because we're focused on network security, like theft of information from your machine. Here's yet a different kind of threat. And the threat here is not so much reading the contents of a message, but tricking someone into giving you information when they really wouldn't have given it if they'd known what was going on. So the attacker here is an impersonator, and an ability that's used a lot is something called social engineering. You might call someone up and claim to be someone else and trick them into revealing information. The same sort of thing can go on the network. It's all of these phishing attacks and something else. And here's yet another threat just to provide something that's really very different than encrypting messages. The threat here is one of availability. The threat is about disrupting the network services. Who might do that? Well, an extortionist. Someone who had a botnet or many remote machines which could somehow jam up the network by sending a lot of traffic, for instance. This is also a kind of security. It's a very different threat than encrypting messages for secrecy. And as so now we have a bit of an understanding of the different threats and there are different kinds of security. As we assess security, we'll often take a risk management point of view. And this is because security is really a negative goal. That makes it hard. You're trying to stop something happening. So you're trying to ensure positive properties by making sure that you don't let anything bad happen. Well, how are you going to make sure that's the case? The difficulty here is that security, a system, is only as secure for whatever property you care about as the weakest link in the chain. So if we're trying to understand the security of a system, often we might take a risk management point of view and look at all of the different risks which will undermine the security of the system and see how big they all are. And the reason for saying this, of course, is that we're going to use cryptography. And if the designs are well put together, if the primitives are very strong, you won't be able to break the cryptography itself. However, the system may not be secure. It could well be that there is a design flaw not in the pieces themselves, but the way they're put together. This is quite common, the way they're used. Or there could simply be a bug in the code. The design was fabulous, but someone made a mistake implementing it. Whoops. Or actually, more often than not, the weak link in the chain is something else. It's something in here, and guess what? It's you and I. For instance, people need to choose passwords to use all of these systems. If you choose very weak passwords or share passwords, you might compromise the security of the system, no matter how good the crypto is. So people are often viewed as the weakest link in security schemes. So just as an example of risk management and how everything comes to play, let's just think for a moment about 802.11. This is the kind of network that we would want to be secure against eavesdropping. So 802.11 security. Actually, early on, you probably heard that there were big problems here. Early on, there was this scheme called WEP. It stood for Wide Equivalent Privacy. It used cryptography. However, it turned out that the cryptography was really flawed in many different ways. People discovered this over time and found that these compromises weren't theoretical, they were very practical. Now you can download software packages which, if a network is using WEP, can just intercept messages as an eavesdropper and crack the security of the scheme, get the network password, and be able to read everything within a few minutes. So really, this is not a strong defense against security. This is well known, and today the standard is not to use WEP, but there's a new scheme. We'll look at this eventually. This is WPA2 or 802.11i. This is a much better cryptographic design, and as far as we know, it's computationally infeasible to break this. Computers would just have to compute for so long to read messages that it's not going to happen. So we've taken a major step up here. My question for you is, does this mean that 802.11 is secure against eavesdropping? I have to say what the threat is. So against someone eavesdropping and listening into your messages. Is it secure against that? Well, not necessarily. And the reason is that there are many possible threats. In fact, I've listed some here in this table here. And you can see that the one we've been talking about with WEP and WPA2 is intercepting messages from the outside and breaking the encryption. We shifted that from very easy to very difficult by moving from WEP to WPA2. However, there are many other ways that someone might successfully be able to eavesdrop on your messages. They might be able to guess your Wi-Fi password. This is often possible. It shouldn't be if you've chosen a good password for your wireless network. But there are many networks out there that might still be running with the default network. You know, many networks you can see already have Linksys or something as a name. So often what was shipped with the system hasn't been changed. Or your choice of password might be fairly obvious because it's related to your birthday or something like that, or other passwords you've used. So often it will be possible to compromise the system here. Even if you can't do that, it might be possible, and this requires more access, to get the password from a computer. Maybe when you're not at home, you have your laptop around work or somewhere, and someone is able to look at your laptop and get passwords off them, or your mobile phone, and so forth. There are lots of passwords on all of these devices. This might be possible. It seems a little harder, but your home network security could be broken, so people could eavesdrop into it by people outside your house gaining access to the password, where it exists in many other places. Failing all of this, you could physically break into the home where you have physical access to the device, in which case you'd be able to find out what's going on. This seems like much more effort. I've listed this as difficult. Seems very unlikely compared to the others. What's the point of all of this exercise? The point is that there are many possible threats which would lead to the same outcome of people being able to read your messages. So if we want to understand if a system is secure, we really need to consider the range of threats here, because the weakest one will be the issue. We've strengthened with WEP. We've moved from WEP to WPA2, and we've addressed this threat much more effectively. But there are other threats. So in fact, 802.11 is not secure in any absolute sense. Rather, it's more secure with WPA2 than WEP. So if you care about security, you should get used to thinking in terms of this way, because things like physical access matter. as much as the security protocols sometimes. Okay, so let's move on. I've completed most of an introduction. As we look at security designs, we'll actually talk about, we won't so much go over the details, but we'll see cryptographic schemes in use. So cryptographic schemes are part of cryptology. Cryptology has a very rich history. You know, these are all of the classic stories you'd read about spies in the military sending secret messages from one to the other in code. This is great stuff. Cryptology or cryptography comes from the Greek for hidden writing. So there are really two parts to it. The cryptography part is the encryption of information, coding information, you know, so you can send spy messages with no one being able to read them. The flip side of this is cryptanalysis. This is really breaking the code, so obtaining encoded information and possibly some unencoded information that goes with it, and really working out how the scheme works so that you can break it, and someone, like that eavesdropper, can successfully read messages. Now, for all of the modern codes we will look at, the emphasis is on designing codes which are considered computationally infeasible to break. That is, it's not impossible to break them in theory, but you'd have to compute for so long it's just not possible. So the emphasis is on coming up with designs which are clever in this way, rather than, for instance, obscuring the algorithm for encoding information, writing it down and just letting no one find it, and assuming if they can't find it, they won't be able to decode it. Or using a key that's, for instance, the time of day, and just not telling anyone that, because if they knew that, they'd be able to break the scheme. That is called security by obscurity, and our focus is elsewhere for all of these other schemes. So we'll see some of the designs in the following videos, and another point I would like you to take away is that while we're going to use encryption for concealing information from eavesdroppers, encryption is actually much more useful, and in most of the protocols we look at, we'll be doing more than concealing information from eavesdroppers. For instance, and this is pretty cool, you can use encryption to prove that a message came from a real sender, the sender you thought it did, to prove that the remote party you're interacting with is who they say they are, or to prove that a message that came over the network not only hasn't been read by an eavesdropper, but hasn't been altered while it's in transit. These are all very useful properties, of course, and we'll want them in many of the schemes we put together. I also want to make the point that designing cryptographic schemes, good ones, which are secure in terms of the properties we want, is very difficult. I don't think many of you would try and expect that you could go and design your own cryptographic scheme and put it to use and it would survive attacks. None of us are likely to do that. So rather, we're likely to use approved designs. And this is what you should do in any system. But it's also important to use them in an approved way. Many security compromises are the result of using sound techniques and primitives, cryptographic primitives, but in an unusual way, a way which wasn't approved, which often led to some subtle flaw which let someone completely defeat the system. So it's important not only to use approved designs, but to use them in the right way. Oh, okay, and one more point to make, just as our lead into security. And that's to give you a sense of the internet and where security fits in. Actually, the internet's a little different in terms of security. Most of the key protocols, all of the TCP, IP, DNS, all of the protocols we know and love, they were developed well before security problems became a pressing issue. When they were developed and deployed and first used, the internet was a smaller and more trusted world. Initially, it was, almost a bunch of academics talking to one another, you could think, is a reasonable proxy for it. In this world, it was smaller and more trusted, more friendly, so security was simply a less pressing issue, and many of the protocols lacked any kind of reasonable security protection. The world has changed today, and now we know that we need strong security in the internet. There are a lot of nasty people out there that if you use the internet, you would want to defend yourself against. And it's a big internet. We have clients. You will often use your host to talk to unverified servers out there who you don't really know who they are. You just hope they're not going to do anything nasty. Servers are often talking to clients that they've never met before, so these clients are anonymous in some sense. We just hope everything's good. And to deal with all of the various problems that would arise, security has been retrofitted into all of these protocols. They're much stronger than they used to be, but retrofitting security is not ideal from a security point at all. It's much better to design security as part and parcel of the scheme. Just as an example, we often want compatibility too. So many protocols will downgrade to the earlier version. Well, just think of that as downgrading to the insecure version. If you're an attacker and you could either use the secure version of the protocol or the insecure version of the protocol, which version do you think you would try and talk to a server with? Well, the insecure version, of course. So there's a bit of a tension there with retrofitting protocols. Security really needs to be built in from the start. Okay, so that's our introduction. So far we've talked about some of the threat models, the concept of threat models. Next, we're going to cover our introduction to crypto and talk about how you can provide confidentiality and authentication of messages. And after that, we're going to go through various material. You'll see how crypto is applied in different ways at different layers. So you're securing 802.11 through securing the web, for instance, as well as the DNS and new constructs like virtual private networks. And we'll also see some security problems that have little to do with crypto. Firewalls and distributed denial of service attacks are really more about preserving connectivity properties. And that's why they're not handled so much with encryption, but nonetheless, they're important security properties in the internet today. Great, so let's get on with it. G'day viewers. In this segment I'll talk about message confidentiality using cryptography. So what we're really trying to do in this lecture is understand how to encrypt information that's sent over the network to provide confidentiality. This is the classic threat of eavesdroppers being able to read messages and spies wanting to be able to send coded messages that can't be understood. Of course, we're going to get a little more modern and think about how it's used in networks. I'm going to tell you about two different kinds of schemes that are used to provide encryption for confidentiality. And they're symmetric or secret key schemes and public key or asymmetric encryption. And as I go through this, we're going to treat the crypto functions themselves as black boxes. So this is really more about how to use some of the primitives rather than exactly what bit operations are used inside the primitives themselves. It's very interesting to understand more about the crypto primitives themselves, but to do that, we'll need to go over to a security course. Okay, so one of the first things I want to talk about here is the goal and threat model, so we understand what kind of security it is that we're trying to provide. The goal here is to send a private message from Alice to Bob. So Alice can send that message across the network to Bob and it will remain private. No one in the middle, Eve, will not be able to understand the contents of the message. This is called confidentiality. And you can see I have the diagram here. Alice is sending that message to Bob. And Eve here should not be able to read the contents of the message. That's the threat we're trying to protect against. Eve here is what's called a passive adversary. That means that she just gets to observe the messages as they go to and fro. She doesn't get to inject any of her own messages or tamper with them or do anything like that. So the threat model is simply that by observing them and looking carefully, she'll be able to understand what they say. If they're just sending the plane, well, that will be pretty obvious. So we're going to have to do something about that. Here's what we'll do about it. We'll use an encryption and decryption model. So this figure here shows the general setup for encryption and decryption to provide confidentiality. Alice is here over on the left, Bob's here over on the right. Alice and Bob, by the way, are standard names in cryptographic schemes. They were invented by Ron Rivest in some of his early papers, and now they're just used all over the literature. So Alice is going to send to Bob, and the message itself is called this plain text. So here's the plain text here. I love networks, of course. What else are you going to say? Now, we can't send this plain text over the network, or Eve's job in the middle will be trivial because she'll get the message. Instead, we want to encipher it and send what's called the ciphertext. That's this scrambled message here. So what Alice will do is she will encrypt the message before sending it. And she will encrypt it using this box here, this function, which we'll look at some schemes a little bit more in a moment. Once it's encrypted into this ciphertext, Eve will see the ciphertext because she's observing all of the network messages, but she won't be able to relate it to the original message. The encryption is parameterized here by a key. Now, if Bob has the same key, he'll be able to decrypt it and get back to plain text. And under this model, we've then sent a message across the network from Alice to Bob, but Eve hasn't been able to read it. Well, let's talk about that a little more and begin to go into some of the details and look at the schemes. The picture gives you the general setup. You should realize here that the encryption operation is a reversible mapping. So the ciphertext, in some sense, is the plain text. It's just confused. But there's a one-to-one mapping between them that can be reversed. So we can map a plain text into any plain text into its corresponding ciphertext, and any ciphertext into its corresponding plain text. We also assume here, and this typical assumption, is that the attacker knows the algorithm. This dates actually from the 1800s as a general principle, in that you don't want the security of the algorithm, of the scheme, to rely on the security of the algorithm. Because if someone leaks the details of what the algorithm is, then it's all over. Instead, what happens is the algorithm is assumed to be widely known, but it's parameterized by a key. This key is secret, so it has to be held secret. If the key is compromised, then you can use the same algorithm with a different key. And an attacker, even if they were able to break the scheme with one key, they shouldn't be able to break it with another key. Of course, the problem here is that the keys need to be distributed. In some sense, we saw previously that Alice and Bob both had a key, so some kind of key needs to be distributed. This often turns out to be the Achilles heel of encryption schemes, because you've got to be able to get the key somewhere before you can really start sending encrypted information. And that's hard, since you can't easily encrypt that key to send it, because you're bootstrapping the system. Okay, so I'm going to talk briefly about the two different kinds of encryption schemes that you'll run into, and their pros and cons. That's our job for this segment, to find out about these two kinds of encryption. And they are symmetric key encryption, or secret key encryption as it's called sometimes, and public key encryption, or asymmetric encryption as it's called sometimes. I'll go into both in detail, but in a nutshell, the difference is the way the keying and the encryption is done. In symmetric key, Alice and Bob both have the same secret key. So they're sharing a key, and it's got to be secret. If you know the key, everything's over. And encryption is really mangling the bits of a message using this key in some way, making them unrecognizable by mixing them up. An example of a symmetric encryption scheme that you might have heard of, by the way, is AES, the Advanced Encryption Standard. Okay, the second kind of encryption family, and I'll tell you a little bit more about both of these in a moment. The second kind of encryption family is what's called public key encryption. Here, the keys are different. This is really pretty funky. Everyone has a key, so Alice and Bob both have their own key, only each key is split into two parts. It's split into a public part, which can and should be widely known, so everyone can see the public part of a key, and also a corresponding private part. That private part needs to stay secret. Only the owner of the key should have this. If they lose it, it's all over. Encryption in this funny split scheme is actually based on different kinds of mathematical problems. You might have heard of one well-known public key scheme called RSA. That scheme is based on the mathematical problem of factoring. It's very difficult to factor very large numbers that are the product of two large primes. So that difficulty allows the construction of a problem that, the division of a problem into two parts. It's very easy to take the mapping one way and very hard to take it the other way. And that's going to translate into us having a key, part of which is public, part of which is secret. So let's talk about both of these schemes in just a little bit more detail so you can see what's going on. Here's the same general picture as I had before. So in symmetric key encryption or secret key encryption, Alice and Bob have the same key. I've called that here KAB, and you can see here it is. They both have it, and it's marked a secret key. They both have it, and they need to keep it secret, because anyone who possesses this key can read messages and send messages with the same cipher. And they simply go through the same motions that I've described before. They encrypt using this key. It moves from the plain text here to the ciphertext here. And on the other side, they decrypt using the same key, and Bob is able to get the plain text back. So that was symmetric key encryption. That's it. I'm not going to tell you the details of what's inside the encryption boxes, because that's really beyond what we can cover. Okay, the next one, public key encryption, or asymmetric encryption. This is a little stranger. So here's our diagram again, and the key concept here, the key difference is that Alice and Bob each have their own key, and that key is split into a public-private key pair. So there are public and private portions of the key pair. I've shown here Bob's key. So we have KB, that's the public part, and KB to the -1, that's the private part. -1 there is really sort of implying the inverse operation. So now, in this scenario, Alice is going to send to Bob, so we're interested in this direction. And for the keying arrangements, Alice is going to get to use Bob's public key, that's KB, to send a message to him. And Bob is going to have his private key, that K to the -1B here. So those are the keys we have. So here's how it works. Alice is going to perform an encryption operation to get the ciphertext, but to encrypt she simply uses Bob's public key. Now actually Alice is doing this to send to Bob, but since this key is public, anyone can get it, should be able to get it. And since they can get it, anyone can encrypt a message that's sent to Bob. And when it's encrypted with this, it will be ciphertext that no one on the network, like Eve, should be able to understand the contents of. So that was the first step. The second step, as it goes over here, is that Bob decrypts it with his private key, and he can get back the plain text. Now that private key, KB to the -1, is a key that only Bob has. So he hasn't given this key to anyone else, not even Alice. So he's the only person who is able to decrypt and read this message. So we've created a system where anyone can send an encrypted message to someone and only they can read it. That's public key encryption. So one of the difficulties, the key difficulty really, with these schemes has to do with key distribution. Okay, it's a big problem, a major problem on the network. Now, if we were all just spies, and maybe it wouldn't be such a problem actually, because presumably there are a small number of spies and we have long-standing relationships and we can set up a key between us ahead of time. Maybe we needed to meet to ensure there was some trust initially. On a network, however, hosts will often want to talk to other parties who they've never met before and they have only the faintest notion of who they are. So to do that, we would always like to be setting up new keying arrangements. We can't really do that. It's problematic with symmetric key encryption. And that's because, before we can use symmetric key encryption, you need to set up a key with someone. So you sort of need to know them ahead of time to set up the key, but we're always meeting these new parties. This is where public key encryption really comes in handy. You can send a message to someone, and if their public key is available, they can publish the key on their web page. Everyone can know it. So public key encryption would seem to go a long way to help us with setting up key arrangements, because servers can publish their own public keys, and that way you can send a message to the server that no one else can read. This is great. We'll see later though that it has its own difficulties. And the difficulties really have to do with needing a trusted directory service to distribute the public keys. I mean, how do you know you have the public key for the server as opposed to someone else's public key? It's just a public key after all. So there's a problem between binding public keys and their identities. And we'll look later at how certificates are used to deal with this problem and make it a little easier to solve. These are used widely on the web, for instance. Okay, so now you know a little bit about symmetric key and public key encryption. To compare them a little more, I'm saying here really that they have complementary properties. We covered this property, key distribution. For a symmetric key scheme, it's hard because you have a key per pair of different users or hosts. There are a lot of different pairs, so there are a lot of keys, and every time you want to talk to a new person, you need to distribute these keys. With public key encryption, it's easier because you only have one key per host, not per pair of hosts, so that's a lot fewer keys. And For the host, the public portion can simply be written on a web page or made available anywhere, so we can distribute it widely. We want to do that. We want everyone to know everyone else's public key. Well, the flip side of this is this other property, runtime performance. Now, it turns out that symmetric key encryptions that mangle bits are relatively fast. These days you can encrypt with symmetric key schemes quickly enough to be able to send data at high rates over the internet, all by doing it in software. You used to have crypto boards and other kinds of hardware support, but these days even your microprocessor instruction set has a little bit of support for encryption, and you can just encrypt in software and it's usually fine. On the other hand, for public key schemes, encryption tends to be very slow. And I'm talking about orders of magnitude, maybe 3 orders of magnitude slower than symmetric key encryption. So you'll tend to want to send infrequent messages or small messages with public key cryptography. The catch here, of course, is that we want to get the best of both worlds. Public key was very useful for keying arrangements, but we really want the performance of symmetric key encryption. No one, by the way, wants to pay extra for security. We all like security for free. We don't want it to slow us down or inconvenience us in other ways. But it turns out that we actually can come up with a winning combination that gives us the best of both of these properties fairly well. And it works like this. If you think about it, actually, maybe you could work it out ahead of time. That would be a good exercise. But we can do this. So if Alice is trying to send confidential messages to Bob, she can begin using public key encryption. She can send a very small message to Bob. That can be a secret key. So this might be 256 bits. Once she's done this, Alice and Bob share a secret key. Yay, that's exactly what we wanted. Then Alice and Bob can switch over to symmetric encryption and use that to send many large messages very quickly, all using the shared key that we've now established. So this combination, this technique is used very frequently in practice, and this key which they generate just to use, the symmetric key, is called a session key. So a session key is typically generated and used over the short term just for a particular session. And the next time you want to do it again, you generate a fresh session key. Okay, so now we've seen how to encrypt messages for confidentiality. We've got the basics of that. We'll see how to apply that to different schemes later on. G'day viewers. In this segment I'll talk about using cryptography to provide message authentication. Okay, so what we're talking about doing now is using encryption, but encrypting information to provide authenticity, to make sure messages came from the correct sender, the sender we thought they came from, they're authentic, and integrity. These properties often go hand in hand, making sure the message hasn't been altered. So often these are actually different properties than confidentiality. Often confidentiality of messages isn't enough on its own. So a little bit on the goal and threat model, just so we're clear on what it is we're trying to do. Our goal here is to let Bob, who just received a message from Alice, at least that's what he thinks. Bob would like to verify that the message really did come from Alice and that the message has not been changed in the network. These properties are called integrity and authenticity. And the threat here that we're trying to protect against is that Trudy, here in the middle of the network, will tamper with messages. You might notice I've changed from Eve to Trudy. Trudy, short for intruder, is an active adversary. So whereas Eve just listened to messages, she intercepted and overheard them, Trudy can interfere with messages. She can tamper with them, rewrite them, send messages of her own to either Alice or Bob. So Trudy is an active adversary. Now, here's one interesting thing. You might just say, well, wait a minute. We just did all of this unit on using encryption to provide confidentiality. That, really hid the message inside the network and everything. Isn't this enough? Haven't we really provided some of these properties that I just was going to talk about already? Well, the answer is no, obviously, because we're going to go through them a little more, but you might wonder why it is that encryption isn't enough. Let's go through a couple of issues and so that I can just convince you that encryption for confidentiality isn't always enough to provide authenticity and integrity. In particular, let's just imagine, as a thought experiment, what's going to happen if Trudy, as the message goes by in the network, flips some of the bits. the message really came from Alice, but it's been mangled now in some way. Trudy's flipped some of the bits. Well, Bob will get it. Bob's going to decrypt it over here. And, I mean, at least he will apply his usual decryption operation with the key which he shares with Alice to the bag of bits that came in. And what's going to happen? Well, this will probably happen. Bob will receive some message. The ciphertext which was sent, any ciphertext can be mapped to a corresponding plaintext. So even though Trudy flipped some of the bits, that didn't mean that Bob couldn't decrypt it. He could still decrypt it and get some message. So Bob will receive an altered message. This is a little worrying. Trudy didn't read the message, but she still kind of messed with what Bob got. Bob got this altered message. Now, you can see this is a bit of a garbage message, and Bob is just saying, And you might think that it would be very unlucky that Trudy could mangle the bits and cause a correct message to come out. So it's probably okay. Bob can realize that that's not a good message. But this isn't always the case either. Trudy can be more subtle in terms of how she flips bits, depending upon the encryption scheme. So in particular, it's often the case that encryption schemes will work with blocks of data. They will encrypt a block of bits at once and then move on to the next bit. And depending on the schemes, we have to be very careful here. Suppose we have a scheme that lets Trudy reorder the messages. You can see here the message, here's the blocks. They should have been sent 1, 2, 3, 4, 5 if they're all one big message and they've been chopped up left to right if this was one big message. However, you can see here Trudy's reordered them. She's just, she knows maybe what the block size is because that might be well known as part of the algorithm, and she's reordered them. Bob will decrypt this because Bob will decrypt anything that comes in to see what's there. And what's going to happen? Well, Bob will get a message. Here's the message he happens to get. Buy now, do not stop. Okay, so Bob goes away and does it. But that's not the message that was sent because we've changed the order. What was the message that was sent? Well, let's just write it out. If we rearrange these blocks to be in the correct order, the first block should be 1, so that's stop. Second block 2, do not buy now. Oops, that's a very different message than the one that Alice sent, that Trudy has somehow managed to happen. So we're really not going to want to allow Trudy to alter the message. We can see here, even though the confidentiality of the message is being maintained, no, Trudy was not able to read this message, but she sure messed it up in some way. So we would like to provide for integrity and authenticity to make sure the message only came from Alice and that it hasn't been messed with in the network. That's going to defeat some of these kinds of attacks on simple encryption schemes. How are we going to do it? Well, there are a couple of different mechanisms which are used to provide integrity and authenticity, and I'll tell you about them. The first is what's called a MAC. This is not medium access control. It's called the message authentication code. You might actually see people in networking sometimes talk about MICS for message integrity code or message integrity check. And they do that just to avoid the term MAC because MAC means something else in the context of networks. It was all about multiple access schemes. However, in all of the security literature, MAC is what you'll see for this concept all of the time. So I'm just using MAC here, and you'll just have to know which MAC it is from the context. So what a MAC is, here's the MAC. It's been added to the message. A MAC is a small token which is used to validate the integrity and authenticity of the message. So it's an extra bit, if you like. You compute the MAC and you send it along with the message. So you can see here the message goes. The message might be encrypted if it's confidential. It might not be encrypted if it can be public, and we didn't care if everyone sees it. But in either case, you compute this MAC, this extra token, and you send it along with the message. Bob will then receive both, and he will then validate the MAC to make sure that it passes, that this check passes. He'll compute it from the message and see if it matches what he received for the MAC. If it does, then he'll say the message is legitimate. It's not been altered and it really did come from Alice, and he can then process it. An example of a MAC scheme is something called HMAC, a hashed MAC. I'm not going to tell you any of the details, but if you're, I just mentioned this in case so that you can relate MACs to some schemes you might see in practice written down somewhere, or you could go look it up. Now, a MAC itself is really conceptually it's some kind of symmetric key operation. And so I've drawn a picture here that should look very like our encryption for confidentiality. What happens here is that Alice starts with the plain text and she runs it through some generation function for the MAC. This is just like an encryption box, only slightly different. It's parameterized by a key, and because this is a symmetric kind of operation, Alice and Bob share the same key. So this generation function for the MAC is going to produce the MAC, and it is not a very long message like the... Where are we? It's not a very long message like the message itself. It's a shorter token here. But either way, it gets sent along. At the other side, Bob runs the same computation on the message and sees if he gets the same MAC, and he uses this to validate whether the MAC check is correct, and so the message has been is authentic and has not been altered. Bob needs to know the same secret key to do this, so this key needs to be separate. So I guess just to recap here, what I'm saying is that this operation, because Alice and Bob share a key, it's going to let Bob validate that the message has not been altered and that it must have come from Alice, because Alice is the only other person who has the key, so she's the only other person who could generate this kind of MAC. However, you might notice here that this MAC does not let Bob convince someone else, say Charlie, that Alice sent him this message. And the reason is that Bob can also generate the MAC. So Charlie doesn't know whether the MAC and the message really came from Alice or whether Bob just generated it himself. So Bob can't prove anything to anyone else. So the second scheme that's used for integrity and authenticity is what's called a digital signature. It's, just the analogy is a physical written signature. The signature is going to validate the integrity and authenticity of a message. And just like the MAC here, you can see it replaces the MAC here. We're going to send it along with the message so that the receiver can check it. You might wonder what the difference is between a signature and a MAC. The difference is that the signature lets all parties validate. So you can see I don't just have Bob here. Well, I have a set of people here. They could all receive the message, check the signature, and validate that it came from Alice. An example that you might see around if you look in security schemes is RSA encryption, RSA used to compute signatures. So just to look a little more, here is what happens in a digital signature. A digital signature is effectively some kind of public key operation. The keys again have a public and a private part to them. So you can see here Alice is going to compute a signature. Alice has her private key, only she should have it. She keeps that secret, she doesn't give it to anyone else. And everyone else who wants to check this message, such as Bob here, is going to have Alice's public key. This is Bob, but really anyone could have got this message. Because Alice is the only one who has her private key here, she's the only one who can run this signing operation and produce the signature. Because if you don't have the right private key, you generate a wrong signature, a false signature that won't verify at the other end. This signing operation is just like a public key encryption operation, only a bit different. It's producing a small fixed length output that's the signature. That signature goes along with the message, and on the other side, Bob can take them both in and do the verification operation. And if that's the case, he will know that the message which came through really did come from Alice and it really hasn't been altered. Because we're working with public key here, note that this scheme does let Bob convince someone else, like Charlie, that Alice sent him the message. He can simply send Charlie the message along with the signature and say, look, Charlie, I got this. Charlie can check using his public key that the signature is correct, and then Charlie will know that Alice did in fact send that message because she has signed it. Okay, so now you've seen the signatures and MACs which are used to provide for integrity and authenticity. There's a little bit more I can tell you about them just to get towards the way that they're used in practice. The first one is pretty similar to the way we combined public key and private encryption before, public key and secret key encryption before. There's the same sort of tension as we had for confidentiality. The public key kind of integrity and authenticity using a digital signature has some keying advantages. It was more powerful, really. We could create a signature and hand it around, and all sorts of people could verify it. You didn't get that with a Mac. On the other hand, it has much poorer performance. It's much slower than computing a Mac. So there's a technique that we can use to speed up signature operations in practice. And that is, they're based on the use of something called a message digest. A message digest is a relatively small, fixed-length token that stands for a message. It represents the message. If we can create a message digest, then we can simply sign the digest in place of signing the message. Let me explain a little bit more about how that works. To do that, I want to tell you what these message digests are first. So I'll do that. You might hear the term message digest or a cryptographic hash. These are incredibly cool things, so you want to find out about them. They're used to speed up signatures, but they're also used all over the place for security schemes. Now, what a digest or a hash is it's just think of it as like a checksum, like a CRC or an internet checksum, only it's longer and it's secure in some way. Like a checksum, it deterministically takes in the bits of a variable length input message and it processes them down, and it mangles them in the same way as encryption does to get a pseudo-random output. This is sort of like a CRC. Your CRC, by doing the division, it's really coming up with just some set of numbers you wouldn't guess ahead of time. So they're effectively pseudo-random, even though there's a well-defined operation. They might look random to us, yet they're deterministic. They are literally a function of the message. The key property for a message digest or a cryptographic hash is that by construction, you can't find two messages that have the same hash. Now, it's not that they don't exist. Because the hash is small, say 160 bits or something like that, and messages can be much longer, there clearly must be many messages which have the same hash value, just because there are infinitely more messages around. So many of them are going to end up having the same hash value. However, it's computationally infeasible to find two messages that have the same hash value. You would have to do a tremendous amount of computing, too long for it to be feasible, as long as the scheme hasn't been cracked. So when this is true, and we have schemes for which we believe this is true today, then this digest is sort of like a magic token that is it's like a fixed length descriptor of the actual message itself. So in some cases, we can treat it as the message. It's very useful for many things. Here's just an example of the scheme below. Here's the input message here going on, and you run it through a hash function. It's sort of like almost, you could imagine it's like a symmetric key encryption operation. Well, actually, let me take that back. There's no keying, it's deterministic. But it's a fairly simple, fast function which just mangles the bits. That's all I meant. You run it through this function and you get out a pseudo-random set of bits that's a fixed length, and that is the message digest. An example of a message digest function is SHA-1. You might hear SHA-1, SHA-1 is how it's pronounced. And that is 160 bits long. So any message, whether it's kilobytes through megabytes of text, can be reduced to 160 byte hash. There's still an awfully large number of hashes. There are 2 to the 160 different possible hashes. So that's sort of that's why we can't find collisions so easily, or a big factor in it. There are more hashes than we can possibly come up with, or than we could enumerate messages for, because 2 to the 160 is incredibly large. So here's how we use hashes to speed up signatures, and it's fairly straightforward. Conceptually, we'll do just what we did before. The only difference is the change in this picture is here. Instead of signing the message, we'll sign the hash of the message. That's it. This is going to help because the hash itself is fast to compute. You can go over a long message fairly quickly, and that way you only have to do the signing with a public key of a smaller portion of message, 160 bits, say. So overall, this is much faster. It's still secure because at the other side, Bob can deterministically compute the hash from the message, and the hash is standing in for the message since we don't know of ways to easily come up with different messages that have the same hash. So if I see that someone signed a hash, I could defeat this scheme if I could find a different message with the same hash. That would trick you maybe into thinking that I sent the other message. But we don't know how to do this. So we still retain security with this scheme. Okay, well, we've done a lot of stuff. There's just one more thought that I'd like to try and squeeze into your head, and then we'll understand how to send messages which are authentic messages and haven't been tampered with. The one thing we're missing is something to deal with what is called replays. Now, the point is this. Often, actually, we want more than confidentiality, integrity, and authenticity for secure messages. What? You might be thinking, more? Geez, we just added integrity and authenticity and we already had confidentiality. It seems like we're getting a lot of different security properties from a message. Yes, we are. They're all properties we need for secure systems, but we need one more. We want to make sure a message is what's called fresh, recent, or new. And that's because we don't want to inadvertently, when we receive a message, mistake some old message that might have been sent a year ago for a brand new message which someone has sent today. That's, if we do, that old message which is sent again, saved and sent again at a much later time, is called a replay. And we don't want to treat it as a new message, because if we do think it's a new message and we act on it, that might cause a lot of trouble. That might break the security of the system. Here's just an example of a replay attack, just to get you thinking about it. Maybe an overly simple example, but nonetheless. Just imagine that Trudy records all of the messages that Alice sends to Bob. And much later, Trudy's going to replay them. Now, these messages are unread. Trudy hasn't cracked the scheme. She hasn't cracked confidentiality. So she doesn't really know what the messages says in detail, but she can guess. Suppose Alice and Bob had a login. Bob asked for a password and then Alice sent the password. It's sort of a common protocol exchange for many login things. If Trudy had recorded that, Trudy could later replay them. So maybe when Bob's asking for a password from Alice, Trudy can replay this message, which, even though she can't read it, contains an encrypted version of the password. If Bob were to accept this, he would think Alice just successfully logged in. Say, great, hi, okay, what do you want to do, Alice? This would be bad. So any reasonable scheme should provide protections against this. So we want to prevent replays. How can we do this? Well, conceptually, it's not too bad. It's fairly straightforward. It gets a little more tricky in terms of implementation, just due to a few little difficulties. But to prevent replays, what you want to do is you want to provide proof of freshness in the messages. You want some way, by looking at a message, to be able to know that it's a new message you haven't seen before. So to solve that, here are two simple approaches. You can include a timestamp on the message, so you know when it was sent, just as part of the format of the message. Or you might also include something that's called a nonce on a message. Nonce just stands for number once. So a nonce is simply a number which is on a message which you haven't seen before in a well-defined position. You might simply use a counter as a nonce, counting up. And so every time you send a new message, you might increment this counter. That way the receiver could check that the counter's been incremented, so that way they could be sure that it's a new message. You can do nonces in other ways than counters, but you get the idea that it's a number you haven't seen before. So here's Alice sending to Bob. And you can see, for freshness, all I've done is we've changed the format and we've required in messages that, in this case, there's some kind of timestamp in there. It would be to more than a second, most likely, but it's some timestamp. That way, when Bob receives the message, he can know if it is a new message he hadn't seen before, depending on the time, or if it's an old message which he saw long ago. Right, so now we've gone through replays too. Sure, okay. Well, what I want you to take away here is really you've seen a bit of cryptography in action. And I'd like you to realize that we can use cryptography in different designs to provide different kinds of security properties about messages. And there are many properties. We want integrity and authenticity and freshness, as well as confidentiality often. And we can provide them with different designs. This is what cryptography will give us if we do it the right way. It's very useful for secure network schemes. We'll see in a while real protocols that combine these properties in different ways, depending on what they're trying to do. What I have to tell you, though, is that there are many pitfalls in different security protocol designs. And we've talked about this a little before, but what I would say is the way all of these different primitives are combined, it's very easy to get the combination wrong and include subtle flaws. So not only do you not want to make up your own cryptography and use approved designs, but you want to use them in an approved way so that you're using them in a safe way and you don't expose yourself to unexpected vulnerabilities. Okay, so that is integrity and authenticity for message authentication. G'day viewers. In this segment I'll talk about wireless security. So there are many important kinds of wireless networks. Cellular networks come to mind, for instance. But in this segment I'm going to talk about wireless security in the context of 802.11. I think that by doing so you'll get a sense of how wireless security is different than wired security and the kind of problems we need to pay attention to. And we'll also discuss a specific wireless context that should be of interest to many of you. Okay, so let's start with the goal and threat model. Again, just to be clear what kind of security it is that we are trying to provide. And the key difference, which you should realize between wired networks and wireless networks, is this: that the wireless messages are broadcast to all nearby receivers. This is very different than your average wired setting, in that you don't need physical access to the network in the same way to be able to use it. And it heightens security problems. Here we have, in the figure, we have Alice and Bob communicating using a wireless network, and the dotted line means that they're inside, some building. Maybe it's your home apartment. Now, Trudy and Eve are outside this apartment. If this were a wired network, they would not directly have access. But it's dotted because actually the signals leak to all nearby locations, and Trudy and Eve can receive messages from this network, and they can probably send messages to this network too. I've called the attacker there Trudy and Eve because they may have different capabilities. We could consider eavesdroppers who can only just hear messages and are interested in understanding what they say, as well as intruders that send messages to use the network. Okay, so there are two main threats that we're going to consider. The first threat is that of eavesdropping on conversations, reading the contents of your mail and so forth as you send information across that network, seeing the web pages that you're downloading and all of this sort of stuff. This is a little bit like our recorded conversations that always seems to make the newspapers on cellular networks. Now it's on an 802.11 network. So the first threat is this eavesdropping. The second threat that you might not have considered is unauthorized access to the network. The network is going to provide access to authorized clients, but it needs some way to be able to tell those authorized clients apart from other clients who just happen to be near enough the network to use it. And as I said before, we're going to focus on 802.11. When the setting here for Trudy and Eve, you can see it says that they're external attackers, so we assume they don't have access to the equipment and so forth, but they can receive and send messages. Eve really receives messages, Trudy would be able to send them too. So for 802.11, the overall picture is that we're going to secure the network for all of access control to ensure that only authorized parties can use the network, as well as confidentiality, integrity, and authenticity on messages, probably freshness of some kinds too. And the way we're going to do this is with a security scheme which is in which everything is based on a password to gain access to the network. This is the network password that you usually have to enter into a laptop to use an 802.11 network. Security is built into the 802.11 standard, and it has been from the beginning. The original security scheme actually was this thing called WEP, which stood for Wired Equivalent Privacy. You've probably heard of WEP, if only because of all of the security problems it's had and the many articles saying that it can be cracked and it shouldn't be used. This is true. The design of WEP is badly flawed, and it's easily broken now using off-the-shelf software that you could get, even by Eve with no physical access. The more recent versions of security are built into 802.11. They're part of the 802.11i substandard. This is known by the trade name WPA2. WPA stands for Wi-Fi Protected Access, and I think I want to put a 2 here just to say the version you actually get on any standard device these days should be WPA2. WPA1 was an interim version which never sort of went anywhere. It was draft. It was only on the way. So the real standard is WPA2. And this is what you should be using when you use any modern wireless network where you have control over the setup. At least if you want to provide secure access to the network and to provide confidentiality and integrity and authenticity of your messages. In terms of our protocols, let's just look at a diagram to make sure we understand what 802.11 security is actually doing. Here's the protocol stack, and you can see down here we have 802.11. IP will be above for nearly all uses of the internet, and the protocols above that, well, it depends what you're doing. I've just shown examples. Security, such as WPA2, is built in to 802.11. But now, since we are operating at the link layer, this 802.11 layer works between a client and an AP, say. So the security has been provided only over this wireless link, not further on here as we go into the internet. The packets would be unencrypted according to 802.11 security as we went into the network. Of course, it's just operating over the 802.11 link. Also, in terms of encryption and the protections, what's going to happen if we look at a frame here? Here's an 802.11 frame. It's the contents of the frame that are encrypted. The header still needs to be sent in the clear with addresses in the clear so that the receiver can understand that the message is intended for it and so forth and who it came from and all of that. So usually with all of these encryption schemes, they provide encryption for the contents of messages, but not everything, not the header. So we can still see the devices between which messages are flowing. Okay, so that's what 802.11 security does. I'd like to just talk briefly about two different settings in which it can be used, so you can relate the way you use it to the different settings. The first setting is your typical home network setting. And in this setting, the AP here is set up with a network password. This is where you have to enter the password for the network. And the actors in this system really are just your clients, like your laptop and your AP. Every client or every user who has a client who's going to use the network also knows the network password, or they need to be able to access the network. And what happens is the client proves to the AP that it has the network password, and if it can prove that, then the AP will grant the client access to the network, and all of the messages that are sent between the two will also be protected, encrypted and so forth for good measure. And of course that is just over this link, even though many of the packets from the client will continue on to the internet or they came from the internet. The encryptions are just over the link between the client and the AP. Going into a little more detail, this is what needs to happen for the client to use the network. Well, to provide access here, the client authenticates to the AP. It basically needs to prove to it that it has the right to use the network because it knows the password for the network. And the way this is done is that both the client and the AP compute a shared session key that's based on the password. If the client can successfully do this, then it's really proving to the AP that it must, if it has this shared session key and the key's right, it can prove to the network that it must know the password and therefore it's allowed to use it. And all of this is done in a way such that the client doesn't simply tell the network its password in case it's really talking to the wrong party, because the client doesn't trust the AP at the beginning of this exchange either. So they're both authenticating one another. Once we've done that and then we have the session key, really everything is set because we can then use the network with the client and the AP encrypting the messages using their shared session key. And this will provide all of the usual properties we want. Moreover, no access is provided to people who don't have this shared session key. So if you don't have this session key, you can't read any of the messages that have been sent. And for completeness, I'll also tell you that there's a group key. The session keys are between APs and individual clients. The group key is something the AP uses if it needs to broadcast a message to all clients. Okay, let's look at the authentication step in a little more detail. Whoa! Okay, well here's a rather hairy diagram. We're not going to go into all of the details of this diagram. It's beyond what we can cover quickly. I presented this just to show you the exchange that takes place. We'll talk about it a little. There's more detail in your text and online. Essentially what happens here is that both on the client side, so by the way, this is one of our time sequence diagrams. Time, runs down the page, and you can see the exchanges between the client on the left and the access point on the right. Essentially, both the client on the left and the AP on the right are going to compute a session key. And if they can both compute the same session key, then they're in business. They've authenticated one another. Now, this session key is based on several inputs. It's based on what's called a master key. Well, that really just comes from the password processed in some way. It comes from nonces for freshness, to ensure that both of them are actually talking to a live party right now who's doing the computation. And you can see each side sends a nonce to the other side, because each side doesn't trust the other side yet. It wants to make sure that the other side is really doing some work on this as a new exchange. And there are also other inputs to the session key, such as the MAC addresses, that's the Ethernet addresses or the Wi-Fi addresses of both the client and the AP, just to bind everything together. Now, once they've both computed this session key, they're in business as soon as they prove to the other side that they hold the session key. The AP distributes to the client the group access key, the group key, which is used to read broadcasts from the AP. If the client can get this message in the right format, then it knows that the AP has the same session key, and the client knows it's a real AP it's talking to. The client then sends an acknowledgement, and if the AP can understand this acknowledgement and decrypt it into the right format, then it knows that the client also has the session key, so everything's good. And then after this, we have the messages, the data messages, which are sent across the network and with encryption to protect them, and they can be unencrypted by the other side. So that's how 802.11 is used in a home network setting. There's one other setting that I'll tell you about without going into the details. And again, this is really just so you know the different ways 802.11 security is used in practice. The other setting is an enterprise setting, when you use 802.11 inside a company network. And the difference here, you might wonder, why is this different than a home network at all? The difference is this authentication server. There's not usually a single password for the network in a company. Instead, all of the users in the company, they have some credentials for an account that's been set up on a server. So each client, that's a user of the company network. And what the access point does is, for new clients, it provides a path for them to talk to the authentication server, and only the authentication server. The client and the authentication server then go through an exchange via the AP, and if the client's successfully able to authenticate, then the AP learns that it was successful, and it then grants it access to the network, setting up all of the session keys and so forth along the way. So that's an enterprise setting, and you can see it's different. I haven't told you all of the details of how it works, just because we don't have enough time to go into it, but there's always more interesting stuff to learn in networks. So that's wireless security for 802.11. G'day viewers. In this segment I'll talk about securing the web. Wow, well, securing the web is actually a very big topic. What I'm really going to do, since we're talking about network security here, is focus on the protocols called SSL and TLS, which are used as part of HTTPS, which I bet you've heard of, since you no doubt enter many HTTPS URLs or see them in your browser. And I'll also talk about something called certificates as part of this. They're a key part of the operation. Okay, so goal and threat model. Let's start off again. This is particularly important here because, well, I think many things can go wrong on the web today. Clients can run into all sorts of malicious content as they surf around the web and download strange web pages. Web servers are often the target of break-ins by external parties, compromising different bugs on the servers to gain control of it and see what data is on it. There's all sorts of phishing scams with fake data misdirecting you in other places in different ways to steal your data, and so forth and so on. The web is a bit of a dangerous place just to be out there. What we're going to focus on, however, is a much more restricted subset of the general web security problem. Our goal really is to secure HTTP using a protocol called HTTPS. That stands for HTTP Secure, if you like. Now, by secure HTTPS, I mean that we should defend against several attacks, and they're listed here. And you can see that these are all attacks or threats that are focused on the network portion of the protocol. The first attack is against eavesdropping on traffic between the client and the server. So someone being able to read the messages that you send between a client and a server as you use HTTPS, as you download that web page or post and upload your mail. The second threat is tampering with this traffic as it goes between the client and the server. Maybe that's changing your mail message as it's sent up from the client to the server. So it looks like you sent a message that's different than the one you actually did. And the third threat is that of impersonating a web server. When a client's talking to a web server, it thinks it's talking to a certain server. It should be right. So if you think you're talking to your bank, we would like it to be the case that you really are talking to your bank, or at least that you have some way to check that. You'll notice that all of these threats relate to the network portion of the protocol here. So what we haven't done is focused on break-ins to either the client or the server, or malicious content which is downloaded by them and exploits bugs in their operating system and so forth. That's a great topic, it's just wide of what we're looking at. So HTTPS, that's where we're heading. What can I tell you about HTTPS? Just to give you a little bit of context first. Well, HTTPS is actually an add-on to HTTP. What it really means is simply running HTTP over these other protocols, SSL or TLS. SSL stands for the Secure Socket Layer, and TLS stands for Transport Layer Security. SSL was the protocol that came first. It started as a proprietary version, and eventually it was standardized under the name TLS. So TLS is the more modern version of it. But now this protocol is really inserted here, that's what I mean, it's an add-on, between HTTP and TCP. So HTTP is running unaltered, it's now running over a transport which encrypts everything and provides some kind of security. TCP is also unaltered. TCP is just moving information around. It doesn't know that the information is encrypted. And the approach by doing this is that one could reuse all of these components without altering them, yet add important security properties to the web that protects against some of the most common threats that we worry about. A little more context just in terms of the timeline for how all of this evolved. SSL was actually a protocol pioneered by the company Netscape. Starting in the early 90s, I think, SSL first came out publicly as SSL version 2, which had cryptographic flaws in it. And it was fairly soon fixed into SSL 3, which is the more standard version of SSL that you should see around today. That's been standardized since and available since 1996. So it's really been out there for some time. It's maybe the most common version of SSL and TLS that's used today, perhaps. TLS is an IETF standard, so it's not a proprietary protocol. TLS has been standardized since 1999, and it's been revised slowly in the years after that. TLS is still a protocol which is being deployed today in the internet to provide security, both for HTTPS and actually, you might notice the name here is Transport Layer Security for TLS. It's not specific to the web. So increasingly you'll see things like email with the SMTP protocol sent over TLS. So it can really secure any kind of transport application. That was the intent, that it be used more widely. Actually, the motivation for all of this was really web commerce. So people buying things over the web and typing in their credit card number and sending it from the client to the server. They wanted to make sure that this information would be sent securely and so that no one else on the network could steal your credit card number. This was the genesis of HTTPS. The adoption was actually rather slow. Initially it was just used for credit cards rather than everywhere. Partly due to the difficulties of just rolling out any change, partly due to the performance hit that it took to do some of the public key cryptography in HTTPS. Today that's a little less of a concern, and HTTPS is being rolled out really everywhere. It's now in widespread use, and it can be used by any app, not just HTTP. Actually, apps and HTTP are all being blended together. So your email application running in your browser is a good example. there is a lot of traffic on top of HTTP, an application on top of HTTP is implementing this email, it's likely to use HTTPS as a transport so that all of your mail will be sent around securely. Actually, if you look at systems like Gmail, which ran in your web browser on top of HTTP, when they first came out, they didn't have security. They didn't have HTTPS, so your email was being sent in the clear. It's a while ago now, but at some point, due to people realizing what was going on, there was increased pressure to use HTTPS to move your mail around while encrypting it, so not just anyone could read it. Now it's standard that your mail application in your browser and many other applications will use HTTPS by default, and I would expect it to be more of a default over time, not less. So we'll switch now to SSL because HTTPS was really HTTP over SSL or TLS as the standard version. So we just want to know what SSL or TLS does. So in terms of operation, the protocol is really providing a couple of features here. It's allowing the client to verify the identity of the server to make sure that the client's talking to the right web server, someone who really is your bank, not just pretending to be your bank. Optionally, it lets the client identify the server, but this is typically not done in the web usage. It might be useful in other protocols like your email exchange. And as well as verification, we would like to provide a secure message exchange between the two parties. So after they've identified one another and everything's good, they should be able to send encrypted messages that give all of the usual properties of confidentiality, integrity, authenticity, and freshness. And to do all of this, we really have an authentication phase where the client's working out who the server is, making sure they're really who it thinks it is. As a side effect of this, we're going to end up setting up all of those session keys, which we can then use for encryption. And the encryption is all used as part of the data transfer phase to make sure all of the messages are secured. Well, all of the magic then for us is really in the authentication phase. Afterwards, we're just using standard kinds of encryption for confidentiality, integrity, and authenticity. Boy, I'm getting a little sick of saying that. You're probably getting used to those phrases for that being a secure message exchanges. So let's just focus on the authentication. The whole point of the authentication here is to allow the clients to securely connect to servers that they haven't used before. If clients were always talking to just a few servers that they knew and trusted, we could set up keys between them and everything would be great. But in the web, you're always talking to some party, it seems, that you've never met before, and you want to exchange information securely with them. So the client's going to need to authenticate that the server is who it says it is. And this, when it's used in your browser, by the way, we also want to reflect security properties to users. You'll often see in a browser some it used to be a lock on a page or other visual indication that the page has been authenticated. So you really knew who it came from as well as it was sent securely. And as I said, the server typically doesn't identify the client, at least in web usage, because any client can use a server. It's not just that anyone can buy anything, it's usually that the identification of the client as part of credentials like a credit card and so forth is done later. It's not used as part of the SSL exchange. Now, for the client to identify the server, especially servers we haven't seen before, we're going to end up using public key authentication. That way, servers can just publish their key, and if clients can get it, then they can authenticate the server. But we still haven't answered really how the client gets that server key. Where does it go to look for it? The server's web page or what? Well, to solve this problem, we'll end up using something called certificates. Certificates are messages which really serve to distribute public keys and other information. A certificate binds an identity to a public key. So here's an identity, Robert John Smith, and an email and whatever, and here is a public key that corresponds to the identity of Robert John Smith. This certificate is binding these two together. The identity here is a name and an email address for a mail certificate, but in the context of a web, what you would probably have here is a domain name, like so that your bank is bound to a particular public key. This certificate, it just says what these two things are, but it then needs to be signed by someone you trust, again using public key cryptography. And we'll get to this in just a minute. This is the whole crux of it. And these certificates are commonly put together in a format called X509. You might hear or see that around. But the certificate is really used to distribute these public key bindings, as long as we can just verify the signature bit. So let's get to that next. Okay, so these certificates, just to get towards this validation question, these certificates are what is part of what is called a PKI, a public key infrastructure. A public key infrastructure gives you everything you need to manage and distribute public keys for everyone. So it's going to use these certificates, and importantly, it's going to end up adding hierarchy to these certificates. So you can see here in this picture we have a hierarchy. We go from the root down a level and down another level. And the purpose of this hierarchy is to let many different parties issue these certificates. If there was just one server that issued certificates, everyone with a website in the world would have to get this one server to issue a certificate binding their identity to their public key. So they would have to go and show themselves to this server and all of that. Instead, we would like many different parties to be able to issue these certificates. These parties are called CAs, or certificate authorities. So there might be different companies running in different countries and so forth. This will sort of remove that bottleneck and let many people, by letting many people issue these certificates. Of course, we still need to be able to verify that these certificates are good. Here we have a situation where a particular certification authority, CA1, is certifying the ABC website. So this message CA1 would be sending a message which says, for the ABC website, this is the public key. Suppose we get that, we would like to know if that's actually correct, because we don't yet know CA1. So the question really is here, how we can verify the information that we receive in a certificate. So say you're a web browser, and you receive and you want to contact a particular website, the ABC website, and you receive from CA1 this information about the ABC website that tells you it's public key. Great, you know the public key, except you haven't yet verified that it's correct, and you want to do that to make sure you're talking to the right party. So how does the browser do this? Well, Well, in your browser, we have to start somewhere. So you have, as a trust anchor, a root of trust. Your browser is programmed with the public key of the root of this hierarchy for the PKI. It just has it and it assumes it is correct. The root can then tell you information about this other box here, RA1. This is an intermediate authority who's issuing certificates. So in fact, the root can make a statement to say that RA1's key is X, some key X, and sign it using its key. Now you can check this because you have the root's public key, so you can check that this statement has been certified by the root, in which case, if you trust the root, you will believe that RA1's key is X. RA1 can then make a statement saying that CA1's key is Y, and sign it by its with its own key, and that would be X. So it would be signed by RA1 with X, and this would be right. Let me just put that notation in to make the linkage clearer in this figure. So you'll then be able to, since you have the key X, you'll be able to verify whether the statement is true, and you will learn the key for CA1 is Y. Now you're able to take this statement that you got from CA1 saying that ABC's key is some other thing Z, this is the bit you want, and you'll be able to check the signature from CA1 using the key Y to see if everything matches. If it does match, then you will have the public key for website ABC, and you'll be able to use it as part of the SSL exchange to see if you're really talking to ABC. Let's see how that works next. Oh, before we do that, just here's a picture in more browser-specific terms. So I said what your browser did in terms of having the public keys of the roots and so forth. But you can look at this yourself. So your browser or your operating system has inside it, is configured when you get it with the public keys of what are called the trusted roots of the PKIs, these at the very top of the tree. These are called, it has things called root certificates. So it's a certificate that's signed by the root itself that you just sort of take to be true, that tells you the root's public keys. Now, it's interesting here, if you look inside your browser, you might find there's not one root certificate, but many that your browser trusts. Maybe there are 100 different root certificates that are out there and trusted by all of the different browsers. This is actually a problem because it means that in deciding whether you are talking to the right website, your browser is trusting maybe 100 different parties. The more parties you're trusting, the more risk there is that you're actually going to end up trusting someone who shouldn't be trusted. So it's a little problematic that you're depending on so many people and you may not even realize who you're depending on. If you'd like to see some of this, you can use your browser itself. Just under some of its options, there will be a place to inspect the certificates and you can have a look yourself and you'll see all of this information inside your browser so that you can inspect it and configure it and override it if you want. On the right here, I've shown the certificate for wikipedia.org. And as you would find inside a web browser. And so you can see a few details here. You might not be able to read that, but it says it's issued to wikipedia.org. It's a certificate that it tells you the all of the details here would have the information about the public key for wikipedia.org, and you can see that it's been issued by some certificate authority here, DigiCert. And there's various fingerprint and signature information that you can use to verify everything's good. Okay, I still have a little more to say about PKI as it turns out. This is a detail that I don't want to go into, but I just do want to tell you another real-world complication. So this should really give you a sense that working with public keys is not straightforward just because they can be public. There are a few wrinkles involved. Here, another real-world complication that public key infrastructures need to deal with is this one. Public keys can be compromised. Your computer could be hacked into. Your computer was where you stored your private portion that corresponds to your public key. Someone has stolen it. Now they can sign things as you. So that key has been compromised. Well, to allow for this to happen, we need some way to revoke certificates which are signed by this key. Because now they can no longer be trusted, at least in the future. And so what a PKI includes, as well as all of the machinery to distribute these certificates, is something called a CRL, or a certificate revocation list. This is really a list of bad certificates which are no longer considered valid and they can no longer be trusted, even though they're within their expiry date. And it's really a way to weed out some of the bad keys there. So all PKIs will also need to provide a certificate revocation list. Okay, so now we're at the stage where the client has somehow got the public key for the web server that it wants to contact by using all of this PKI and verifying things all the way down the hierarchy. Wow, it's quite a lot of work actually. But now we get to go through SSL authentication. This is a timeline, so again, time goes down the page here. This is a timeline for SSL version 3 authentication. And like, wow, this is complicated again. I'm not going to explain all of it to you. It's there so we can see it. There's more information available in your text and other resources to learn more about how these protocols work. I'll just sketch a few features of it for you. Now, first of all, some of the first steps here is a bit of a negotiation between the client and the server. Many different cryptographic algorithms can be used. And so the client usually tells the server what algorithms it speaks, and the server out of them chooses when it intersects what ones the client speaks and what ones it wants to use. It tells the server what algorithms they're going to use. You can also see, as part of the information that's going here, the server is helpfully sending back its certificate information and everything it needs so that the client can verify the public key of the server. Right? That's how, using only the trust anchors which are already in the browser and the server. So this is just a phase for everything to get initialized. And here is that Alice checking the certificate from Bob, that website, which could be ABC or some other website, using these certificates. Now this is all before we actually do any of the authentication. Now we want to do the authentication. So what happens? Well, Alice essentially computes some what's called a pre-master key that is sent. This is sort of keying information which Alice can compute using all of the information she has so far, including information about Bob's public key. The real Bob, and you can see here, it's encrypted with, it looks like it's encrypted with Bob's public key. The real Bob, if he possesses the right keys, will be able to understand these messages and also compute the session key that Alice has computed. So Alice now switches to the session key and Bob switches to the session key, and we're finished with this protocol. So if they, again, this is like 8211, if they can both compute the right session key, and they don't send it to one another directly, they just have to both compute it, then they can both switch over to use it, and if they can both understand it, and all of this is happening when we send the change cipher messages to know when to switch over. If they can both understand the new messages, then everything's good. Alice has successfully authenticated to Bob, and they've set up an encrypted session. And down here you can see the encrypted data messages just flow back and forth between the two now that we've set it up. And that's SSL version 3 authentication. And now we've seen how HTTPS works. I guess I'd like you to take away a couple of things from this. The main thing I'd like you to remember is just SSL and TLS is used with HTTP to make a secure transport, HTTPS for the web, and as well as SSL and TLS being available as a secure transport for other applications. We'll see more of this in the future. Secure here means all of the usual properties that we want, confidentiality, integrity, and authenticity, as well as the client being able to authenticate they're talking to the right web server. These protocols are very widely used today in the web, and they'll only be more widely used in the future. You can see here as part of the protocol, the client's authenticating to the web server. I guess I'd also like you to remember that this is done with a PKI and the use of certificates. And as you can also see, that some of this is quite complicated. Both the authentication and the certificates are major areas of complexity and hence risk. We sort of take all of this for granted because it's inside the protocol. If everything's used in the right way, it works fine. But it's worth understanding what's really going on so you know what you're actually depending on. G'day viewers. In this segment I'm going to talk about DNS security. And the main protocol we'll look at to secure naming in the internet is this one, DNSSEC, which provides DNS security extensions. Okay, so first we'll begin with a little bit of motivation and get towards a goal and a threat model. The motivation here is that naming is really a critical internet service. We better get this right. This is fairly clear if you think about it, because naming really binds a host name to an IP address. We use it all of the time when we, for instance, surf the web and contact websites. The DNS is used to translate the host name of the website into an IP address. So it can be disastrous if this binding can be compromised and broken so that wrong bindings are returned. Instead of contacting your real bank, you might end up contacting some other site altogether, and this just can't be good. So our real goal here is to secure the DNS, where secure the DNS means ensuring that the returned binding is correct. Now, actually it's quite interesting to observe that this property is all about the integrity and authenticity of answers from the DNS. It's not about confidentiality. Actually, we don't particularly care if the DNS replies are encrypted across the network or not. Since the DNS was a service where anyone could ask for these translations and see it, then it seems fine to return the answers in plain text where everyone can read it. So this is interesting just because it contrasts with the need for confidentiality when we looked at 8211 and the web. Now our attacker model, the threat here, is that someone in the middle of the network, Trudy here, can intercept and tamper with the messages. And this can cause us to get the binding wrong. It would also be possible to consider some attack models where you compromise some DNS servers, but we're going to ignore all of that for now. And in this quick look, we're just going to look at activity across the network where information is corrupted on the network. Okay, so here's one interesting topic for us to look at. with DNS spoofing. Now, you might have wondered this. We're talking about making sure the DNS is secure, but how is it that you can corrupt the DNS in the first place, especially if I'm just talking about an attacker somewhere in the network? I guess if you're an ISP or someone really on the path, you could change messages as they go through. But it turns out that even if you're a remote attacker on the internet, you're not on the path between the DNS server and the other DNS servers it queries, you can still often influence the result. This is called DNS spoofing. And what we do here is the following. Trudy essentially tricks a name server into caching an incorrect binding by using the DNS protocol itself. So we're going to exploit the DNS protocol and misuse it. It's really evil. It's the sort of thing that security is all about. Let's see how it works. So here's DNS spoofing. Don't do this at home. Learn it, but don't do this at home. So this is the setup that we would like to accomplish, and then I'll get to how we're going to accomplish this. We have a local name server. We want to poison the cache here. And by poison the cache, I mean insert bogus information into it that has incorrect bindings. That way, the wrong information will be returned to all of the clients of the name server should they ask for that translation. Now, this name server will be using the DNS protocol to query other DNS servers, like the .com server, and get information. So what we want to do is have Trudy send a fake DNS reply or a false DNS reply, which has a bad binding, back to the name server in such a way that the name server will accept it and put it in its cache. This is great. This is what we want to do. Well, that's all good and well, but to accomplish that, there are just a few questions. You probably start thinking about them immediately as I was sketching that scenario. So here are at least 3 issues that occur to me right away, and they probably occur to you, which we have to deal with. How does Trudy know when that DNS name server is sending a query to other DNS name servers and what it's making the query for? So, because we've got to know that to be able to send the reply. And how can Trudy send a fake reply that looks good enough that it can trick the name server into believing it's the real reply? And then, even if this happens, the real reply from the real DNS system will probably show up sooner or later. If it does, how can we make sure that Trudy's reply is kept in the DNS name server instead of the real answer? Well, it turns out that there are reasonable solutions to all of these issues if you look at the details. And in security, the devil is always in the details. Here's how you could go about solving those issues. So first of all, how does Trudy know what requests the DNS name server is making and to who? Well, for the ones she wants to poison, easy. Trudy can just make the query herself of the local name server, and this will cause it to use the DNS protocol to try and find out. Now, remember that a name server is really some device which works on behalf of a pool of local clients. Trudy can really just act as another of those local clients. You can impersonate a local client and use the services of the name server. Often DNS name servers, local name servers, don't have access restrictions on them because they want to make it easy for many different clients who are part of the local ISP or whatever to use them. Okay, so the second question. How can Trudy supply a fake DNS reply that looks so good that it's taken to be real? Well, this is a bit more difficult. It's more difficult because the local name server, when it gets the reply, is going to do some number of checks. So we really need to understand what they are in detail so we can know how to fool them. I'll tell you some of them. One of them is that we're going to see where the reply comes from. Look at the IP address. It should be from one of the authoritative name servers from whom we were expecting a reply because we sent the request there. That's one issue. The other one is that replies and queries have an ID number that's filled out by the local name server, all of the name servers. So these should match between the query and the reply. This is how a name server pairs them together. And the final issue is that name servers only accept responses when there is a query outstanding. So we need to make sure that we're sending that when there's a query outstanding. But note that there's nothing actually about the content, what this binding is, because the name server doesn't know that. It's just going to accept any reasonable answer. Okay, so here's some techniques we could use to come up with a pretty good fake DNS reply. For the IP address, we'll simply put the IP address of the real name server who should be returning the response as the source address of our packet. Can we do this? Yes. On IP packets, there's a source and a destination address. The destination address is used for forwarding, so it has to be right to take you to the right place. But the source address is often not checked by the network. It's really there for the destination to use and send information back. So if the network doesn't check this, we can spoof the IP source address. What about the ID? Well, the ID is actually only a 16-bit field, so there are only 64,000 possibilities, which is not many for a computer that can send thousands of packets a second. So we could just send a big bag of replies, hoping that one of them has the right ID. And we might only have a small chance of succeeding, but over time, if we try this technique, pretty soon we'll get it right. This actually used to be even easier, and often is, with old implementations. Some implementations used the ID field as a counter. So in that way, if Trudy can just sample about where the counter's at by observing some message, any message that the name server, target name server sends out to another name server, then she'll be able to predict roughly where the counter will be and send only a small number of packets to have the right value. And to make sure that there is a request outstanding, well, we can simply send the reply right away after the query, so it'll get through. When you put these together, all of these techniques have a pretty good chance of succeeding. And finally, there was one remaining issue of what was going to happen when the real DNS reply showed up, the real answer, the one we wanted. Actually, this is likely not a problem, because at this stage, if Trudy has accepted the fake answer, there is no outstanding response as far as Trudy is concerned, so that when the real response arrives, most likely it will be discarded as unwanted or some spurious duplicate. So we're really throwing away the real response and not worrying about it. So you can see when you put all of these techniques together that the DNS can be spoofed. And this is very much a real problem in practice because it can be done, it is done, and the DNS is a critical service, so undermining it causes very bad things to happen. Well, now that we've got our security hats on, let's fix the problem. Actually, rather, let's understand how the problem can be fixed, because people have been working on fixing this problem for a long time in the guise of work on DNS security extensions. And these extensions have very slowly, until recently, been rolled out into the internet, and recently deployment is really beginning to accelerate, so they're being rolled out. Okay, so the DNS security extensions simply extend the DNS with several new types of records. I'll talk about the records in a minute, but there's an RRSig record for digital signatures of records, so we can check them. And there are two records which contain public keying information, so that we can validate things and delegate from one name server to the other. Now, DNSSEC is something that's been under development for a long time. The first version was standardized in '97. There are actually quite a lot of issues with it, so as people gain experience with it, eventually it was rewritten, totally revised in 2005, and then it's been deployed relatively slowly. Deployment is a little difficult because it requires software upgrades essentially everywhere, like clients as well as all sorts of servers. So it's a fairly big thing to accomplish. But recently, especially with renewed pressure because of the rise of security attacks, there's been a concerted effort. The root servers have all been upgraded to speak DNSSEC and have signed certificates, and this happened in 2010. And now there is a substantial uptick in the deployment of DNSSEC, starting at the highest layers of the DNS on down. So I think now you can attain authenticated information about servers in the .com domain, for instance. So let's learn a little more about DNSSEC. So DNSSEC introduces new records, and these are in addition to the records we've already learned about for the DNS, such as the A records for IP addresses, the NS records for name servers. The new records are the RRSig record. This contains a digital signature of the domain records. So whoever's receiving the information can check the digital signature to make sure that the information in the record was correct. There is also a DNS key record. This contains the public key, which is used by a server to sign records in a zone. So this is the key that we'll use with the RRSig records to check things. And there's also a DS record. This is for delegation, delegation server record. This is used by one name server to tell you the public key of another name server which handles a small portion of the space, like uw.edu being inside edu. And finally, there are other records that I'm not really going to get into that provide authenticated denial of existence. So if you look up a name and you find it's not there, you can get an authoritative answer that you can check to learn that it really came from the name server, so that really there is no such address. Now, the interesting question for us really has to do with validating all of the replies. So when a client gets the DNS replies, it would like to validate them to see that it actually has the correct binding. The rest of the DNS just works as usual. So that's what I really want to talk about, how a client, when they get all of the replies, can check that they are the right replies. Well, to do this, we're going to use a method that's similar in some ways to the certificate hierarchy in the PKI used for web security with SSL. We're going to have clients assume a trust anchor to be the root of the DNS tree, the public keys for the root of the DNS tree. This is part of the DNS configuration. In the same way that you had the IP addresses for the root servers, now you have public keying information for all of the root servers. And trust is then going to proceed down the DNS hierarchy. So from one level, we will work out the public keys, and we can check signatures for the next lower level, and so forth, until we get down to the level we want. So let's see an example to see how this process works. So just imagine here, our example is that a client queries www.uw.edu just as usual. So it's going to follow the same path as usual and receive all of the binding information. But in addition, it will also receive signatures and keys to validate the answer. So actually the answer is down here, the final answer. You can see that the uw.edu name server returns www.uw.edu saying that it has a certain IP address. And this information is signed. This is the signature, this is the RR-SIG information. It's signed by the uw.edu server. So now we just want to check all of the signatures, and if they hold, we will then decide that we believe this is a correct binding. So how can we do that? Well, we start at the top. So we're going to validate from the top down. First of all, we have here, we know the key for the root because that's a trust anchor we're configured with. So the root will then tell us information such as edu has been delegated to use a certain key, kedu. Well, we can use the key we have for the root to check that delegation statement. This is signed with the key for the root. If the signature there is okay, then we know the key for the edu level. Now the edu level then says that uw.edu has been delegated from it with a certain key here, and it's signed with the edu key. So we can check that statement with the right key. And now if that statement holds, now we know the key for uw.edu. Now uw.edu has now made a statement about the binding. And, oh sorry, that was this one. We use uw.edu to check uw.edu. And then finally, now that we have the uw.edu key, we can use that key to check the information in the resource record about the IP address to see that the signature for that holds, so that that binding is correct. And if that holds, we've got the right IP address that corresponds to this host name. And we can contact it with a good degree of confidence that it's the right IP address. And there's a lot more in the DNSSEC too. So some other features would just be authoritative answers that a record doesn't exist. These were the other methods I mentioned. There is also some optional anti-spoofing to more tightly bond the query and reply. And there are also flags related to deployment. But in this brief overview, we don't have time to go over them. You can look up that information yourself if you're interested. So some of the takeaways here that I'd like you to remember is just this whole idea of DNS spoofing, and that it's possible without added security measures. It gives you a sense of how things can be corrupted in practice, and it's very much a large problem in practice. DNSSEC also as a solution is interesting because it's just adding authentication only to the replies of the DNS, not confidentiality and so forth. And it does this using a hierarchy of public keys. So now you know about DNS security. G'day viewers. In this segment I'm going to talk about firewalls. So firewalls are very useful network devices that protect a local network from all of those hosts out there, other hosts out there on the internet. They're also very interesting to us from a security point of view because they protect the local host by really restricting IP connectivity rather than using cryptographic measures as we've looked at before. Okay, so let me start with a little bit of motivation. Say here the best part of IP connectivity is that you can send packets to any other host on the internet. That's really been a key to the success of the internet, so it's wonderful. Well, the worst part of IP connectivity, guess what it is? Any other host on the internet can send packets to you. Even hosts which are nasty, which you don't like, and there's certainly a lot of nasty hosts and strange traffic out there, which you wouldn't necessarily want on your own network. So let's move to a goal and threat model here to understand what we're trying to accomplish. Well, with a firewall, our goal is to implement some kind of network boundary at the entrance to your network, your home network or a corporate network, that restricts IP connectivity so that you can talk to hosts on the public internet just as you want it, but Trudy is kept out. Trudy is unable to talk to hosts on your local network. So ideally, we would like to obtain a picture like this. Ideally, we want to partition the internet in such a way that Trudy is kept over here on one side. There's Trudy with all of her bad packets, and you were able to use the internet and talk to the host you actually want to talk to just fine. That's what we would like to happen. Of course, it's going to prove to be a little difficult to get just this to happen. So let's see how we might go about doing that. Well, a firewall is actually a kind of middle box. So I want to just show you this slide again and have you remember how middle boxes work, because that will tell us most of what a firewall is going to do. So a middle box, and this device here is a middle box, is a device which sits logically inside the network, so it's occupying a position almost as if it were a router. Yet, unlike a real router, it's performing more than processing at higher than the IP layer. It shouldn't be. That's this strange bit here. It shouldn't be because it has no clean way, according to our layering model, to operate beyond the IP layer. But it just does because it's a convenient way to add new functionality that couldn't easily be added otherwise. In the case of a firewall, this device will be looking beyond the IP layer to filter packets and decide which packets are allowed into the local network and which ones aren't. And we've already seen a nice example of a middle box, and that is a NAT box. Firewalls or intrusion detection systems are often other examples of middle boxes. So let's go a little further and just look at our protocol layering diagram to help us understand what's going on, to see how a firewall fits in as a middle box. Okay, so here we have an organization. If you like, this is a local network. This is like your network, the network you want to protect. So you have hosts on the inside here, and we have one here, and they have a regular protocol stack, and they're just talking to hosts on the rest of the internet, just as usual. But of course, there are two kinds of hosts out there. There are hosts that you want to talk to. Great, you should talk to them with all the normal protocols. And then there are hosts that you don't want to talk to. That's Trudy. So the job of a firewall here is to act as a kind of router. So this is the usual router functionality. But in addition, look inside packets at the transport and higher layers, possibly all the way up to the application, to filter packets so that we let through packets from the good hosts, packets that have been sent from us to and from the good hosts, whereas we get rid of packets that have been sent to and from the bad hosts. This will make it look like the bad hosts can't even be reached, as though they're not on the internet. This is what we would like a firewall to do. And if we accomplish this, then they won't be able to send us nasty packets, with all sorts of viruses and nasty content. So zooming in on the operation of a firewall a little more, here's the firewall device here. And you can see that it has two sides. The internal side, that's the organization, and the external side, that's the public internet. The job of a firewall is to relay packets, as a router would, between these two sides. But for each packet, since a firewall must operate at the packet layer to forward packets, For every packet that tries to cross from one side to the other, actually in both directions, I've drawn the incoming direction here because this is the one that people would intuitively most care about. They would care about how packets from the public internet can enter their network. You might also care about restricting connectivity in the other direction to make sure your hosts don't contact strange computers. But let's just look at the incoming direction. For every packet that comes in, the job of the firewall is to make a decision. And the decision is whether to accept the packet. And to do that, you'll simply pass it unaltered, and the packets and the hosts that are communicating won't even know the firewall is there. Or you could decide to deny that packet, in which case you'll simply discard it silently without sending error messages anywhere. And to the two hosts that are involved, it will look like the network is broken, there's no connection. You can see this is why middle boxes have some strange effects, because we now have a bit of a strange model where connectivity might work sometimes and suddenly vanish. It's okay if it vanishes for the host which we didn't want to talk to, but if it ever vanishes where you wanted to talk to a host for some reason because the firewall's not properly configured, it can be a pretty strange sort of error to find. So the key task for us is really to make this accept-deny decision. What packets should we accept or deny? Well, this is actually a local policy. Oh, where's my pen gone? This is actually a local policy. It should be set up according to how you want to run your site. And really that you could think of the firewall here as centralizing the IT job so that people who are administering the network would have a nice central point of control to inspect and get rid of unwanted packets as they enter or leave the network. So the key design decision in firewalls is to decide whether to accept or deny packets as they transit the firewall. And there's a key tension there. The key tension is that we need to be able to translate from policies that people would like to implement to decision rules that we can implement on every individual packet. The tension is that policies are really relatively high-level statements for what we would like to happen. Usually they'll relate to the kinds of apps you can use and the kinds of content that could go through the firewall. On the other hand, packet filtering is inherently a low-level operation. It occurs for individual packets, so we're operating at the network layer. This means that we have a limited viewpoint into the network. You don't directly get to see the application messages, for instance, because they may be spread across many packets. And in fact, if high-level encryption is being used, then you won't even be able to peek inside the messages at all. Well, so there are several different kinds of firewalls that implement decisions in slightly different ways. And I'm going to tell you briefly about each of them, starting from the simplest and working up. The simplest kind of firewall is a stateless firewall. It really has very simple static rules, which are packet filtering rules. Now, you can only filter on the attributes of packets, so typically these rules will use things like TCP, and UDP ports as you peek inside the packets as they go through the firewall. This will allow you to do things like, you'll be able to allow or disallow different kinds of services or destinations across the network and so forth. An example rule is shown here, deny TCP port 22. I happen to know port 22 is the port that's used for Telnet. So with this rule, you would disallow Telnet connections from outside the internet or between the public internet and the hosts on your private network. That might be a policy you would want to implement for security reasons, so no one could remotely access the command lines on your different hosts. But this is all fairly, it's a static rule set, so it's only good for implementing a few kinds of decisions which can be expressed statically for every packet. Let's take a step up, and you have what's called a stateful firewall. A stateful firewall implements the same kind of packet filtering rules. We're going to look at the attributes that are on the packets, but we will allow some kind of state to track the exchange of packets and model what's going on and make decisions according to that. That allows you to make various kinds of if-then rules. In fact, we've already seen a good example of this, a NAT device. A NAT device is a device which, as well as doing the address translation, allows connections to be made from an internal to an external host, and if that has happened, then it allows the following packets from external hosts on the public internet that correspond to the connection back into the private network or the local network. So you can see that a NAT box is implementing this kind of if-then rule. If a connection's been established from the inside, then allow packets in from the outside. That's the kind of thing you could do with a stateful firewall, whether you did address translation or not. And another step up to the top level here is an application layer firewall. Really, an application layer firewall here tries to implement rules that are directly based on application usage and content. The kinds of things, the high-level statements we wanted to make for policies. For instance, you might try and inspect the contents that's coming into your network to look for well-known viruses and chuck any packets that contain viruses. Well, to do this, we have a bit of a problem because firewalls operate at the packet level and application messages which carry content may be split across many packets. So an application level firewall, because it tries to look beyond packets, it's going to have to emulate things that hosts would do, for example, by reassembling many IP packets and looking at the application messages that are carried in those packets. Because it's only by looking at those application messages that it will be able to decide whether there are viruses and so forth in it. So an application level firewall is trying to operate at this high level. As you might imagine, that's somewhat of a difficult task and it can only be done imperfectly and with a fair bit of work. But where you can do it, you maybe find a way of shielding your organization from viruses and other undesirable high-level actions that couldn't otherwise be expressed in terms of individual packet characteristics like TCP and UDP port numbers. And finally, to finish with firewalls, I'd like to talk briefly about deployment. Here is a classic deployment scenario. Actually, in all of the cases, what you're going to want to do is place a firewall around the internal-external boundary. So where your organization meets the public internet, at all of those places, you would want to place a firewall to control the traffic that's going across that boundary. Now, so we have here in this classic picture, we have an internal network and an external network, which is the internet. Here's the boundary between internal and external. In a classic setup, you'll, in addition, also often have what's called a demilitarized zone, or a DMZ. Here's the DMZ between the firewall device, which is here, and the external internet. So the DMZ is like the last bit. It's outside the internal network, but it's within your organization, not the external internet. The reason you might do this is you could put hosts inside the DMZ, such as your web server or email server, chatty hosts that talk a lot to other hosts on the internet. This way, you could, if these hosts were ever compromised from the connections they had to make, then you could prevent connections between these hosts and other hosts on your network here, because you could chop this off with your firewall. So if in the worst case that your web server did get infected, you could prevent an infection from spreading from there to your other hosts on your network, maybe your more sensitive hosts, because those other hosts were behind a different firewall, even though both the web server and the other hosts were both in your local network in some sense. So that's how our DMZ can help provide better separation between the external internet and your precious internal hosts. And as a final note on deployment, I would say that firewalling technology is now being built into many different devices. So we have various options in how we would deploy it. It always fits this picture I've talked about in terms of protocol layering, of operating logically at the IP layer, even though it peeks at other things. So it sits like a router. It could either be deployed as a specialized network device, like a router. That's what we saw in the previous picture with a classic firewall and a DMZ just beyond it in the internal internet. Firewalling technology can also be built into other devices which sit at the boundary. A good example here is your AP, your wireless access point. That usually sits between your home network and some kind of wide access like cable or DSL to the rest of the internet. So it's a good place to implement a firewall. And so a firewall is often built into your AP these days. And in addition, you could, or instead, you can actually do them both. You can also imagine that firewalling technology can be built into the network layer of individual hosts. This is as part of the OS. So many OSs today will have firewalling technology built into them. It's doing the same thing we've talked about, it's moving it down to the host level to provide more protection. In fact, there's a little bit of a trade-off here. as you might imagine that putting a firewall in the one spot, like in your AP, where you go into your local network or leave it, it can centralize things and it can simplify your job of your IT job, because it's centralizing the policies which you use to accept or discard packets. On the other hand, distributing the implementation of the firewalls to all hosts has other advantages. It actually tends to improve the protection. That's because if one host on your network is compromised, you still have the firewall between it and another host on your network. Whereas if you just have it at the boundary, once you get past that firewall, you can roam freely amongst all of the hosts in your network. So distributing the implementation of a firewall actually provides better protection. It can provide better visibility into apps, because a firewall on your local host can know what applications are actually running and sending the traffic. It doesn't have to guess from the TCP and UDP port numbers. Applications like Skype, for instance, don't use a well-defined set of port numbers, so it can be difficult to know if packets actually come from a Skype application or not. If you're running on the local host, presumably your operating system has a very good idea what process generated the packets, so it can know if that's the Skype implementation. And even in terms of performance, a firewall running at every host is gaining the performance advantage of having many hosts implemented in parallel, rather than one firewall which has to be a very high performance host. So you can see this is an interesting trade-off, and I would expect that we'll see a greater use of distributed firewalling technology over time, with the application of centralized policies to make it more manageable. Okay, so there you go. Now you know about firewalls, what they try to achieve, and how they operate. G'day viewers. In this segment we'll talk about virtual private networks. So virtual private networks are a very useful networking construct that allow us to run our own private network on top of the internet. To do that, messages need to be secured as they're sent across the internet, and this is usually done with a scheme called IPsec for IP security. We'll look at both of these topics in this lecture. Let's start with a little bit of motivation. I've told you before, the best part of IP connectivity is the fact that you can simply send a message to any other host on the internet. It's wonderful. The worst part is, well, the same thing. Any other host on the internet can send packets to you. And there's a lot of nasty stuff out there. You may not want packets from any other host, particularly if you're trying to implement your own private network. So it's often desirable, if you have a company here we have 3 different sites, A, B, and C. It's often desirable to implement your own network that is somewhat separate from the internet. It will connect all of the different sites of your company, but not allow any random person on the internet to inject packets into your own corporate network. If you wanted to do this, you could actually do this by building your own physical network. What you would do is you would actually you would rent or lease a line. This is a leased line. Just think of this as a private link. If you call up a telecommunications company, you could get one. And it would cost you money. But it would be a link for your own use, which is physically separate from the rest of the internet in some way, so that internet packets, regular internet packets, don't travel over it. We'd still need some way to connect this corporate network to the internet, assuming we wanted to allow people on the corporate network to ever get to the internet. But this would be through control points of interconnection that I haven't shown here. So the network I've shown here is separate from the network, and so you can see Eve here, well, or Trudy, who exists on the physical, on the public internet, then has no real way into the private network. They're separate. However, let's advance our thinking a little bit. Here's a brilliant idea. You know, those leased lines were kind of expensive, so the brilliant idea is, let's just use the public internet instead of leased lines. That will be much cheaper. It might also be more reliable as a better managed service provided by ISPs and so forth. In this case, what we're going to try and do is run a logically separate private network on top of the internet. So the separation will be logical, not physical, in the sense of having different links through which private and public internet traffic go. You can see that this could afford you many cost savings, for instance, but it raises a lot of security problems since we now have a logical separation. In fact, this kind of network is called a VPN, a virtual private network. And now, since we're all using the internet, Trudy here maybe has a chance of messing up your security. So the goal and threat model for a VPN, let me just go over it briefly. So again, we know what it is we're trying to accomplish. The goal here is to maintain our own logical network called a VPN, a virtual private network, that runs on top of the internet yet is separated from it so that traffic can't go from the public internet onto the VPN, or vice versa. If you're on the VPN, you can't get to the public network except via specially designated gateways that might scrub traffic for that purpose. The threat here is that Trudy, who is also on the public internet, will somehow be able to send packets from the public internet to your VPN, or vice versa. She'll be able to get packets out of your VPN and understand what they're saying, read the contents of messages and so forth. Now, in the ideal case, we'll perform this separation so that Trudy is on one side and our VPN is on the other side, as though it was composed of physical leased lines. That's what we want to get. So I'm going to go over a couple of things to explain VPNs to you. First of all, I'm going to talk about the mechanism. How is it that we can create these virtual links and send packets over them? And then I'll talk briefly about how we would secure messages over these links, because that turns out to be the standard solutions almost. Okay, so the question here for us is, how can we build this virtual link, a virtual link or a tunnel? Now in the figure here, I have a corporate network on two sides. You can see I have here private network A and private network B. Just think of that as two different sites from one company. So hosts in that network, such as this host here, would like to be able to send packets to other hosts. Maybe there's some other computer just here in the network, or they would like to be able to send packets all the way through to some other host who's also in the corporate network. It just so happens to connect these two remote sites, we're using the public internet with this virtual link or tunnel. So for hosts inside the private network, we want them to work normally. They just send packets with addressing according to whoever is in this private network. To cross this virtual link or tunnel, this is where we have to do something special. And all we need to do actually is encapsulate packets as they go out of this tunnel endpoint and change the source and destination address so that they will go into this tunnel endpoint. So if you send a packet out of this router, the only place you want it to go is into this router, this other tunnel endpoint, so that it can reach hosts on the other network. This is a tunnel. Just to be a little clearer maybe about how a tunnel actually works, what we should do is we should look at our usual kinds of protocol diagrams, because they'll explain to us what's going on at these different points. When I said a tunnel endpoint encapsulated the IP packets as they went out so that they would reach the other tunnel. This is what's going on if we look at this protocol diagram. Actually, encapsulation is often called IP in IP. The simplest way to encapsulate is to sort of add another IP header. Okay, but I'm jumping ahead. Let's look at this diagram carefully. So on the very left, we have just a host on the private network, and maybe they're sending to another host on the private network on the very right-hand side. The routing is going to take us through this tunnel endpoint here on the left, and then we want to go all the way to the tunnel endpoint on the right across the public internet. You'll see the difference is, so actually we're going to have an IP layer all the way across here. This is the top IP layer. It's all the way across all of the devices which you use to handle packets in this private network. But there's something funky going on at the tunnel endpoint here. We have this. There's an extra IP layer. We have an IP layer. That's the one that we're using at the host to communicate. And underneath it, we have this other IP layer here. So that means that IP is running on top of IP. In fact, and it's talking to a corresponding endpoint on the other end of the tunnel. Here's the other layer. So what we're really doing is using, normally we would have a link would be something like an Ethernet where we would go one hop. Here with IP underneath, we are using IP, the public internet, as one hop. In fact, as you send from one particular tunnel endpoint to another tunnel endpoint using IP, you may cross over many different routers that are in the public internet. That doesn't matter for us. The packets that are going between the tunnel endpoints won't see all of these other routers. It will be as though they weren't there and it was just one big virtual link. So this is how a tunnel works. And this extra IP layer, which is sandwiched in here, is going to add an outer IP header, or it's going to modify somehow the existing IP headers to provide for delivery from one side of the tunnel to the other side of the tunnel without allowing any escape from the tunnel while you're on the public internet. Let's look at that just a little more by looking at what a packet looks like as it goes across the tunnel. So here on the inside, you can see I've got the inner packet. That's shown in pink here. And I showed encapsulation not simply as adding a header, but wrapping, because often the contents here is going to be encrypted in a tunnel. So you wouldn't be able to see them literally because they'll be encrypted. Now, this inner packet, it has an IP header, and it will have source and destination addresses, IP addresses, which will correspond to the hosts in the private network. Because this is just another packet going across the private network. As far as those hosts are concerned, they might not even realize that the public internet has been used as a link between some portions of their own private network. What the tunnel endpoint does is it adds this outer layer of IP addressing. This is the tunnel, the header that's put on by the tunnel. This extra IP header here will have a source address, which is the tunnel endpoint which made it, and a destination address, which is the remote tunnel endpoint to which this whole unit is destined. And that way, this inner packet will be carried across the public internet. So now you've seen tunneling with about 3 different pictures showing different aspects of it. And hopefully the concept makes sense to you and you understand how a tunnel works. Well, to get to a VPN is essentially a set of tunnels, but in addition to that, we need security. So tunneling alone is not secure. We've worked out how to build this logical structure on top of the internet and tie together the little islands of a company that all were connected to the internet. By the way, I should say one island could be a single computer, which is you on a work trip, or a single computer, which is you at home connecting in to the corporate network. But this tunneling, as we've seen it so far, is not secure. We don't have any of the usual properties we care about: confidentiality, integrity, and authenticity. If we simply slap an outer header on them, then Eve on the network can look at the contents of the packets which have been sent across our VPN. That's not good. Trudy could also send packets to the remote tunnel endpoint, and she could maybe fake packets so that they'll be accepted and get into the private network on the other side. That's not good. Both of these things violate the kind of separation that we wanted. And so the solution we need for security here is fairly straightforward. We need all of our usual cryptographic protections to make sure that messages which are sent from one tunnel endpoint to another tunnel endpoint have all of the usual confidentiality, so Eve can't read them, and integrity and authenticity, so Trudy can't tamper with them or inject her own messages. Well, to do that, we'll simply use cryptographic protocols of the kind we've looked at. We've looked at how these kinds of properties are provided, both at the link layer with 802.11 and at the transport layer with SSL for the web. Well, here for VPNs, we're going to use a different scheme, but conceptually it's doing a lot of the same things. The scheme we'll use is called IPsec, short for IP security. This is often used for VPNs. It provides security at the IP layer, so it's going to wrap up these IP packets in a nice secure way so that we can send them across the tunnel endpoint. For VPNs, the level at which we want to secure is the network layer, which is why we're going to use IPsec. Okay, so I have just one slide for you on how IPsec works. There are actually lots of interesting details in IPsec, but given the lack of time, I'm not going to go into them. You can read a little bit more about them in your text. I will say, like many other things, so IPsec is a long-standing effort to secure the IP layer by adding security. In the same way that we've been trying to add various kinds of security and even IPv6, many of these efforts on DNS security have been around for a long time. It's just adoption has been fairly slow until recently due to various problems. But what IPsec will do, and it's all standardized, is add confidentiality, integrity, and authenticity to the network layer, to packets as they're sent across the internet. Actually, there are many options and you can have various combinations of all of these things. So I'm just showing you one particular mode, tunnel mode, which is going to add all of these properties. So briefly, here's how IPsec operates. Like all cryptographic protocols, we need keys. So keys need to be set up for all communicating host pairs. These host pairs, this is the tunnel endpoints. And you might note, because I said the pairs, what we're really going to do here is end up setting up a pair, a key amongst a pair of hosts that we're going to use for a symmetric encryption scheme. So that will be fast. That will provide a fairly efficient way to encrypt information as it goes across the internet. So these keys need to be set up. This is one reason why IPsec is often used with VPNs, because we'll be configuring the tunnel endpoints anyhow. You have to know how you're talking to. So we can often easily add keying information to them. Whereas it's more difficult to simply talk to random hosts on the internet with IPsec because we haven't established keying. So once we do that, actually interestingly, communication across using IPsec from one IP host to another IP host tends to look a little more connection oriented than does pure IP. That's because we have to make sure that we've got all of the session keys set up and other parameters and so forth. So it's almost like a connection is established before we can just begin sending. Again, this fits very well with a VPN where the connection is setting up a tunnel and then using it to send many packets. And as we go over the tunnel, we talked about encapsulating the packet. So the IPsec layer will add information to secure the packet. Actually, you can see here in the picture, it adds both a header and a trailer. Now in this picture we have, here is the old packet, the old IP header. This was the one on the private network that's going between two hosts on the private network. Here's the new IP header that we slapped on as we went over the tunnel. And with just these two things, we don't have our packet secured to provide confidentiality, integrity, and authenticity. So what IPsec does is it adds these two other blocks. This is when you're using it in a particular mode called tunnel mode. It adds a header. This is called, I think, the ESP header, Encapsulating Security Protocol, I think. And this header provides information about encryption, and you can see here the whole body of this packet. I'm going to hash it out because it's all encrypted, you can see here. IPsec also adds a trailer. That's this thing here. This is an authentication token. It's actually a MAC. HMAC is the particular algorithm that's often used, but it's a MAC as in a message authentication code of the kind we looked at when we talked about crypto designs. And this authentication tag is authenticating everything here. I'll hash in the opposite way. So it's authenticating everything, even including the ESP header. And when we've done that, we've got all of our properties, and that is IPsec in a nutshell. Okay, so I'd like you to take away a couple of things from this lecture. First of all, just the idea of VPNs, how we can build these logically separate networks on top of the internet. This is a very useful building block for networking in general. And like some of the other devices we've seen, like firewalls and so forth, it really alters IP connectivity, the IP connectivity that hosts see. In this way, it alters the IP connectivity maybe in a beneficial way to build these separate networks. Now, of course, to do this, to really accomplish the goal of separating things, VPNs need some kind of cryptographic protections to secure the messages. And traditionally, IPsec is used with VPNs. It's a fairly standard design in some ways. We've looked at all of these different properties and ways they can be provided by cryptography. IPsec does this at the network layer, and that's VPNs.
G'day viewers! Today we're going to talk about bits, bytes and cupcakes.
So our topic, distributed denial of service, is interesting to us because it's actually an attack on network availability. So this is really very different than many of the different kinds of security problems we've seen before, where we could provide confidentiality, integrity and authenticity to secure messaging in some way. distributed denial of service has none of those aspects. It's simply about sending packets. So all of these cryptographic protections, they don't help us at all. That makes it interesting for you to see just as a contrast for a different kind of security problem. And it's also kind of cool just to learn about some of the various difficulties we face in the internet today and the nasty things that go on. Okay, so let me start with a little bit of motivation. You've seen this before. The best part of IP connectivity, you can send to any other host. The worst part of IP connectivity, any other host can send to you. And, well, other hosts who you don't know or don't like can send lots of nasty stuff to you. In fact, if there are many of them, as there are here, there's Trudy has really become an army of Trudies, if you like. Trudy, or the army of Trudies, can flood a target host by simply sending packets to it across the network. If you send enough packets, this interferes with IP connectivity. And the host may then become unresponsive because all of the resources in the network and at the host are consumed by this flood of packets. That's going to leave no resources left over for the server or the host over here to interact with whoever it really wanted to interact with. And this is called, or this is called denial of service. Actually, denial of service is a more general term. This is one example, one form of denial of service. Okay, so let's just talk about the goal and threat model to be clear what it is we're trying to accomplish. Now, the goal is simply for a host to be able to maintain network connectivity for it to use for all of the desired services it's providing. Typically, this will be a server talking to its other clients on the internet, its intended users. Great, so they should just be able to talk. And we would like to, in the ideal case, you see I have this line, we've separated Trudy out so that she can't interfere with this exchange. The threat is that Trudy may somehow overwhelm the host with undesired traffic, simply by sending packets actually, that's all she'll have to do, and that this will interfere with using the normal services of the network. Now, about now is where things go a little south, and I tell you the state of distributed denial of service in the internet today. Actually, well, it's a huge problem today. Just one relatively recent example is that there have been many attacks on US banks, which are distributed denial of service attacks, in which traffic purportedly from Iran has been targeted at US banks in retaliation for other things, and has flooded those all of these bank servers and made them very difficult to use. Akamai, who monitors the state of the internet, in their third quarter of 2012 report, they described that DDoS attacks were on the increase and that actually against the US banks, they peaked at 65 gigabits per second of traffic flooding the banks. That is a lot of attack traffic, and you can imagine that could be very hard to deal with, and it could overload pretty much any server you could come up with. Wow, so that's kind of nasty that anyone can just send packets and overwhelm other internet hosts. Now, the thing that's a little unfortunate in the internet reality check for us is that unlike many of these other security problems we've looked at, there really are no great solutions to this problem in the internet today. There are certainly things that can help using CDNs and filtering traffic and all of those things. I'm going to mention them briefly. But because denial of service at its heart comes from simply sending many packets, and that's what the internet does, it's really quite difficult to defend against it. That makes it an interesting but also a very challenging problem. So let's go on and just have a little bit of fun and learn what distributed denial of service is all about. So first of all, starting with denial of service. Denial of service really simply means that service is denied. So a system is made unavailable to its intended users. And typically, the way you'll accomplish this, because we're not really usually talking about bugs in the system that can compromise the host, typically the way you will accomplish this is to simply consume all of the resources of the system. Attackers, if they consume all of the usable resources of the system, there'll be none left over for the intended users, and they'll see a system that's unresponsive, doesn't really work. Now, denial of service could be talked about in many different contexts in computer systems. In the network context, what I'm really going to be talking about when we talk about a system, we really usually mean a server, something that's on the internet to provide a service. It could be just your host 2 at home, and you could be unlucky enough to receive a flood of traffic. but we're usually talking about a server that's there to allow legitimate clients to use it. Resources mean a couple of different things. They might mean network bandwidth if we're talking about the network resources, or if we're talking about host resources at the server, just its CPU, its memory, and things like that. If we just focus on the host for a while, denial of service at a host can be accomplished simply by sending strange packets to the host that totally zap its resources and deplete them. Here are a couple of examples. Now there used to be, well there still are, packets called ping of death, malformed packets. You could send this ping packet to a host and it was constructed in such a way that it would trigger a kernel bug and crash your system. So you'd send one packet and you would take down a host. That's why it was the ping of death. If you got it, you died. That would be one example causing host denial of service. Another example is a SYN flood, where an attacker sends many TCP connection requests, that is TCP SYN packets, to a host. The host will respond by sending SYNACK packets and doing all of the usual things to open a connection, including setting aside resources in the kernel for connection structures. But what would happen if the attacker simply sent many SYNs, flooded SYNs, but never ever bothered following up with the in response to the SYNACKs? Pretty soon you would fill up all of the connection structures at the host and it would be unable to accept new connections. This is called a SYN flood. This used to work in the old days. So you can see here the idea is that a relatively small number of bad packets can deplete the host resources. It's either its CPU or its memory or other resources on the host. And this is host denial of service. Now, I'm actually not really going to focus on that. These strange packets are really having, well, nasty effects on the host. You can often patch all of the specific vulnerabilities that are identified. Patches for pings of death have been around for a long time and would be deployed on most servers that you would care about, so you can no longer take them down. There are many different kinds of vulnerabilities, so a best practice when you run a server to keep it robust is to always apply these different patches for new vulnerabilities as new vulnerabilities are discovered. If you're interested, you could read about SYN cookies as a defense against SYN floods. That's a pretty interesting one because it is a little bit of a protocol design. But for host denial of service, we're not going to focus on it much because you can defend against it mostly by keeping your host up to date. So let's move to network denial of service. The resource which is going to be exhausted here is the network. It's simply bandwidth. So the nasty fact here is that you can cause network denial of service simply by sending enough packets to saturate the network. Doesn't matter what they are. If you can just send many packets, then you'll be able to saturate the network links. If you do, and here's a picture of it, you can see this access link here is leading up to a server or a host at the other end. This pipe, this access link in the middle here, it's full of bad packets, from nasty packets from Trudy. If Trudy sends enough packets, then as the traffic approaches this access link, there will tend to be congestion and loss in the routers that lead up to the access link. And packets from your intended user here, you can see there's one ping packet here, we'll see very high congestion and loss. Most of them won't get through, and the server won't be able to respond and have a reasonable conversation with them. So this is what happens with network denial of service, where the attack is on the network bandwidth. That's the bandwidth inside this link that's leading up to the server. As you might imagine here, if you want to undertake this kind of attack, you're going to want to send a lot of packets. So it's helpful here to have many different attackers. And when you have many different attackers, and they're going to be at different places on the network, this denial of service is called distributed denial of service. There are many distributed attackers, all of whom have it in for you. In fact, it looks somewhat like this. As you can imagine, an effective way to provide distributed denial of service attacks is with a botnet. A botnet is a large network of compromised hosts. So if there really are nasty people out there who have compromised various machines, your home machine could be one of them, you might not even know. And having compromised those machines, they can then use them as a source of attack traffic. There are believed to be botnets that that have many thousands of compromised hosts, maybe hundreds of thousands of compromised hosts. If whoever is running that botnet decides to use them all in concert to send packets to you, you'll receive an awful lot of packets. So you can see here, just all of the different hosts in the botnet. If they simply flood traffic towards the victim, now I've changed terminology to call this server the victim because that's what it is, then the network will increasingly saturate as you get closer to the victim because there's only a certain amount of network capacity that leads up to the victim. Typically the access link will be the most restricted link leading up to the victim. That's why I showed it in the previous slide. And we'll saturate that link, causing congestion and loss, and it's over. Actually, it's even worse than I've said so far. Because when the attackers send packets, they might also be able to falsify their IP addresses. How do you do that? Well, you simply put a fake source address, IP source address on your packet. Historically, the network doesn't check IP source addresses. They're used by the destination to be able to send a packet back to you. But in this case, we're not using that functionality, so a source might be able to put any old identification there. If you do that, you're hiding your location. You're hiding the location of the attackers. It makes it more difficult for the network, the people who run the network, to track down what's going on. This is called IP address spoofing. And so you can see here Trudy's sending packets, and Trudy simply changes the IP source address to say it's from Bob. Alice then, thinks Bob really has it in for her, even though it's actually Trudy. Okay, so this is definitely can be a complication. Actually, it's even worse than that. Here's an example of nasty things you can do with address spoofing. Look at this trick. Trudy can actually trick Bob into actually sending a packet to Alice. So, in which case, it's really Bob who has been tricked into attacking Alice. If Trudy sends packets to many, many, many different Bobs, if they each send a trickle of traffic to Alice, it will add up to a flood. So to do this, Trudy would send a packet to Bob, and so here's Trudy sending a packet that's to Bob, but the key bit is that Trudy spoofs the source address and says this packet's coming from Alice. It just has to be some kind of packet that will elicit a reply from Bob. If you pinged Bob, maybe Bob would return a ping reply, for instance. If Bob was a DNS server, maybe Bob would return a DNS reply in response to a query. But Bob's reply is shown here. It's this packet here. Well, this is going to be from Bob, of course. Where's it going to be sent? It's going to be sent to the source address, and that was listed as Alice. So Bob will send a packet to Alice. Alice may not be sure what these packets are all about because they're a reply to a query she never sent. So she might not be sure what's going on. But simply by sending them, they may accomplish their goal by clogging up the network close to Alice. So you can see this is pretty nasty. This is an example of some of the nasty things that can go on with attacks. Well, with best practices in the internet today, we can disable most of these kinds of attacks. Now, in fact, there is a specific best practice called ingress filtering. And the idea here is to validate the source address of a packet at the network boundary. So that's like when it enters the ISP, when it goes into the internet at large. This might just seem like common sense, actually. You just make sure that it's okay so that people from the edge of the network can't attack. If you like, you could say that in the internet today, it's the responsibility of the end host that makes the packet to check that the source address is okay. Well, if that host is compromised, that may be a little comfort. So here we would have the ISP check the source address of the packet. This is actually not too hard to do. Here is the ISP boundary. Now, when packets come in, this router can look at where they come from. It says here they come from Bob. And then this router can look up where it would forward packets if packets were being sent back to Bob. Well, the answer should be that they're sent back in the same direction. For instance, if they said from Trudy, if we looked up Trudy, we would send back to Trudy. So we would be pretty confident that, they really came from the right place. If we look at Bob, though, if this ISP router looks at Bob, Bob will be somewhere different. He won't be at this end of the access link. Only Trudy is. So this router will be able to work out that these packets don't come from Bob. They come from someone else like Trudy, and so the router can simply discard them. And they won't get onto the internet, and so they won't be able to attack Alice, who's a long way away. This is a best practice. However, deployment of this idea has been relatively slow, partly due to incentives. As an ISP, I have to do extra work here to make sure all of these checks are okay and that they don't mess up anything. And this extra work is really to help hosts somewhere a long way away on the internet, hosts who actually aren't paying me money and might not be on my network at all. So it's something extra to do that doesn't directly benefit yourself. Somewhat like vaccines, I guess, it benefits everyone if everyone does it. So we're getting there, but it's taken a while. Okay, so imagine, however, that ingress filtering has been deployed and we take all of these measures. We're back to a basic flood. So the best we can do with a lot of the protections today is render a distributed denial of service attack a simple flood of packets. That can still take us down, especially if it's 65 gigabits per second. What can we do? Not much. I've listed 2 possible flooding defenses here, both of which are used in practice, both of which help. The first one is to increase the network capacity around the server. We said we were going to fill up those access links and clog them. If we can make those access links bigger, they'll be harder for an attacker to clog. And a particular approach which is used here a lot, if you're a high-end internet service and you want to stay up, is to use a CDN. A CDN is really replicating the server at many different locations, so we'll be getting a higher access link bandwidth across all of those locations. We're really summing it together. And it's actually quite clever to use the CDN to do this because we're getting some statistical multiplexing effects amongst the customers of the CDN. To survive a distributed denial of service attack, we want our CDN to provide us with a high peak capacity. And so a CDN should have lots of bandwidth. But realize that not everyone is going to be subject to a distributed denial of service attack at the same time. So we can use the bandwidth of the CDN to protect whoever is under attack right now. Okay, and the second approach, and this is what we really want to do to deal with the DDoS flood, is to filter out the attack traffic within the network. This means at the routers within the network. And really here, the earlier the filtering is done, the closer to the source and the further away from the victim, the better. Because there's more capacity in the network, it won't be clogged up yet. So this is really what we need to do to deal with distributed denial of service attacks today. It's ultimately what's needed. It's somewhat done today, but the measures are employed by ISPs in a fairly ad hoc way. You might need to call up your ISP, for instance, so that they can find out what's going on. And it's not really automated. So now you know the state of denial of service, distributed denial of service. It's a topic on which we would expect to make some progress towards solutions in the future. Okay, hope that was fun. G'day viewers. In this last video we'd like to wish you a brief farewell. Well, the main thing we'd like to say to you is congratulations. We know that this is a very long course, and if you've made it this far, we've covered a lot of material, and we're confident that you've learned a great deal about computer networks, whether you've been doing the homeworks or not. I also want to say that it has been really wonderful from our point of view to be able to see an online community come together and really to hear from many of you in many different situations all around the world. It's really a wonderful thing. Okay, so I've shown here, just on this slide, some of the material we've covered to remind you of things that we've talked about during the course. Don't worry, I'm not going to go over it all. I really just want to show you how much ground we've covered. And as I point out here, this is really just a selection, a small selection actually, of the different topics and concepts that we've talked about in some detail so far. I also hope, now that you have this picture of networking, that this is really the beginning of your networking journey. You can build on the knowledge that you have now as you use practical tools like Traceroute and so forth to debug your own home networks and understand what's going on. And I also expect, as you learn more about different kinds of networking technologies in the future, that you'll be able to add that knowledge into your sort of knowledge base just by knowing how it fits into this conceptual framework. So one thing that I really do want to do is to say a special thanks to all of the course staff. You're all familiar with the iceberg analogy. Well, you get to see me up top here as a presenter in all of these videos. But really, as I'm sure all of you realize, creating a course like this is a tremendous amount of effort. And it's only possible because of the efforts of all of the course staff. This is this hidden bit of the iceberg that you don't really see, but you know it's there because it's making everything happen. You know some of these people from interacting with them on the discussion boards, and you've also probably seen all of us talked about on the web pages where you can find everyone who's contributing to this course. But let's have a brief round of applause for all of these people. Yeah, that's right. Thanks very much. And finally, we'd just like to say best of luck for the final, for those of you who have yet to take the final. In addition to that, we'd ask you just to take a brief moment to give us a little bit of feedback on how we're doing with an end of class survey, also with the discussion board, however you like. If you don't want to spend a lot of time, one thing that's helpful to us is just if you upvote or downvote other comments, depending on whether you agree with them or not. The reason is we're really looking to understand what to do, what changes to make to improve this course in future iterations. And there are many possible things we could do. We can't do them all. So we really want to know which ones are the most important changes that we could make for the next iteration. Many of you probably have different questions and concerns about statements of accomplishment, other possible offerings and all of that. Don't worry, information on all of this is coming. We'll use announcements to cover all of this sort of stuff and any other wrap up. Okay, that's it. Best of luck to all of you from the Computer Networks team, and we hope that you'll enjoy your journey in the future learning more about networks. Bye.